Hello aspiring data scientist. Welcome to yet another informative video from Simplilearn. Did you know that the demand for data scientists has been rapidly growing in recent years? As businesses gather massive amounts of digital data from sources like social media, e-commerce and IoT devices, the need for skilled professionals to analyze and interpret this information has never been higher. Job opportunities in data science have surged by more than 30% annually. And data scientists are consistently among the highest paid professionals globally. Whether you're just starting out or looking to advance your career, mastering data science skills can open doors to exciting opportunities across various industries. If you want to join this trend and become a highly demanded data scientist, you are in the right place. This video covers everything you need to know to kickstart or advance your career in data science. We will start with the basics of data science and cover the essential topics like statistics, machine learning, regression analysis, deep learning, Python libraries, and data visualization. Plus, we will help you prepare your data science resume and ace those interview questions. So stick around and let's dive into the world of data science together.
Craving a career upgrade? Subscribe, like, and comment below. Dive into the link in the description to fast-track your ambitions. Whether you're making a switch or aiming higher, Simplilearn has your back.
But before we begin, if you are planning to start a career in data science, check out the Caltech postgraduate program in data science from Simplilearn, ranked at the top of PG data science program by AIM. In collaboration with Caltech CTME and IBM, this program equips you with essential skills and tools, including Python, machine learning, Tableau, generative AI, ChatGPT, and more. Learn from industry leaders through masterclasses taught by Caltech instructors and IBM experts. Join this comprehensive program to gain hands-on experience and advance your career. You can find the course link in the description box and pinned comments. Alright, so let's get started.
Do you know how Netflix decides which movies suit your taste better? Or how Google Maps can provide routes with low traffic at given moment in seconds? This is all possible thanks to data science. The popularity of data science exploded in the 2010s, causing an approximate 15% year-on-year growth in the job market and is expected to grow even higher in the coming decade. Now, what exactly is data science? Data science is the field of study that works with massive amounts of data, utilizing relevant tools and techniques to derive valuable data. The day-to-day work of a data scientist involves collecting, analyzing, and interpreting this data to help businesses achieve their goals. Companies across various industries generate vast amounts of data, so its application range all the way from education, healthcare, and entertainment to finance and marketing. When it comes to the subfields of data science, it comprises many technologies like artificial intelligence, machine learning, natural language processing, and deep learning, each of different purposes and having varied functionalities. The role of a data scientist was voted the sexiest job of the 21st century, and it is for a good reason. The demand for professionals who can make sense of vast amount of data is more than ever in this day and age. Companies like Microsoft, Google, and Amazon hire data scientists as they deal with problem-solving models involving massive amounts of data daily. This is why data science professionals are in high demand, with average salaries going as high as $1,864 per annum. With 2.5 million terabytes of data being transferred over the internet on a daily basis, the data science industry is slated to grow even higher, promoting further innovation and job opportunities.
Google had gathered 5 exabytes of data between the beginning of time 2003. This amount of data started to be produced every 2 days in 2010 and every 40 minutes by 2021. The responsibility of a data scientist is to gather, clean and present data and have a keen business sense and analytical abilities. Let us have a discussion about it in the upcoming slides. How can you become a data scientist as a beginner? I guarantee you, after watching this video, you will have a clear understanding on how to drive your career as a data scientist. Hey guys, welcome to Simplilearn. Before proceeding, please make sure you subscribe to Simplilearn's YouTube channel and press the bell icon to never miss any updates. Today we are going to cover significance of data scientists in industries. After that, prerequisites and technologies required for a data scientist. And finally, salary of a data scientist. I have a query for you. Which technology is used by Google Maps to predict traffic jams? Deep learning, machine learning, natural language processing, data structure. Please leave the answer in the comment section below. And stay tuned to get the answer. Significance. Now we will see how top industries are involved in the field of data science. By 2025, the data science industry is anticipated to grow to a value of $16 billion. There is an abundance of data science jobs all over the world. Now let's list out crucial areas where data science is used. Media and entertainment. The major player in the media and entertainment sector such as YouTube, Netflix, Hotstar, etc. have begun to use data science to better understand their audience and provide them with recommendations that are both relevant and personalized. E-commerce. Data science has aided retail companies in better meeting their expectations. As they bring a unique combination of deep data knowledge, technology skills, and statistical experience, data scientists are in high demand in the retail industry. Top recruiters are Amazon, Flipkart, Walmart, Myntra, etc. Digital marketing. Large volumes of data are currently being fetched from its users through search pages, social networks, online traffic display networks, movies, web pages, etc. A high level of business intelligence is needed to analyze such large amount of data, and this can only be done with the proper use of data science approaches. Top recruiters are Amazon, Flipkart, Facebook, Google, etc. Cybersecurity. Data science and AI are now being used by the cybersecurity industry to prevent the growing usage of algorithms for harmful purposes. Top recruiters includes IBM, Microsoft, Accenture, Cisco, and many more. Before moving forward, what is the response to the Google Map question that I asked? Answer is machine learning. Coming to prerequisites. Now that we know significance of data science in industries, let us explore the prerequisites and technologies required for a data scientist. Seeing the demand of data scientists in every industry, it is obvious that the scope of a data scientist is very high. So, how to start? There is no necessity that you should be knowing any technology or programming language. You can be a layman too. Data scientists typically have a variety of educational and professional experiences. Most should be proficient in 4 crucial areas. Important skill is mathematical expertise. 3 concepts like linear algebra, multivariable calculus, and optimization technique are crucial because they aid in our understanding of numerous machine learning algorithms that are crucial to data science. Similar to that, knowing statistics is crucial because they are used in data analysis. Additionally, important to statistics, probability is regarded as a must for mastering machine learning. Next is computer science. In the field of computer science, there is a lot to learn. But one of the key inquiries that arises in relation to programming is R or Python language. There are many factors to consider when deciding which language to choose for data science because both have a comprehensive collection of libraries to implement complex machine learning algorithms. In addition to learning a programming language, you should learn the following computer science skill: fundamentals of algorithm and data structures, distributed computing, machine learning, deep learning, Linux, SQL, MongoDB, etc. Domain expertise. Most individuals wrongly believe that domain expertise is not crucial to data science, yet it is. Consider the following scenario. If you are interested in working as a data scientist in the banking industries and you already know a lot about it. For instance, you are knowledgeable about stock trading, finance, etc. This will be very advantageous for you, and the bank itself will favor you over other applicants. And finally, communication skill. It covers both spoken and written communication. In a data science project, the project must be explained to others when findings from the analysis have been reached. This can occasionally be a report that you provide to your team or employer at work. Sometimes it might be a blog entry. It is frequently a presentation to a group of co-workers. Regardless, a data science project always involves some form of communication of the project's findings. Therefore, having a good communication skill is a requirement for being a data scientist. Apart from all this, practicing is very important. Keep using different tools. Also start reading blogs on data science. Start building projects on data science which can be added to your resume. Also, you can find many interesting courses on data science by Simplilearn. Salary reward is the result of good work. Now we shall discuss salaries that a data scientist will get. It should come as no surprise that data scientists may add significantly to a business. Every step of the process, from data processing to data cleansing, requires persistence, a lot of arithmetic and statistics, as well as scattering of engineering skills. One of the most important factors in a data scientist's salary is experience. At the beginner level, a data scientist can make $95,000 annually. The typical annual compensation for a mid-level data scientist is between $130,000 and $195,000. A seasoned data scientist typically earns between $165,000 and $250,000 per year. In India, at the beginner level, a data scientist can make 9,40,000 rupees on average per year. At mid-level, data scientist will get 20 lakhs rupees per annum. And if you are at the advanced level, you will get paid an average of rupees 25 lakhs annually. This salary will vary in different countries. The top hiring businesses in the US that provide the highest salaries for data scientists are Apple with $180,000 per annum. Next is Twitter with $170 per annum. Meta Technology $170 annually. LinkedIn $160,000 per annum. Wipro Technology provides 17,50,000 per annum. IBM provides 14 lakhs per annum. And Accenture will provide you with 19 lakhs per annum. And finally, American Express will provide on average of 13 lakhs per annum.
If you are an aspiring data scientist who's looking out for online training and certification in data science from the best universities and industry experts, then search no more. Simplilearn's postgraduate program in data science from Caltech University in collaboration with IBM should be the right choice. For more details on this program, please use the link in the description box below.
Deep learning. Deep learning was first introduced in the 1940s. Deep learning did not develop suddenly. It developed slowly and steadily over 7 decades. Many theses and discoveries were made on deep learning from the 1940s to 2000. Thanks to companies like Facebook and Google, the term deep learning has gained popularity and may give the perception that it is a relatively new concept. Deep learning can be considered as a type of machine learning and artificial intelligence, or AI, that imitates how humans gain certain types of knowledge. Deep learning includes statistics and predictive modeling. Deep learning makes processes quicker and simpler, which is advantageous to data scientists to gather, analyze, and interpret massive amounts of data. Having the fundamentals discussed, let's move into the different types of deep learning. Neural networks are the main component of deep learning, but neural networks comprise 3 main types, which contain artificial neural networks, or ANN, convolution neural networks, or CNN, and recurrent neural networks, or RNN. Artificial neural networks are inspired biologically by the animal brain. Convolutional neural networks surpass other neural networks when given inputs such as images, voice, or audio. It analyzes images by processing data. Recurrent neural networks uses sequential data or series of data. Convolutional neural networks and recurrent neural networks are used in natural language processes, speech recognition, image recognition, and many more. Machine learning. The evolution of ML started with the mathematical modeling of neural networks that served as the basis for the invention of machine learning. In 1943, Neuroscientist Warren McCulloch and logician Walter Pitts attempted to quantitatively map out how humans make decisions and carry out thinking processes. Therefore, the term machine learning is not new. Machine learning is a branch of artificial intelligence and computer science that uses data and algorithms to imitate how humans learn, gradually increasing the system's accuracy. There are three types of machine learning, which include supervised learning. What is supervised learning? Well, here, machines are trained using labeled data. Machines predict output based on this data. Now, coming to unsupervised learning, models are not supervised using a training data set. It is comparable to the learning process that occurs in the human brain while learning something new. And the third type of machine learning is reinforcement learning. Here, the agent learns from feedback. It learns to behave in a given environment based on actions and the result of the action. And this feature can be observed in robotics. Now, coming to the evolution of AI. The potential of artificial intelligence wasn't explored until the 1950s, although the idea has been known for centuries. The term artificial intelligence has been around for a decade. Still, it wasn't until British polymath Alan Turing posed the question of why machines couldn't use knowledge like humans do to solve problems and make decisions. We can define artificial intelligence as a technique of turning a computer-based robot to work and act like humans. Now let's have a glance at the types of artificial intelligence. Weak AI performs only specific tasks, like Apple's Siri, Google Assistant, and Amazon's Alexa. You might have used all of these technologies, but the types I am mentioning after this are under experiment. General AI can also be addressed as artificial general intelligence. It is equivalent to human intelligence, hence an AGI system is capable of carrying out any task that a human can. Strong AI aspires to build machines that are indistinguishable from the human mind. Both general and strong AI are hypothetical right now. Rigorous research is going on this matter. There are many branches of artificial intelligence, which include machine learning, deep learning, natural language processing, robotics, expert systems, fuzzy logic. Therefore, the correct answer for which is not a branch of artificial intelligence is option A, data analysis. Now that we have covered deep learning, machine learning, and artificial intelligence, the final topic is data science. Concepts like deep learning, machine learning, and artificial intelligence can be considered a subset of data science. Let us cover the evolution of data science. The phrase data science was coined in the early 1960s to characterize a new profession that would enable the comprehension and analysis of the massive volumes of data being gathered at the time. Since its beginnings, data science has expanded to incorporate ideas and methods from other fields, including artificial intelligence, machine learning, deep learning, and so forth. Data science can be defined as the domain of study that handles vast volumes of data using modern tools and techniques to find unseen patterns, derive meaningful information, and make business decisions. Therefore, data science comprises machine learning, artificial intelligence, and deep learning.
There are a lot of areas where data science can be used. One of the very common one is fraud detection or fraud prevention. There are a lot of fraudulent activities or transactions, primarily on the internet. It's very easy to commit fraud, and therefore we can use data science to either prevent or detect fraud. There are certain algorithms, machine learning algorithms, that can be used, like for example some outlier techniques, clustering techniques that can be used to detect fraud and prevent fraud as well. So who is a data scientist rather? It is actually a very generic role that defines somebody who is working with data is known as a data scientist, but there can be very specific activities and the roles can be actually much more specific. What exactly a person does within the area of data science can be much more specific. But broadly, anybody working in the area of data science is known as a data scientist. So what does a data scientist do? These are some of the activities: data acquisition, data preparation, data mining, data modeling, and then model maintenance. We will talk about each of these in a great detail, but at a very high level, The first step obviously is to get the raw data, which is known as data acquisition. It can be in all kinds of format and it could be multiple sources, but obviously that raw data cannot be used as it is for performing data mining activities or data modeling activities. So the data has to be cleansed and prepared for using in the data models or in the data mining activity. So that is the data preparation. Then we actually do the data mining, which can also include some exploratory activities. And then if we have to do stuff like machine learning, then you need to build a machine learning model and test the model, get insights out of it. And then if the model is fine, you deploy it, and then you need to maintain the model, because over a period of time it is possible that you need to tweak the model because of change in the process or change in the data and so on. So that all comes under the model maintenance. So let's take a deeper look at each of these activities. Let's start with data acquisition. So in the stage of data acquisition, basically the data scientist will collect raw data from all possible sources. So this could be typically an RDBMS, which is a relational database, or it can also be a non-RDBMS, or it could be flat files or unstructured data and so on. So we need to bring all that data from different sources. If required, we need to do some kind of homogeneous formatting so that it all fits into looks, at least format, from a format perspective, it looks homogeneous. So that may be requiring some kind of transformation. Very often this is loaded into what is known as data warehouse. So this can also be sometimes referred to as ETL, or extract, transform and load. So our data warehouse is like a common place where data from different sources is brought together so that people can perform data science activities like reporting or data mining or statistical analysis and so on. So data from various sources is put in a centralized place, which is known as a data warehouse. So that is also known as ETL. And in order to do this, there can be, the data scientist can take help of some ETL tools. There are some existing tools that a data scientist can take help of, like for example, DataStage or Talent or Informatica. These are pretty good tools for performing these ETL activities and getting the data. The next stage, now that you have the raw data into a data warehouse, you still probably are not in a position to straight away use this data for performing the data mining activities. So that is where data preparation comes into play, and there are multiple reasons for that. One of them could be the data is dirty, there are some missing values and so on and so forth. So a lot of time is actually spent in this particular stage. So a data scientist spends a lot of time, almost 60 to 70% of the time, in this part of the project or the process, which is data preparation. So there are, again, within this there can be multiple sub activities, starting from, let's say, data cleaning. You will probably have missing values. The data, there is some columns, the values are missing, or the values are incorrect, there are null values, and so on and so forth. So that is basically the data cleaning part of it. Then you need to perform certain transformations, like for example normalizing the data and so on, right? So, or you could probably have to modify categorical values into numerical values and so on and so forth. So these are transformational activities. Then we may have to handle outliers. So the data could be such that there are a few values which are way beyond the normal behavior of the data. For whatever reason, either people have keyed in wrong values, or for some reason some of the values are completely out of range. So those are known as outliers. So there are certain ways of handling these outliers and detecting and handling these outliers. So this is a part of what is known as exploratory analysis. So you quickly explore the data to find out and you can use visual tools like plots and identify what are the outliers and see how we can get rid of the outliers and so on. Then the next part could be data integrity. Data integrity is to validate, for example, if there are some primary keys, that all the primary keys are populated. There are some foreign keys, then at least most of the foreign keys should be populated, and otherwise when we are trying to query the data, you may get wrong values and so on. So that is the data integrity part of it. And then we have what is known as data reduction. Sometimes we may have duplicate values, we may have columns that may be duplicated because they are coming from different sources, the same values are there, and so on. So a lot of this can be done using what is known as data reduction, and thereby you can reduce the size of the data drastically, because very often this could be redundant data which can be removed and so on. So let's take a look at what are the various techniques that are used for data cleaning. So we need to ensure that the data is valid and it is consistent and uniform and accurate. So these are the various parameters that we need to ensure as a part of the data cleaning process. Now, what are the techniques that are used for data cleaning? So we will see what each of these are in this particular case. And so what is the data set that we have? We have data about a bank and its customer details. So let's take an example and see how we go about cleaning the data. And in this particular example, we are assuming we are using Python. So let's assume we loaded this data, which is the raw file.csv. This is how the customer data looks like. And we will see, for example, if we take a closer look at the geography column, we will see that there are quite a few blank spaces. So how do we go about when we have some blank spaces? Or if it is a string value, then we put an empty string here, or we just use a space or empty string. If they are numerical values, then we need to come up with a strategy. For example, we put the mean value. So wherever it is missing, we find the mean for that particular column. So in this case, let's assume we have credit score and we see that quite a few of these values are missing. So what do we do here? We find the mean for this column for all the existing values, and we found that the mean is equal to 638.6. So we kind of write a piece of code to replace wherever there are blank values. NaN is basically like null, and we just go ahead and say fill it with the mean value. So this is the piece of code we are writing to fill it. So all the blanks or all the null values get replaced with the mean value. Now, one of the reasons for doing this is that very often if you have some such situation, many of your statistical functions may not even work. So that's the reason you need to fill up these values, or either get rid of these records or fill up these values with something meaningful. So this is one mechanism, which is basically using a mean. There are a few others. As we move forward, we can see what are the other ways. For example, we can also say that any missing value in a particular row, if even one column the value is missing, you just drop that particular row, or delete all rows where even a single column has missing values. So that is one way of dealing. Now the problem here can be that if a lot of data has, let's say, one or two columns missing, and we drop many such rows, then overall you may lose out on, let's say, 60% of the data has some value or the other missing, 60% of the rows. Then it may not be a good idea to delete all the rows like in that manner, because then you're losing pretty much 60% of your data. Therefore your analysis won't be accurate. But if it is only 5 or 10%, then this will work. Another way is only to drop values where, or rather drop rows where all the columns are empty, which makes sense, because that means that record is of really no use because it has no information in it. So there can be some situations like that. So we can provide a condition saying that drop the records where all the columns are blank or not applicable. We can also specify some kind of a threshold. Let's say you have 10 or 20 columns in a row. You can specify that maybe 5 columns are blank or null, then you drop that record. So again, we need to take care that such a condition, such a situation, the amount of data that has been removed or excluded is not large. If it is like maybe 5%, maximum 10%, then it's okay. But by doing this, if you're losing out on a large chunk of data, then it may not be a good idea. You need to come up with something better. What else we need to do next is, so the data preparation part is done. So now we get into the data mining part. So what exactly we do in data mining? primarily we come up with ways to take meaningful decisions. So data mining will give us insights into the data, what is existing there, and then we can do additional stuff like maybe machine learning and so on to perform advanced analytics and so on. So one of the first steps we do is what is known as data discovery, and which is basically like exploratory analysis. So we can use tools like Tableau for doing some of this. So let's just take a quick look at how we go about that. So Tableau is excellent data mining, or actually more of a reporting or a BI tool. And you can download a trial version of Tableau at tableau.com, or there is also Tableau Public, which is free and you can actually use and play around. However, if you want to use it for enterprise purpose, then it is commercial software, so you need to purchase license, and you can then run some of the data mining activities. Say your data source, your data is in some Excel sheet, so you can select the source as Microsoft Excel or any other format, and the data will be brought into the Tableau environment, and then it will show you what is known as dimensions and measures. So dimensions are all the descriptive columns, and Tableau is intelligent enough to actually identify these dimensions and measures. So measures are the numerical values. So as you can see here, customer ID, gender, geography, these are all dimensions, non-numerical values, whereas age, balance, credit score and so on are numeric values, so they come under measures. So you got your data into Tableau, and then you want to, let's say, build a small model, and you want to, let's say, solve a particular problem. So what is the problem statement? All right, let's say we want to analyze why customers are leaving the bank, which is known as exit, and we want to analyze and see what are some of the factors for exiting the bank, and we want to, let's assume, consider these three of them, like let's say gender, credit card and geography, these as a criteria, and analyze if these are in any way impacting or have some bearing on the customer exiting or the customer exit behavior. Okay, so let's use Tableau, and very quickly we will be able to find out how these parameters are affecting. All right, so let's see. So this is our customer data. So from our Excel sheet, we have data set about let's say 10,000 rows, and we want to find out what is the criteria. Let's start with gender. Let's say we want to first use gender as a criteria. So Tableau really offers an easy drag and drop kind of a mechanism, so that makes it really easy to perform this kind of analysis. So what we need to do is exited says whether the customer has exited or not, so it has a value of 0 and 1, and then of course you have gender and so on. So we will take these two and simply drag and drop. Okay, so exited, and then we will put gender. And if we drag and drop into the analysis side of Tableau. All right, so here what we are doing is we are showing male, female as two different columns here, and 0 for people who did not exist and 1 for people who exited, and that is color coded. So the blue color means people who did not exit, and this yellow color means people who did exit. All right, so now if we pull the data here, create like bar graphs, this is how it would look. So what is yellow? Let's go back. So yellow is who exited, and for the male only 16.45% have exited. And we can also draw a reference line that will help us, or even provide aliases. So these are a lot of fancy stuff that is provided by Tableau. You can create aliases, and so that it looks good rather than basic labels. And you can also add a reference line. So if you add a reference line, something like this, from here we can make out that on an average female customers exit more than the male customers, right? So that is what we are seeing here on an average. So we have analyzed based on gender. We do see that there is some difference in the male and female behavior. Now let's take the next criteria, which is the credit card. So let's see if having a credit card has any impact on the customer exit behavior. So just like before, we drag and drop the credit card has credit card column. If we drag and drop here, and then we will see that there is pretty much no difference between people having credit card and not having credit card. 20.81% of people who have no credit card have exited, and similarly 20.18% of people who have credit card have also exited. So the credit card is not having much of an impact. That's what this piece of analysis shows. Last, we will basically go and check how the geography is impacting. So once again, we can drag and drop geography column onto this side, and if we see here, there are geographies like, I think there are about 3 geographies like France, Germany, and Spain, and we see that there is some kind of impact with the geography as well. Okay, so what we derive from this is that the credit card is really, we can ignore the credit card variable or feature from our analysis because that doesn't have any impact, but gender and geography we can keep and do further analysis. Okay, all right. So what are some of the advantages of data mining? Bit more detailed analysis can help us in predicting the future trends, and it also helps in identifying customer behavior patterns. Okay, so you can take informed decisions because the data is telling you or providing you with some insights, and then you take a decision based on that. If there is any fraudulent activity, data mining will help in quickly identifying such a fraud as well. And of course, it will also help us in identifying the right algorithm for performing more advanced data mining activities like machine learning and so on. All right, so the next activity, now that we have the data, we have prepared the data and perform some data mining activity, the next step is model building. Let's take a look at model building. So what is a model building? If we want to perform a more detailed data mining activity, like maybe perform some machine learning, then you need to build a model. And how do you build a model? First thing is you need to select which algorithm you want to use to solve the problem on hand, and also what kind of data that is available, and so on and so forth. So you need to make a choice of the algorithm, and based on that you go ahead and create a model, train the model, and so on. Now machine learning is kind of at a very high level classified into supervised and unsupervised. So if we want to predict a continuous value, could be a price or a temperature or a height or a length or things like that. So those are continuous values, and if you want to find some of those, then you use techniques like regression, linear regression, simple linear regression, multiple linear regression, and so on. So these are the algorithms. On the other hand, there will be situations, or there may be situations where you need to perform unsupervised learning. In case of unsupervised learning, you don't have any historical labeled data so to learn from. So that is when you use unsupervised learning, and some of the algorithms in unsupervised learning are clustering. K-means clustering is the most common algorithm used in unsupervised learning. And similarly, in supervised learning, if you want to perform some activity on categorical values, like for example, it is not measured but it is counted, like you want to classify whether this image is a cat or a dog, whether you want to classify whether this customer will buy the product or not, or you want to classify whether this email is spam or not spam. So these are examples of categorical values, and these are examples of classification. Then you have algorithms like logistic regression, k nearest neighbor or KNN, and support vector machine. So these are some of the algorithms that are used in this case. And similarly, in case of unsupervised learning, if you need to perform on categorical values, you have some algorithms like association analysis and hidden Markov model. Okay, so in order to understand this better, let's take an example and take you through the whole process, and then we will also see how the code can be written to perform this. Now let's take our example here where we want to perform a supervised learning, which is basically we want to do a multilinear regression, which means there are multiple independent variables, and then we want to perform a linear regression to predict certain value. So in this particular example, we have world happiness data. So this is the data about the happiness quotient of people from various countries, and we are trying to predict and see whether how our model will perform. So what is the question that we need to ask? First of all, how to describe the data, and then can we make a predictive model to calculate the happiness score, right? So based on this, we can then decide on what algorithm to use and what model to use, and so on. So variables that are available or used in this model, this is a list of variables that are available. There is a happiness rank. I'll load the data or I'll show you the data in a little bit. So it becomes clear what are these. So there is what is known as a happiness rank, happiness score, which is happiness score is more like an absolute value, whereas rank is what is the ranking. And then which country we are talking about, and within that country which region, and what kind of economy, and whether the family, which family, and health details, and freedom, trust, generosity, and so on and so forth. So there are multiple variables that are available to us, and the specific details probably are not required, and there can be in another example the variables can be completely different, so we don't have to go into the details of what exactly these variables are, but it's just enough to understand that we have a bunch of these variables, and now we need to use either all or some of these variables, and then which we also sometimes refer to as features, and then we need to build our model and train our model. Alright, so let's assume we will use Python in order to perform this analysis or perform this machine learning activity, and I will actually show you in our lab in a little bit. This whole thing we will run the live code, but quickly I will run you through the slides and then we will go into the lab. So what are we doing here? First thing we need to do is import a bunch of libraries in Python which are required to perform our analysis. Most of these are for manipulating the data, preparing the data, and then scikit-learn or sklearn is the library which we will use actually for this particular machine learning activity, which is linear regression. So we have NumPy, we have pandas, and so on and so forth. So all these libraries are imported, and then we load our data, and the data is in the form of a CSV file, and there are different files for each year. So we have data for 2015, 16, and 17, and so we will load this data and then combine them, concatenate them to prepare a single data frame. And here we are making an assumption that you are familiar with Python, so it becomes easier if you are familiar with Python programming language, or at least some programming language, so that you can at least understand by looking at the code. So we are reading the file, each of these files for each year, and this is basically we are creating a list of all the names of the columns we will be using later on. You will see in the code. So we have loaded 2015, then 2016, and then also 2017. So we have created 3 data frames, and then we concatenate all these 3 data frames. This is what we are doing here. Then we identify which of these columns are required, which, for example, some of the categorical values do we really need? We probably don't. Then we drop those columns so that we don't unnecessarily use all the columns and make the computation complicated. We can then create some plots using Plotly library, and it has some powerful features including creation of maps and so on, just to understand the pattern, the happiness quotient, or how the happiness is across all the countries. So it's a nice visualization. We can see each of these countries, how they are in terms of their happiness score. This is the legend here. So the lighter colored countries have lower ranking, and so these are the lower ranking ones, and these are higher ranking, which means that the ones with these dark colors are the happiest ones. So as you can see here, Australia and maybe this side US and so on are the happiest ones. Okay, the other thing that we need to do is the correlation between the happiness score and happiness rank. We can find a correlation using a scatter plot, and we find that yes, they are kind of inversely proportional, which is obvious. So if the score is high, happiness score is high, then they are ranked number 1, for example. Highest is scored as number 1. So that's the idea behind this. So the happiness score given here and the happiness rank is actually given here. So they are inversely proportional, because the higher the score, the absolute value of the rank will be lower, right? So number 1 has the highest value of the score and so on. So they are inversely correlated, but there is a strong, what this graph shows is that there is a strong correlation between happiness rank and happiness score. And then we do some more plots to visualize this. We determine that probably rank and score are pretty much conveying the same message, so we don't need both of them. So we will kind of drop one of them, and that is what we are doing here. So we drop the happiness rank. And similarly, so this is one example of how we can remove some columns which are not adding value. So we will see in the code as well how that works. Moving on, this is a correlation between pretty much each of the columns with the other columns. So this is a correlation you can plot using plot function, and we will see here that, for example, happiness score and happiness score are correlated, strongest correlation, right? Because every variable will be highly correlated to itself. So that's the reason. So the darker the color is, the higher the correlation. And correlation in numerical terms goes from 0 to 1. So 1 is the highest value and it can only be between 0 and 1. Correlation between two variables can be only have a value between 0 and 1. So the numerical value can go from 0 to 1, and 1 here is dark color, and 0 is kind of dark but it is blue color. From red it goes down, the dark blue color indicates pretty much no correlation. So from this heat map we see that happiness and economy and family are probably, also health probably are the most correlated, and then it keeps decreasing after freedom, kind of keeps decreasing and coming to pretty much 0. Alright, so that is a correlation graph, and then we can probably use this to find out which are the columns that need to be dropped, which do not have very high correlation, and we take only those columns that we will need. So this is the code for dropping some of the columns. Once we have prepared the data, when we have the required columns, then we use scikit-learn to actually split the data. First of all, this is a normal machine learning process. You need to split the data into training and test data set. In this case, we are splitting into 80-20. So 80 is the training data set and 20 is the test data set. So that's what we are doing here. So we use train test split method or function. So you have all your training data in x_train, the labels in y_train. Similarly, x_test has the test data, the inputs, whereas the labels are in y_test. So that's how, and this value, whether it is 80-20 or 50-50, that is all individual preference. So in our case, we are using 80-20. All right. And then the next is to create a linear regression instance. So this is what we are doing. We are creating an instance of linear regression, and then we train the model using the fit function, and we are passing x and y, which is the x value and the label data, regular input and the label data, label information. Then we do the test. We run we perform the evaluation on the test data set. So this is what we are doing with the test data set, and then we will evaluate how accurate the model is and using the scikit-learn functionality itself. We can also see what are the various parameters and what are the various coefficients, because in linear regression you will get like a equation of like a straight line, y is equal to beta 0 plus beta 1 x1 plus beta 2 x2. Those beta 1, beta 2, beta 3 are known as the coefficients, and beta 0 is the intercept. After the training, you can actually get these information of the model. What is the intercept value, what are the coefficients, and so on, by using these functions. So let's quickly go into the lab and take a look at our code. Okay, so this is my lab. This is my Jupyter notebook where the code, I have the actual code, and I will take you through this code to run this linear regression on the world happiness data. So we will import a bunch of libraries, NumPy, Pandas, Plotly, and so on. Also, yeah, scikit-learn, that's also very important. So that's the first step. Then I will import my data, and the data is in 3 parts. There are 3 files, one for each year, 2015, 2016, and 2017, and it is a CSV file. So I've imported my data. Let's take a look at the data, quickly glance at data. So this is how it looks. We have the country, region, happiness rank, and then happiness score. There are some standard errors, and then what is the per capita, family, and so on. So, and then we will keep going. We will create a list of all these column names we will be using later. So for now, I will run this code, and no need of major explanation at this point. We know that some of these columns probably are not required. So you can use this drop functionality to remove some of the columns which we don't need. Like for example, region and standard error will not be contributing to our model. So we will basically drop those values out here. So we use the drop, and then we created a vector with these names, column names. That's what we are passing here. Instead of giving the names of the columns here, we can pass a vector. So that's what we are doing. So this will drop from our data frame. It will remove region and standard error, these two columns. Then the next step, we will read the data for 2016 and also 2017, and then we will concatenate this data. So let's do that. So we have now data frame called happiness, which is a concatenation of both all the three files. Let's take a quick look at the data now. So most of the unwanted columns have been removed, and you have all the data in one place for all the 3 years, and this is how the data looks. And if you want to take a look at the summary of the columns, you can say describe, and you will get this information. For example, for each of the columns, what is the count, what is the mean value, standard deviation, especially the numeric values, okay, not the categorical values. So this is a quick way to see how the data is, and initial little bit of exploratory analysis can be done here. So what is the maximum value, what's the minimum value, and so on for each of the columns. Alright, so then we go ahead and create some visualizations using Plotly. So let us go and build a plot. So if we see here, now this is the correlation between happiness rank and happiness score. This is what we have seen in the slides as well. We can see that there is a tight correlation between them. Only thing is it is inverse correlation, but otherwise they are very tightly correlated, which also says that they both probably provide the same information. So there is not much of value add. So we'll go ahead and drop the happiness rank as well from our columns. So that's what we are doing here. And now we can do the creation of the correlation heat map. Let us plot the correlation heat map to see how each of these columns is correlated to the others. And as we have seen in the slides, this is how it looks. So happiness score is very highly correlated. So this is the legend we have seen in the slide as well. So blue color indicates pretty much 0 or very low correlation. Deep red color indicates very high correlation, and the value correlation is a numeric value, and the value goes from 0 to 1. If two items or two features or columns are highly correlated, then there will be as close to 1 as possible, and two columns that are not at all correlated will be as close to 0 as possible. So that's how it is. For example, here happiness score and happiness score, every column or every feature will be highly correlated to itself. So it is like between them there will be correlation value will be 1. So that's why we see deep red color. But then others are, for example, with higher values are economy, and then health, and then maybe family and freedom. So these are generosity and trust are not very highly correlated to happiness score. So that is one quick exploratory analysis we can do, and therefore we can drop the country and the happiness rank, because they also again don't have any major impact on the analysis, on our analysis. So now we have prepared our data. There was no need to clean the data because the data was clean, but if there were some missing values and so on, as we have discussed in the slides, we would have had to perform some of the data cleaning activities as well. But in this case, the data was clean. All we needed to do was just the preparation part. So we removed some unwanted columns and we did some exploratory data analysis. Now we are ready to perform the machine learning activity. So we use scikit-learn for doing the machine learning. Scikit-learn is a Python library that is available for performing our machine learning. Once again, we will import some of these libraries like pandas and numpy, and also scikit-learn. First step we will do is split the data in 2080 format. So you have all the test data, which is 20% of the data is test data and 80% is your training data. So this test size indicates how much of it is in the what is the size of the test data. So the remaining, which is here we are saying 0.2, therefore that means training is 0.8. So training data is 80%. All right, so we have executed that, split the data, and now we create an instance of the linear regression model. So LM is our linear regression model, and we pass X and Y, the training data set, and call the function fit so that the model gets trained. So now once that is done, training is completed, and now what we have to do is we need to predict the values for the test data. So the next step is using, so you see here fit will basically run the training method, predict will actually predict the values. So we are passing the input values, which is the independent variables, and we are asking for the values of the dependent variable, which we are capturing in y_pred, and we use the predict method here, lm.predict. So this will give us all the predicted y values, and remember we already have y_test has the actual values, which are the labels, so that we can use these two to compare and find out how much of it is error. So that's what we are doing here. We are trying to find the difference between the predicted value and the actual value. Y_test is the actual value for the test data, and y_predict is the predicted value. We just found out the predicted value. So we will run that and we can do a quick check as to how the data looks, how is the difference. So in some cases it is positive, some cases it is negative, but in most of the cases I think the difference is very small. This is exponential to the power of 0, -0.4 and so on. So looks like our model has performed reasonably well. We can now check some of the parameters of our model, like the intercept and the coefficients. So that's what we are doing here. So these are the coefficients of the various parameters that we are, the coefficients of the various independent variables. Okay, so these are the values. Then we can quickly go ahead and list them down as well against the corresponding independent variable. So the coefficients against the corresponding independent variable. So 1.00051 is the coefficient for economy, 0.99983 is for family, coefficient for family and health, and so on and so forth, right? So that's what this is showing. Now we can use the functionality, readily available functionality of scikit-learn, and then plot that to find some of the parameters which determine the accuracy of this model, like for example what is the mean square error and so on. So that's what we are doing here. So let's just go ahead and run this. So you can see here that the root mean square error is pretty low, which is a good sign, and which is one of the measures of how well our model is performing. We can do one more quick plot to just see how the actual values and the predicted values are looking. And once again you can see that, as we have seen from the root mean square error is very, very low. That means that the actual values and the predicted values are pretty much matching up, almost matching up, and this plot also shows the same. So this line is going through the predicted values and the actual values, and the difference is very, very low. So again, this is actual data. This is one example where the accuracy is high and the predicted values are pretty much matching with the actual values, but in real life you may find that these values are slightly more scattered, and you may get the error value can be relatively on the higher side, the root mean square error. Okay, so this was a good and quick example of the code to perform data science activity or a machine learning or data mining activity. In this case, we did what is known as linear regression. So let's go back to our slides and see what else is there. So we saw this. These are the coefficients of each of the features in our code, and we have seen the root mean square error as well, and we can take a few hundred countries, certain values, and actually predict to see if how the model is performing, and I think we have done this as well. And in this case, as we have seen, pretty much the predicted values and the actual values are pretty much matching, which means our model is almost 100% accurate. As I mentioned, in real life it may not be the case, but in this particular case we have got a pretty good model, which is very good. Also, subsequently we can assume that this is how the equation in linear regression, the model is nothing but an equation like y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 and so on. So this is what we are showing here. So this is our intercept, which is beta 0, and then we have beta 1 into economy value, beta 2 into the family value, beta 3 into health value, and so on. So that is what is shown here. Okay, so I think the next step, once we have the results from the data mining or machine learning activity, the next step is to communicate these results to the appropriate stakeholders. So that is what we will see here now. So how do we communicate? Usually you take these results and then either prepare a presentation or put it in a document and then show them these actionable results or actionable insights. And you need to find out who are your target audience and put all the results in context. And maybe if there was a problem statement, you need to put the results in the context of the problem statement. What was our initial goal that we wanted to achieve? So that we need to communicate here. Based based on, you remember we started off with what is the question and what is the data and so on, and then what is the answer. So we need to put the results and then what is the methodology that we have used. All that has to be put and clearly communicated in business terms so that the people understand very well from a business perspective. So once the model building is done, once the results are published and communicated, the last part is maintenance of this model. Now, very often what can happen is the model may have to be subsequently updated or modified because of multiple reasons. Either the data has changed, the way the data comes has changed, or the process has changed, or for whatever reason the accuracy may keep changing. Once you have trained the model, for example, we got a very high accuracy, but then over a period of time there can be various factors which can cause that. So from time to time we need to check whether the model is performing well or not. The accuracy needs to be tested once in a while, and if required you may have to rebuild or retrain the model. So you do the assessment, you see if it needs any tweaks or changes, and then if it is required you need to probably retrain the model with the latest data that you have, and then you deploy it. You build the model, train it, and then you deploy it. So that is like the maintenance cycle that you may have to take the model.
Data analyst versus data engineer versus data scientist. Which one to choose? This is one of the most popular questions asked by learners looking for a career in data and analytics. I'm sure you too would have come across these job roles in the ever-growing data science landscape. Though they all deal with data, these jobs are not the same. There are significant differences between what a data analyst, data engineer, and a data scientist does. We will look at these job roles and the differences in detail. First, let's look at some data analytics and data science trends. The analytics and data science market is thriving. Data analytics, data engineering, and data science are the key trends in today's accelerating market. As per Statista.com, the global big data analytics market revenue will grow at a CAGR of 30%, with revenue reaching over $68 billion by 2025. According to TechNavio, the enterprise data management market is expected to increase by $64.08 billion by 2025. As per marketsandmarkets.com, the big data market size is projected to grow from $162.6 billion in 2021 to $273.4 billion in 2026. Now, another report from Research Drive says that the data science platform market is estimated to reach $224.3 billion by 2026. So with so much data available and companies making huge investments to drive business insights, the job opportunities for data analysts, data engineers, and data scientists are going to increase in 2022 and over the coming years. Now, let's learn the major differences between data analyst versus data engineer versus data scientist. So, who are they? A data analyst analyzes and interprets vast volumes of data in order to extract meaningful information out of it. They find solutions to a business problem and make critical business decisions. The insights provided by data analysts are important to companies that want to understand the needs of their end customers. Now, talking about who a data engineer is, a data engineer, on the other hand, builds infrastructure and scalable pipelines to manage the flow of data and prepare it for analysis. So basically, they optimize the systems that enable data analysts and data scientists to perform their job efficiently. Data scientists are professionals who analyze and visualize existing data and use algorithms to build predictive models for making future decisions. They also engage with business leaders to understand their needs and present complex findings. With that, let's look at the primary roles and responsibilities of these three job roles. Data analysts are responsible to collect, clean, store, and process data. They discover hidden patterns from data by performing exploratory data analysis and visualize data by creating charts and graphs. Acquiring data from primary and secondary sources is one of their key tasks. They build reports and dashboards and also maintain databases. Now, talking about the roles and responsibilities of a data engineer. A data engineer performs data acquisition. They design, build and test data as well to develop and maintain data architecture. Data engineers are tasked with testing, integrating, managing and optimizing data from a variety of sources. So they integrate data into existing data pipelines, prepare data for modeling and perform various ETL operations. Now, talking about the roles and responsibilities of a data scientist. So data scientists develop machine learning models to identify trends in data for making decisions. They develop hypotheses and use their knowledge of statistics, data visualization and machine learning to forecast the future for the business. Data scientists visualize data and use storytelling techniques and also write programs to automate data collection and processing. Now move on to the skills possessed by data analysts, data engineers and data scientists. To become a data analyst, you need to have good hands-on experience with writing SQL queries. You should have excellent Microsoft Excel skills for analyzing data. Data analysts are also good at programming and they need to know how to visualize data, solve business problems and possess domain knowledge. Data engineers should have a solid understanding of SQL, MongoDB and programming. They need to have a good command of data architecture, scripting, data warehousing, and ETL. Data engineers are also good at Hadoop-based analytics. Now, talking about the skills for a data scientist. So a data scientist should have experience with programming in Python and R. They should have a very good understanding of mathematics and statistics as well. Data scientists need to possess analytical thinking and data visualization skills as well. Machine learning, deep learning, and decision making are other critical skills every data scientist should have. Now, we'll look at the salaries of a data scientist, a data analyst, as well as a data engineer. So, a data analyst in the United States earns over $70,000 per annum, while in India, a data analyst can earn nearly 7,25,000 rupees per annum. A data engineer in the United States can earn over $112,500 per year, and in India, you can earn over 9 lakh rupees per annum. Now, talking about the salary of a data scientist in the United States earns over $117,000 per annum, and in India, a data scientist can earn over 11 lakh rupees per annum. Now, coming to the final section of this video, we'll look at the top companies hiring for data analysts, data engineers, and data scientists. So we have the first company as Google, then we have Tesla, next we have the e-commerce giant Amazon, the internet giant Facebook or the social media giant Facebook, we have the tech giant Oracle, we also have Verizon and Airbnb. So these are some of the top companies that hire for the 3 roles.
Now let's talk about the life cycle of a data science project. Okay, the first step is the concept study. In this step, it involves understanding the business problem, asking questions, get a good understanding of the business model, meet up with all the stakeholders, understand what kind of data is available, and all that is a part of the first step. So here are a few examples. We want to see what are the various specifications, and then what is the end goal, what is the budget, is there an example of this kind of a problem that has been maybe solved earlier. So all this is a part of the concept study. And another example could be a very specific one to predict the price of a 1.35 carat diamond, and there may be relevant information, inputs that are available, and we want to predict the price. The next step in this process is data preparation, data gathering and data preparation, also known as data munging, or sometimes it is also known as data manipulation. So what happens here is the raw data that is available may not be usable in its current format for various reasons. So that is why in this step, a data scientist would explore the data. he will take a look at some sample data, maybe pick, if there are millions of records, pick a few thousand records and see how the data is looking. Are there any gaps? Is the structure appropriate to be fed into the system? Are there some columns which are probably not adding value, may not be required for the analysis? Very often these are like names of the customers. They will probably not add any value or much value from an analysis perspective. The structure of the data, maybe the data is coming from multiple data sources and the structures may not be matching. What are the other problems? There may be gaps in the data. So the data, all the columns, all the cells are not filled. If you're talking about structured data, there are several blank records or blank columns. So if you use that data directly, you'll get errors or you'll get inaccurate results. So how do you either get rid of that data or how do you fill these gaps with something meaningful? So all that is a part of data munging or data manipulation. So these are some additional subtopics within that. So data integration is one of them. If there are any conflicts in the data, data may be redundant. Yeah, data redundancy is another issue. There may be, you have, let's say, data coming from two different systems and both of them have customer table, for example, customer information. So when you merge them, there is a duplication issue. So how do we resolve that? So that is one. Data transformation. As I said, there will be situations where data is coming from multiple sources and then when we merge them together, they may not be matching. So we need to do some transformations to make sure everything is similar. We may have to do some data reduction. If the data size is too big, you may have to come up with ways to reduce it meaningfully without losing information. Then data cleaning. So there will be either wrong values or null values or there are missing values. So how do you handle all of that? A few examples of very specific stuff. So if there are missing values, how do you handle missing values or null values? Here in this particular slide, we are seeing three types of issues. One is missing value. Then you have null value. You see the difference between the two, right? So in the missing value, there is nothing, blank. Null value, it says null. Now, the system cannot handle if there are null values. Similarly, there is improper data. So it's supposed to be numeric value, but there is a string or a non-numeric value. So how do we clean and prepare the data so that our system can work flawlessly? So there are multiple ways and there is no one common way of doing this. It can vary from project to project. It can vary from what exactly is the problem we are trying to solve. It can vary from data scientist to data scientist, organization to organization. So these are like some standard practices people come up with. And of course, there will be a lot of trial and error. Somebody would have tried out something and it worked and will continue to use that mechanism. So that's how we need to take care of data cleaning. Now, what are the various ways of doing, if values are missing? How do you take care of that? Now, if the data is too large and only a few records have some missing values, then it is okay to just get rid of those entire rows, for example. So if you have 1 million records and out of which 100 records don't have full data, so there are some missing values in about 100 records. So it's absolutely fine because it's a small percentage of the data. So you can get rid of the entire records which have missing values. But that's not a very common situation. Very often you will have multiple or at least a large number of data set. For example, out of 1 million records, you may have 50,000 records which are like having missing values. Now, that's a significant amount. You cannot get rid of all those records. Your analysis will be inaccurate. So how do you handle such situations? So there are again multiple ways of doing it. One is you can probably, if a particular values are missing in a particular column, you can probably take the mean value for that particular column and fill all the missing values with the mean value. So that first of all, you don't get errors because of missing values. And second, you don't get results that are way off because these values are completely different from what is there. So that is one way. Then a few other could be either taking the median value or depending on what kind of data we are talking about. So something meaningful we will have put in there. If we are doing some machine learning activity, then obviously as a part of data preparation, you need to split the data into training and test data set. The reason being, if you try to test with a data set which the system has already seen as a part of training, then it will tend to give reasonably accurate results because it has already seen that data, and that is not a good measure of the accuracy of the system. So typically you take the entire data set, the input data set, and split it into two parts. And again, the ratio can vary from person to person, individual preferences. Some people like to split it into 50-50. Some people like it as 63.33 and 33.3 is basically 2/3 and 1/3. And some people do it as 80-20. 80 for training and 20 for testing. So you split the data, perform the training with the 80%, and then use the remaining 20% for testing. All right. So that is one more data preparation activity that needs to be done before you start analyzing or applying the data or putting the data through the model. Then the next step is model planning. Now these models can be statistical models, this could be machine learning models. So you need to decide what kind of models you're going to use. Again, it depends on what is the problem you're trying to solve. If it is a regression problem, you need to think of a regression algorithm and come up with a regression model. So it could be linear regression. Or if you're talking about classification, then you need to pick up an appropriate classification algorithm like Logistic Regression or decision tree or SVM, and then you need to train that particular model. So that is the model building or model planning process, and the cleaned up data has to be fed into the model. And apart from cleaning, you may also have to, in order to determine what kind of model you will use, you have to perform some exploratory data analysis to understand the relationship between the various variables and see if the data is appropriate and so on, right? So that is the additional preparatory step that needs to be done. So a little bit of details about exploratory data analysis. So what exactly is exploratory data analysis? It's basically to, as the name suggests, you're just exploring. You just receive the data and you're trying to explore and find out what are the data types and what is the data clean in each of the columns. What is the maximum minimum value? So for example, there are out of the box functionality available in tools like R. So if you just ask for a summary of the table, it will tell you for each column, it will give some details as to what is the mean value, what is the maximum value, and so on and so forth. So this exercise or this exploratory analysis is to get an understanding of your data. And then you can take steps to, during this process, you find there are a lot of missing values. You need to take steps to fix those. You will also get an idea about what kind of model to be used and so on and so forth. What are the various techniques used for exploratory data analysis? Typically, these would be visualization techniques, like you use histograms, you can use box plots, you can use scatter plots. So these are very quick ways of identifying the patterns or a few of the trends of the data and so on. And then once your data is ready, you've decided on the model, what kind of algorithm you're going to use. If you're trying to do machine learning, you need to pass your 80% the training data, or rather you use that training data to train your model. And the training process itself is iterative. So the training process you may have to perform multiple times. And once the training is done and you feel it is giving good accuracy, then you move on to test. So you take the remaining 20% of the data. Remember, we split the data into training and test. So the test data is now used to check the accuracy or how well our model is performing. And if there are further issues, let's say, and model is still, during testing, if the accuracy is not good, then you may want to retrain your model or use a different model. So this whole thing again can be iterative. But if the test process is passed, or if the model passes the test, then it can go into production and it will be deployed. All right. So what are the various tools that we use for model planning? R is an excellent tool in a lot of ways. Whether you're doing regular statistical analysis or machine learning or any of these activities, R, along with R Studio, provides a very powerful environment to do data analysis, including visualization. It has a very good integrated visualization or plot mechanism, which can be used for doing exploratory data analysis and then later on to do analysis, detailed analysis, and machine learning, and so on and so forth. Then, of course, you can write Python programs. Python offers a rich library for performing data analysis and machine learning and so on. MATLAB is a very popular tool as well, especially during education. So this is a very easy to learn tool. So MATLAB is another tool that can be used. And then last but not least, SAS. SAS is again very powerful. It is a proprietary tool and it has all the components that are required to perform very good statistical analysis or perform data science. So those are the various tools that would be required for or that can be used for model building. And so the next step is model building. So we have done the planning part. We said, okay, what is the algorithm we are going to use? What kind of model we are going to use? Now we need to actually train this model or build the model rather so that it can then be deployed. So what are the various ways or what are the various types of model building activities? So it could be, let's say in this particular example that we have taken, you want to find out the price of 1.35 carat diamond. So this is, let's say, a linear regression problem. You have data for various carats of diamond and you use that information, you pass it through a linear regression model or you create a linear regression model which can then predict your price for 1.35 carat. So this is one example of model building. And then a little bit details of how linear regression works. So linear regression is basically coming up with a relation between an independent variable and a dependent variable. So it is pretty much like coming up with equation of a straight line which is the best fit for the given data. So like for example here, y is equal to mx plus c. So y is the dependent variable and x is the independent variable. We need to determine the values of m and c for our given data. So that is what the training process of this model does. At the end of the training process, you have a certain value of m and c, and that is used for predicting the values of any new data that comes. All right, so the way it works is we use the training and the test data set to train the model and then validate whether the model is working fine or not using test data. And if it is working fine, then it is taken to the next level, which is put in production. If not, the model has to be retrained. If the accuracy is not good enough, then the model is retrained, maybe with more data, or you come up with a newer model or algorithm and then repeat that process. So it is an iterative process. Once the training is completed, training and test, then this model is deployed and we can use this particular model to determine what is the price of 1.35 carat diamond. Remember, that was our problem statement. So now that we have the best fit for this given data, we have the price of 1.35 carat diamond, which is 10,000. So this is one example of how this whole process works. Now, how do we build the model? There are multiple ways. You can use Python, for example, and use libraries like Pandas or NumPy to build the model and implement it. This will be available as a separate tutorial, a separate video in this playlist. So stay tuned for that. Moving on, once we have the results, the next step is to communicate these results to the appropriate stakeholders. So which is basically taking this results and preparing like a presentation or a dashboard and communicating these results to the concerned people. So finishing or getting the results of the analysis is not the last step, but you need to, as a data scientist, take these results and present it to the team that has given you this problem in the first place and explain your findings, explain the findings of this exercise and recommend maybe what steps they need to take in order to overcome this problem or solve this problem. So that is the pretty much once that is accepted, and the last step is to operationalize. So if everything is fine, your data scientist presentations are accepted, then they put it into practice and thereby they will be able to improve or solve the problem that they stated in step 1. Okay, so quick summary of the life cycle. You have a concept study, which is basically understanding the problem, asking the right questions, and trying to see if there is enough data to solve this problem. And then even maybe gather the data. Then data preparation, the raw data needs to be manipulated. You need to do data munging so that you have the data in a certain proper format to be used by the model or our analytics system. And then you need to do the model planning, what kind of a model, what algorithm you will use for a given problem, and then the model building. So the exact execution of that model happens in step 4, and you implement and execute that model and put the data through the analysis in this step, and then you get the results. These results are then communicated, packaged and presented and communicated to the stakeholders, and once that is accepted, that is operationalized. So that is the final step.
Let's begin this lesson by defining the term statistics. Statistics is a mathematical science pertaining to the collection, presentation, analysis, and interpretation of data. It's widely used to understand the complex problems of the real world and simplify them to make well-informed decisions. Several statistical principles, functions, and algorithms can be used to analyze primary data, build a statistical model, and predict the outcomes. An analysis of any situation can be done in 2 ways: statistical analysis or a non-statistical analysis. Statistical analysis is the science of collecting, exploring, and presenting large amounts of data to identify the patterns and trends. Statistical analysis is also called quantitative analysis. Non-statistical analysis provides generic information and includes text, sound, still images, and moving images. Non-statistical analysis is also called qualitative analysis. Although both forms of analysis provide results, statistical analysis gives more insight and a clearer picture, a feature that makes it vital for businesses. There are 2 major categories of statistics: descriptive statistics and inferential statistics. Descriptive statistics helps organize data and focuses on the main characteristics of the data. It provides a summary of the data numerically or graphically. Numerical measures such as average, mode, standard deviation or SD, and correlation are used to describe the features of a dataset. Suppose you want to study the height of students in a classroom. In the descriptive statistics, you would record the height of every person in the classroom and then find out the maximum height, minimum height, and average height of the population. Inferential statistics generalizes the larger dataset and applies probability theory to draw a conclusion. It allows you to infer population parameters based on the sample statistics and to model relationships within the data. Modeling allows you to develop mathematical equations which describe the interrelationships between 2 or more variables. Consider the same example of calculating the height of students in the classroom. In inferential statistics, you would categorize height as tall, medium, and small, and then take only a small sample from the population to study the height of students in the classroom. The field of statistics touches our lives in many ways, from the daily routines in our homes to the business of making the greatest cities run. The effect of statistics are everywhere. There are various statistical terms that one should be aware of while dealing with statistics: population, sample, variable, quantitative variable, qualitative variable, discrete variable, continuous variable. A population is the group from which data is to be collected. A sample is a subset of a population. A variable is a feature that is characteristic of any member of the population differing in quality or quantity from another member. A variable differing in quantity is called a quantitative variable. For example, the weight of a person, number of people in a car. A variable differing in quality is called a qualitative variable or attribute. For example, color, the degree of damage of a car in an accident. A discrete variable is one which no value can be assumed between the 2 given values. For example, the number of children in a family. A continuous variable is one in which any value can be assumed between the 2 given values. For example, the time taken for a 100-meter run. Typically, there are 4 types of statistical measures used to describe the data. They are measures of frequency, measures of central tendency, measures of spread, measures of position. Let's learn each in detail. Frequency of the data indicates the number of times a particular data value occurs in the given dataset. The measures of frequency are number and percentage. Central tendency indicates whether the data values tend to accumulate in the middle of the distribution or toward the end. The measures of central tendency are mean, median, and mode. Spread describes how similar or varied the set of observed values are for a particular variable. The measures of spread are standard deviation, variance, and quartiles. The measure of spread are also called measures of dispersion. Position identifies the exact location of a particular data value in the given data set. The measures of position are percentiles, quartiles, and standard scores. Statistical Analysis System, or SAS, provides a list of procedures to perform descriptive statistics. They are as follows: proc print, proc contents, proc means, proc frequency, proc univariate, proc gchart, proc boxplot, proc gplot. Proc print. It prints all the variables in a SAS dataset. Proc contents. It describes the structure of a dataset. Proc means. It provides data summarization tools to compute descriptive statistics for variables across all observations and within the groups of observations. Proc frequency. It produces one-way to n-way frequency and cross-tabulation tables. Frequencies can also be an output of a SAS dataset. Proc univariate. It goes beyond what proc means does and is useful in conducting some basic statistical analyses and includes high-resolution graphical features. Proc gchart. The gchart procedure produces 6 types of charts: block charts, horizontal, vertical bar charts, pie, donut charts, and star charts. These charts graphically represent the value of a statistic calculated for one or more variables in an input SAS dataset. The charted variables can be either numeric or character. Proc boxplot. The boxplot procedure creates side-by-side box and whisker plots of measurements organized in groups. A box and whisker plot displays the mean, quartiles, and minimum and maximum observations for a group. Proc gplot. Gplot procedure creates 2-dimensional graphs, including simple scatter plots, overlay plots in which multiple sets of data points are displayed on one set of axes, plots against a second vertical axis, bubble plots, and logarithmic plots. In this demo, you'll learn how to use descriptive statistics to analyze the mean from the electronic dataset. Let's import the electronic dataset into the SAS console. In the left plane, right-click the electronic.xlsx dataset and click Import Data. The code to import the data generates automatically. Copy the code and paste it in the new window. The proc means procedure is used to analyze the mean of the imported dataset. The keyword data identifies the input dataset. In this demo, the input dataset is electronic. The output obtained is shown on the screen. Note that the number of observations, mean, standard deviation, and maximum and minimum values of the electronic dataset are obtained. This concludes the demo on how to use descriptive statistics to analyze the mean from the electronic dataset. So far, you have learned about descriptive statistics. Let's now learn about inferential statistics. Hypothesis testing is an inferential statistical technique to determine whether there is enough evidence in a data sample to infer that a certain condition holds true for the entire population. To understand the characteristics of the general population, we take a random sample and analyze the properties of the sample. We then test whether or not the identified conclusions correctly represent the population as a whole. The population of hypothesis testing is to choose between 2 competing hypotheses about the value of a population parameter. For example, One hypothesis might claim that the wages of men and women are equal, while the other might claim that women make more than men. Hypothesis testing is formulated in terms of two hypotheses: null hypothesis, which is referred to as H-null; alternative hypothesis, which is referred to as H1. The null hypothesis is assumed to be true unless there is strong evidence to the contrary. The alternative hypothesis is assumed to be true when the null hypothesis is proven false. Let's understand the null hypothesis and alternative hypothesis using a general example. Null hypothesis attempts to show that no variation exists between variables, and alternative hypothesis is any hypothesis other than the null. For example, say a pharmaceutical company has introduced a medicine in the market for a particular disease, and people have been using it for a considerable period of time, and it's generally considered safe. If the medicine is proved to be safe, then it is referred to as null hypothesis. To reject null hypothesis, we should prove that the medicine is unsafe. If the null hypothesis is rejected, then the alternative hypothesis is used. Before you perform any statistical tests with variables, it's significant to recognize the nature of the variables involved. Based on the nature of the variables, it's classified into four types. They are categorical or nominal variables, ordinal variables, interval variables, and ratio variables. Nominal variables are ones which have two or more categories, and it's impossible to order the values. Examples of nominal variables include gender and blood group. Ordinal variables have values ordered logically. However, the relative distance between two data values is not clear. Examples of ordinal variables include considering the size of a coffee cup, large, medium, and small, and considering the ratings of a product, bad, good, and best. Interval variables are similar to ordinal variables, except that the values are measured in a way where their differences are meaningful. With an interval scale, equal differences between scale values do have equal quantitative meaning. For this reason, an interval scale provides more quantitative information than the ordinal scale. The interval scale does not have a true zero point. A true zero point means that a value of 0 on the scale represents zero quantity of the construct being assessed. Examples of interval variables include the Fahrenheit scale used to measure temperature and distance between two compartments in a train. Ratio scales are similar to interval scales in that equal differences between scale values have equal quantitative meaning. However, ratio scales also have a true zero point, which give them an additional property. For example, the system of inches used with a common ruler is an example of a ratio scale. There is a true zero point because 0 inches does in fact indicate a complete absence of length. In this demo, you'll learn how to perform the hypothesis testing using SAS. In this example, let's check against the length of certain observations from a random sample. The keyword data identifies the input dataset. The input statement is used to declare the aging variable and cards to read data into SAS. Let's perform a t-test to check the null hypothesis. Let's assume that the null hypothesis to be that the mean days to deliver a product is 6 days. So null hypothesis equals 6. Alpha value is the probability of making an error, which is 5% standard, and hence alpha equals 0.05. The variable statement names the variable to be used in the analysis. The output is shown on the screen. Note that the p-value is greater than the alpha value, which is 0.05. Therefore, we fail to reject the null hypothesis. This concludes the demo on how to perform the hypothesis testing using SAS. Let's now learn about hypothesis testing procedures. There are two types of hypothesis testing procedures. They are parametric tests and non-parametric tests. In statistical inference or hypothesis testing, the traditional tests, such as t-test and ANOVA, are called parametric tests. They depend on the specification of a probability distribution except for a set of free parameters. In simple words, you can say that if the population information is known completely by its parameter, then it is called a parametric test. If the population or parameter information is not known, and you are still required to test the hypothesis of the population, then it's called a non-parametric test. Non-parametric tests do not require any strict distributional assumptions. There are various parametric tests. They are as follows: t-test, ANOVA, chi-squared, linear regression. Let's understand them in detail. T-test. A t-test determines if two sets of data are significantly different from each other. The t-test is used in the following situations: to test if the mean is significantly different than a hypothesized value, to test if the mean for two independent groups is significantly different, to test if the mean for two dependent or paired groups is significantly different. For example, let's say you have to find out which region spends the highest amount of money on shopping. It's impractical to ask everyone in the different regions about their shopping expenditure. In this case, you can calculate the highest shopping expenditure by collecting sample observations from each region. With the help of the t-test, you can check if the difference between the regions are significant or a statistical fluke. ANOVA. ANOVA is a generalized version of the t-test and used when the mean of the interval dependent variable is different to the categorical independent variable. When we want to check variance between two or more groups, we apply the ANOVA test. For example, let's look at the same example of the t-test example. Now you want to check how much people in various regions spend every month on shopping. In this case, there are four groups, namely East, West, North, and South. With the help of the ANOVA test, you can check if the difference between the regions is significant or a statistical fluke. Chi-square. Chi-square is a statistical test used to compare observed data with data you would expect to obtain according to a specific hypothesis. Let's understand the chi-square test through an example. You have a data set of male shoppers and female shoppers. Let's say you need to assess whether the probability of females purchasing items of $500 or more is significantly different from the probability of males purchasing items of $500 or more. Linear regression. There are two types of linear regression: simple linear regression and multiple linear regression. Simple linear regression is used when one wants to test how well a variable predicts another variable. Multiple linear regression allows one to test how well multiple variables, or independent variables, predict a variable of interest. When using multiple linear regression, we additionally assume the predictor variables are independent. For example, finding a relationship between any two variables, say sales and profit, is called simple linear regression. Finding a relationship between any three variables, say sales, cost, and telemarketing, is called multiple linear regression. Some of the non-parametric tests are Wilcoxon rank sum test and Kruskal-Wallis H-test. Wilcoxon rank sum test. The Wilcoxon signed rank test is a non-parametric statistical hypothesis test used to compare two related samples or matched samples to assess whether or not their population mean ranks differ. In Wilcoxon rank sum test, you can test the null hypothesis on the basis of the ranks of the observations. Kruskal-Wallis H-test. Kruskal-Wallis H-test is a rank-based non-parametric test used to compare independent samples of equal or different sample sizes. In this test, you can test the null hypothesis on the basis of the ranks of the independent samples. The advantages of parametric tests are as follows. Provide information about the population in terms of parameters and confidence intervals. Easier to use in modeling, analyzing, and for describing data with central tendencies and data transformations. Express the relationship between two or more variables. Don't need to convert data into rank order to test. The disadvantages of parametric tests are as follows. Only support normally distributed data. Only applicable on variables, not attributes. Let's now list the advantages and disadvantages of non-parametric tests. The advantages of non-parametric tests are as follows. Simple and easy to understand. Do not involve population parameters and sampling theory. Make fewer assumptions. Provide results similar to parametric procedures. The disadvantages of non-parametric tests are as follows. Not as efficient as parametric tests. Difficult to perform operations on large samples manually.
We'll discuss the types of distribution in statistics. But before we move ahead, let's have a brief introduction on what is probability distribution. A probability distribution is a list of all of the possible outcomes of a random variable along with their corresponding probability values. And it is used in many fields, but we rarely do explain what they are. So, in this video, we'll discuss the three main types of probability distribution, that is normal, binomial, and Poisson distribution. So, let's move ahead.
So what is normal distribution? Normal distribution is a continuous probability density that has a probability density function which gives us a symmetrical bell curve. Now data can be distributed or spread out in different ways, but there are many cases where the data tends to be around a central value with no bias to the left or right, which means that it doesn't show any particular spikes towards the left or the right, and it gets close to a normal distribution. Half of the data will fall on the left of the mean and the other half will fall on the right. Now let's take a look at a graph which shows the height distribution in a class. As you can see, the average height is in the middle and the data to the left of the average height represents the short people and the data to the right of it represents the taller people. The y-axis shows us the likelihood of any of these heights occurring. The average height has the most distribution, or it has the most number of cases in the class, and as the height decreases or increases, the number of people who have that height also decreases. This kind of a distribution is called a normal distribution, where the average or the mean is always the highest point and any other point after that or before that is significantly lower. The resulting data gives us a bell curve, and as you can see, there is no abrupt bias or spike in the data anywhere except for the average height. So this kind of a curve is called a bell curve, and it's usually seen in a normal distribution. The reason we call this a normal distribution is because the data is normally distributed, with the average being the highest and all the other data points having a lower likelihood. Now we came across two terms which are associated with normal distribution: continuous probability density and probability density function. What is continuous probability density? Continuous probability density is a probability distribution where the random variable x can take any given value. Because there are infinite values that x could assume, the probability of x taking on any specific value is 0. For example, let's say you have a continuous probability density for men's height. What is the probability that a man will have the exact height of 70 inches? It is impossible to find this out, because the probability of one man measuring exactly 70 inches is very low. It is more probable that he will measure around 70.1 inches or maybe 69.97 inches. And it doesn't stop there. The fact is that it's impossible to exactly measure any variable that's on a continuous scale, and because of this it's impossible to figure out the probability of one exact measurement which is occurring in a continuous probability density. Next we have the probability density function. It's nothing but a function or an expression which is used to define the range of values that a continuous random variable can take. An example of this would be to gauge the risk and reward of a stock. A probability density function is a statistical measure which is used to gauge the likelihood of a discrete value. A discrete variable can be measured exactly, while a continuous variable can have infinite values. However, for both continuous as well as discrete variables, we can define a function which gives us the range of values within which these variables will fall, and that function is known as the probability density function. Now let's take a look at standard deviation. What is standard deviation? Standard deviation is used to measure how the values in your data differ from one another, or how spread out your data is. A standard deviation is a statistic that measures the dispersion of a data set relative to its mean. The standard deviation is calculated as the square root of variance by determining each data point's deviation relative to the mean. If the data points are further from the mean, that means that there's a higher deviation within the data set, and then the data is said to be more spread out. This leads to a higher standard deviation too. Let's take an example of income in rural and urban areas. In rural areas, let's say such as farming areas, the income doesn't differ that much. More or less everyone earns the same. Because of this, our bell curve has a very low standard deviation and it has a very narrow peak. However, in urban areas, the wealth distribution is very uneven. Some people can have very high incomes and can be earning a lot, while other people can have very low incomes. Furthermore, the data distribution between these two income points is going to be more spread out because there are a lot more people living there who work in various fields and who have various incomes. Because of this, our standard deviation is more spread out and our bell curve will also have a wider peak. Now, how can we find the standard deviation? Standard deviation is obtained by subtracting each data value from the mean and finding the squared average of these values. Let's look at how we can do this with the help of an example. These values correspond to the height of various dogs. We can find the mean by finding the average of all these values, which is nothing but adding all the values and dividing it by the total number of values. The mean that we get is 394. This means that the average height of a dog is 394 millimeters. To find the standard deviation, first we need to subtract the height from the mean. This will tell us how far from the mean our data points actually are. Next, we will square up all of these differences and add them up and again divide it by the total number of values that we have. This is called the variance. The variance that we get in this case is 21704. Finally, when we find the square root of this value, we will get the standard deviation. The standard deviation here is 147. The standard deviation will tell us how our data points differ from the average, and it gives us a basic value suggesting how spread out our data is from the very middle or from the mean. So when we plot these values, this value 147 will mean that a curve will have a width of 147 points around the mean. Now, what is the standard normal distribution? The standard normal distribution is a type of normal distribution that has a mean of 0 and a standard deviation of 1. This means that the normal distribution has its center at 0 and it has intervals which increase by 1. All normal distributions, like the standard normal distribution, are unimodal and symmetrically distributed with a bell-shaped curve. However, a normal distribution can take on any value as its mean and standard deviation. In the standard normal distribution, however, the mean and standard deviation are always fixed. When you standardize a normal distribution, the mean becomes 0 and the standard deviation becomes 1. This allows you to easily calculate the probability of certain values occurring in your distribution, or to compare data sets with different mean and standard deviations. The curve shows a standard normal distribution. As you can see, again, the data is centered at 0. This does not mean that the data necessarily starts at 0. This means that after standardizing, this point is where our mean will lie. In a standard normal distribution, the standard deviation is 1. So all the data points will increase or decrease in steps of 1. Let's better understand a standard normal distribution with the help of an example. Again, as you can see,
the data is centered around 0, which is nothing but the mean. Let's again consider the weights of students in class 8th. The average weight here is around 50 kgs and the data increases and decreases in steps of 5. The data over here in this curve is evenly distributed along these steps. This is what a standard normal distribution will look like. We already know that the mean of our data is 50, and because the data is increasing and decreasing in equal steps, we can just standardize it and take it to mean that the data is increasing and decreasing in steps of 1. This is what a standard normal distribution looks like, and when you have a data which looks like this, you can always standardize it and convert it into a standard normal distribution. Now, standard normal distribution has a couple of properties which makes calculation comparatively easy. The first one is that 68% of the values fall within the first standard deviation, which means that 68% of all data values on this curve will fall between the range of -1 to 1, or the first interval ranging from -1 to 1. The second property is that 95% of the rest of the values are within the second standard deviation, or from the second negative point to the second positive point. And finally, 99.7% of the values fall within the third standard deviation, or from the third negative point to the third positive point. This makes calculations on standard normal distribution fairly easy. You can compare scores on different distributions with different means and standard deviations. You can normalize scores for statistical decision making using standard normal distribution. You can find the probability of observations in a distribution which fall above or below a given value. And finally, you can find the probability that a mean significantly differs from a population mean. Now let's take a look at z-score. So what is a z-score? A z-score is used to tell us how far from the mean our data point actually is. It is calculated using the mean and standard deviation, so it can be said that the z-score is how many standard deviations below the mean our data is. Basically, by using the z-score, we can get an approximate location of where our data point lies on the graph with regards to the mean. Now the z-score is given by subtracting the data point from the mean and dividing it by standard deviation. This can also be written as x minus mu divided by sigma. Now any normal distribution can be standardized by converting its values into z-scores. The z-score will tell you how many standard deviation from the mean each values lie. While data points are referred to as x in a normal distribution, they are called z or z-scores in the z distribution. A z-score is a standard score that will tell you how many standard deviations away from the mean an individual point will lie. A positive z-score will mean that your x value is greater than the mean, and a negative z-score will mean that your x value is less than the mean. A z-score of 0 will mean that your x value is equal to the mean. And again, to standardize a value from a normal distribution, all we have to do is convert it to a z-score by subtracting the mean from our individual value and dividing it by the standard deviation. Now let's see how we can find the z-score from data points with the help of a solved example. Let's do a case study. In this case study, we'll be taking the summary of daily travel time of a person who's commuting to and from work. All these values are in minutes. And using these values, we have to calculate the mean, the standard deviation, and the z-score. These values are as shown. As we can see, there are 13 values in total. Let's start by finding the mean. The mean is the average, and it can be gotten by adding all of these values and dividing it by the total number of values. This gives us a value of 38.6. The mean tells us the average of all our data points, which means on an average, he travels for 38.6 minutes to reach work. Next, let's subtract the individual values from our mean and calculate the variance and standard deviation. The values on the left give us the values that we get after subtracting it from the mean, and the variance can be calculated by squaring all of these values, adding up all of the squared values, and dividing it by the total number of values. At the end of the day, we get a variance of 140. To calculate the standard deviation, all we have to do is take a square root of the variance, which gives us a value of 11.8. Now, the mean signifies the average of our values, and we already know this. It gives us the average time which is taken to travel. But the standard deviation will tell us the average value of how much our data points differ from the mean. It tells us the deviation within our own data, and it tells us how far away on an average a point is from the mean. Now, the value that we get is 11.8, which means that on an average, a single data point is around 11.8 data points away from the mean. Now let's calculate the z-score. The z-score is given by subtracting individual data points from the mean and dividing it by the standard deviation. We know that we have a standard deviation of 11.8 and a mean of 38.6. Using these values, we can calculate the z-scores for individual x values. Now we know that a negative z-score means that our x value is lower than our mean. But what does the number 1.06 mean? This means that the z-score for 26 is 1.06 standard deviations away from the mean. The negative symbol here means that our x value is less than the mean. And by how less? 1.06 times the standard deviation. Now we know that the negative value of a z-score means that our x value is less than our mean. But what does the number 1.06 mean? This means that the z-score is 1.06 times the standard deviation less than the mean. The same thing can be said for the z-score of 33. It is 0.47 times the standard deviation less than the mean. The z-score of 65 is 2.23 times the standard deviation more than the mean. That means it has to be added to the mean. The reason that we know it's more than the mean is because this has a positive value. So this means that using z-scores, we can know where our data points fall relative to other points on the graph. The z-score will tell us how far away from the mean a point is in steps of our standard deviation.
Basics and terminology. The first one is outcome. Whenever we do an experiment like flipping a coin or rolling a dice, we get an outcome. For example, if we flip a coin, we get an outcome of heads or tails, and if we roll a die, we get an outcome of 1, 2, 3, 4, 5 or 6. Random experiment. A random experiment is any well-defined procedure that produces an observable outcome that could not be perfectly predicted in advance. A random experiment must be well defined to eliminate any vagueness or surprise. It must produce a definite observable outcome so that you know what happened after the random experiment is run. Random events. Consider a simple example. Let us say that we toss a coin up in the air. What can happen when it gets back? It either gives a head or a tail. These two are known as outcome, and the occurrence of an outcome is an event. Thus, the event is the outcome of some phenomenon. The last one is sample space. A sample space is a collection or a set of possible outcomes of a random experiment. The sample space is represented using the symbol S. The subset of all possible outcomes of an experiment is called events, and a sample space may contain a number of outcomes that depends on the experiment. If it contains a finite number of outcomes, then it is known as a discrete or finite sample spaces. Now let's discuss what is random variable. A random variable is a numerical description of the outcome of a statistical experiment. A random variable that may assume only a finite number of values is said to be discrete. One that may assume any value in some interval on the real number line is said to be continuous. Let's see an example. Let x be a random variable defined as the sum of numbers when two dice are rolled. X can assume the values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. Notice there is no 1 here because the sum on the two dice can never be 1. Now that we know the basics, let's move on to binomial distribution. The binomial distribution is used when there are exactly two mutually exclusive outcomes of a trial. These outcomes are appropriately labeled success and failure. The binomial distribution is used to obtain the probability of observing X successes in n number of trials, with the probability of success on a single trial denoted by P. The binomial distribution assumes that P is fixed for all the trials. Here is a real-life example of a binomial distribution. Suppose you purchase a lottery ticket, then either you are going to win the lottery or not. In other words, the outcome will be either success or failure that can be proved through binomial distribution. There are 4 important conditions that needs to be fulfilled for an experiment to be a binomial experiment. The first one is there should be a fixed number of n trials carried out. The outcome of a given trial is only 2, that is either a success or a failure. The probability of success remains constant from trial to trial. It does not change from one trial to another. And the trials are independent. The outcome of a trial is not affected by the outcome of any other trial. To calculate the binomial coefficient, we use the formula which is NCR into p to the power r into 1 minus p to the power n minus r, where r is the number of success in n number of trials and p is the probability of success. 1 minus p denotes the probability of a failure. Now, let's use this formula to solve an example. Suppose a die is tossed 3 times. What is the probability of no 5 turning up, 1 5 and 3 5s turning up? To calculate the no 5 turning up, here r is equal to 0 and n is equal to 3. Substituting the value in the formula, we have 3c0 into 1 by 6 to the power 0 into 5 by 6 to the power 3, where 1 by 6 is the probability of success and 5 by 6 is the probability of failure. Calculating this equation, we'll get the value to be 0.5787. In a similar manner, to calculate the probability of 1 5 turning up, we'll replace r with 1 and n will be 3. So px1 will be equal to 3c1 into 1 by 6 to the power 1 into 5 by 6 to the power 2, which will come out to be 0.347. And for 3 5 turning up, we'll substitute r equal to 3 and the formula will remain the same and we'll get the value to be 0.0046. Now that we are done with the concepts of binomial probability distribution, here's a problem for you to solve. Post your answers in the comment section and let us know. A Poisson distribution is a probability distribution used in statistics to show how many times an event is likely to happen over a given period of time. To put it another way, it's a count distribution. Poisson distributions are frequently used to comprehend independent event at a constant rate over a given interval of time. The Poisson distribution was developed by French mathematician Simon Denis Poisson in 1837. A Poisson distribution is used in cases where the chances of any individual event being a success is very small. The number of defective pencils per box of a 6,000 pencil, the number of plane crashes in India in 1 year, or the number of printing mistakes in each page of a book. All of these examples can have use of Poisson distribution. The Poisson distribution can be used to calculate how likely it is that something will happen x number of times. A random variable x has a Poisson distribution with parameter lambda, and the formula for that is e to the power minus lambda into lambda to the power x divided by x factorial, where x can be the number of times the event is happening. The value of e is taken as 2.7182. Let's discuss some application of Poisson distribution. If you want to calculate the number of deaths per day or week due to rare disease in a hospital, you can use the Poisson distribution. In a similar manner, the count of bacteria per cc in blood or the number of computers infected with virus per week. The number of mishandled baggage per 1000 passengers can also have an application for Poisson distribution. Let's discuss one example to see how you can calculate the Poisson distribution. Suppose on an average, a cancer kills 5 people each year in India. What is the probability that one person is killed this year? We'll assume all these events are independent random events. So, by the formula, we have x is equal to 1 because we have to calculate the probability of one person that is killed this year. So, p x equal to 1 will be equal to e to the power minus 5 into 5 to the power 1 divided by 1 factorial, which will come out to be 0.033, which will be near to 3.3%. So, the probability that only one person is killed this year due to cancer is 3.3%.
If you are an aspiring data scientist who's looking out for online training and certification in data science from the best universities and industry experts, then search no more. Simplilearn's postgraduate program in data science from Caltech University in collaboration with IBM should be the right choice. For more details on this program, please use the link in the description box below.
Hello everyone, welcome to another session by Simplilearn. Today, we are going to discuss the Bayes theorem, an important subtopic that comes under probability theory. We'll start this video by talking about probability and conditional probability. After that, we'll move on to the Bayes theorem and understand its formula and a real-life example where the Bayes theorem can be used. So, let's get started. What is probability? Probability is a branch of mathematics concerning numerical descriptions of how likely an event is to occur, or how likely it is that a proposition is true. The probability of an event is a number between 0 and 1, where roughly speaking, 0 indicates the impossibility of the event and 1 indicates certainty. The higher the probability of an event, the more likely is that the event will occur. Let's look at an example. A simple example is the tossing of a fair unbiased coin. Since the coin is fair, the outcome, that is heads and the tails, are both equally probable. The probability of heads equals the probability of the tails, and since no other outcomes are possible, the probability of either heads or tails can be said to be 1 by 2, which is also 50%. The probability of an event can be calculated by number of ways it can happen divided by the total number of outcomes. Now that we know about the probability, let's see if you can answer this question. What is the probability of drawing a jack and a queen consecutively from a deck of 52 cards without replacement? Here are your options. Post your answers in the comment section and let us know. Now let's move on to conditional probability. Let A and B be the two events associated with a random experiment. Then the probability of A's occurrence under the condition that B has already occurred and probability of B is not equal to 0 is called the conditional probability. It is denoted by PA/B. Thus, we can say that PA/B is equal to PA intersection B divided by P of B, where PA/B is the probability of occurrence of A given that B has already occurred, and PB is the probability of occurrence of B. To know more about conditional probability, you can check our previous video which is specifically on conditional probability. Now let's move on to Bayes theorem. The Bayes theorem is a mathematical formula for calculating conditional probability in probability and statistics. In other words, it is used to figure out how likely an event is associated on its proximity to another. Bayes' law or Bayes' rule are the other names of this theorem. The formula for the Bayes theorem can be written in a variety of ways. The most common version is PA/B is equal to P of B/A into P of A divided by P of B, where PA/B is the conditional probability of event A occurring given that B is true, and PA and P of B are the probabilities of A and B occurring independently of one another. Let's solve a problem using the Bayes theorem to understand it better. There is a cricket match tomorrow, and in recent years it has rained only 5 days each year. Unfortunately, the meteorologist has predicted the rain for tomorrow. Now, when it rains, the meteorologist correctly forecasts rain 90% of the time, and when it doesn't rain, he incorrectly forecasts rain 10% of the time. Let's calculate what is the probability that it will rain on the match day. So, the two sample spaces here are the events that it rains and it does not rain. Additionally, a third event is also there that meteorologist predicts the rain. So the notation for these events appear below. Event A1 is equal to it rains on the match day, event A2 that it does not rain on the match day, and event B is the meteorologist predicting the rain. Now in terms of probability, we know the following. Probability of A1 is 5 by 365 that it rains 5 days in a year, which will come out to be 0.0136. PA2 is 360 by 365, that is no days for 360 days in a year, which will come out to be 0.986. PB/A1 is 0.9, This signifies when it rains, the meteorologist predicts the rain 90% of the time. In a similar manner, PB by A2 is 0.1, that it does not rain, the meteorologist predicts the rain 10% of the time. Combining all this, we can calculate PA1/B, that is the probability it will rain on the given match day, given a forecast of rain by meteorologist. The answer can be determined using the Bayes theorem as shown below. So here's the formula of the Bayes theorem, and putting all the values that we have calculated in the previous slide, the probability that it will rain on the match day given a forecast of the rain by meteorologist will come out to be 0.111, which will be equal to 11.11%. So there's an 11% chance that it will rain on the match day given that the meteorologist has predicted the rain. I hope this example is clear to you.
It's a weekend, and John decided to watch the latest movie recommended by Netflix at his friend's place. Before heading out, he asked Siri about the weather and realized it would rain. So he decided to take his Tesla for the long journey and switch to autopilot on the highway. After coming home from the eventful day, he started wondering how technology has made his life easy. He did some research on the internet and found out that Netflix, Siri, and Tesla are all using AI. So, what is AI? AI, or artificial intelligence, is nothing but making computers-based machines think and act like humans. Artificial intelligence is not a new term. John McCarthy, a computer scientist, coined the term artificial intelligence back in 1956. But it took time to evolve as it demanded heavy computing power. Artificial intelligence is not confined to just movie recommendations and virtual assistants. Broadly classifying, there are three types of AI. Artificial narrow intelligence, also called weak AI, is the stage where machines can perform a specific task. Netflix, Siri, chatbots, facial recommendation systems are all examples of artificial narrow intelligence. Next up, we have artificial general intelligence, referred to as an intelligent agent's capacity to comprehend or pick up any intellectual skill that a human can. We are halfway into successfully implementing this phase. IBM's Watson supercomputer and GPT-3 fall under this category. And lastly, artificial superintelligence. It is the stage where machines surpass human intelligence. You might have seen this in movies and imagined how the world would be if machines occupy it. Fascinated by this, John did more research and found out that machine learning, deep learning, and natural language processing are all connected with artificial intelligence. Machine learning, a subset of AI, is the process of automating and enhancing how computers learn from their experiences without human help. Machine learning can be used in email spam detection, medical diagnosis, etc. Deep learning can be considered a subset of machine learning. It is a field that is based on learning and improving on its own by examining computer algorithms. While machine learning uses simpler concepts, deep learning works with artificial neural networks, which are designed to imitate the human brain. This technology can be applied in face recognition, speech recognition, and many more applications. Natural language processing, popularly known as NLP, can be defined as the ability of machines to learn human language and translate it. Chatbots fall under this category. Artificial intelligence is advancing in every crucial field like healthcare, education, robotics, banking, e-commerce, and the list goes on. Like in healthcare, AI is used to identify diseases, helping healthcare service providers and their patients make better treatment and lifestyle decisions. Coming to the education sector, AI is helping teachers automate grading, organizing, and facilitating parent-guardian conversations. In robotics, AI-powered robots employ real-time updates to detect obstructions in their path and instantaneously design their routes. Artificial intelligence provides advanced data analytics that is transforming banking by reducing fraud and enhancing compliance. With this growing demand for AI, more and more industries are looking for AI engineers who can help them develop intelligent systems and offer them lucrative salaries going north of $120,000. The future of AI looks promising, with the AI market expected to reach $190 billion by 2025.
We know humans learn from their past experiences, and machines follow instructions given by humans. But what if humans can train the machines to learn from their past data and do what humans can do and much faster? Well, that's called machine learning. But it's a lot more than just learning. It's also about understanding and reasoning. So today, we will learn about the basics of machine learning. So that's Paul. He loves listening to new songs. He either likes them or dislikes them. Paul decides this on the basis of the song's tempo, genre, intensity, and the gender of voice. For simplicity, let's just use tempo and intensity for now. So here, tempo is on the x-axis, ranging from relaxed to fast, whereas intensity is on the y-axis, ranging from light to soaring. We see that Paul likes the song with fast tempo and soaring intensity, while he dislikes the song with relaxed tempo and light intensity. So now we know Paul's choices. Let's say Paul listens to a new song. Let's name it as Song A. Song A has fast tempo and a soaring intensity, so it lies somewhere here. Looking at the data, can you guess whether Paul will like the song or not? Correct. So Paul likes this song. By looking at Paul's past choices, we were able to classify the unknown song very easily, right? Let's say now Paul listens to a new song. Let's label it as Song B. So Song B lies somewhere here with medium tempo and medium intensity. Neither relaxed nor fast, neither light nor soaring. Now can you guess whether Paul likes it or not? Not able to guess whether Paul will like it or dislike it? Are the choices unclear? Correct. We could easily classify Song A. But when the choice became complicated, as in the case of Song B, yes, and that's where machine learning comes in. Let's see how. In the same example, for Song B, if we draw a circle around the Song B, we see that there are 4 votes for like, whereas 1 vote for dislike. If we go for the majority votes, we can say that Paul will definitely like the song. That's all. This was a basic machine learning algorithm also. It's called k-nearest neighbors. So this is just a small example in one of the many machine learning algorithms. Quite easy, right? Believe me, it is. But what happens when the choices become complicated, as in the case of Song B? That's when machine learning comes in. It learns the data, builds the prediction model, and when the new data point comes in, it can easily predict for it. More the data, better the model, higher will be the accuracy. There are many ways in which the machine learns. It could be either supervised learning, unsupervised learning, or reinforcement learning. Let's first quickly understand supervised learning. Suppose your friend gives you 1 million coins of 3 different currencies, say 1 rupee, 1 euro and 1 dirham. Each coin has different weights. For example, a coin of 1 rupee weighs 3 grams, 1 euro weighs 7 grams and 1 dirham weighs 4 grams. Your model will predict the currency of the coin. Here, your weight becomes the feature of coins, while currency becomes their label. When you feed this data to the machine learning model, it learns which feature is associated with which label. For example, it will learn that if a coin is of 3 grams, it will be a 1 rupee coin. Let's give a new coin to the machine. On the basis of the weight of the new coin, your model will predict the currency. Hence, supervised learning uses labeled data to train the model. Here the machine knew the features of the object and also the labels associated with those features. On this note, let's move to unsupervised learning and see the difference. Suppose you have cricket dataset of various players with their respective scores and wickets taken. When we feed this dataset to the machine identifies the pattern of player performance. So it plots this data with the respective wickets on the x-axis while runs on the y-axis. While looking at the data, you will clearly see that there are 2 clusters. The one cluster are the players who scored high runs and took less wickets, while the other cluster is of the players who scored less runs but took many wickets. So here we interpret these 2 clusters as batsmen and bowlers. The important point to note here is that there were no labels of batsmen and bowlers. Hence, the learning with unlabeled data is unsupervised learning. So we saw supervised learning where the data was labeled and the unsupervised learning where the data was unlabeled. And then there is reinforcement learning, which is reward-based learning, or we can say that it works on the principle of feedback. Here, let's say you provide the system with an image of a dog and ask it to identify it. The system identifies it as a cat. So you give a negative feedback to the machine saying that it's a dog's image. The machine will learn from the feedback, and finally if it comes across any other image of a dog, it will be able to classify it correctly. That is reinforcement learning. To generalize machine learning model, let's see a flowchart. Input is given to a machine learning model, which then gives the output according to the algorithm applied. If it's right, we take the output as a final result. Else, we provide feedback to the training model and ask it to predict until it learns. I hope you've understood supervised and unsupervised learning. So let's have a quick quiz. You have to determine whether the given scenarios uses supervised or unsupervised learning. Simple, right? Scenario 1. Facebook recognizes your friend in a picture from an album of tagged photographs. Scenario 2. Netflix recommends new movies based on someone's past movie choices. Scenario 3. Analyzing bank data for suspicious transactions and flagging the fraud transactions. Think wisely and comment below your answers. Moving on, don't you sometimes wonder, how is machine learning possible in today's era? Well, that's because today we have humongous data available. Everybody's online, either making a transaction or just surfing the internet, and that's generating a huge amount of data every minute. And that data, my friend, is the key to analysis. Also, the memory handling capabilities of computers have largely increased, which helps them to process such a huge amount of data at hand without any delay. And yes, computers now have great computational powers. So there are a lot of applications of machine learning out there. To name a few, machine learning is used in healthcare, where diagnostics are predicted for doctors' review. The sentiment analysis that the tech giants are doing on social media is another interesting application of machine learning. Fraud detection in the finance sector, and also to predict customer churn in the e-commerce sector. While booking a cab, you must have encountered surge pricing often, where it says the fare of your trip has been updated. Continue booking? Yes, please, I'm getting late for office. Well, that's an interesting machine learning model which is used by global taxi giant Uber and others, where they have differential pricing in real time based on demand, the number of cars available, bad weather, rush hour, etc. So they use the surge pricing model to ensure that those who need a cab can get one. Also, it uses predictive modeling to predict where the demand will be high, with the goal that drivers can take care of the demand and surge pricing can be minimized. Great! Hey Siri, can you remind me to book a cab at 6 p.m. today?
Okay, I'll remind you.
Thanks.
No problem.
If you are an aspiring data scientist who's looking out for online training and certification in data science from the best universities and industry experts, then search no more. Simplilearn's postgraduate program in data science from Caltech University in collaboration with IBM should be the right choice. For more details on this program, please use the link in the description box below.
Let's dive in a little deeper and see how machine learning works. Let's say you provide a system with the input data that carries the photos of various kinds of fruits. Now you want the system to figure out what are the different fruits and group them accordingly. So what the system does, it analyzes the input data. Then it tries to find patterns like shapes, size, and color. Based on these patterns, the system will try to predict the different types of fruit and segregate them. Finally, it keeps track of all such decisions it took in the process to make sure it's learning. The next time you ask the same system to predict and segregate the different types of fruits, it won't have to go through the entire process again. That's how machine learning works. Now let's look into the types of machine learning. Machine learning is primarily of three types. First one is supervised machine learning. As the name suggests, you have to supervise your machine learning while you train it to work on its own. It requires labeled training data. Next up is unsupervised learning, wherein there will be training data but it won't be labeled. Finally, there is reinforcement learning, wherein the system learns on its own. Let's talk about all these types in detail. Let's try to understand how supervised learning works. Look at the pictures very carefully. The monitor depicts the model or the system that we are going to train. This is how the training is done. We provide a data set that contains pictures of a kind of a fruit, say an apple. Then we provide another data set which lets the model know that these pictures were that of a fruit called apple. This ends the training phase. Now, what we will do is we provide a new set of data which only contains pictures of apple. Now here comes the fun part. The system can actually tell you what fruit it is. and it will remember this and apply this knowledge in future as well. That's how supervised learning works. You are training the model to do a certain kind of an operation on its own. This kind of a model is generally used into filtering spam mails from your email accounts as well. Yes, surprised, aren't you? So let's move on to unsupervised learning now. Let's say we have a data set which is cluttered. In this case, we have a collection of pictures of different fruits. We feed this data to the model and the model analyzes the data to figure out patterns in it. In the end, it categorizes the photos into 3 types, as you can see in the image, based on their similarities. So, you provide the data to the system and let the system do the rest of the work. Simple, isn't it? This kind of a model is used by Flipkart to figure out the products that are well suited for you. Honestly speaking, this is my favorite type of machine learning out of all the 3. And this type has been widely shown in most of the sci-fi movies lately. Let's find out how it works. Imagine a newborn baby. You put a burning candle in front of the baby. The baby does not know that if it touches the flame, its fingers might get burned. So it does that anyway and gets hurt. The next time you put that candle in front of the baby, it will remember what happened the last time and would not repeat what it did. That's exactly how reinforcement learning works. We provide the machine with a data set wherein we ask it to identify a particular kind of a fruit, in this case an apple. So what it does as a response, it tells us that it's a mango. But as we all know, it's a completely wrong answer. So as a feedback, we tell the system that it's wrong, it's not a mango, it's an apple. What it does, it learns from the feedback and keeps that in mind. When the next time, when we ask a same question, it gives us the right answer. It is able to tell us that it's actually an apple. That is a reinforced response. So that's how reinforcement learning works. It learns from its mistakes and experiences. This model is used in games like Prince of Persia or Assassin's Creed or FIFA, wherein the level of difficulty increases as you get better with the games. Just to make it more clear for you, let's look at a comparison between supervised and unsupervised learning. Firstly, the data involved in case of supervised learning is label. As we mentioned in the examples previously, we provide the system with a photo of an apple and let the system know that this is actually an apple. That is called label data. So the system learns from the label data and makes future predictions. Now, unsupervised learning does not require any kind of label data because its work is to look for patterns in the input data and organize it. The next point is that you get a feedback in case of supervised learning. That is, once you get the output, the system tends to remember that and uses it for the next operation. That does not happen for unsupervised learning. And the last point is that supervised learning is mostly used to predict data, whereas unsupervised learning is used to find out hidden patterns or structures in data. I think this would have made a lot of things clear for you regarding supervised and unsupervised learning. Now, let's talk about a question that everyone needs to answer before building a machine learning model. What kind of a machine learning solution should we use? Yes, you should be very careful with selecting the right kind of solution for your model. Because if you don't, you might end up losing a lot of time, energy, and processing cost. I won't be naming the actual solutions because you guys aren't familiar with them yet. So we will be looking at it based on supervised, unsupervised, and reinforcement learning. So let's look into the factors that might help us select the right kind of machine learning solution. First factor is the problem statement describes the kind of model you will be building, or as the name suggests, it tells you what the problem is. For example, let's say the problem is to predict the future stock market prices. So for anyone who is new to machine learning would have trouble figuring out the right solution. But with time and practice, you will understand that for a problem statement like this, solution based on supervised learning would work the best for obvious reasons. Then comes the size, quality, and nature of the data. If the data is cluttered, you go for unsupervised. If the data is very large and categorical, we normally go for supervised learning solutions. Finally, we choose the solution based on their complexity. As for the problem statement wherein we predict the stock market prices, it can also be solved by using reinforcement learning. But that would be very, very difficult and time consuming, unlike supervised learning. Algorithms are not types of machine learning. In the most simplest language, they are methods of solving a particular problem. So the first kind of method is classification, which falls under supervised learning. Classification is used when the output you are looking for is a yes or a no, or in the form A or B, or true or false. Like if a shopkeeper wants to predict if a particular customer will come back to his shop or not, he will use a classification algorithm. The algorithms that fall under classification are decision tree, naive Bayes, random forest, logistic regression, and KNN. The next kind is regression. This kind of a method is used when the predicted data is numerical in nature. Like if the shopkeeper wants to predict the price of a product based on its demand, it would go for regression. The last method is clustering. Clustering is a kind of unsupervised learning again. It is used when the data needs to be organized. Most of the recommendation systems used by Flipkart, Amazon, etc. make use of clustering. Another major application of it is in search engines. The search engines study your old search history to figure out your preferences and provide you the best search results. One of the algorithms that fall under clustering is k-means. Now that we know the various algorithms, let's look into 4 key algorithms that are used widely. We will understand them with very simple examples. The 4 algorithms that we will try to understand are k-nearest neighbor, linear regression, decision tree, and naive Bayes. Let's start with our first machine learning solution, k-nearest neighbor. K-nearest neighbor is again a kind of a classification algorithm. As you can see on the screen, the similar data points form clusters. The blue one, the red one, and the green one. There are 3 different clusters. Now, if we get a new and unknown data point, it is classified based on the cluster closest to it or the most similar to it. K in KNN is the number of nearest neighboring data points we wish to compare the unknown data with. Let's make it clear with an example. Let's say we have 3 clusters in a cost to durability graph. The first cluster is of footballs. The second one is of tennis balls. And the third one is of basketballs. From the graph, we can say that the cost of footballs is high and the durability is less. The cost of tennis balls is very less, but the durability is high. And the cost of basketballs is as high as the durability. Now let's say we have an unknown data point. We have a black spot which can be one kind of the balls, but we don't know what kind it is. So what we'll do, we'll try to classify this using KNN. So if we take k is equal to 5, we draw a circle keeping the unknown data point as the center, and we make sure that we have 5 balls inside that circle. In this case, we have a football, a basketball, and 3 tennis balls. Now, since we have the highest number of tennis balls inside the circle, the classified ball would be a tennis ball. So that's how k-nearest neighbor classification is done. Linear regression is again a type of supervised learning algorithm. This algorithm is used to establish linear relationship between variables, one of which would be dependent and the other one would be independent. Like if we want to predict the weight of a person based on his height, weight would be the dependent variable and height would be independent. Let's have a look at it through an example. Let's say we have a graph here showing a relationship between height and weight of a person. Let's put the y-axis as age and the x-axis as weight. So the green dots are the various data points. These green dots are the data points. And D is the mean squared error, that is the perpendicular distances from the line to the data points are the error values. This error tells us how much the predicted values vary from the original value. Let's ignore this blue line for a while. So let's say if this is our regression line, you can see the distance from all the data points from this line is very high. So if we take this line as a regression line, the error in the prediction will be too high. So in this case, the model will not be able to give us a good prediction. Let's say we draw another regression line here like this. Even in this case, you can see that the perpendicular distance of the data points from the line is very high. So the error value will still come as high as the last one. So this model will also not be able to give us a good prediction. So what to do? So finally, we draw a line which is this blue line. So here we can see that the distance of the data points from the line is very less relative to the other two lines we drew. So the value of D for this line will be very less. So in this case, if we take any value on the x-axis, the corresponding value on the y-axis will be our prediction. And given the fact that the D is very low, our prediction should be good also. This is how regression works. We draw a line, a regression line that is, in such a way that the value of D is the least, eventually giving us good predictions. This algorithm, that is decision tree, is a kind of an algorithm you can very strongly relate to. It uses a kind of a branching method to realize the problem and make decisions based on the conditions. Let's take this graph as an example. Imagine yourself sitting at home getting bored. You feel like going for a swim. What you do is you check if it's sunny outside. So that's your first condition. If the answer to that condition is yes, you go for a swim. If it's not sunny, then the next question you would ask yourself is if it's raining outside. So that's condition number 2. If it's actually raining, you cancel the plan and stay indoors. If it's not raining, then you would probably go outside and have a walk. So that's the final node. That's how decision tree algorithm works. You probably use this every day. It realizes a problem and then takes the decisions based on the answers to every conditions. Naive-Bayes algorithm is mostly used in cases where a prediction needs to be done on a very large dataset. It makes use of conditional probability. Conditional probability is the probability of an event, say A, happening given that another event B has already happened. This algorithm is most commonly used in filtering spam mails in your email account. Let's say you receive a mail. The model goes through your old spam mail records. Then it uses Bayes' theorem to predict if the present mail is a spam mail or not. So PC of A is the probability of event C occurring when A has already occurred. PA of C is the probability of event A occurring when C has already occurred. And PC is the probability of event C occurring, and PA is the probability of event A occurring. Let's try to understand Naive-Bayes with a better example. Naive-Bayes can be used to determine on which days to play cricket. Based on the probabilities of a day being rainy, windy or sunny, the model tells us if a match is possible. If we consider all the weather conditions to be event A for us, and the probability of a match being possible event C, so the model applies the probabilities of event A and C into the Bayes theorem and predicts if a game of cricket is possible on a particular day or not. In this case, if the probability of C of A is more than 0.5, we can be able to play a game of cricket. If it's less than 0.5, we won't be able to do that. That's how Naive-Bayes algorithm works.
We're going to cover reinforcement learning today. And what's in it for you? We'll start with why reinforcement learning. We'll look at what is reinforcement learning. We'll see what the different kinds of learning strategies are that are being used today in computer models under supervised versus unsupervised versus reinforcement. We'll cover important terms specific to reinforcement learning. We'll talk about Markov's decision process, and we'll take a look at a reinforcement learning example. Well, we'll teach a tic-tac-toe how to play. Why reinforcement learning? Training a machine learning model requires a lot of data, which might not always be available to us. Further, the data provided might not be reliable. Learning from a small subset of actions will not help expand the vast realm of solutions that may work for a particular problem. And you can see here we have the robot learning to walk. Very complicated setup when you're learning how to walk, and you'll start asking questions like, if I'm taking one step forward and left, well, what happens if I pick up a 50-pound object? How does that change how a robot would walk? These things are very difficult to program because there's no actual information on it until it's actually tried out. Learning from a small subset of actions will not help expand the vast realm of solutions that may work for a particular problem. And we'll see here it learned how to walk. This is going to slow the growth that technology is capable of. Machines need to learn to perform actions by themselves and not just learn off humans. And you see the objective climb a mountain. A real interesting point here is that as human beings we can go into a very unknown environment and we can adjust for it and kind of explore and play with it. Most of the models, the non-reinforcement models in computer machine learning, aren't able to do that very well. There's a couple of them that can be used or integrated. See how it goes is what we're talking about with reinforcement learning. So what is reinforcement learning? Reinforcement learning is a sub-branch of machine learning that trains a model to return an optimum solution for a problem by taking a sequence of decisions by itself. Consider a robot learning to go from one place to another. The robot is given a scenario and must arrive at a solution by itself. The robot can take different paths to reach the destination. It will know the best path by the time taken on each path. It might even come up with a unique solution all by itself. And that's really important as we're looking for unique solutions. We want the best solution, but you can't find it unless you try it. So when we're looking at our different systems, our different model, we have supervised versus unsupervised versus reinforcement learning. And with the supervised learning, that is probably the most controlled environment. We have a lot of different supervised learning models, whether it's linear regression, neural networks, there's all kinds of things in between, decision trees. The data provided is labeled data with output values specified. And this is important because when we talk about supervised learning, you already know the answer for all this information. You already know the picture has a motorcycle in it, so you're supervised learning. You already know that the outcome for tomorrow, for going back a week, you're looking at stock, you can already have like the graph of what the next day looks like, so you have an answer for it. And you have labeled data which is used, you have an external supervision, and solves problems by mapping labeled input to known output. So very controlled. Unsupervised learning, and unsupervised learning is really interesting because it's now taking part in many other models. They start with, you can actually insert an unsupervised learning model in almost either supervised or reinforcement learning as part of the system, which is really cool. Data provided is unlabeled data. The outputs are not specified. Machine makes its own predictions. Used to solve association with clustering problems. Unlabeled data is used. No supervision. Solves problems by understanding patterns and discovering output. So you can look at this and you can think some of these things go with each other. They belong together. So it's looking for what connects in different ways. And there's a lot of different algorithms that look at this. When you start getting into those, there's some really cool images that come up of what unsupervised learning is. How it can pick out, say, the area of a donut. One model will see the area of the donut, and the other one will divide it into 3 sections based on its location versus what's next to it. So there's a lot of stuff that goes in with unsupervised learning. And then we're looking at reinforcement learning. Probably the biggest industry in today's market in machine learning, or growing market. It's very infant stage as far as how it works and what it's going to be capable of. The machine learns from its environment using rewards and errors. Used to solve reward-based problems. No predefined data is used. No supervision. Follows trial and error problem solving approach. So again, we have a random, at first you start with a random, I try this, it works and this is my reward, doesn't work very well maybe, or maybe it doesn't even get you where you're trying to get it to do, and you get your reward back, and then it looks at that and says, well, let's try something else, and it starts to play with these different things, finding the best route. So let's take a look at important terms in today's reinforcement model. And this has become pretty standardized over the last few years, so these are really good to know. We have the agent. Agent is the model that is being trained via reinforcement learning. So this is your actual entity that has, however you're doing it, whether you're using a neural network or a Q table or whatever, combination thereof. This is the actual agent that you're using. This is the model. And you have your environment. The training situation that the model must optimize to is called its environment. And you can see here, I guess we have a robot who's trying to get a chest full of gems or whatever, and that's the output. And then you have your action. This is all possible steps that can be taken by the model, and it picks one action. And you can see here that it's picked 3 different routes to get to the chest of diamonds and gems. We have a state, the current position condition returned by the model. And you could look at this if you're playing like a video game. This is the screen you're looking at. So when you go back here, the environment is a whole game board. So if you're playing one of those Mobius games, you might have the whole game board going on, but then you have your current position. Where are you on that game board? What's around that? What's around you? If you were talking about a robot, the environment might be moving around the yard, where it is in the yard and what it can see, what input it has in that location. That would be the current position condition returned by the model. And then the reward. To help the model move in the right direction, it is rewarded. Points are given to it to appraise some kind of action. So, yeah, you did good, or if didn't do as good, trying to maximize the reward and have the best reward possible. And then policy. Policy determines how an agent will behave at any time. It acts as a mapping between action and present state. This is part of the model. What is your action that you're going to take? What's the policy you're using to have an output from your agent? One of the reasons they separate policy as its own entity is that you usually have a prediction of a different options, and then the policy, well, how am I going to pick the best? Based on those predictions, I'm going to guess at different options, and we'll actually weigh those options in and find the best option we think will work. So it's a little tricky, but the policy thing is actually pretty cool how it works. Let's go ahead and take a look at a reinforcement learning example. And just in looking at this, we're going to take a look, consider what a dog that we want to train. So the dog would be like the agent. So you have your puppy or whatever. And then your environment is going to be the whole house or whatever it is where you're training them. And then you have an action. We want to teach the dog to fetch. So action equals fetching. And then we have a little biscuit, so we can get the dog to perform various actions by offering incentives such as a dog biscuit as a reward. The dog will follow a policy to maximize this reward, and hence will follow every command and might even learn new actions like begging by itself. So you have, so we start off with fetching. It goes, oh, I get a biscuit for that. It tries something else, and you get a handshake or begging or something like that, and it goes, oh, this is also reward based, and so it kind of explores things to find out what will bring it as biscuit. And that's very much like how a reinforced model goes. Is it looks for different rewards. How do I find? Can I try different things and find a reward that works? The dog also will want to run around and play and explore its environment. This quality of model is called exploration. So there's a little randomness going on in exploration. And it explores new parts of the house. Climbing on the sofa doesn't get a reward. In fact, it usually gets kicked off the sofa. So let's talk a little bit about Markov's decision process. Markov's decision process is a reinforcement learning policy used to map a current state to an action where the agent continuously interacts with the environment to produce new solutions and receive rewards. And you'll see here's all of our different vocabulary we just went over. We have a reward, our state, our agent, our environment, and our action. And so even though the environment kind of contains everything, that you really, when you're actually writing the program, your environment's going to put out a reward and state that goes into the agent. The agent then looks at this state, or it looks at the reward usually first, and it says, okay, I got rewarded for whatever I just did, or I didn't get rewarded. And then it looks at the state, and then it comes back, and if you remember from policy, the policy comes in, and then we have a reward. The policy is that part that's connected at the bottom. And so it looks at that policy and it says, hey, what's a good action that will probably be similar to what I did, or sometimes they're completely random, but what's a good action that's going to bring me a different reward? So taking the time to just understand these different pieces as they go is pretty important in most of the models today. And so a lot of them actually have templates based on this you can pull in and start using. Pretty straightforward as far as once you start seeing how it works, You can see your environment says, hey, this is the agent did this. If you're a character in a game, this happened, and it shoots out a reward in a state. The agent looks at the reward, looks at the new state, and then takes a little guess and says, I'm going to try this action. And then that action goes back into the environment. It affects the environment. The environment then changes depending on what the action was. And then it has a new state and a new reward that goes back to the agent. So in the diagram shown, we need to find the shortest path between node A and D. Each path has a reward associated with it, and the path with the maximum reward is what we want to choose. The nodes A, B, C, D denote the nodes to travel from node A to B is an action. Reward is the cost of each path, and policy is each path taken. And you can see here A can go to B, or A can go to C right off the bat, or it can go right to D. And if you explored all three of these, you would find that A going to D was a 0 reward, A going to C and D would generate a different reward, or you could go A, C, B, D. There's a lot of options here. And so when we start looking at this diagram, you start to realize that even though today's reinforced learning models do really good at finding an answer, they end up trying almost all the different directions you see. And so they take up a lot of work or a lot of processing time for reinforcement learning. They're right now in their infant stage, and they're really good at solving simple problems. And we'll take a look at one of those in just a minute in a tic-tac-toe game. But you can see here, once it's gone through these and it's explored, it's going to find the A, C, D is the best reward. It gets a full 30 points for it. So let's go ahead and take a look at a reinforcement learning demo. In this demo, we're going to use reinforcement learning to make a tic-tac-toe game. You will be playing this game against the machine learning model. And we'll go ahead, we're doing it in Python. So let's go ahead and go through, not always, I actually have a lot of Python tools. Let's go through Anaconda, which will open up a Jupyter notebook. Seems like a lot of steps, but it's worth it to keep all my stuff separate, and it also has a nice display when you're in the Jupyter notebook for doing Python. So here's our Anaconda navigator. I open up the notebook, which is going to take me to a web page, and I've gone in here and created a new Python folder. In this case, I've already done it and enabled it to change the name to tic-tac-toe. And then for this example, we're going to go ahead and import a couple things. We're going to import numpy as np. We'll go ahead and import pickle. Numpy, of course, is our number array, and then pickle is just a nice way sometimes for storing different information, different states that we're going to go through on here. And so we're going to create a class called state. We're going to start with that. And there's a lot of lines of code to this class that we're going to put in here. Don't let that scare you too much. There's not as much here. It looks like there's going to be a lot here, but there really is just a lot of setup going on in our class state. And so we have up here, we're going to initialize it. We have our board. It's a tic-tac-toe board, so we're only dealing with 9 spots on the board. We have player 1, player 2 is end. We're going to create a board hash. We'll look at that in just a minute. We're just going to store some information in there. Symbol of player equals 1. So there's a few things going on as far as the initialization. Then something simple, we're just going to get the hash of the board. We're going to get the information from the board on there, which is columns and rows. We want to know when a winner occurs, so if you get 3 in a row, that's what this whole section here is for. Let me go ahead and scroll up a little bit. And you can get a copy of this code if you send a note over to Simplilearn. We'll send you over this particular file, and you can play with it yourself and see how it's put together. I don't want to spend a huge amount of time on this because this is just some real general Python coding. But you can see here we're just going through all the rows, and you add them together, and if it equals 3 in a row, same thing with columns. Diagonal, so you got to check the diagonal. That's what all this stuff does here, is it just goes through the different areas. Actually, let me go ahead and put, there we go. And then it comes down here and we do our sum, and it says true, -3 just says did somebody win, or is it a tie? So you got to add up all the numbers on there anyway, just in case they're all filled up. And next we also need to know available positions. These are ones that no one's ever used before. This way when you try something, or the computer tries something, it's not going to give it an illegal move. That's what the available positions is doing. Then we want to update our state. And so you have your position going in. We're just sending in the position that you just chose. And you'll see there's a little user interface we put in there. You can pick the row and column in there. And again, I mean, this is a lot of code. So really it's kind of a thing you'd want to go through and play with a little bit and just read through it, get a copy of it. A great way to understand how this works. And here is a given reward. So we're going to give a reward, result equals self winner. This is one of the hearts of what's going on here, is we have a result self.winner. So if there's a winner, then we have a result. If the result equals 1, here's our feedback. If it doesn't equal 1, then it gets a 0. So it only gets a reward in this particular case if it wins. And that's important to know because different systems of reinforced learning do rewarding a lot differently depending on what you're trying to do. This is a very simple example with a 3x3 board. Imagine if you're playing a video game, certainly you only have so many actions, but your environment is huge. You have a lot going on in the environment. And suddenly a reward system like this is going to be just, is going to have to change a little bit. It's going to have different rewards and different setup. And there's all kinds of advanced ways to do that as far as weighing. You add weights to it. And so they can add the weights up depending on where the reward comes in. So it might be that you actually get a reward. In this case, you get the reward at the end of the game. And I'm spending just a little bit of time on this because this is an important thing to note. But there's different ways to add up those rewards. It might have, like if you take a certain path, the first reward is going to be weighed a little bit less than the last reward because the last reward is actually winning the game or scoring or whatever it is. So this reward system gets really complicated in some of the more advanced setups. In this case, though, you can see right here that they give a 0.1 and a 0.5 reward just for picking the right value and something that's actually valid instead of picking an invalid value. So rewards, again, that's like key. It's huge. How do you feed the rewards back in? Then we have a board reset. That's pretty straightforward. It just goes back and resets the board to the beginning because it's going to try out all these different things while it's learning. It's going to do it by trial and error, so you have to keep resetting it. And then, of course, there's the play. We want to go ahead and play rounds equals 100. Depends on what you want to do on here. You can set this different. You can obviously set that to higher level. But this is just going to go through, and you'll see in here that we have player 1 and player 2. This is the computer playing itself. One of the more powerful ways to learn to play a game or even learn something that isn't a game is to have two of these models that are basically trying to beat each other. And so they keep explore new things. This one works for this one, so this one tries new things. It beats this. We've seen this in chess, I think was a big one, where they had the two players in chess with reinforcement learning. It was one of the ways they trained one of the top computer chess playing algorithms. So this is just what this is. It's going to choose an action, it's going to try something, and the more it tries stuff, the more we're going to record the hash. We actually have a board hash where you self get the hash set up on here where it stores all the information. And then once you get to a win, one of them wins, it gets the reward. Then we go back and reset and try again. And then kind of the fun part we actually get down here is we're going to play with a human. So we'll get a chance to come in here and see what that looks like when you put your own information in. And then it just comes in here and does the same thing it did above. It gives it a reward for its things, or sees if it wins or ties, looks at available positions, all that kind of fun stuff. And then finally we want to show the board. So it's going to print the board out each time. Really, as an integration, is not that exciting. What's exciting in here is, one, looking at this reward system. Whoops, play one more up. The reward system is really the heart of this. How do you reward the different setup? And the other one is when it's playing, it's got to take an action. And so what it chooses for an action is also the heart of reinforcement learning. How do we choose that action? And those are really key to right now where reinforcement learning is in today's technology, is figuring this out. How do we reward it, and how do we guess the next best action? So we have our environment, and you can see the environment is or the state, which is kind of like what's going on. We're going to return the state depending on what happens. And we want to go ahead and create our agent, in this case our player. So each one is, let me go and grab that. And so we look at a class player. This is where a lot of the magic is really going on, is how is this player figuring out how to maneuver around the board, and then the board of course returns a state that it can look at and a reward. So we want to take a look at this. We have name, self-state, this is class player, and when we say class player, we're not talking about a human player, we're talking about just the computer players. And this is kind of interesting. So remember I told you depending on what you're doing, there's going to be a decay gamma, explore rate. These are what I'm talking about, is how do we train it. As you try different moves, it gets to the end, the first move is important, but it's not as important as the last one. And so you could say that the last one has the heaviest weight, and then as you get there, the first one, let's see, the first move gives you a 5 reward, the second gives you a 2 reward, and the third one gives you a 10 reward, because that's the final ending. You got it. The 10's going to count more than the first step. And here's our, we're going to get the board information coming in, and then choose an action. This was the second part that I was talking about that was so important. So once you have your training going on, we have to do a little randomness, and you can see right here is our NP random uniform. So it's picking out a random number. Take a random action. This is going to just pick which row and which column it is. And so choosing the action, this one you can see we're just doing random states, choice, length of positions, action position, and then it skips in there and takes a look at the board for P in positions. And it's actually storing the different boards each time you go through, so it has a record of what it did, so it can properly weigh the values. And this simply just appends a hash state. What's the last state? Append it to the to our states on here. Here's our feedback reward. So the reward comes in, and it's going to take a look at this and say, is it none? What is the reward? And here is that formula. Remember I was telling you about up here that was important because it has decay gamma times the reward. This is where, as it goes through each step, and this is really important, this is kind of the heart of this, of what I was talking about earlier. You have step 1, and this might have a reward of 2. You have step 2, I probably should have done ABC. This has a step 3, step 4, and so on until you get to step N, and this might have a reward of 10. So reward of 10, we're going to add that, but we're not adding, let's say this one right here, let's say this reward here right before 10 was, let's say it's also 10. That just makes the math easy. So we had 10 and 10. We had 10, this is 10 and 10n, whatever it is, but it's 0.9. So instead of putting a full 10 here, we only do 9. That's 0.9 times 10. And so this formula, as far as the decay times the reward minus the cell state value, it basically adds in, it says here's 1, or here's 2, I'm sorry, I should have done this ABC, it would have been easier. So the first move goes in here and it puts 2 in here. Then we have our self setup on here. You can see how this gets pretty complicated in the math, but this is really the key, is how do we train our states? And we want the final state, the win, to get the most points. If you win, you get most points. And the first step gets the least amount of points. So you're really training this almost in reverse. You're training it from the last place where you have, like it says, okay, this is now where I need to sum up my rewards, and I want to sum them up going in reverse, and I want to find the answer in reverse. Kind of an interesting play on the mind when you're trying to figure this stuff out. And of course we want to go ahead and reset the board down here and save the policy, load policy. These are the different things that are going in between the agent and the state to figure out what's going on. Let's go ahead and load that up. And then finally we want to go ahead and create a human player. And the human player is going to be a little different in that you choose an action, row and column. Here's your action. If action in positions, meaning positions that are available, you return the action. If not, it just keeps asking you until you get the action that actually works. And then we're going to go ahead and append to the hash state, which we don't need to worry about because it returns the action up here. And feed forward. Again, this is because it's a human. At the end of the game, backpropagate and update state values. This part isn't being done because it's not programming the model. The model is getting its own rewards. So we've gone ahead and loaded this in here. So here's all our pieces, and the first thing we want to do is set up P1 player 1, P2 player 2, and then we're going to send our players to our state. So now it has P1, P2, and it's going to play, 50,000 rounds. Now we can probably do a lot less than this, and it's not going to get the full results. In fact, you know what? Let's go ahead and just do 5. Just to play with it, because I want to show you something here. Oops, somewhere in there I forgot to load something. There we go. I must have forgot to run this. Run. Oops, forgot a reference there for the board, rows and columns, 3 by 3. There's actually in the state, it references that. We can just tack it on the end. It was supposed to be at the beginning. So now I've only set this up with, let's see, where are we going here? I've only set this up to train 5 times. And the reason I did that is we're going to come in and actually play it, and then I'm going to change that, and we can see how it differs on there. There we go. And it didn't even make it through a run, and we're going to go ahead and save the policy. So now we have our player 1 and our player 2 policy. The way we set it up, it has 2 separate policies loaded up in there. And then we're going to come in here and we're going to do player 1 is going to be the computer, experience rate 0, load policy 1, human player human, and we're going to go ahead and play this. Now remember, I only went through it just 1 round of training, in fact minimal training. And so it puts an X there, and I'm going to go ahead and do row 0, column 1. You can see this is very basic on here. And so I put in my 0, and then I'm going to go 0, block it, 0, 0. And you can see right here, it let me win. Just like that, I was able to win. 0, 2, and woo, human wins. So I only trained it 5 times. We're going to run this again, and this time, instead of 5, let's do 5,000 or 50,000. I think that's what the guys in the back had. And this takes a while to train it. This is where reinforcement learning really falls apart. Look how simple this game is. We're talking about a 3 by 3 set of columns. And so for me to train it on this, I could do a Q table which would go much quicker. You could build a quick Q table with almost all the different options on there, and you would probably get the same result much quicker. We're just using this as an example. So when we look at reinforcement learning, you need to be very careful what you apply it to. It sounds like a good deal until you do like a large neural network where you're doing, you set the neural network to a learning increment of 1, so every time it goes through it learns, and then you do your actions. So you pick from the learning setup, and you actually try actions on the learning setup until you get what you think is going to be the best action. So you actually feed what you think is right back through the neural network. There's a whole layer there, which is really fun to play with. And then it has an output. Well, think of all those processes. I mean, that is just a huge amount of work it's going to do. Let's go ahead and skip ahead here. Give it a moment. It's going to take a minute or two to go ahead and run. Now, to train it, we went ahead and let it run, and it took a while. This took, I got a pretty powerful processor, and it took about 5 minutes plus to run it. And we'll go ahead and run our player setup on here. Oops, it brought in the last, whoops, it brought in the last round. So give me just a moment to redo the policy save. There we go. I forgot to save the policy back in there. And then go ahead and run our player again. So we've saved the policy, and then we want to go ahead and load the policy for P1 as a computer. And we can see the computer's gone in the bottom right corner. I'm going to go ahead and go 1, 1, which is the center. And it's gone right up the top, and if you have ever played tic-tac-toe, you know the computer has me. But we'll go ahead and play it out. Row 0, column 2. There it is, and then it's gone here, and so I'm going to go ahead and go row 0, 1, 2, no, 0, 1, there we go, and column 0. That's where I wanted. Oh, and it says, okay, your action, there we go, boom. So you can see here, we've got didn't catch the win on this, it said tie. Kind of funny that it didn't catch the win on there. But if we play this a bunch of times, you'll find that it's going to win more and more. The more we train it, the more the reinforcement happens. This lengthy training process is really the stopper on reinforcement learning. As this changes, reinforcement learning will be one of the more powerful packages evolving over the next decade or two. In fact, I would even go as far as to say it is the most important machine learning tool and artificial intelligence tool out there, as it learns not only a simple tic-tac-toe board, but we start learning environments. And the environment would be like in language. If you're translating a language or something from one language to the other, so much of it is lost if you don't know the context it's in, what's the environments it's in. And so being able to attach environment and context and all those things together is going to require reinforcement learning to do. So again, if you want to get a copy of the tic-tac-toe board, it's kind of fun to play with. Run it, you can test it out, you can do test it for different values. You can switch from P1 computer where we loaded the policy 1 to load the policy 2 and just see how it varies. There's all kinds of things you can do on there.
Supervised learning uses labeled data to train machine learning models. Labeled data means that the output is already known to you. The model just needs to map the inputs to the outputs. An example of supervised learning can be to train a machine that identifies the image of an animal. Below you can see we have a trained model that identifies the picture of a cat. Unsupervised learning uses unlabeled data to train machines. Unlabeled data means there is no fixed output variable. The model learns from the data, discovers patterns and features in the data, and returns the output. Here is an example of an unsupervised learning technique that uses the images of vehicles to classify if it's a bus or a truck. So the model learns by identifying the parts of a vehicle, such as the length and width of the vehicle, the front and rear end covers, roof hoods, the types of wheels used, etc. Based on these features, the model classifies if the vehicle is a bus or a truck. Reinforcement learning trains a machine to take suitable actions and maximize reward in a particular situation. It uses an agent and an environment to produce actions and rewards. The agent has a start and an end state, but there might be different paths for reaching the end state, like a maze. In this learning technique, there is no predefined target variable. An example of reinforcement learning is to train a machine that can identify the shape of an object given a list of different objects such as square, triangle, rectangle, or a circle. In the example shown, the model tries to predict the shape of the object, which is a square here. Now, let's look at the different machine learning algorithms that come under these learning techniques. Some of the commonly used supervised learning algorithms are linear regression, logistic regression, support vector machines, k-nearest neighbors, decision tree, random forest, and naive Bayes. Examples of unsupervised learning algorithms are k-means clustering, hierarchical clustering, DB scan, principal component analysis, and others. Choosing the right algorithm depends on the type of problem you are trying to solve. Some of the important reinforcement learning algorithms are Q-learning, Monte Carlo, SARSA, and Deep Q network. Now let's look at the approach in which these machine learning techniques work. So supervised learning takes labeled inputs and maps it to known outputs, which means you already know the target variable. Unsupervised learning finds patterns and understands the trends in the data to discover the output. So the model tries to label the data based on the features of the input data. While reinforcement learning follows trial and error method to get the desired solution. After accomplishing a task, the agent receives an award. An example could be to train a dog to catch the ball. If the dog learns to catch a ball, you give it a reward such as a biscuit. Now, let's discuss the training process for each of these learning methods. So supervised learning methods need external supervision to train machine learning models, and hence the name supervised. They need guidance and additional information to return the result. Unsupervised learning techniques do not need any supervision to train models. They learn on their own and predict the output. Similarly, reinforcement learning methods do not need any supervision to train machine learning models. And with that, let's focus on the types of problems that can be solved using these three types of machine learning techniques. So supervised learning is generally used for classification and regression problems. We'll see the examples in the next slide. And unsupervised learning is used for clustering and association problems. While reinforcement learning is reward based, so for every task or for every step completed, there will be a reward received by the agent. And if the task is not achieved correctly, there will be some penalty used. Now, let's look at a few applications of supervised, unsupervised, and reinforcement learning. As we saw earlier, supervised learning are used to solve classification and regression problems. For example, you can predict the weather for a particular day based on humidity, precipitation, wind speed, and pressure values. You can use supervised learning algorithms to forecast sales for the next month or the next quarter for different products. Similarly, you can use it for stock price analysis or identifying if a cancer cell is malignant or benign. Now, talking about the applications of unsupervised learning, we have customer segmentation. So based on customer behavior, likes, dislikes, and interests, you can segment and cluster similar customers into a group. Another example where unsupervised learning algorithms are used is customer churn analysis. Now, let's see what applications we have in reinforcement learning. So reinforcement learning algorithms are widely used in the gaming industries to build games. It is also used to train robots to perform human tasks.
If you are an aspiring data scientist who's looking out for online training and certification in data science from the best universities and industry experts, then search no more. Simplilearn's postgraduate program in data science from Caltech University in collaboration with IBM should be the right choice. For more details on this program, please use the link in the description box below.
Often, professionals want to know if there is a relationship between two or more variables. For instance, is there a relationship between the grade on the third French exam a student takes and the grade on the final exam? If yes, then how is it related and how strongly? Regression can be used here to arrive at a conclusion. This is an example of bivariate data, that is, two variables. However, statisticians are mostly interested in multivariate data. Regression analysis is used to predict the value of one variable, the dependent variable, on the basis of other variables, the independent variables. In the simplest form of regression, linear regression, you work with one independent variable. The formula for simple linear regression is shown on the screen. In the next screen, we'll look at a few examples of regression analysis. Regression analysis is used in several situations, such as those described on the screen. In example 1, using the data given on the screen, you have to analyze the relation between the size of a house and its selling price for a realtor. In example 2, you need to predict the exam scores of students who study for 7.2 hours with the help of the data shown on the slide. A couple more examples are given on the screen. In example 3, based on the expected number of customers and the previous day's data given, you need to predict the number of burgers that will be sold by a KFC outlet. In example 4, you have to calculate the life expectancy for a group of people with the average length of schooling based on the data given. Let's look at the two main types of regression analysis, simple linear regression and multiple linear regression. Both of these statistical methods use a linear equation to model the relationship between two or more variables. Simple linear regression considers one quantitative and independent variable x to predict the other quantitative but dependent variable y. Multiple linear regression considers more than one quantitative and qualitative variable to predict a quantitative and dependent variable y. We'll look at the two types of analyses in more detail in the slides that follow. In simple linear regression, the predictions of the explained variable y when plotted as a function of the explanatory variable x from a straight line. The best fitting line is called the regression line. The output of this model is a function to predict the dependent variable on the basis of the values of the independent variable. The dependent variable is continuous, and the independent variable can be continuous or discrete. Let's look at the different kinds of linear and nonlinear analyses. List of linear techniques are simple, method of least squares, coefficient of multiple determination, standard error of the estimate, dummy variable, and interaction. Similarly, there are many nonlinear techniques available, such as polynomial, logarithmic, square root, reciprocal, and exponential. To understand this model, we'll first look at a few assumptions. The simple linear regression model depicts the relationship between one dependent and two or more independent variables. The assumptions which justify the use of this model are as follows. Linear and additive relationship between the dependent and independent variables. Multivariate normality. Little or no collinearity in the data. Little or no autocorrelation in the data. Homoscedasticity, that is, variance of errors same across all values of x. The equation for this model is shown on the screen. A more descriptive graphical representation of simple linear regression is given on the screen. Beta naught represents the slope. A slope with two variables implies that 1 unit changes in x result in a 2-unit change in y. Beta 1 represents the estimated change in the average value of y as a result of 1 unit change in x. Epsilon represents the estimated average value of y when the value of x is 0. This demo will show the steps to do simple linear regression in R. In this demo, you'll learn how to do simple linear regression. Let's use x and y vectors that we have created in the previous demo. We also ensured there exists a relationship between x and y visually by plotting a graph. To build a simple linear regression model, let's use the LM function. To see how the linear model fits into x and y, let's plot the linear line by the AB line function. Let's use the predict function to test or predict the linear model. We can pass a known variable to predict the unknown variables.
Let's look at an example of a common use for linear regression, profit estimation of a company. if I was going to invest in a company, I would like to know how much money I could expect to make. So we'll take a look at a venture capitalist firm and try to understand which companies they should invest in. So we'll take the idea that we need to decide the companies to invest in. We need to predict the profit the company makes, and we're going to do it based on the company's expenses, and even just a specific expense. In this case, we have our company, we have the different expenses, so we have our R&D, which is your research and development, we have our marketing, we might have the location, we might have what kind of administration it's going through. Based on all this different information, we would like to calculate the profit. Now, in actuality, there's usually about 23 to 27 different markers that they look at if they're a heavy-duty investor. We're only going to take a look at one basic one. We're going to come in, and for simplicity, let's consider a single variable R&D and find out which companies to invest in based on that. So when we take our R&D and we're plotting the profit based on the R&D expenditure, how much money they put into the research and development, and then we look at the profit that goes with that. We can predict a line to estimate the profit. So we can draw a line right through the data. And when you look at that, you can see how much they invest in the R&D is a good marker as to how much profit they're going to have. We can also note that companies spending more on R&D make good profit. So let's invest in the ones that spend a higher rate in their R&D. What's in it for you? First, we'll have an introduction to machine learning, followed by machine learning algorithms. These will be specific to linear regression and where it fits into the larger model. Then we'll take a look at applications of linear regression, understanding linear regression, and multiple linear regression. Finally, we'll roll up our sleeves and do a little programming in use case profit estimation of companies. Let's go ahead and jump in. Let's start with our introduction to machine learning, along with some machine learning algorithms and where that fits in with linear regression. Let's look at another example of machine learning. Based on the amount of rainfall, how much would be the crop yield? So here we have our crops, we have our rainfall, and we want to know how much we're going to get from our crops this year. So we're going to introduce two variables, independent and dependent. The independent variable is a variable whose value does not change by the effect of other variables and is used to manipulate the dependent variable. It is often denoted as x. In our example, rainfall is the independent variable. This is a wonderful example because you can easily see that we can't control the rain, but the rain does control the crop. So when we talk about the independent variable controlling the dependent variable, let's define dependent variable as a variable whose value change when there is any manipulation in the values of the independent variables. It is often denoted as y. And you can see here our crop yield is dependent variable, and it is dependent on the amount of rainfall received. Now that we've taken a look at a real-life example, let's go a little bit into the theory and some definitions on machine learning and see how that fits together with linear regression. Numerical and categorical values. Let's take our data coming in, and this is kind of random data from any kind of project. We want to divide it up into numerical and categorical. So numerical is numbers, age, salary, height, where categorical would be a description, the color, a dog's breed, gender. Categorical is limited to very specific items, where numerical is a range of information. Now that you've seen the difference between numerical and categorical data, let's take a look at some different machine learning definitions. When we look at our different machine learning algorithms, we can divide them into three areas: supervised, unsupervised, reinforcement. We're only going to look at supervised today. Unsupervised means we don't have the answers and we're just grouping things. Reinforcement is where we give positive and negative feedback to our algorithm to program it, and it doesn't have the information until after the fact. But today we're just looking at supervised because that's where linear regression fits in. In supervised data, we have our data already there and our answers for a group, and then we use that to program our model and come up with an answer. The two most common uses for that is through the regression and classification. Now we're doing linear regression, so we're just going to focus on the regression side. And in the regression, we have simple linear regression, we have multiple linear regression, and we have polynomial linear regression. Now on these three, simple linear regression is the examples we've looked at so far where we have a lot of data and we draw a straight line through it. Multiple linear regression means we have multiple variables. Remember where we had the rainfall and the crops? We might add additional variables in there like how much food do we give our crops? When do we harvest them? Those would be additional information added into our model. And that's why it'd be multiple linear regression. And finally, we have polynomial linear regression. That is, instead of drawing a line, we can draw a curved line through it. Now that you see where a regression model fits into the machine learning algorithms, and we're specifically looking at linear regression, let's go ahead and take a look at applications for linear regression. Let's look at a few applications of linear regression. Economic growth, used to determine the economic growth of a country or a state in the coming quarter, can also be used to predict the GDP of a country. Product price can be used to predict what would be the price of a product in the future. We can guess whether it's going to go up or down, or should I buy today. Housing sales, to estimate the number of houses a builder would sell and what price in the coming months. Score predictions, cricket fever, to predict the number of runs a player would score in the coming matches based on the previous performance. I'm sure you can figure out other applications you could use linear regression for. So let's jump in and let's understand linear regression and dig into the theory. Understanding linear regression. Linear regression is a statistical model used to predict the relationship between independent and dependent variables by examining two factors. The first important one is which variables in particular are significant predictors of the outcome variable. And the second one that we need to look at closely is how significant is the regression line to make predictions with the highest possible accuracy. If it's inaccurate, we can't use it. So it's very important we find out the most accurate line we can get. Since linear regression is based on drawing a line through data, we're going to jump back and take a look at some Euclidean geometry. The simplest form of a simple linear regression equation with one dependent and one independent variable is represented by y equals m times x plus c. And if you look at our model here, we plotted 2 points on here, x1 and y1, x2 and y2. Y being the dependent variable, remember that from before, and x being the independent variable. So y depends on whatever x is. M, in this case, is the slope of the line, where m equals the difference in the y2 minus y1 and x2 minus x1. And finally we have c, which is the coefficient of the line, or where it happens to cross the zero axes. Let's go back and look at an example we used earlier of linear regression. We're going to go back to plotting the amount of crop yield based on the amount of rainfall. And here we have our rainfall. Remember, we cannot change rainfall. And we have our crop yield, which is dependent on the rainfall. So we have our independent and our dependent variables. We're going to take this and draw a line through it as best we can through the middle of the data. And then we look at that, we put the red point on the y-axis is the amount of crop yield you can expect for the amount of rainfall, represented by the green dot. So if we have an idea what the rainfall is for this year and what's going on, then we can guess how good our crops are going to be. And we've created a nice line right through the middle to give us a nice mathematical formula. Let's take a look and see what the math looks like behind this. Let's look at the intuition behind the regression line. Now, before we dive into the math and the formulas that go behind this and what's going on behind the scenes, I want you to note that when we get into the case study and we actually apply some Python script, that this math that you're going to see here is already done automatically for you. You don't have to have it memorized. It is, however, good to have an idea what's going on, so if people reference the different terms, you'll know what they're talking about. Let's consider a sample data set with 5 rows and find out how to draw the regression line. We're only going to do 5 rows because if we did like the rainfall with hundreds of points of data, that would be very hard to see what's going on with the mathematics. So we'll go ahead and create our own 2 sets of data, and we have our independent variable x and our dependent variable y. And when x was 1, we got y equals 2. When x was 2, y was 4, and so on and so on. If we go ahead and plot this data on a graph, we can see how it forms a nice line through the middle. You can see where it's kind of grouped going upwards to the right. The next thing we want to know is what the means is of each of the data coming in, the x and the y. The means doesn't mean anything other than the average. So we add up all the numbers and divide by the total. So 1 plus 2 plus 3 plus 4 plus 5 over 5 equals 3. And the same for y, we get 4. If we go ahead and plot the means on the graph, we'll see we get 3, 4, which draws a nice line down the middle. A good estimate. Here we're going to dig deeper into the math behind the regression line.
Now remember before I said you don't have to have all these formulas memorized or fully understand them, even though we're going to go into a little more detail of how it works. And if you're not a math whiz and you don't know, if you've never seen the sigma character before, which looks a little bit like an E that's opened up, that just means summation. That's all that is. So when you see the sigma character, it just means we're adding everything in that row. And for computers, this is great because as a programmer, you can easily iterate through each of the XY points and create all the information you need. So in the top half, you can see where we've broken that down into pieces. And as it goes through the first 2 points, it computes the squared value of X, the squared value of Y, and X times Y. And then it takes all of X and adds them up, all of Y adds them up, all of X squared adds them up, and so on and so on. And you can see we have the sum of equal to 15, the sum is equal to 20, all the way up to X times Y, where the sum equals 66. This all comes from our formula for calculating a straight line, where y equals the slope times x plus the coefficient c. So we go down below, and we're going to compute more like the averages of these, and we're going to explain exactly what that is in just a minute, and where that information comes from. It's called the square means error. But we'll go into that in detail in a few minutes. All you need to do is look at the formula and see how we've gone about computing it line by line instead of trying to have a huge set of numbers pushed into it. And down here you'll see where the slope m equals, and on the top part, if you read through the brackets, you have the number of data points times the sum of x times y, which we computed one line at a time there, and that's just the 66. And take all that and you subtract it from the sum of x times the sum of y. And those have both been computed. So you have 15 times 20. And on the bottom, we have the number of lines times the sum of x squared, easily computed as 86 for the sum, minus, I'll take all that and subtract the sum of x squared. And we end up, as we come across with our formula, you can plug in all those numbers, which is very easy to do on the computer. You don't have to do the math on a piece of paper or a calculator. And you'll get a slope of 0.6. And you'll get your c coefficient. If you continue to follow through that formula, you'll see it comes out as equal to 2.2. Continuing deeper into what's going behind the scenes, let's find out the predicted values of y for corresponding values of x using the linear equation where m equals 0.6 and c equals 2.2. We're going to take these values and we're going to go ahead and plot them. We're going to predict them, so y equals 0.6 times where x equals 1, plus 2.2 equals 2.8, so on and so on. And here, the blue points represent the actual y values, and the brown points represent the predicted y values, based on the model we created. The distance between the actual and predicted values is known as residuals or errors. The best fit line should have the least sum of squares of these errors, also known as e-square. If we put these into a nice chart where you can see x and you can see y, what the actual values were, and you can see y predicted, you can easily see where we take y minus y predicted and we get an answer. What is the difference between those two? And if we square that, y minus y prediction squared, we can then sum those squared values. That's where we get the 0.64 plus the 0.36 plus 1, all the way down until we have a summation equals 2.4. So the sum of squared errors for this regression line is 2.4. We check this error for each line and conclude the best fit line having the least e-square value. In a nice graphical representation, we can see here where we keep moving this line through the data points to make sure the best fit line has the least square distance between the data points and the regression line. Now, we only looked at the most commonly used formula for minimizing the distance. There are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. What you want to take away from this is whatever formula is being used, you can easily, using a computer programming and iterating through the data, calculate the different parts of it. That way, these complicated formulas you see with the different summations and absolute values are easily computed one piece at a time. Up until this point, we've only been looking at two values, x and y. Well, in the real world, it's very rare that you only have two values when you're figuring out a solution. So let's move on to the next topic, multiple linear regression. Let's take a brief look at what happens when you have multiple inputs. So in multiple linear regression, we have, we'll start with the simple linear regression, where we had y equals m plus x plus c, and we're trying to find the value of y. Now with multiple linear regression, we have multiple variables coming in. So instead of having just x, we have x1, x2, x3. And instead of having just one slope, each variable has its own slope attached to it. As you can see here, we have m1, m2, m3, and we still just have the single coefficient. So when you're dealing with multiple linear regression, you basically take your single linear regression and you spread it out. So you have y equals m1 times x1 plus m2 times x2, so on all the way to m to the nth, x to the nth, and then you add your coefficient on there. Implementation of linear regression. Now we get into my favorite part. Let's understand how multiple linear regression works by implementing it in Python. If you remember before, we were looking at a company and just based on its R&D, trying to figure out its profit. We're going to start looking at the expenditure of the company. We're going to go back to that, and we're going to predict its profit. But instead of predicting it just on the R&D, we're going to look at other factors like administration costs, marketing costs, and so on. And from there, we're going to see if we can figure out what the profit of that company is going to be. To start our coding, we're going to begin by importing some basic libraries. And we're going to be looking through the data before we do any kind of linear regression. We're going to take a look at the data to see what we're playing with. Then we'll go ahead and format the data to the format we need to be able to run it in the linear regression model. And then from there, we'll go ahead and solve it and just see how valid our solution is. So let's start with importing the basic libraries. Now, I'm going to be doing this in Anaconda Jupyter Notebook, a very popular IDE. I enjoy it because it's such a visual to look at and it's so easy to use. Just any IDE for Python will work just fine for this. So break out your favorite Python IDE. So here we are in our Jupyter Notebook. Let me go ahead and paste our first piece of code in there. And let's walk through what libraries we're importing. First, we're going to import NumPy as NP. And then I want you to skip one line and look at import pandas as PD. These are very common tools that you need with most of your linear regression. The NumPy, which stands for NumPython, is usually denoted as NP, and you have to almost have that for your sklearn toolbox. So you always import that right off the beginning. Pandas, although you don't have to have it for your sklearn libraries, it does such a wonderful job of importing data, setting it up into a data frame so we can manipulate it rather easily, and it has a lot of tools also in addition to that. So we usually like to use the pandas when we can, and I'll show you what that looks like. The other three lines are for us to get a visual of this data and take a look at it. So we're going to import matplotlibary.pyplot as PLT and then Seaborn as SNS. Seaborn works with the matplot library. So you have to always import matplotlibary and then Seaborn sits on top of it. And we'll take a look at what that looks like. You could use any of your own plotting libraries you want. There's all kinds of ways to look at the data. These are just very common ones, and the Seaborn is so easy to use that it just looks beautiful. It's a nice representation that you can actually take and show somebody. And the final line is the ampersand matplotlibary inline. That is only because I'm doing an inline IDE. My interface in the Anaconda Jupyter Notebook requires I put that in there, or you're not going to see the graph when it comes up. Let's go ahead and run this. It's not going to be that interesting because we're just setting up variables. In fact, it's not going to do anything that we can see, but it is importing these different libraries and setup. The next step is load the data set and extract independent and dependent variables. Now, here in the slide, you'll see companies equals pd.read CSV, and it has a long line there with the file at the end, 1000companies.csv. You're going to have to change this to fit whatever setup you have. And the file itself, you can request. Just go down to the commentary below this video and put a note in there, and Simplilearn will try to get in contact with you and supply you with that file so you can try this coding yourself. So we're going to add this code in here, and we're going to see that I have companies equals pd.reader_csv, and I've changed this path to match my computer, c:/Simplilearn/1000_companies.csv. And then below there, we're going to set the x equals to companies under the I location, and because this is companies is a PD data set, I can use this nice notation that says take every row. That's what the first colon is, comma, except for the last column. That's what the second part is, where we have a :-1, and we want the values set into there. So X is no longer a data set, a pandas data set, but we can easily extract the data from our pandas data set with this notation. And then Y, we're going to set equal to the last row. Well, the question is going to be, what are we actually looking at? So let's go ahead and take a look at that. and we're going to look at the companies.head, which lists the first 5 rows of data. And I'll open up the file in just a second so you can see where that's coming from. But let's look at the data in here as far as the way the Pandas sees it. When I hit run, you'll see it breaks it out into a nice setup. This is what Pandas, one of the things Pandas is really good about, is it looks just like an Excel spreadsheet. You have your rows, and remember, when we're programming, we always start with 0. We don't start with 1. So it shows the first 5 rows. 0, 1, 2, 3, 4, and then it shows your different columns: R&D spend, administration, marketing spend, state, profit. It even notes that the top are column names. It was never told that, but Pandas is able to recognize a lot of things that they're not the same as the data rows. Why don't we go ahead and open this file up in a CSV so you can actually see the raw data. So here I've opened it up as a text editor, and you can see at the top we have R&D spend, comma, administration, comma, marketing spend, comma, state, comma, profit, carriage return. I don't know about you, but I'd go crazy trying to read files like this. That's why we use the Pandas. You could also open this up in an Excel and it would separate it, since it is a comma-separated variable file. But we don't want to look at this one. We want to look at something we can read rather easily. So let's flip back and take a look at that top part, the first 5 rows. Now, as nice as this format is, where I can see the data, to me it doesn't mean a whole lot. Maybe you're an expert in business and investments and you understand what $165,349.20 compared to the administration cost of $136,897.80, so on, helps to create the profit of $192,261.83. That makes no sense to me whatsoever. No pun intended. So let's flip back here and take a look at our next set of code where we're going to graph it so we can get a better understanding of our data and what it means. So at this point, we're going to use a single line of code to get a lot of information so we can see where we're going with this. Let's go ahead and paste that into our notebook and see what we got going. And so we have the visualization, and again we're using SNS, which is Pandas. As you can see, we imported the matplot library, .pyplot as PLT, which then the Seaborn uses. And we imported the Seaborn as SNS. And then that final line of code helps us show this in our inline coding. Without this, it wouldn't display, and you could display it to a file and other means. And that's the matplot library inline with the ampersand at the beginning. So here we come down to the single line of code. Seaborn is great because it actually recognizes the Panda data frame. So I can just take the companies.core for coordinates, and I can put that right into the Seaborn. And when we run this, we get this beautiful plot. And let's just take a look at what this plot means. If you look at this plot, on mine the colors are probably a little bit more purplish and blue than the original one. We have the columns and the rows. We have R&D spending, we have administration, we have marketing spending, and profit. And if you cross-index any 2 of these, since we're interested in profit, if you cross-index profit with profit, it's going to show up, if you look at the scale on the right, way up in the dark. Why? Because those are the same data. They have an exact correspondence. So R&D spending is going to be the same as R&D spending, and the same thing with administration costs. So right down the middle, you get this dark row, or dark diagonal row, that shows that this is the highest corresponding data. That's exactly the same. And as it becomes lighter, there's less connections between the data. So we can see with profit, obviously profit is the same as profit. And next, it has a very high correlation with R&D spending, which we looked at earlier. And it has a slightly less connection to marketing spending, and even less to how much money we put into the administration. So now that we have a nice look at the data, let's go ahead and dig in and create some actual useful linear regression models so that we can predict values and have a better profit. Now that we've taken a look at the visualization of this data, we're going to move on to the next step. Instead of just having a pretty picture, we need to generate some hard data, some hard values. So let's see what that looks like. We're going to set up our linear regression model in 2 steps. The first one is we need to prepare some of our data so it fits correctly. And let's go ahead and paste this code into our Jupyter notebook. And what we're bringing in is we're going to bring in the sklearn pre-processing, where we're going to import the label encoder and the one-hot encoder. To use the label encoder, we're going to create a variable called label encoder and set it equal to capital L label capital E encoder. This creates a class that we can reuse for transferring the labels back and forth. Now about now you should ask, what labels are we talking about? Let's go take a look at the data we processed before and see what I'm talking about here. If you remember when we did the companies.head and we printed the top 5 rows of data, we have our columns going across. We have column 0, which is R&D spending, column 1, which is administration, column 2, which is marketing spending, and column 3 is state. And you'll see under state we have New York, California, Florida. Now, to do a linear regression model, it doesn't know how to process New York. It knows how to process a number. So the first thing we're going to do is we're going to change that New York, California, and Florida, and we're going to change those to numbers. That's what this line of code does here. X equals, and then it has the colon, comma, 3 in brackets. The first part, the colon, comma, means that we're going to look at all the different rows. So we're going to keep them all together. But the only row we're going to edit is the third row. And in there we're going to take the label coder and we're going to fit and transform the X, also the third row. So we're going to take that third row, we're going to set it equal to a transformation. And that transformation basically tells it that instead of having a New York, it has a 0 or a 1 or a 2. And then finally we need to do a one hot encoder, which equals one hot encoder categorical features equals 3. And then we take the X and we go ahead and do that equal to one hot encoder fit transform X to array. This final transformation preps our data for us so it's completely set the way we need it as just a row of numbers. Even though it's not in here, let's go ahead and print X and just take a look at what this data is doing. You'll see you have an array of arrays, and then each array is a row of numbers. And if I go ahead and just do row 0, you'll see I have a nice organized row of numbers that the computer now understands. We'll go ahead and take this out there because it doesn't mean a whole lot to us. It's just a row of numbers. Next, on setting up our data, we have avoiding dummy variable trap. This is very important. Why? Because the computer has automatically transformed our header into the setup, and it's automatically transformed all these different variables. So when we did the encoder created 2 columns. And what we need to do is just have the 1, because it has both the variable and the name. That's what this piece of code does here. Let's go ahead and paste this in here, and we have X equals X colon, comma, 1 colon. All this is doing is removing that one extra column we put in there when we did our one hot encoder and our label encoding. Let's go ahead and run that. And now we get to create our linear regression model. And let's see what that looks like here. And we're going to do that in 2 steps. The first step is going to be in splitting the data. Now, whenever we create a predictive model of data, we always want to split it up so we have a training set and we have a testing set. That's very important. Otherwise, we'd be very unethical without testing it to see how good our fit is. And then we'll go ahead and create our multiple linear regression model and train it and set it up. Let's go ahead and paste this next piece of code in here, and I'll go ahead and shrink it down a size or 2 so it all fits on one line. So from the sklearn model selection, we're going to import train, test, split. And you'll see that we've created 4 completely different variables. We have capital X train, capital X test, smaller case y train, smaller case y test. That is the standard way that they usually reference these when we're doing different models. You usually see that a capital X, and you see the train and the test and the lowercase y. What this is X is our data going in. That's our R&D spend, our administration, our marketing. And then Y, which we're training, is the answer. That's the profit. Because we want to know the profit of an unknown entity. So that's what we're going to shoot for in this tutorial. The next part, train, test, split, we take X and we take Y. We've already created those. X has the columns with the data in it, and Y has a column with profit in it. And then we're going to set the test size equals 0.2. That basically means 20%. So 20% of the rows are going to be tested. We're going to put them off to the side. So since we're using 1,000 lines of data, that means that 200 of those lines we're going to hold off to the side to test for later. And then the random state equals 0. We're going to randomize which ones it picks to hold off to the side. We'll go ahead and run this. It's not overly exciting because it's setting up our variables. But the next step we actually create our linear regression model. Now that we got to the linear regression model, we get that next piece of the puzzle. Let's go ahead and put that code in there and walk through it. So here we go. We're going to paste it in there. And let's go ahead and, since this is a shorter line of code, let's zoom up there so we can get a good look. And we have from the sklearn.linear_model, we're going to import linear regression. Now, I don't know if you recall from earlier when we were doing all the math. Let's go ahead and flip back there and take a look at that. Do you remember this, where we had this long formula on the bottom and we were doing all this summization? And then we also looked at setting it up with the different lines. And then we also looked all the way down to multiple linear regression, where we're adding all those formulas together. All of that is wrapped up in this one section. So what's going on here is I'm going to create a variable called regressor. And the regressor equals the linear regression. That's a linear regression model that has all that math built in. So we don't have to have it all memorized or have to compute it individually. And then we do the regressor.fit. In this case, we do xtrain and ytrain because we're using the training data, x being the data in and y being profit, what we're looking at. And this does all that math for us. So within one click and one line, we've created the whole linear regression model. And we fit the data to the linear regression model. And you can see that when I run the regressor, it gives an output, linear regression. It says copy x equals true, fit intercept equals true, in jobs equal 1, normalize equals false. It's just giving you some general information on what's going on with that regressor model. Now that we've created our linear regression model, let's go ahead and use it. And if you remember, we kept a bunch of data aside. So we're going to do a yPredict variable, and we're going to put in the xTest. And let's see what that looks like. Scroll up a little bit, paste that in here. Predicting the test set results. So here we have yPredict equals regressor.predict xTest going in, and this gives us yPredict. Now because I'm in Jupyter inline, I can just put the variable up there, and when I hit the run button, it'll print that array out. I could have just as easily done print yPredict. So if you're in a different IDE that's not an inline setup like the Jupyter Notebook, you can do it this way, print yPredict. And you'll see that for the 200 different test variables we kept off to the side, it's going to produce 200 answers. This is what it says the profit are for those 200 predictions. But let's don't stop there. Let's keep going and take a couple look. We're going to take just a short detail here and calculating the coefficients and the intercepts. This gives us a quick flash at what's going on behind the line. We're going to take a short detour here, and we're going to be calculating the coefficient and intercepts. So you can see what those look like. What's really nice about our regressor we created is it already has the coefficients for us. And we can simply just print regressor.coefficient underscore. When I run this, you'll see our coefficients here. And if we can do the regressor coefficient, we can also do the regressor intercept. And let's run that and take a look at that. This all came from the multiple regression model, and we'll flip over so you can remember where this is going into and where it's coming from. You can see the formula down here where y equals m1 times x1 plus m2 times x2 and so on plus c, the coefficient. So these variables fit right into this formula. Y equals slope 1 times column 1 variable plus slope 2 times column 2 variable all the way to the m into the n and x to the n plus c, the coefficient. Or in this case, you have minus 8.89 to the power of 2, etc., times the first column and the second column and the third column. And then our intercept is the minus 103,009 point. Boy, it gets kind of complicated when you look at it. This is why we don't do this by hand anymore. This is why we have the computer to make these calculations easy to understand and calculate. Now, I told you that was a short detour, and we're coming towards the end of our script. As you remember from the beginning, I said if we're going to divide this information, we have to make sure it's a valid model, that this model works and understand how good it works. So, calculating the R-squared value. That's what we're going to use to predict how good our prediction is. And let's take a look at what that looks like in code. And so we're going to use this from sklearn.metrics. We're going to import R2 score. That's the R-squared value. We're looking at the error. So, in the R2 score, we take our y-test versus our y-predict. Y-test is the actual values we're testing. That was the one that was given to us so we know are true. The y-predict of those 200 values is what we think it was true. And when we go ahead and run this, we see we get a 0.9352. That's the R2 score. Now, it's not exactly a straight percentage, so it's not saying it's 93% correct. But you do want that in the upper 90s, and higher, shows that this is a very valid prediction based on the R2 score. And if R-squared value of 0.91, or 92 as we got on our model, because remember it does have a random generation involved, this proves the model is a good model, which means success! Yay! We successfully trained our model with certain predictors and estimated the profit of the companies using linear regression. So now that we have a successful linear regression model, let's take a look at what we went over today and take a look at our key takeaways. First,
If you are an aspiring data scientist who's looking out for online training and certification in data science from the best universities and industry experts, then search no more. Simplilearn's postgraduate program in data science from Caltech University in collaboration with IBM should be the right choice. For more details on this program, please use the link in the description box below.
What is logistic regression? Let's say we have to build a predictive model or a machine learning model to predict whether the passengers of the Titanic ship have survived or not, the shipwreck. So how do we do that? So we use logistic regression to build a model for this. How do we use logistic regression? So we have the information about the passengers, their ID, whether they have survived or not, their class and name and so on and so forth. And we use this information where we already know whether the person has survived or not. That is the labeled information. And we help the system to train based on this information, based on this labeled data. This is known as labeled data. And during the process of building the model, we probably will remove some of the non-essential parameters or attributes here. We only take those attributes which are really required to make these predictions. And once we train the model, we run new data through it, whereby the model will predict whether the passenger has survived or not. So let's see what we will learn in this video. We will talk about what is supervised learning, and we will go into details about classification, which is one of the techniques for supervised learning. And then we will further focus on logistic regression, which is one of the algorithms for performing classification, especially binary classification. Then we will compare linear and logistic regression and what are some of the logistic regression applications. And finally, we will end with a use case or a demo of actual Python code for doing logistic regression in Jupyter Notebook. Alright, so let's start with what is supervised learning. Supervised learning is one of the two main types of machine learning methods. Here we use what is known as labeled data to help the system learn. This is very similar to how we human beings learn. So let's say you want to teach a child to recognize an apple. How do we do that? We never tell the child, okay, this is an apple has a certain diameter on the top, a certain diameter at the bottom, and this has a certain RGB color. No, we just show an apple to the child and tell the child this is apple. And then next time when we show an apple, child immediately recognizes, yes, this is an apple. Supervised learning works very similar on the similar lines. So where does logistic regression fit into the overall machine learning process? Machine learning is divided into two types, mainly two types. There is a third one called reinforcement learning, but we will not talk about that right now. So one is supervised learning and the other is unsupervised learning. Unsupervised learning uses techniques like clustering and association, and supervised learning uses techniques like classification and regression. Now, supervised learning is used when you have labeled data. You have historical data, then you use supervised learning. When you don't have labeled data, then you used unsupervised learning. In supervised learning, there are two types of techniques that are used, classification and regression, based on what is the kind of problem we are solving. Let's say we want to take the data and classify it. It could be binary classification, like a 0 or a 1. An example of classification we have just seen, whether the passenger has survived or not survived. It's like a 0 or 1. That is known as binary classification. Regression, on the other hand, is you need to predict a value, what is known as a continuous value. Classification is for discrete values. Regression is for continuous values. Let's say you want to predict the share price, or you want to predict the temperature that will be there. What will be the temperature tomorrow? That is where you use regression. Whereas classification are discrete values. Will the customer buy the product or will not buy the product? Will you get a promotion or you will not get a promotion? I hope you're getting the idea. Or it could be multi-class classification as well. Let's say you want to build an image classification model. So the image classification model would take an image as an input and classify into multiple classes, whether this image is of a cat or a dog or an elephant or a tiger. So there are multiple classes, so not necessarily binary classification. So that is known as multi-class classification. So we are going to focus on classification because logistic regression is one of the algorithms used for classification. Now, the name may be a little confusing. In fact, whenever people come across logistic regression, it always causes confusion because the name has regression in it, but we are actually using this for performing classification. Okay, so yes, it is logistic regression, but it is used for classification. And in case you are wondering, is there something similar for regression? Yes, for regression, we have linear regression. Keep that in mind. So linear regression is used for regression. Logistic regression is used for classification. So in this video, we are going to focus on supervised learning, and within supervised learning, we are going to focus on classification, and then within classification, we are going to focus on logistic regression algorithm. So first of all, classification. So what are the various algorithms available for performing classification? The first one is decision tree. There are of course multiple algorithms, but here we will talk about a few. Decision trees are quite popular and very easy to understand, and therefore they are used for classification. Then we have k-nearest neighbors. This is another algorithm for performing classification. And then there is logistic regression, and this is what we are going to focus on in this video, and we are going to go into a little bit of details about logistic regression. Alright, what is logistic regression? As I mentioned earlier, logistic regression is an algorithm for performing binary classification. So let's take an example and see how this works. Let's say your car has not been serviced for quite a few years, and now you want to find out if it is going to break down in the near future. So this is like a classification problem. Find out whether your car will break down or not. So how are we going to perform this classification? So here's how it looks. If we plot the information along the x and y axis, x is the number of years since the last service was performed, and y is the probability of your car breaking down. And let's say this data was collected from several car users. It's not just your car, but several car users. So that is our labeled data. So the data has been collected, and for the number of years and when the car broke down and what was the probability, and that has been plotted along x and y axis. So this provides an idea, or from this graph we can find out whether your car will break down or not. We'll see how. So first of all, the probability can go from 0 to 1. As you all are aware, probability can be between 0 and 1. And as we can imagine, it is intuitive as well. As the number of years are on the lower side, maybe 1 year, 2 years, or 3 years still after the service, the chances of your car breaking down are very limited, right? So for example, chances of your car breaking down, or the probability of your car breaking down within 2 years of your last service are 0.1 probability. Similarly, 3 years is maybe 0.3, and so on. But as the number of years increases, let's say if it was 6 or 7 years, there is almost a certainty that your car is going to break down. That is what this graph shows. So this is an example of an application of the classification algorithm, and we will see in little details how exactly logistic regression is applied here. One more thing needs to be added here is that the dependent variables outcome is discrete. So if we are talking about whether the car is going to break down or not, so that is a discrete value, the y that we are talking about, the dependent variable that we are talking about. What we are looking at is whether the car is going to break down or not, yes or no. That is what we are talking about. So here the outcome is discrete and not a continuous value. So this is how the logistic regression curve looks. Let me explain a little bit what exactly and how exactly we are going to determine the outcome rather. So for a logistic regression curve, a threshold has to be set, saying that because this is a probability calculation, remember this is a probability calculation, and the probability itself will not be 0 or 1. But based on the probability, we need to decide what the outcome should be. So there has to be a threshold. Like for example, 0.5 can be the threshold let's say in this case. So any value of the probability below 0.5 is considered to be 0, and any value above 0.5 is considered to be 1. So an output of, let's say, 0.8 will mean that the car will break down. So that is considered as an output of 1. And let's say an output of 0.29 is considered as 0, which means that the car will not break down. So that's the way logistic regression works. Now, let's do a quick comparison between logistic regression and linear regression, because they both have the term regression in them. So that can cause confusion. So let's try to remove that confusion. So what is linear regression? Linear regression is a process, is once again an algorithm for supervised learning. However, here you're going to find a continuous value. You're going to determine a continuous value. It could be the price of a real estate property. It could be your hike, how much hike you're going to get, or it could be a stock price. These are all continuous values. These are not discrete compared to a yes or a no kind of a response that we are looking for in logistic regression. So this is one example of a linear regression. Let's say the HR team of a company tries to find out what should be the salary hike of an employee. So they collect all the details of their existing employees, their ratings and their salary hikes, what has been given, and that is the labeled information that is available, and the system learns from this. It is trained and it learns from this labeled information, so that when a new employee's information is fed based on the rating, it will determine what should be the hike. So this is a linear regression problem and a linear regression example. Now, salary is a continuous value. You can get 5,000, 5,500, 5,600. It is not discrete like a cat or a dog or an apple or a banana. These are discrete, or a yes or a no. These are discrete values, right? So this, where you're trying to find continuous values, is where we use linear regression. So let's say, just to extend on this scenario, we now want to find out whether this employee is going to get a promotion or not. So we want to find out, that is a discrete problem, right? A yes or no kind of a problem. In this case, we actually cannot use linear regression, even though we may have labeled data. So this is the labeled data. So based on the employee rating, these are the ratings, and then some people got the promotion, and this is the ratings for which people did not get promotion. That is a no. And this is the rating for which people got promotion. We just plotted the data about whether a person has got, an employee has got promotion or not. Yes, no, right? So there is nothing in between. And what is the employee's rating? Okay. And ratings can be continuous. That is not an issue. But the output is discrete in this case. Whether employee got promotion, yes, no. Okay. So if we try to plot that and we try to find a straight line, this is how it would look. And as you can see, it doesn't look very right, because it looks like there will be a lot of errors. The root mean square error, if you remember, for linear regression would be very, very high. And also the values cannot go beyond 0 or beyond 1. So the graph should probably look somewhat like this, clipped at 0 and 1. But still, the straight line doesn't look right. Therefore, instead of using a linear equation, we need to come up with something different. And therefore, the logistic regression model looks somewhat like this. So we calculate the probability, and if we plot that probability, not in the form of a straight line, but we need to use some other equation. We will see very soon what that equation is. Then it is a gradual process, right? So you see here, people with some of these ratings are not getting any promotions, and then slowly at certain rating they get promotion. So that is a gradual process. And this is how the math behind logistic regression looks. So we are trying to find the odds for a particular event happening. And this is the formula for finding the odds. So the probability of an event happening divided by the probability of the event not happening. So P, if it is the probability of the event happening, probability of the person getting a promotion, and divided by the probability of the person not getting a promotion, that is 1 minus P. So this is how you measure the odds. Now, the values of the odds range from 0 to infinity. So when this probability is 0, then the value of the odds is equal to 0, and when the probability becomes 1, then the value of the odds is 1 by 0, that will be infinity. But the probability itself remains between 0 and 1. Now, this is how an equation of a straight line looks. So y is equal to beta 0 plus beta 1x, where beta 0 is the y-intercept and beta 1 is the slope of the line. If we take the odds equation and take a log of both sides, then this would look somewhat like this, and the term logistic is actually derived from the fact that we are doing this. We take a log of px by 1 minus px. This is an extension of the calculation of odds that we have seen, right? And that is equal to beta 0 plus beta 1x, which is the equation of the straight line. And now from here, if you want to find out the value of px, you will see we can take the exponential on both sides, and then if we solve that equation, we will get the equation of px like this. Px is equal to 1 by 1 plus e to the power of minus beta 0 plus beta 1x. And recall, this is nothing but the equation of the line, which is equal to y. Y is equal to beta 0 plus beta 1x. So this is the equation also known as the sigmoid function, and this is the equation of the logistic regression algorithm. Alright, and if this is plotted, this is how the sigmoid curve is obtained. So let's compare linear and logistic regression, how they are different from each other. Let's go back. So linear regression is solved or used to solve regression problems, and logistic regression is used to solve classification problems. So both are called regression, but linear regression is used for solving regression problems where we predict continuous values, whereas logistic regression is used for solving classification problems where we have to predict discrete values. The response variables in case of linear regression are continuous in nature, whereas here they are categorical or discrete in nature. And linear regression helps to estimate the dependent variable when there is a change in the independent variable, whereas here in case of logistic regression, it helps to calculate the probability or the possibility of a particular event happening. And linear regression, as the name suggests, is a straight line. That's why it's called linear regression, whereas logistic regression is a sigmoid function, and the shape of the curve is S. It's an S-shaped curve. This is another example of application of logistic regression in weather prediction, whether it's going to rain or not rain. Now keep in mind, both are used in weather prediction. If we want to find the discrete values, like whether it's going to rain or not rain, that is a classification problem. We use logistic regression. But if we want to determine what is going to be the temperature tomorrow, then we use linear regression. So just keep in mind that in weather prediction we actually use both. But these are some examples of logistic regression. So we want to find out whether it's going to be rain or not, whether it's going to be sunny or not, whether it's going to snow or not. These are all logistic regression examples. A few more examples. Classification of objects. This is again another example of logistic regression. Now here, of course, one distinction is that these are multi-class classification. So logistic regression is not used in its original form, but it is used in a slightly different form. So we say whether it is a dog or not a dog. I hope you understand. So instead of saying is it a dog or a cat or an elephant, we convert this into saying, so because we need to keep it to binary classification. So we say, is it a dog or not a dog? Is it a cat or not a cat? So that's the way logistic regression can be used for classifying objects. Otherwise, there are other techniques which can be used for performing multi-class classification. In healthcare, logistic regression is used to find the survival rate of a patient. So they take multiple parameters like trauma score and age and so on and so forth, and they try to predict the rate of survival. Alright, now finally let's take an example and see how we can apply logistic regression to predict the number that is shown in the image. So this is actually a live demo. I will take you into Jupyter Notebook and show the code. But before that, let me take you through a couple of slides to explain what we are trying to do. So let's say you have an 8x8 image and the image has a number 1, 2, 3, 4, and you need to train your model to predict what this number is. So how do we do this? So the first thing is, obviously, in any machine learning process, you train your model. So in this case, we are using logistic regression. So, and then we provide a training set to train the model, and then we test how accurate our model is with the test data, which means that, like any machine learning process, we split our initial data into two parts, training set and test set. With the training set, we train our model, and then with the test set, we test the model till we get good accuracy, and then we use it for inference, right? So that is typical methodology of training, testing, and then deploying of machine learning models. So let's take a look at the code and see what we are doing. So I'll not go line by line, but just take you through some of the blocks. So first thing we do is import all the libraries, and then we basically take a look at the images and see what is the total number of images. We can display using matplotlib some of the images or a sample of these images, and then we split the data into training and test, as I mentioned earlier, and we can do some exploratory analysis, and then we build our model. We train our model with the training set, and then we test it with our test set and find out how accurate our model is using the confusion matrix, the heat map, and use heat map for visualizing this. And I will show you in the code what exactly is the confusion matrix and how it can be used for finding the accuracy. In our example, we get an accuracy of about 0.94, which is pretty good, or 94%, which is pretty good. Alright, so what is a confusion matrix? This is an example of a confusion matrix, and this is used for identifying the accuracy of a classification model, or like a logistic regression model. So the most important part in a confusion matrix is that, first of all, this, as you can see, this is a matrix, and the size of the matrix depends on how many outputs we are expecting. So the most important part here is that the model will be most accurate when we have the maximum numbers in its diagonal. Like in this case, that's why it has almost 93-94%, because the diagonals should have the maximum numbers, and the others other than diagonals, the cells other than the diagonals, should have very few numbers. So here that's what is happening. So there is a 2 here, there is a 1 here, but most of them are along the diagonal. What does this mean? This means that the number that has been fed is 0, and the number that has been detected is also 0. So the predicted value and the actual value are the same. So along the diagonals, that is true, which means that let's take this diagonal, right? If the maximum number is here, that means that like here in this case it is 34, which means that 34 of the images that have been fed, or rather actually there are 2 misclassifications in there. So 36 images have been fed which have number 4, and out of which 34 have been predicted correctly as number 4, and 1 has been predicted as number 8, and another one has been predicted as number 9. So these are 2 misclassifications. Okay, so that is the meaning of saying that the maximum number should be in the diagonal. So if you have all of them, so for an ideal model which has, let's say, 100% accuracy, everything will be only in the diagonal. There will be no numbers other than 0 in all other cells. So that is like a 100% accurate model. Okay, so that's the gist of how to use this matrix, how to use this confusion matrix. I know the name is a little funny sounding, confusion matrix, but actually it is not very confusing. It's very straightforward. So you are just plotting what has been predicted and what is the labeled information, or what is the actual data. That's also known as the ground truth sometimes. Okay, these are some fancy terms that are used. So predicted label and the actual label, that's all it is. Okay, yeah, so we are showing a little bit more information here. So 38 have been predicted, and here you will see that all of them have been predicted correctly. There have been 38 zeros, and the predicted value and the actual value is exactly the same. Whereas in this case, right, it has, there are, I think, 37 plus 5, 42 have been fed the images. 42 images are of digit 3, and the accuracy is only 37 of them have been accurately predicted. 3 of them have been predicted as number 7 and 2 of them have been predicted as number 8, and so on and so forth. Okay. Alright, so with that, let's go into Jupyter Notebook and see how the code looks. So this is the code in Jupyter Notebook for logistic regression. In this particular demo, what we are going to do is train our model to recognize digits, which are the images which have digits from let's say 0 to 5 or 0 to 9, and then we will see how well it is trained and whether it is able to predict these numbers correctly or not. So let's get started. So the first part is, as usual, we are importing some libraries that are required, and then the last line in this block is to load the digits. So let's go ahead and run this code. Then here we will visualize the shape of these digits. So we can see here, if we take a look, this is how the shape is, 1797 by 64. These are like 8 by 8 images. So that's what is reflected in this shape. Now from here onwards, we are basically once again importing some of the libraries that are required, like NumPy and Matplot, and we will take a look at some of the sample images that we have loaded. So this one, for example, creates a figure, and then we go ahead and take a few sample images to see how they look. So let me run this code, and so that it becomes easy to understand. So these are about 5 images, sample images that we are looking at. 0, 1, 2, 3, 4. So this is how the images, this is how the data is. Okay, and based on this, we will actually train our logistic regression model, and then we will test it and see how well it is able to recognize. So the way it works is the pixel information. So as you can see here, this is an 8 by 8 pixel kind of a image, and each pixel, whether it is activated or not activated, that is the information available for each pixel. Now based on the pattern of this activation and non-activation of the various pixels, this will be identified as a 0, for example, right? Similarly, as you can see, so overall each of these numbers actually has a different pattern of the pixel activation, and that's pretty much that our model needs to learn for which number, what is the pattern of the activation of the pixels, right? So that is what we are going to train our model. Okay, so the first thing we need to do is to split our data into training and test data set. Right? So whenever we perform any training, we split the data into training and test, so that the training data set is used to train the system. So we pass this probably multiple times, and then we test it with the test data set, and the split is usually in the form of and there are various ways in which you can split this data. It is up to the individual preferences. In our case here, we are splitting in the form of 23 and 77. So when we say test size as 0.23, that means 23% of the entire data is used for testing, and the remaining 77% is used for training. So there is a readily available function which is called train test split. So we don't have to write any special code for the splitting. It will automatically split the data based on the proportion that we give here, which is test size. So we just give the test size, automatically training size will be determined, and we pass the data that we want to split, and the results will be stored in x_train and y_train for the training data set. And what is x_train? These are the features, right, which is like the independent variable, and y_train is the label, right? So in this case, what happens is we have the input value, which is, or the features value, which is in x_train, and since this is labeled data, for each of them, each of the observations, we already have the label information saying whether this digit is a 0 or a 1 or a 2, so that this is what will be used for comparison to find out whether the system is able to recognize it correctly or there is an error. For each observation, it will compare with this. right? So this is the label. So the same way, x underscore train, y underscore train is for the training data set, x underscore test, y underscore test is for the test data set. Okay, so let me go ahead and execute this code as well, and then we can go and check quickly what is the how many entries are there and in each of these. So x underscore train, the shape is 1383 by 64, and y underscore train has 1383 because there is nothing like the second part is not required here. And then x underscore test shape we see is 414. So actually there are 414 observations in test and 1383 observations in train. So that's basically what these 4 lines of code are saying. Okay, then we import the logistic regression library, and which is a part of scikit-learn. So we don't have to implement the logistic regression process itself. We just call these the function, and let me go ahead and execute that. So that we have the logistic regression library imported. Now we create an instance of logistic regression, right? So logistic regr is an instance of logistic regression, and then we use that for training our model. So let me first execute this code. So these 2 lines. So the first line basically creates an instance of logistic regression model, and then the second line is where we are passing our data, the training data set. Right, this is our the predictors, and this is our target. We are passing this data set to train our model. All right. So once we do this, in this case the data is not large, but by and large the training is what takes usually a lot of time. So we spend in machine learning activities, in machine learning projects, we spend a lot of time for the training part of it. Okay, so here the data set is relatively small, so it was pretty quick. So all right, so now our model has been trained using the training data set, and we want to see how accurate this is. So what we'll do is we will test it out in probably phases. So let me first try out how well this is working for one image. Okay, I will just try it out with one image, the first entry in my test data set, and see whether it is correctly predicting or not. So and in order to test it, so for training purpose we use the fit method. There is a method called fit which is for training the model. And once the training is done, if you want to test for a particular value, new input, you use the predict method. Okay, so let's run the predict method, and we pass this particular image, and we see that the shape is or the prediction is 4. So let's try a few more. Let me see for the next 10. Seems to be fine. So let me just go ahead and test the entire data set. Okay, that's basically what we will do. So now we want to find out how accurately this has performed. So we use the score method to find what is the percentage of accuracy, and we see here that it has performed up to 94% accurate. Okay, so that's on this part. Now what we can also do is we can also see this accuracy using what is known as a confusion matrix. So let us go ahead and try that as well, so that we can also visualize how well this model has done. So let me execute this piece of code, which will basically import some of the libraries that are required, and we basically create a confusion matrix, an instance of confusion matrix, by running confusion matrix and passing these values. So we have, so this confusion underscore matrix method takes 2 parameters. One is the y underscore test, and the other is the prediction. So what is the y underscore test? These are the labeled values which we already know for the test data set, and predictions are what the system has predicted for the test data set. Okay, so this is known to us, and this is what the system has, the model has generated. So we kind of create the confusion matrix and we will print it, and this is how the confusion matrix looks. As the name suggests, it is a matrix, and the key point out here is that the accuracy of the model is determined by how many numbers are there in the diagonal. The more the numbers in the diagonal, the better the accuracy is. Okay, and first of all, the total sum of all the numbers in this whole matrix is equal to the number of observations in the test data set. That is the first thing, right? So if you add up all these numbers, that will be equal to the number of observations in the test data set. And then out of that, the maximum number of them should be in the diagonal. That means the accuracy is pretty good. If the numbers in the diagonal are less and in all other places there are a lot of numbers, which means the accuracy is very low. The diagonal indicates a correct prediction. This means that the actual value is same as the predicted value. Here again, actual value is same as the predicted value, and so on, right? So the moment you see a number here, that means the actual value is something and the predicted value is something else, right? Similarly here, the actual value is something and the predicted value is something else. So that is basically how we read the confusion matrix. Now, how do we find the accuracy? You can actually add up the total values in the diagonal. So it's like 38 plus 44 plus 43 and so on, and divide that by the total number of test observations. That will give you the percentage accuracy using a confusion matrix. Now let us visualize this confusion matrix in a slightly more sophisticated way using a heat map. So we will create a heat map with we'll add some colors as well. It's like a more visually more appealing. So that's the whole idea. So if let me run this piece of code, and this is how the heat map looks. And as you can see here, the diagonals again are all the values are here, most of the values. So which means this seems to be reasonably accurate. And yeah, basically the accuracy score is 94%. This is calculated, as I mentioned, by adding all these numbers divided by the total test values, or the total number of observations in test data set. Okay, so this is the confusion matrix for logistic regression. Alright, so now that we have seen the confusion matrix, let's take a quick sample and see how well the system has classified, and we will take a few examples of the data. So if we see here, we picked up randomly a few of them. So this is number 4, which is the actual value and also the predicted value. Both are 4. This is an image of 0. So the predicted value is also 0. Actual value is of course 0. Then this is the image of 9. So this has also been predicted correctly, 9, and actual value is 9. And this is the image of 1. And again, this has been predicted correctly as like the actual value. Okay, so this was a quick demo of logistic regression, how to use logistic regression to identify images.
So we put them side by side. We have our linear regression, which is a predictive number used to predict a dependent output variable based on independent input variable. Accuracy is measured using least squares estimation. So that's where you take, you could also use absolute value. The least squares is more popular. There's reasons for that mathematically and also for computer runtime. But it does give you an accuracy based on the least square estimation. The best fit line is a straight line, and clearly that's not always used in all the regression models. There's a lot of variations on that. The output is a predicted integer value. Again, this is what we're talking about when we talk about linear regression. And we're talking about regression, it means the number's coming out. Linear usually means we're looking for that line versus a different model. And it's used in business domain, forecasting stocks. It's used as a basis of most predictions with numbers. So if you're looking at a lot of numbers, you're probably looking at a linear regression model. For instance, if you do just the high lows of the stock exchange, and you're going to take a lot more of that if you want to make money off the stock, you'll find that the linear regression model fits probably better than almost any of the other models, even high-end neural networks and all these other different machine learning and AI models, because they're numbers. They're just a straight set of numbers. You have a high value, a low value, volume, that kind of thing. So when you're looking at something that's straight numbers and are connected in that way, usually you're talking about a linear regression model, and that's where you want to start. A logistic regression model used to classify dependent output variable based on independent input variable. So just like the linear regression model and like all of our machine learning tools, you have your features coming in. And so in this case, you might have label, an image or something like that is probably the very popular thing right now, labeling broccoli and vegetables or whatever. Accuracy is measured using maximum likelihood estimation. The best fit is given by a curve, and we saw that when we're talking about linear regression, you definitely are talking about a straight line, although there is other regression models that don't use straight lines. And usually when you're looking at a logistic regression, the math, as you saw, was still kind of a Euclidean line, but it's now got that sigmoid activation, which turns it into a heavily weighted curve. And the output is a binary value between 0 and 1. And it's used for classification. Image processing, as I mentioned, is what people usually think of, although they use it for classification of like a window of things. So you could take a window of stock history and you could generate classifications based on that and separate the data that way. If it's going to be that this particular pattern occurs, it's going to be upward trending or downward trending. In fact, a number of stock traders use that not to tell them how much to bid or what to bid, but they use it as to whether it's worth looking at the stock or not, whether the stock's going to go down or go up. And it's just a 0 or 1. Do I care or do I even want to look at it? So let's do a demo so you can get a picture of what this looks like in Python code. Let's predict the price at which insurance should be sold to a particular customer based on their medical history. We will also classify on a mushroom dataset to find the poisonous and non-poisonous mushrooms. And when you look at these two datas, the first one, we're looking at the price. So the price is a number. So let's predict the price which the insurance should be sold to. And the second one is we're looking at either it's poisonous or it's not poisonous. So first off, before we begin the demo, I'm in the Anaconda Navigator. In this one, I've loaded the Python 3.6 and using the Jupyter Notebook. And you can use Jupyter Notebook by itself. You can use the Jupyter Lab, which allows multiple tabs. It's basically the notebook with tabs on it. But the Jupyter Notebook is just fine, and it'll go into Google Chrome, which is what I'm using for my Internet Explorer. And from here, we open up New, and you'll see Python 3. And again, this is loaded with Python 3.6. And we're doing the linear versus logic regression, or logit. You'll see L-O-G-I-T is one of the names that kind of pops up when you do a search on here. But it is a logic. We're looking at the logistic regression models. And we'll start with the linear regression because it's easy to understand. You draw a line through stuff. And so in programming, we got a lot of stuff to unfold here in our startup as we preload all of our different parts. And let's go ahead and break this up. We have at the beginning import pandas. So this is our data frame. It's just a way of storing the data. Think of when you talk about a data frame, think of a spreadsheet. You have rows and columns. It's a nice way of viewing the data. And then we have, we're going to be bringing in our pre-processing label encoder. I'll show you what that is. When we get down to it, it's easier to see in the data, but there's some data in here like sex. It's male or female, so it's not like an actual number. It's either you're one or the other. That kind of stuff ends up being encoded. That's what this label encoder is right here. We have our test split model. If you're going to build a model, you do not want to use all the data. You want to use some of the data and then test it to see how good it is. And if it can't have seen the data you're testing on until you're ready to test it on there and see how good it is. And then we have our logistic regression model, our categorical one, and then we have our linear regression model. These are the two, these right here. Let me just clear all that. There we go. These two right here are what this is all about. Logistic versus linear. Is it categorical? Are we looking for a true false, or are we looking for a specific number? And then finally, usually at the very end, we have to take and just ask how accurate is our model. Did it work? If you're trying to predict something, in this case we're going to be doing insurance costs. How close to the insurance cost does it measure that we expect it to be? You know, if you're an insurance company, you don't want to promise to pay everybody's medical bill and not be able to. And in the case of the mushrooms, you probably want to know just how much at risk you are for following this model as far as whether you're going to eat a poisonous mushroom and die or not. So we'll look at both of those, and we'll talk a little bit more about the shortcomings and the value of these different processes. So let's go ahead and run this. This is loaded the data set on here, and then because we're in Jupyter Notebook, I don't have to put the print on there. We just do data set, and it prints out all the different data on here, and you can see here for our insurance, because that's what we're starting with, we're loading that with our pandas, and it prints it in a nice format where you can see the age, sex, body mass index, number of children, smoker. So this might be something that the insurance company gets from the doctor. It says, hey, this is what we need to know to give you a quote for what we're going to charge you for your insurance. And you can see that it has 1,338 rows and 7 columns. You can count the columns, 1, 2, 3, 4, 5, 6, 7. So there's 7 columns on here. And the column we're really interested in is charges. I want to know what the charges are going to be. What can I expect? Not a very good arrow drawn. What to expect them to charge on there. So is this going to be, is this person going to cost me $16,884, or is this person only going to cost me $3,866? How do we guess that so that we can guess what the minimal charge is for their insurance? And then there's one other thing you really need to notice on this data. And I mentioned it before, but I'm going to mention it again because pre-processing data is so much of the work in data science. Sex. Well, how do you deal with female versus male? Are you a smoker? Yes or no? What does that mean? Region. How do you look at region? It's not a number. How do you draw a line between southwest and northwest? They're objects. It's either your southwest or your northwest. It's not like I'm southwest. I guess you could do longitude and latitude, but the data doesn't come in like that. It comes in as true, false, or whatever. It's either your southwest or your northwest. So we need to do a little bit of pre-processing of the data on here to make this work. Oops, there we go. Okay, so let's take a look and see what we're doing with pre-processing. And again, this is really where you spend a lot of time with data science, is trying to understand how and why you need to do that. And so we're going to do, you'll see right up here, label. And then we're going to do a label encoder, one of the modules we brought in. So this is sklearn's label encoder. I like the fact that it's all pretty much automated, but if you're doing a lot of work with the label encoder, you should start to understand how that fits. And then we have label.fit right here, where we're going to go ahead and do the dataset .sex.drop duplicates, and then for dataset sex, we're going to do the label transform the dataset sex. And so we're looking right here at male or female. And so it usually just converts it to a 0 or 1 because there's only 2 choices on here. Same thing with the smoker. It's 0 or 1, so we're going to change the smoker 0 or 1 on this. And then finally we did region down here. Region does it a little bit different. We'll take a look at that. I think in this case it's probably going to do it because we did it on this label transform. With this particular setup, it gives each region a number, like 0, 1, 2, 3. So let's go ahead and take a look and see what that looks like. Go ahead and run this. And you can see that our new data set has age, that's still a number. Sex is 0 or 1, so 0 is female, 1 is male. Number of children, we left that alone. Smoker, 1 or 0. It says no or yes on there. We actually just do 1 for no, 0 or no. Yeah, 1 for no. I'm not sure how it organized them, but it turns the smoker into 0 or 1, yes or no. And then region, it did this as 0, 1, 2, 3. So it's 3 regions. Now, a lot of times when you're working with data science and you're dealing with regions or even word analysis, instead of doing one column and labeling it 0, 1, 2, 3, a lot of times you increase your features, and so you would have region northwest would be one column, yes or no. Region southwest would be one column, yes or no. True, 0, 1. But for this particular setup, this will work just fine on here. Now that we spent all that time getting it set up, here's the fun part. Here's the part where we're actually using our setup on this, and you'll see right here we have our Y linear regression data set drop the charges, because that's what we want to predict. And so our X linear data set drop the charges, because that's what we're going to predict. We're predicting charges right here, so we don't want that as our input for our features. And our Y output is charges. That's what we want to guess. We want to guess what the charges are. And then what we talked about earlier is we don't want to do all the data at once, so we're going to take 0.3, means 30%. We're going to take 30% of our data, and it's going to be as the testing site. So here's our Y test and our X test down there. And so that part, our model will never see it until we're ready to test to see how good it is. And then of course right here you'll see our training set, and this is what we're going to train it. We're going to train it on 70% of the data. And then finally the big ones, this is where all the magic happens. This is where we're going to create our magic setup, and that is right here. Our linear model, we're going to set it equal to the linear regression model, and then we're going to fit the data on here. And then at this point, I always like to pull up, if you're working with a new model, it's good to see where it comes from. And this comes from the Scikit-learn, and this is the sklearn linear model, linear regression that we imported earlier. And you can see they have different parameters. The basic parameter works great if you're dealing with just numbers. I mentioned that earlier with stock, high-lows. This model will do as good as any other model out there if you're doing just the very basic high-lows and looking for a linear fit, a regression model fit. And one of the things when I'm looking at this is I look for methods. And you'll see here's our fit that we're using right now, and here's our predict. And we'll actually do a little bit in the middle here as far as looking at some of the parameters hidden behind it, the math that we talked about earlier. And so when we go in this, we go ahead and run this, you'll see it loads the linear regression model and just has a nice output that says, hey, I loaded the linear regression model. And then the second part is we did the fit. And so this model is now trained. Our linear model is now trained on the training data. And so one of the things we can look at is the, for IDX and column name and enumerate X linear trained columns, kind of an interesting thing. This prints out the coefficients. So when you're looking at the back end of the data, you remember we had that formula, bxx1 plus bxx2 plus the intercept, and so forth. These are the actual coefficients that are in here. This is what it's actually multiplying these numbers by. And you can see like region gets a minus value, so when it adds it up, I guess region. You can read a lot into these numbers. It gets very complicated. There's ways to mess with them. If you're doing a basic linear regression model, you usually don't look at them too closely. But you might start looking in these and saying, hey, you know what, smoker, look how smoker impacts the cost. It's just massive. So this is a flag that, hey, the value of the smoker really affects this model. And then you can see here where the body mass index, so somebody who is overweight is probably less healthy and more likely to have cost money. And then of course age is a factor, and then you can see down here we have sex is then a factor also, and it changes as you go in there. Negative number, it probably has its own meaning on there. Again, it gets really complicated when you dig into the workings and how the linear model works on that. And so we can also look at the intercept. This is just kind of fun. So it starts at this negative number and then adds all these numbers to it. That's all that means. That's our intercept on there. And that fits the data we have on that. And so you can see right here, we can go back and, oops, give me just a second, there we go. We can go ahead and predict the unknown data, and we can print that out. And if you're going to create a model to predict something, we'll go ahead and predict it. Here's our Y prediction value, linear model predict. And then we'll go ahead and create a new data frame. In this case, from our X linear test group, we'll go ahead and put the cost back into this data frame. And then the predicted cost, we're going to make that equal to our Y prediction. And so when we pull this up, you can see here that we have the actual cost and what we predicted the cost is going to be. There's a lot of ways to measure the accuracy on there, but we're going to go ahead and jump into our mushroom data. And so in this, you can see here we've run our basic model. We've built our coefficients. You can see the intercept, the back end. You can see how we're generating a number here. Now with mushrooms, we want a yes or no. We want to know whether we can eat them or not. And so here's our mushroom file. We're going to go ahead and run this, take a look at the data. And again, you can ask for a copy of this file. Send a note over to Simplilearn.com. And you can see here that we have a class, the cap shape, cap surface, and so forth. So there's a lot of feature. In fact, there's 23 different columns in here going across. And when you look at this, I'm not even sure what these particular, like PEE, PE, I don't even know what the class is on this. I'm going to guess by the notes that the class is poisonous or edible. So if you remember before, we had to do a little pre-coding on our data. Same thing with here. We have our cap shape, which is B or X or K. We have cap color. These really aren't numbers, so it's really hard to do anything with just a single number. So we need to go ahead and turn those into a label encoder, which again, there's a lot of different encoders. With this particular label encoder, it's just switching it to 0, 1, 2, 3 and giving it an integer value. In fact, if you look at all the columns, all of our columns are labels. And so we're just going to go ahead and loop through all the columns in the data, and we're going to transform it into a label encoder. And so when we run this, you can see how this gets shifted from XBXXK to 0, 1, 2, 3, 4, 5, or whatever it is. Class is 0, 1, 1 being poisonous, 0 looks like it's editable, and so forth on here. So we're just encoding it. If you were doing this project, depending on the results, you might encode it differently. Like I mentioned earlier, you might actually increase the number of features as opposed to labeling it 0, 1, 2, 3, 4, 5. In this particular example, it's not going to make that big of a difference how we encode it. And then, of course, we're looking for the class, whether it's poisonous or edible. So we're going to drop the class in our X logistics model, and we're going to create our Y logistics model is based on that class. So here's our XY. And just like we did before, we're going to go ahead and split it using 30% for test, 70% to program the model on here. And that's right here. Whoops, there we go. There's our train and test. And then you'll see here on this next setup, this is where we create our model. All the magic happens right here. We go ahead and create a logistics model. I've upped the max iterations. If you don't change this for this particular problem, you'll get a warning that says this has not converged. Because that's what it does, is it goes through the math and it goes, hey, can we minimize the error? And it keeps finding a lower and lower error, and it still is changing that number. So that means it hasn't converged yet. It hasn't found the lowest amount of error it can. And the default is 100. There's a lot of settings in here. So when we go in here to, let me pull that up from the sklearn. So we pull that up from the sklearn model. You can see here we have our logistic. It has our different settings on here that you can mess with. Most of these work pretty solid on this particular setup, so you don't usually mess a lot. Usually I find myself adjusting the iteration, and I'll get that warning and then increase the iteration on there. And just like the other model, you can go, just like you did with the other model, we can scroll down here and look for our methods. And you can see there's a lot of methods available on here, and certainly there's a lot of different things you can do with it. But the most basic thing we do is we fit our model, make sure it's set right, and then we actually predict something with it. So those are the two main things we're going to be looking at on this model, is fitting and predicting. There's a lot of cool things you can do that are more advanced, but for the most part, these are the two which I use when I'm going into one of these models and setting them up. So let's go ahead and close out of our sklearn setup on there, and we'll go ahead and run this. And you can see here it's now loaded this up there. We now have a logistic model, and we've gone ahead and done a predict here also, just like I was showing you earlier. So here's where we're actually predicting the data. So we've done our first two lines of code as we create the model. We fit the model to our training data, and then we go ahead and predict for our test data. Now, in the previous model, we didn't dive into the test score. I think I just showed you a graph, and we can go in there, and there's a lot of tools to do this. We're going to look at the model score on this one. And let me just go ahead and run the model score. And it says that it's pretty accurate. We're getting a roughly 95% accuracy. Wow, that's good. 95% accuracy. 95% accuracy might be good for a lot of things. But when you look at something as far as whether you're going to pick a mushroom on the side of the trail and eat it, we might want to look at the confusion matrix. And for that, we're going to put in our logistic test, the actual values of edible and unedible, and we're going to put in our prediction value. And if you remember on here, let's see, I believe it's poisonous was 1, 0 is edible. So let's go ahead and run that, 0, 1. 0 is good. So here is a confusion matrix, and this is, if you're not familiar with these, we have true, 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 false, false, false. So it says out of the edible mushrooms, we correctly labeled 1,201 mushrooms edible that were edible. And we correctly measured 1,113 poisonous mushrooms as poisonous. But here's the kicker. I labeled 56 edible mushrooms as being poisonous. Well, that's not too big of a deal. We just don't eat them. But I measured 68 mushrooms as being edible that were poisonous. So probably not the best choice to use this model to predict whether you're going to eat a mushroom or not. And you'd want to dig a little deeper before you start picking mushrooms off the side of the trail. So a little warning there, when you're looking at any of these data models, looking at the error and how that error fits in with what domain you're in, domain in this case being edible mushrooms, be a little careful. Make sure that you're looking at them correctly. So we've looked at edible or not edible. We've looked at regression model as far as the end values, what's going to be the cost and what our predicted cost is, so we can start figuring out how much to charge these people for their insurance. And so these really are the fundamentals of data science. When you pull them together, when I say data science, I'm talking about your machine learning code. Classification is probably one of the most widely used tools in machine learning in today's world. It is also one of the simpler versions to start understanding how a lot of machine learning works. We're going to start by taking a look at what exactly is classification, the important terminologies around classification. We'll look at some real-world applications, my favorite, popular classification algorithms, and there are a lot out there, so we're only going to touch briefly on a variety of them so you can see how the different flavors work. And we'll have some hands-on demos in Python embedded throughout the tutorial. Classification. Classification is a task that requires the use of machine learning algorithms to learn how to assign a class label to a given data. You can see in this diagram we have our unclassified data. It goes through a classification algorithms, and then you have classified data. It's hard to just see it as data, and that really is where you kind of start and where you end when you start running these machine learning algorithms and classification. And the classification algorithms is a little black box in a lot of respects. And we'll look into that. You can see what I'm talking about when we start swapping in and out different models. Let's say we are given the task of classifying a given bunch of fruits and vegetables on the basis of their category, i.e. fruits are to be grouped together and vegetables are to be grouped together. And so we have a data set, we'll call it the bunch, is divided into clusters, one of which consists of the fruits, while the other has the vegetables. You can actually look at this as any kind of data. When we talk about breast cancer, can we sort out in images to see what is malignant, what is benign? Very popular one. Can you classify flowers, the iris data set? Certainly in wildlife, can you classify different animals and track where they're going? Classification is really the bottom starting point or the baseline for a lot of machine learning and setting it up and trying to figure out how we're going to break the data up so we can use it in a way that is beneficial. So here the fruits and the vegetables are grouped into clusters, and each cluster has a specific characteristic, i.e. whether they are a fruit or a vegetable. And you can see we have a pile of fruits and vegetables. We feed it into the algorithm, and the algorithm separates them out, and you have fruits and vegetables. So some important terminologies before we dig into how it sorts them out and what that all means. When we look at the terminologies, you have a classifier. That's the algorithm that is used to map the input data to a specific category. The classification model, the model that predicts or draws a class to the input data given for training. Feature, it is an individual measurable property of the phenomena being observed. And labels, the characteristics on which the data points of a data set are categorized. The classifier and the classification model go together. A lot of times the classifier is part of the classification model. And then you choose which classifier you use after you choose which model you're using. Where features are what goes in, labels are what comes out. So your classifier model is right in the middle of that. That's that little black box we were just talking about. Clusters. They are a group of data points which have some common characteristics. Binary classification. It is a classification condition with two outcomes which are either true or false. Multi-label classification. This is a classification condition where each sample is assigned to a set of labels or targets. Multi-class classification, the classification with more than two classes. Here each sample is assigned to one and only one label. When we look at this group of terminologies, a few important things to notice. Going from the top, clusters, when we cluster data together, we don't necessarily have to have an end goal. We just want to know what features cluster together. These features then are mapped to the outcome we want. In many cases, the first step might not even care about the outcome, only about what data connects with other data. And there's a lot of clustering algorithms out there that do just the clustering part. Binary classification. It is a classification condition with two outcomes which are either true or false. We're talking usually it's either a cat or it's not a cat. It's either a dog or it's not a dog. That's the kind of thing we talk about binary classification. And then that goes into multi-label classification. Think of label as you can have an object that is brown, you can have an object that is labeled as a dog, so it has a number of different labels. That's very different than a multi-class classification where each one's a binary. You can either be a cat or a dog. You can't be both a cat and a dog. Real-world applications. So to make sense of this, of course, the challenge is always in the details, is to understand how we apply this in the real world. So in real-world applications, we use this all the time. We have email spam classifier. So you have your email inbox coming in. It goes through the email filter that we usually don't see in the background, and it goes, this is either valid email or it's a spam, and it puts it in the spam filter if that's what it thinks it is. Alexa's voice classifier, Google Voice, any of the voice classifiers, they're looking for points, so they try to group words together, and then they try to find those groups of words trigger a classifier. So it might be that the classifier is to open your tasks program or open your text program so that you can start sending a text. Sentiment analysis is really big. When we're tracking products, we're tracking marketing, trying to understand whether something is liked or disliked is huge. That's like one of the biggest driving forces in sales nowadays, and you almost have to have these different filters going on if you're running a large business of any kind. Fraud detection. You can think of banks. They find different things on your bank statement and they detect that there's something going on there. They have algorithms for tracking the logs on computers. They start finding weird logs on computers. They might find a hacker. I mentioned cat and dog, so here's our image classification. We have a neighbor who runs an outdoor webcam, and we like to have it come up with a classification when the wild animals in our area are out, like foxes. We actually have a mountain lion that lives in the area, so it's nice to know when he's here. Handwriting prediction, classifying A, B, C, D, and then classifying words to go with that. So let's go ahead and roll our sleeves up and take a look at some popular classification algorithms. Before we look at the algorithms, let's go back and take a look at our definitions. We have a classifier and a classification model. So we're looking at the classifier, an algorithm that is used to map the input data to a specific category. One of those algorithms is a logistic regression. The logistic regression is a classification algorithm used to model the probability of a certain class or event existing, such as pass, fail, or win, lose, etc. It provides its output using the logistic function or sigmoid function to return the probability value that can then be mapped to two or more discrete classes. A sigmoid function is an activation function that fits the variable and limit the output to a range between 0 and 1. A standard sigmoid function or logistic function is represented by the formula fx equals 1 over 1 plus e to the minus x, where x is the equation of the line and e is the exponential. Just taking a quick look at this, you can think of this as being a point of uncertainty. And so as we get closer and closer to the middle of the line, it's either activated or not. And we want to make that just shoot way up. So you'll see a lot of the activation formulas kind of have this nice S-curve where it approaches 1 and approaches 0. And based on that, there's only a small region of error. And so you can see in the sigmoid logistic function, the 1 over 1 plus e minus x to the minus x, you can see it frames that nice S-curve. We also can use a tangent variation. There's a lot of other different models here as far as the actual algorithm. This is the most commonly used one. Let's go ahead and roll up our sleeves and take a look at a demo that is going to use a logistic regression. So we're going to have the activation formula and the model, because you have to have both. For this, we will go into our Jupyter notebook. Now, I personally use the Anaconda Navigator to open up the Jupyter notebook to set up my IDE as a web-based. It's got some advantages that it's very easy to display in, but it also has some disadvantages in that if you're trying to do multi-threads and multi-processing, you start running into single get issues with Python, and then I jump to PyCharm. Really depends on whatever IDE you want. Just make sure you've installed NumPy and the sklearn modules into your Python in whatever environment you're working in so that you'll have access to that for this demo. Now, the team in the back has prepared my code for me, which I'll start bringing in one section at a time so we can go through it. Before we do that, it's always nice to actually see where this information is coming from and what we're working with. So the first part is we're going to import our packages, which you need to install into your Python, and that's going to be your NumPy. We usually use NumPy as NP, and then from sklearn, the learn model, we're going to use a logistic regression. And from sklearn metrics, we're going to import the classification report confusion matrix. And if we go ahead and open up the scikit-learn.org and go under their API, you can see all the different features and models they have. And we're looking at the linear model logistic regression, one of the more common classifiers out there. And if we go ahead and go into that and dig a little deeper, you'll see here where they have the different settings. And it even says right here, note, the regularization is applied by default. So by default, that is the activation formula being used. Now, we're not going to spend, we might come back to this, look at some of the other models, because it's always good to see what you're working with. But let's go ahead and jump back in here. And we have our imports. We're going to go ahead and run those. So these are now available to us as we go through our Jupyter Notebook script. And they put together a little piece of data for us. This is simply going through 0 to 1. Actually, let's go ahead and print this out over here. We'll go ahead and print X just so you can see what we're actually looking for. And when we run this, you can see that we have our X is 0, 1, 2 through 9. We reshaped it. The reason for this is just looking for a row of data. Usually we have multiple features. We just have the one feature which happens to be 0 through 9. And then we have our 10 answers right down here. 0, 1, 0, 0, 1, 1, 1, 1, 1, 1. You can bring in a lot of different data depending on what you're working with. You can make your own. You can, instead of having this as just a single, you could actually have like multiple features in here, but we just have the one feature for this particular demo. And this is really where all the magic happens right here. And I told you it's like a black box. That's the part that is kind of hard to follow. And so if you look right here, we have our model. We talked about the model right there, and then we went ahead and set it for library linear. As I showed you earlier, that's actually default, so it's not that important. Random state equals 0. This stuff you don't worry too much about. And then with the scikit-learn, you'll see the model fit. This is very common to scikit. They use similar stuff in a lot of other different packages, but you'll see that that's very common. You have to fit your data. And that means we're just taking the data and we're fitting our X right here, which is our features. That's our X. And here's Y. These are the labels we're looking for. So before we were looking at, is it fraud? Is it not? Is it cat? Is it not? That kind of thing. And this is looking at 0, 1, so we want to have a binary setup on this. And we'll go ahead and run this. You can see right here it just tells us what we loaded it with as our defaults, and that this model has now been created and we've now fit our data to it. And then comes the fun part. You work really hard to clean your data, to bake it and cook it. There's all kinds of, I don't know why they go with the cooking terms as far as how we get this data formatted. Then you go through and you pick your model, you pick your solver, and you have to test it to see, hey, which one's going to be best. And so we want to go ahead and evaluate the model. And you do this is that once you've figured out which one is going to work the best for you, you want to evaluate it so you can compare it to your last model. And you can either update it to create a new one or maybe change the solver to something else. I mentioned tangent. That's one of the other common ones that's commonly used with language. For some reason the tangent, even though it looks almost to me identical to the one we're using with the sigmoid function, for some reason it activates better with language, even though it's a very small shift in the actual math behind it. We already looked at the data early, but we'll go ahead and look at it again just so you can see what we look at. We have our rows of 0, 1, row, it only has one entity, and we have our output that matches these rows, and these do have to match. You'll get an error if you put in something with a different shape. So if you have 10 rows of data and 9 answers, it's going to give you an error because you need to have 10 answers for it. A lot of times you separate this too when you're doing larger models. But for this, we're just going to take a quick look at that. The first thing we want to start looking at is the intercept, one of the features inside our linear regression model. We'll go ahead and run that and print it. You'll see here we have an intercept of minus 1.516. And if we're going to look at the intercept, we should also look at our coefficients. And if you run that, you'll see that we get our coefficient is the 0.7035. You can just think of this as your Euclidean geometry for a very basic model like this, where it intercepts the y at some point and we have a coefficient multiplying by it. A little more complicated in the back end, but that is the gist of this simple model with just the one feature in there. And we'll go ahead and we'll reprint the y because I want to put them on top of each other with the y predict. And so these were the y values we put in, and this is the y predict we had coming out. And you can see, here we go. There's the y actual, and there's what the prediction comes in. Now keep in mind that we used the actual complete data as part of our training. That is, if you're doing a real model, a big stopper right there, because you can't really see how good it did unless you split some data off to test it on. This is the first step, is you want to see how your model actually tests on the data you trained it with. And you can see here, there is this point right here where it has it wrong, and this point right here where it also has it wrong. And it makes sense, because our input is 0 through 9, and it has to break it somewhere, and this is where the break is. So it says this half the data is going to be 0, because that's what it looked like to me if I was looking at it without an algorithm, and this data is probably going to be 1. And I forgot to point this out, so let's go back up here. I just kind of glanced over this window here where we did a lot of stuff. Let's go back and just take a look at that. What was done here is we ran a prediction. So this is where our predict comes in, is our model.predict. So we had a model fit, We created the model, we programmed it to give us the right answer. Now we go ahead and predict what we think it's going to be. There's our model.predict probability of X. And then we have our Y predict, which is very similar, but this has to do more with the probability numbers. So if you remember down below, we had the setup where we're looking at that sigmoid function. That's what this is returning. And the Y predict is returning a 0 or a 1. And then we have our confusion matrix. We'll look at that. And we have our report, which just basically compares our Y to our Y predict, which we just did. It's kind of nice. It's simple data, so it's really easy to see what we're doing. That's why we use the simple data. This can get really complicated when you have a lot of different features and things going on and splits. So here we go. We've had I printed out our actual and our prediction. So this is the actual data. This is what the predict ran. And then we'll go ahead and we're going to print out the confusion matrix. We were just talking about that. This is great if you have a lot of data to look at. But you can see right here our confusion matrix says, if you remember from the confusion matrix, we have the 2. This is 2 correct. 1, 2. And it's been a while since I looked at a confusion matrix. There's the 2, and then we have this one, which is our 6. That's where the 6 comes from. And then we have this one, which is the 1 false. This is the 2 1s. So we have this one here and this one here, which is misclassified. This really depends on what data you're working with as to what is important. You might be looking at this model, and if this confusion matrix comes up and says that you've misclassified even one person as being non-malignant cancer, that's a bad model. I wouldn't want that classification. I'd want this number to be 0. I wouldn't care if this false positive was off by a little bit more, as long as I knew that I was correct on the important factor that I don't have cancer. So you can see that this confusion matrix really aims you in the right direction of what you need to change in your model, how you need to adjust it. And then there's, of course, a report. Reports are always nice. If you notice, we generated a report earlier. We'll go and just print the report up, and you can remember this is our report. It's a classification report, Y, Y predict. So we're just putting in our 2 values. Basically what we did here visually with our actual and our predicted value. And we'll go ahead and run the report, and you can see it has the precision, the recall, your F1 score, your support, translated into accuracy, macro average, and weighted average. So it has all the numbers. A lot of times when working with clients or with the shareholders in the company, this is really where you start, because it has a lot of data and they can just kind of stare at it and try to figure it out. And then you start bringing in like the confusion matrix. I almost do this in reverse as to what they show. I would never show your shareholders the intercept of the coefficient. That's for your internal team only working on machine language. But the confusion matrix and the report are very important. Those are the 2 things you really want to be able to show on these. And you can see here we did a decent job of classifying the data. Managed to get a significant portion of it correct. We had our accuracy here is a 0.80 F1 score, that kind of thing. So, it's a pretty accurate model. Of course, this is pretty goofy because it's a very simple model, and it's just splitting the model between 1s and 0s. So that was our demo of the on logistic regression on there. Let's go and take a look at k-nearest neighbors. This one is another very highly used and important algorithm to understand. K-nearest neighbors is a simple algorithm which stores all available cases and classifies new cases based on the similarity measure. The k-nearest neighbor finds out the class of the new data point by finding its nearest neighbors. If there are 3 data points of class A and 2 data points of class B near to the new data point, then the KNN classifies the new data point as class A. The k in k-nearest neighbors is the number of nearest neighbors we are looking for. i.e., if we say k equals 3, this means that we are looking for nearest 3 neighbors of unclassified data point. Usually we take the k value between 3 to 10 as it leads to a better result. A smaller value of k means that noise will have a bigger influence on the result, and a larger value of k makes it computationally expensive. Hence, the data scientists prefer the range of k between 3 and 10. when we talk about noise, you remember the data we just looked at was 0, 1, 1, 0, 0. It had some values where it cut it and said everything to the right is a 1, everything to the left is a 0, but it had some 1s and 0s mixed in there. That's called noise. That's what they're talking about, is there's some things that are right in the middle in the classification, which makes it very hard to classify. So suppose we're trying to find the class for a new point indicated by the red color. And you can see it's kind of right between the cat, right between the dogs. Let k equal 3, so we are finding the 3NN for the red data point. By looking at the plot on the right, we can see that the red data point belongs to the class dogs, as it has 2 votes for class dog and 1 vote for class cat. And if you ask the question, well, what are you measuring the distance? What is that distance? It could be the measurements of the ears, whether they're pointed or floppy. That might be one of the features you're looking at, is how floppy the ears are. Another one might be the whiskers versus the nose. And then you take those measurements, and using one of the most common things in k-means measurement is the Euclidean geometry, you can figure out the distance between those points. There's a lot of different algorithms for that. But you can think about it that you do have to have some kind of solid data to measure. And so we can conclude that the new data point belongs to the class dog. So let's go ahead and see what this looks like in code and do a demo on the k nearest neighbors in here. And we'll go right back into our Jupyter Notebook and open up a new Python programming script page. Of course, once we're in here, we'll want to look at the scikit-learn. I did just a quick search for sk neighbors, kn neighbors classifier. This actually is the older version, 0.023 is the one we want. And you'll see here that we have all their defaults. N neighbors equals 5. At defaults, we were talking about that between 3 and 10. There's different ways to weigh it. There's an algorithm based on it. I mentioned Euclidean geometry, finding the distance. There's other algorithms for figuring out what that distance is and how to weight those. And there's a lot of other parameters you can adjust. For the most part, the k-means basic setup is a good place to start, and just let the defaults go. We might play with some of those. We'll see what the guys in the back did. And from here we're going to import NumPy. We're going to use pandas. If you haven't been running pandas, pandas is our data frame which sits on top of NumPys. Data frames are, NumPys is our number array, pandas is our data frame. Matplot library, because we're going to plot some graphs. Everybody likes some pretty pictures. It makes it a lot easier to see what's going on when you have a nice display. And that's also what the Seaborn is in here in the setup that sits on top of the Matplot library. The ones we really want to look at right here are what we're bringing in from sklearn. These ones right here. So from sklearn, we're going to load, I mentioned the breast cancer. That's a very popular one because it has, I believe it's 36 measurements, so there's 36 features, and unless you're an expert, you're not going to know what any of those features really mean. You can sort of guess, but there's special measurements they take of when they take an image. And of course our confusion matrix, so that we can take a look and see what the data looks like and how good we did. And then we have our KN neighbors classifier on here. And then I mentioned that whenever you do training and testing, you want to split the data up. You don't want to train the data and then test it on the same data. That just tells you how good your training model is. It doesn't tell you whether it actually works on unknown data. And so this just splits it off so that we can train it, and then we can take a look at data we don't have in there and see how good it did. And we'll go ahead and load our data up. So here's our setup on that. Oops, there we go. So we're going to go ahead and load the data up. We have our X value, and that's going to come from our breastcancer.data and column breast cancer feature names. So there's our actual, all our different features. We'll print that out here in a second. And then we have our mean area, mean compactness. So I guess we're going to take the data, and we're only going to use a couple of the columns. This just makes it easier to read. Of course, when you actually we're going to do this, you'd want to use all your columns. And then we have our Y, and this is simply whether it's either malignant or benign. And then we want to go ahead and drop the first line because that's how it came in on there. And we'll go ahead, let's just take a look at this a little closer here. Let's go and run this real quick. And just because I like to see my data before I run it, we can look at this and we can look at the original features. Remember, we're only going to use 2 features off of here just to make it a little easier to follow. And here's the actual data, and you can see that this is just this massive stream of data coming in here. It's going to just skip around because there's so much in there to set up. I think there's like 500 if I remember correctly, and you can see here's all the different measurements they take. But we don't really need to see that on here. We're just going to take a look at just the 2 columns and then also our solution. We'll go ahead and just do a quick print Y on here so you can see what the Y looks like. And it is simply just 0, 0, 0, B9, 0, 0, 0, 1. So a 1 means it's B9, a 0 means it's malignant. Is what we're looking at on that. Go ahead and cut that out of there. The next stage is to go ahead and split our data. I mentioned that earlier. We'll just go ahead and let them do the splitting for us. We have X train, X test, Y train, Y test, and so we go ahead and train, test, split, X, Y, random state equals 1. It makes it nice and easy for us. We'll go ahead and run that. And so now we have our training and our testing. Train means we're going to use that to train the model, and then we're going to use the test to see how good our model does. And then we'll go ahead and create our model. Here's our KNN model, the K-neighbors classifier. N neighbors equals 5. The metrics is Euclidean. Remember I talked about Euclidean? This is simply your C squared equals A squared plus B squared plus A squared equals B squared plus C squared plus C squared plus D squared, and then you take the square root of all that. That's what they're talking about here. It's just the length of the hypotenuse of a triangle, but you can actually do that in multiple dimensions, just like you do in 2 dimensions with a regular triangle. And here we have our fit. This should start to look familiar since we already did that in our last example. That's very standard for scikit and any other one, although sometimes the fit algorithms look a little bit more complicated because they're doing more things on there, especially when you get into neural networks. And then you have your k-neighbors. It just tells you we created a k-neighbors setup. They kind of wanted us to reformat the y, but it's not that big of a deal for this. And it comes out and shows you that we're using the Euclidean metric for our measurement. So now we've created a model. Here's our live model. We fitted the data to it. We say, hey, here's our training data. Let's go ahead and predict it. So we're going to take our y predict equals KNN predict y test. So this is data we have not. This model has not seen this data, and so we're going to create a whole new set of data off of there. Now, before we look at our prediction, in fact, let's I'm going to bring this down and put it back in here later. Let's take a look at our X test data versus the Y test. What does it look like? And so we have our mean area. We're going to compare it to our mean compactness. We're going to go ahead and run that. And we can see here the data, if you look at this, just eyeballing it, we put it in here, we have a lot of blue here, and we have a lot of orange here. And so these dots in the middle, especially like this one here and these here, these are the ones that are going to give us false negatives, and so we should expect this is your noise. This is where we're not sure what it is. And then B9 is, in this case, is done in blue, and malignant is done in 1. So if you look at it, there's 2 points based on these features, which makes it really hard to have 100% where the 100% is down here or up here. That's kind of the thing I'd be looking for when we're talking about cancer and stuff like that, where you really don't want any false negatives. You want everything, false positive, great. You're going to go in there and have another setup in there where you might get an autopsy or something like that done on it. Again, that's very data specific on here. So now let's go ahead and pull in and get our prediction in here, and we'll create our Y prediction. We'll go ahead and run that. So now this is loaded with what we think the unknown data is going to be. And we can go ahead and take that and go ahead and plot it, because it's always nice to have some pretty pictures. And when we plot it, we're going to do the mean area versus mean compactness. Again, you look at this map and you can see that there's some clear division here. We can clearly say on some of the stuff that our Y prediction, if we look at this map up here, and this map down here, we probably got some pretty good deal. It looks pretty good, like they match a lot. This is, of course, just eyeballing it. Really, you don't want to eyeball these things. You want to show people the pictures so that they can see it, and you can say, hey, this is what it looks like. But we really want the confusion matrix. And when we do the Y test and the Y predict, we can see in the confusion matrix here, it did pretty good. And we'll just go ahead and point that out real quick. Here's our 42, which is positive, and our 79, And if I remember correctly, I'd have to look at the data, which one of these is a false negative. I believe it's the 9. That's scary. I would not want to be one of those 9 people told that I don't have cancer and then suddenly find out I do. So we would need to find a way to sort this out. And there is different ways to do that. A little bit past this, but you can start messing with the actual Euclidean geometry and the activation measurements and start changing those and how they interact. But that's very advanced. There's also other ways to classify them or to create a whole other class right here of we don't knows. Those are just a couple of the solutions you might use for that. But for a lot of things, this works out great. You can see here, maybe you're trying to sell something. Well, if this was not life dependent, and this was, if I display this ad, 42 of these people are going to buy it. And if I display this other ad, if I don't display it, 79 people are going to go a different direction or whatever it is. So maybe you're trying to display whether they're going to buy something if you add it on to the website. In which case, that's really a good numbers. You've just added a huge number of cells to your company. So that was our k nearest neighbors. Let's go ahead and take a look at support vector machines. So support vector machines is the main objective of a support vector machine algorithm is to find a hyperplane in an n-dimensional space, n is the number of features, that distinctly classifies the data points. And if you remember, we were just looking at those nice graphs we had earlier. In fact, let me go ahead and flip back on over there. If we were looking at this data here, we might want to try to find a nice line through the data. And that's what we're talking about with this next setup. So the main objective of support vector machine algorithm is to find a hyperplane in an n-dimensional space. N is the number of features that distinctly classifies the data points. To separate the two classes of data, there are many hyperplanes that can be chosen. Our objective is to find the plane that has the maximum margin, i.e. the maximum distance between data points of both classes. The dimensions of the hyperplane depends on the number of features. If there are 2 input features, then the hyperplane is just a line. If there are 3 features, then the hyperplane becomes a 2-dimensional plane. The line that separates the data into 2 classes is called as support vector classifier, or hard margin. And that's what I just showed you on the other data. You can see here where we look for a line that splits the data evenly. The problem with hard margin is that it doesn't allow outliers and doesn't work with non-linearly separable data. And we just were looking at that. Let me flip back on over here. And when we look at this setup in here, and we look at this data, here we go. Look how many outliers are in here. These are all these blue dots on the wrong side of the line would be considered an outlier, and the same with the red line. And so it becomes very difficult to divide this data unless there's a clear space. There we go. Therefore, we introduce soft margins, which accept the new data point and optimize a model for nonlinear data points. Soft margins pass through the data points at the border of the classes. The support vector machine can be used to separate the 2 classes of shapes. Here we can see that although triangles and diamond shapes have pointy edges, but we are able to classify them in 2 categories using a support vector machine. Let's go ahead and see what that looks like in a demo. Flip back on over to our Jupyter notebook. We always want to start with taking a look at the sklearn API, in this case the SVM SVC. There is a significant number of parameters because the SVM has been a lot of development in the recent years and it's become very popular. If we scroll all the way down to methods, you'll see right here is our fit and our predict. That's what you should see in most of the scikit-learn packages. So this should look very familiar to what we've already been working on. And we'll go ahead and bring in our import and run that. We should already have pandas, numpy, our matplot library, which we're going to be using to graph some of the things. A little bit different right here. You'll see that we're going to go ahead and bring in one of the fun things you can do with test data is make circles. Circles are really hard to classify. You have a ring on the inside and a ring on the outside, and you can see where that can cause some issues. And we'll take a look at that a little closer in a minute. Here's our SVM setup on there, and then of course our metrics, because we're going to use that to take a closer look at things. So we go ahead and run this. Whoops, already did. Once we've gone ahead and done that, we're going to go ahead and start making ourselves some data. And this part probably a little bit more complicated than we need. I'm not going to go too much in detail on it. We're going to make a mesh grid And we'll see what that looks like in a minute. We're defining the minimums. You can see in here, create a mesh grid of points. Here's our parameters of x, y, and h. It's going to return x, x, y, y. You can also send a note to us. Make sure you get a copy of this if you want to dig deeper into this particular code especially. And we have a y min, y max, y min, y max, plus 1. Here's our mesh grid we're actually going to make, x, x, and y, y. Plot the contours all the way through, and this is just a way of creating data. It's kind of a fun way to create some data. Here we go, plot contours AX, CLF, X, X, Y, Y, and return an out. Add some perimeters here so that when we're doing it, we have our setup on there, train property, and then we'll go ahead and make our data. Just throw that right in there too in the same setup and run that. So now we have X and Y. We're going to make our circles. We have n samples equals samples. In this case, we're going to have 500 samples. We went ahead and gave it noise of 0.05, random state 123. These are all going into, oops, go back up. Here we go. Make our mesh grid, make circles. There it is. So this is going into our make circles up here. And this is part of that setup on this. And then once we've gone ahead and make the circle, let's go ahead and plot it. That way you can see what we're talking about. Right now what I'm saying is really confusing because without a visual it doesn't really mean very much what we're actually doing. So let me go ahead and run this with the plot. And let's go back up here and just take a look. We've made our circle. We have our n samples equals samples. So we're going to have 500. We're going to have training property 0.8. Here's our data frame. We go and load it into the data frame so we can plot it. Groups, df group by label. This is kind of a fun way if you have multiple columns. You can really quickly pull whatever setup is in there. And then we go ahead and plot it. And you can see here we have 2 rings that are formed. And that's all this is doing, is just making this data for us. This is really hard data to figure out. A lot of programs get confused in this because there's no straight line or anything like that. But we can add planes and different setups on here. And so you can see we have some very interesting data. We have our zeros in blue and our ones in the yellow in the middle. And the data points are an XY coordinate plot on this. One of the things we might want to do on here is go ahead and find the min to max ratio set up in there. And we can even do, let's just do a print x so you can see what the data looks like that we're producing on this. There we go. So x equals x minus x min over x max minus x min. All we're doing is putting this between 0 and 1. Whatever this data is, we want a 0 to 1 setup on here. And if you look at this, all our data is 0.8, 0.5. That's what this particular line is doing. That's a pretty common thing to do in processing data, especially in neural networks. Neural networks don't like big numbers. They create huge biases and cause all kinds of problems. And that's true in a lot of our models. Some of the models it doesn't really matter, but when you're doing enough of these, you just start doing them. You just start putting everything between 0 and 1. There's even some algorithms to do that in the sklearn, although it's pretty, as you can see, it's pretty easy to do it here. So let's go ahead and jump into the next thing, which is a linear kind of setup. C equals 1.0. This is the SVM regularization parameter we're going to use. Models, here's our SVM. And let's go and scroll up just a notch. There we go. So here we are with our model. We're going to create the setup with the SVC. Kernel is linear. And we'll come back to that because that's an important setup in there as far as what our kernel is. And you'll see why that's so important here in a minute, because we're going to look at a couple of these. And so this one is, we're actually going to be changing how that processes it. And then our C, here's our 0.0, and then the rest of this is plotting. We're just adding titles, making the contours so it's a pretty graph. You can actually spend, this would be a whole class just to do all the cool things you can do with scatter plots and regular plots and colors and things like that. In this case, we're going to create a graph with a nice white line down the middle so that you can see what's going on here. And when we do this, you can see that as it split the data, the linear did just that. It drew a line through the data, and it says this is supposed to be blue, and this is supposed to be red, and it doesn't really fit very well. And that's because we used a linear division of the data, and it's not very linear data on there. It's anything but linear. So when we look at that, it's like, well, okay, that didn't work. What's the next option? Well, there's a lot of choices in here. One of them is just simply we can change this from the kernel being linear to poly. And we'll just go back up here and use the same chart. Oops, here we go. So here we go, linear kernel. We'll change this to poly. And then when we come in here and create our model, here's our model up here, linear. We can actually just go right in and change this to the poly model. And if you remember, when we go back over here to the SVC, and let's scroll back up here, there's a lot of different options. Oops, even further. Okay, so when we come up here and we start talking about the kernel, here's the kernel. There's linear, there's poly, RBF, sigmoid, pre-computed. There's a lot of different ways to do this setup, and their actual default is RBF. Very important to note that. So when you're running these models, understanding which parameter really has a huge effect on what's going on. In this particular one with the SVM, the kernel is so important. You really need to know that. And we switched our kernel to poly, and when we run this, you can see it's changed a little bit. We now have quite an interesting looking diagram, and you can see on here it now has these classifications correct, but it messes up in this blue up here, and it messes up on this blue is correct, and this blue is supposed to be red. You can see that it still isn't quite fitting on there. And so that is, when we do a polyfit, you can see if you have a split in data where there's a group in the middle that's one kind of data and the groups on the outside are different, the polyfit or the polykernel is what's going to be fit for that. So if that doesn't work, then what are we going to use? Well, they have the RBF kernel. And let's go ahead and take a look and see what the RBF looks like. And let me go and turn my drawing off. And the RBF kernel, oops, there we go, RBF. And then of course for our title, it's always nice to have it match with the RBF kernel. And we go ahead and run this, and you can see that the RBF kernel does a really good job. It actually has divided the data up on here, and this is the kind of what you expect here was that ring. Here's our inner ring and an outer ring of data, and so the RBF fits this data package quite nicely. And that, when we talk about SVM, it really is powerful in that it has this kind of sorting feature to it in its algorithms. This is something that is really hard to get the SK means to do, or the k-means set up. And so when you start looking at these different machine learning algorithms, understanding your data and how it's grouped is really important. It makes a huge difference as far as what you're computing and what you're doing with it. So that was a demo on the support vector. Certainly you could have continued on that and done like a confusion matrix and all that kind of fun stuff to see how good it was and split the data up to see how it vectorizes. The visual on that's so important. It makes a big difference just to see what it looks like and that giant donut and why it does circles so well, or your poly version or your linear version. So we've looked at some very numerical kind of setups where there's a lot of math involved, Euclidean geometry, that kind of thing. A totally different machine learning algorithm for approaching this is the decision trees. And there's also forests that go with the decision trees. They're based on multiple trees combined. The decision tree is a supervised learning algorithm used for classification. It creates a model that predicts the value of a target variable by learning simple decision rules inferred from the data features. A decision tree is a hierarchical tree structure where an internal node represents features or attribute. The branch represents a decision rule, and each leaf node represents the outcome. And you can see here where they have the first one, yes or no, and then you go either left or right, and so forth. One of the coolest things about decision trees is, and I'll see people actually run a decision tree even though their final model is different, because the decision tree allows you to see what's going on. You can actually look at it and say, why did you go right or left? What was the choice? Where's that break? And that is really nice if you're trying to share that information with somebody else as to why. When you start getting into the why this is happening, decision trees are very powerful. So the topmost node of a decision tree is known as the root node. It learns to partition on the basis of the attribute value. It partitions the tree in a recursive manner. So you have your decision node. If you get yes, you go down to the next node. That's a decision node. And either yes, you go to, if it ends on a leaf node, then you know your answer, which is yes or no. So there's your end classification set up on there. Here's an example of a decision tree that tells whether I'll sleep or not at a particular evening. Mine would be depending on whether I have the news on or not. Do I need to sleep? No. Okay, I'll work. Yes. Is it raining outside? Yes, I'll sleep. No, I'll work. So I guess if it's not raining outside, it's harder to fall asleep where you have that nice rain coming in. And again, this is really cool about a decision tree is I can actually look at it and go, oh, I like to sleep when it rains outside. So when you're looking at all the data, you can say, oh, this is where the switch comes in. When it rains outside, I'll sleep really good. If it's not raining or if I don't need sleep, then I'm not going to sleep. I'm going to go work. So let's go ahead and take a look at that looks like in the code. Just like we did before, we go ahead and open up the scikit setup just to say what the decision tree classifier has. You have your parameters, which we'll look a little bit more in depth at as we write the code. It has different ways of splitting it. The strategy used to choose a split at each node, criterion, max depth. Remember the tree, how far down do you want it? Do you want it to take up the space of your whole computer with and map every piece of data, or the smaller that number is, the smaller the level of the tree is and the less processing it takes, but it's also more general, so you're less likely to get as in-depth an answer. And then of course minimal samples you need for it to split, samples for the leaves. There's a lot of things in here as far as how big the tree is and how to define it and when do you define it and how to weight it. And they have their different attributes which you can dig deeper into. That can be very important if you want to know the why of things. And then we go down here to our methods, and you'll see just like everything else, we have our fit method, very important, and our predict, the two main things that we use. What we're going to predict our x to be equal to. And we'll go ahead and go up here and start putting together the code. We're going to import our numpy, our pandas, there's our confusion matrix, our train test split, decision tree classifier. That's the big one that we're actually working with. That's the line right here where we're going to be, decision tree, there it is. Decision tree classifier, that's the one I was looking for. And of course we want to know the accuracy and the classification report on here. And we're going to do a little different than we did in the other examples. And there's a reason for this. Let me go ahead and run this and load this up here. We're going to go ahead and build things on functions. And this is, when you start splitting up into a team, this is the kind of thing you start seeing a lot more, both in teams and for yourself, because you might want to swap one data to test it on a different data depending on what's going on. So we're going to have our import data here, the data set length, the balance, and so forth. This just returns balanced data. Let me just go ahead and print, because I'm curious as to what this looks like. Import data, and it's going to return the balanced data. So if I run that, if we go ahead and print this out here and run that, you can see that we have a whole bunch of data that comes in there, and some interesting setup on here has, let's see, BRR. I'm not sure exactly what that represents on here. 111, 112, and so forth. So we have a different set of data here. The shape is 5 columns, 1, 2, 3, 4, 5. It seems to have a number at the beginning, which I'm going to guess BRL, a letter I mean, and then a bunch of numbers in there. 1111. Let's see, down here we got 555 set up on this. And let's see, balanced data. And since it said balanced data, I'm going to guess that B means balanced, R means you need to move it right, and L means it needs to be moved left or skewed to the left. I'm not sure which one. Let's go and close that out. And we'll go ahead and create a function to split the data set. X balance data equals data values. Y balance equals data values of 0. There's that letter. Remember left, right, and balance. And then we're looking for the values of 1 through 5. And we go ahead and split it just like you would. X train, Y train set, random state 100. Test size is 0.3, so we're taking 30% of the data. And it's going to return your X, your Y train, your X train, your X test, your Y train, your Y test. Again, we do this because if you're running a lot of these, you might want to switch how you split the data and how you train it. I tend to use a bifold method. I'll take a third of the data and I'll train it on the other 2/3 and test it on that third. And then I'll switch it. I'll switch which third is the test data. And then I can actually take that information and correlate it, and it gives me a really robust package for figuring out what the complete accuracy is. But in this case, we're just going to go ahead. This is our function for splitting data. And this is where it kind of gets interesting, because remember we were talking a little bit about the different settings in our model. And so in here we're going to create a decision tree, but we're going to use the Gini setup. And where did that come from? What's the Gini on here? So if we go back to the top of their page, and we have what criterion are we going to use? We're going to use Gini. They have Gini and entropy. Those are the two main ones that they use for the decision tree. So this one's going to be Gini, and if we're going to have a function that creates the Gini model, and it even goes down here, and here's our fit train of the Gini model, we'll probably also want to create one for entropy. Sometimes I even just, I might even make this just one function with the different setups, and I know one of the things I worked on recently, I had to create one that tested across multiple models, and so I would send the parameters to the models, or I would send this part right here where it says decision tree classifier. That whole thing might be what I send to create the model, and I know it's going to fit. We're going to have our X train, and we're going to have our predict, and all that stuff is the same, so you can just send that model to your function for testing different models. Again, this just gives you one of the ways to do it. And you can see here we're going to train with the Gini, and we're also going to train with the entropy to see how that works. And if you're going to have your models going, two separate models you're sending there, we'll go ahead and create a prediction. This simply is our y predict equals our whatever object we sent, whatever model we sent here, the CLF object, and predict against our x test. And you can see here print y predict and return y predict set up on here. And we'll load that definition up. And then if you're going to have a function that runs a predict and prints some things out, we should also have our accuracy function. So here's our calculate the accuracy. What are we sending? We're sending our y test data. This could also be y actual and y predict. And then we'll print out a confusion matrix. Then we'll print out the accuracy of the score on here and print a report, classification report. Bundle it all together there. So if we bring this all together, we have all the steps we've been working towards, which is importing our data. By the way, you'll spend 80% of your time importing data in most machine learning setups and cooking it and burning it and getting it formatted so that it works with whatever models you're working with. The decision tree has some cool features in that if you're missing data, it can actually pick that up and just skip that and says, I don't know how to split this. There's no way of knowing whether it rained or didn't rain last night, so I'll look at something else, like whether you watched TV after 8 o'clock, that blue screen thing. So we have our function importing our data set. We bring in the data. We split the data, so we have our x test and y train. And then we have our different models, our CLF Gini, so it's a decision tree classifier using the Gini setup, and then we can also create the model using entropy. And then once we have that, we have our function for making the prediction, and we have our function for calculating the accuracy. And then if we're going to have that, we should probably have our main code involved here. This probably looks more familiar if you're, depending on what you're working on. If you're working on like a PyCharm, then you would see this in throwing something up real quick in Jupyter Notebook. So here's our main data import, which we've already defined. We get our split data. We create our Gini. We create our entropy, so there's our two models going on here. There's our two models. So these are two separate data models. We've already sent them to be trained. Then we're going to go ahead and print the results using Gini index. So we'll start with the Gini, and we want to go ahead with the Gini and print our predictions, x test to the Gini, and calculate the accuracy on here. And then we want to print the results using entropy. So this is just the same thing coming down like we did with the Gini. We're going to put out our y predict entropy and our calculations. So let's go ahead and run that and just see what this piece of code does. We do have like one of our data is getting a warning on there. That's nothing major because it's just a simple warning. Probably an update of a new version's coming out. And so here we are. We have our data set. It's got 625. You can actually see an example of the data set. B meaning balanced, I guess. And here's our 5 data points. 1111 means it's balanced. It's skewed to the right with 1112 and so forth on here. And then we're going to go ahead and predict from our prediction whether it's to the right or to the left. You can think of a washing machine that's banging on one side of the thing, or maybe it's an automated car where we're down the middle of the road that's in balance and it starts veering to the right, so we need to correct for it. And when we print out the confusion matrix, we have 3 different variables, R, L, and B. So we should see the 3 different variables on here. And you have as far as whether it predicts in this case, the balance, there's not a lot of balanced loads on here, and didn't do a good job guessing whether it's balanced or not. That's what I took from this first one. The second one I'm guessing is the right. So it did pretty good job guessing the right balance. You can see that a bunch of them came up left unbalanced. Probably not good for an automated car, as it tells you 18 out of the 18 missed things and tells you to go the wrong direction. And here we are going the other way, 19 to 71. And of course we can back that up with an accuracy report on here, and you can see the precision, how well the left and right balance is, 79% precision, and so forth. And then we went and used the entropy, and let me just see if we can get, so we can get them both next to each other. Here's our entropy of our the first setup, our first model, which is the Gini model. 67, 18, 1971, 63, 22, 2070, pretty close. The two models, you know, that's not a huge difference in numbers. This second one of entropy did slightly, it looks like slightly worse, because it did one better as far as the right balance and did, what is this, 4 worse on the left balance or whatever. So slightly worse. If I was guessing between these, I'd probably use the first one. They're so close though that it wouldn't be a clear choice as to which one worked better. And there's a lot of numbers you can play with here which might give better results depending on what the data is going in. Now, one of the takeaways you should have from the different category routines we ran is that they run very similar. You certainly change the parameters in them as to whether you're using, what model you're using and how you're using it and what data they get applied to. But when you're talking about the scikit-learn package, it does such an awesome job of making it easy. You split your data up, you train your data, and you run the prediction, and then you see what kind of accuracy, what kind of confusion matrix it generates. So when we talk about algorithm selection, logistic regression, k-nearest neighbors. Logistic regression is used when we have a binomial outcome. For example, to predict whether an email is spam or not, whether the tumor is malignant or not. The logistic regression works really good on that. You can do it in a k-nearest neighbors also. The question is, which one will it work better in? I find the logistic regression models work really good in a lot of raw numbers. So if you're working with, say, the stock market, is this a good investment or a bad investment? So that's one of the things that it handles the numbers better. K-nearest neighbors are used in scenarios where non-parametric, no fixed number of parameters, algorithms are required. It is used in pattern recognition, data mining, and intrusion detection. So K means really good in finding the patterns. I've seen that as a preprocessor to a lot of other processors where you use the k-nearest neighbors to figure out what data groups together. Very powerful package. Support vector machines. Support vector machines are used whenever the data has higher dimensions, the human genome microarray. SVMs are extensively used in the handwriting recognition models. And you can see that we were able to switch between the parabolic and the circular setup on there, where you can now have that donut kind of data and be able to filter that out with the support vector machine. And then decision trees are mostly used in operational researches, specifically in decision analysis to help identify a strategy most likely to reach any goal. They are preferred where the model is easy to understand. I like that last one. It's a good description. Is it easy to understand? So you have data coming in. When am I going to go to bed? You know, was it raining outside? You can go back and actually look at the pieces and see those different decision modes. It takes a little bit more to dig in there and figure out what they're doing, but you can do that, and you can actually help you figure out why. People love it for the why factor. So, strengths and limitations. Big one on all of these. The strengths and limitations, we talk about logistic regressions. The strengths are it is easy to implement and efficient to train. It is relatively easy to regularize the data points. Remember how we put everything between 0 and 1? When you look at logistic regression models, you don't have to worry about that as much. Limitations as a high reliance on proper representation of data. It can only predict a categorical outcome. With the k-nearest neighbors, it doesn't need a separate training period. New data can be added seamlessly without affecting the accuracy of the model. Kind of an interesting thing because you can do partial training. That can become huge if you're running across really large data sets or the data is coming in. You can continually do a partial fit on the data with the k nearest neighbors and continue to adjust that data. It doesn't work on high dimensional and large data sets. We were looking at the breast cancer, 36 different features. What happens when you have 127 features or a million features? And you say, well, what do you have a million features in? Well, if I was analyzing the legal documents, I might have a tokenizer that splits the words up to be analyzed, and that tokenizer might create 1 million different words available that might be in the document for doing weights. Sensitive to noisy data, outliers, and missing values. That's a huge one with k nearest neighbors. They really don't know what to do with a missing value. How do you compute the distance if you don't know what the value is? The SVM works more efficiently on high dimensional data. It is relatively memory efficient. So it's able to create those planes with only a few different variables in there as opposed to having to store a lot of data for different features and things like that. It's not suitable for large data sets. The SVM, you start running this over gigabytes of data, causes some huge issues. Underperforms if the data has noise or overlapping. That's a big one. We were looking at that where the SVM splits it and it creates a soft buffer, but what happens when you have a lot of stuff in the middle that's hard to sort out and doesn't know what to do with? That causes SVM to start crashing or not perform as well. Decision trees. Handles non-linear perimeters and missing values efficiently. The missing values is huge. I've seen this in, the wine tasting data sets where they have 3 different data sets and they share certain features, but then each one has some features that aren't in the other ones and it has to figure out how to handle those. Well, the decision tree does that automatically instead of having to figure a way to fill that data in before processing like you would with the other models. It's easy to understand and has less training period. So it trains pretty quickly. Comes up there and just keeps forking the tree down and moving the parts around, and so it doesn't have to go through the data multiple times guessing and adjusting. It just creates the tree as it goes. Overfitting and high variance are the most annoying part of it. That's an understatement. That has to do with how many leaves and how many decisions you have it do. The more you have, the more overfit it is to the data. It also, just in making the choices and how the choices come in, it might overfit to a specific feature because that's where it started at and that's what it knows. And it really is challenged with large data sets. They've been working on that with the data forest, but it's not suitable for large data sets. It's really something you'd probably run on a single machine and not across a data pool or anything.
If you are an aspiring data scientist who's looking out for online training and certification in data science from the best universities and industry experts, then search no more. Simplilearn's postgraduate program in data science from Caltech University in collaboration with IBM should be the right choice. For more details on this program, please use the link in the description box below.
So the decision tree, one of the many powerful tools in the machine learning library, begins with a problem. I think I have to buy a car. So in making this question, you want to know, how do I decide which one to buy? And you're going to start asking questions. Is the mileage greater than 20? Is the price less than 15? Will it be sufficient for 6 people? Does it have enough airbag, anti-lock brakes? All these questions come up. Then as we feed all this data in, we make a decision. And that decision comes up, oh, hey, this seems like a good idea. Here's a car. So as we go in through this decision process using a decision tree, we're going to explore this, maybe not in buying a car, but in how to process data. What's in it for you? Let's start by finding out what is machine learning and why we even want to know about it for processing our data. And we'll go into the 3 basic types of machine learning and the problems that are used by machine learning to solve. Finally, we'll get into what is a decision tree. What are the problems a decision tree solves? What are the advantages and disadvantages of using a decision tree? And then we want to dig in a little deep into the mechanics. How does the decision tree work? And then we'll go in and do a case loan repayment prediction where we actually are going to put together some Python code and show you the basic Python code for generating a decision tree. What is machine learning? There are so many different ways to describe what is machine learning in today's world and illustrate it. We're going to take a graphic here and making decisions or trying to understand what's going on. And really underlying machine learning is people wish they were smarter, wish we could understand the world better. And so you can see a guy here who's saying, hey, how can I understand the world better? And someone comes up and says, let's use artificial intelligence. And machine learning is a part of artificial intelligence. And now he gets a big smile on his face because now he has artificial intelligence to help him make his decisions. And they can think in new ways. So this brings in new ideas. So what is machine learning? This is a wonderful graph here. You can see where we have a learn, predict, decide. These are the most basic three premises of machine learning. In learning, we can describe the data in new ways and be able to learn new aspects about what we're looking at. And then we can use that to predict things, and we can use that to make decisions. So maybe it's something that's never happened before, but we can make a good guess whether it's going to be a good investment or not. It also helps us categorize stuff so we can remember it better. So it's easier to pull it out of the catalog. We can analyze data in new ways we never thought possible. And then, of course, there's the very large growing industry of recognize. We can do facial recognition, driver recognition, automated car recognition. All these are part of machine learning. Going back to our guy here who's in his ordinary system and would like to be smarter, make better choices. What happens with machine learning is an application of artificial intelligence wherein the system gets the ability to automatically learn and improve based on experience. So this is exciting because you have your ordinary guy who now has another form of information coming in, and this is with the artificial intelligence, helps him see things he never saw or track things he can't track. So instead of having to read all the news feeds, he can now have an artificial intelligence sort it out so he's only looking at the information he needs to make a choice with. And of course we use all those machine learning tools back in there, and he's now making smarter choices with less work. Types of machine learning. Let's break it into three primary types of learning. First is supervised learning, where you already have the data and the answers. So if you worked at a bank, you'd already have a list of all the previous loans and who defaulted on them and who made good payments on them. You then program your machine learning tool, and that lets you predict on the next person whether they're going to be able to make their payments or not on their loan. If you have one category where you already know the answers, the next one would be you don't know the answers. You just have a lot of information coming in. Unsupervised learning allows you to group liked information together. So if you're analyzing photos, it might group all the images of trees together and all the images of houses together without ever knowing what a house or a tree is. Which leads us to the third type of machine learning. The third type of machine learning is reinforcement learning. Unlike supervised or unsupervised learning, you don't have the data prior to starting. So you get the data one line at a time, and then whether you make a good choice or a bad choice, the machine learning tool has to then adjust accordingly. So you get a plus or minus feedback. You can liken this to the way a human learns. We experience life 1 minute at a time, and we learn from that. And either our memories is good or we learn to avoid something. Problems in machine learning. To understand where the decision tree fits into our machine learning tools, we have to understand the basics of some of the machine learning problems. And three of the primary ones fall underneath classification, problems with categorical solutions like yes or no, true or false, 1 or 0. This might be, does it belong to a particular group? Yes or no. Then we have regression, problems where there's a continuous value needs to be predicted, like product prices, profit. And you can see here, this is a very simple linear graph. You can guess what the next value is based on the first 4. It kind of follows a straight line going up. And clustering. This is problems where the data needs to be organized to find specific patterns, like in the case of product recommendation. They group all the different products that people just like you viewed on a shopping site and say, if people who bought this also bought this. The most commonly used for the decision tree is for classification, for figuring out, is it red or is it not? Is it a fruit or is it a vegetable? Yes or no? True, false? Left or right, 0, 1. And so when we talk about classification, we're going to look at the basic machine learning. These are the 4 main tools used in classification. There's Naive Bayes, Logistic Regression, Decision Tree, and Random Forest. The first 2 are for simpler data. So if your data is not very complex, you can usually use these to do a fairly good representation by drawing a line through the data or a curve through the data. They work wonderful in a lot of problems. But as things get more complicated, the decision tree comes in. And then if you have a very large amount of data, you start getting into the random forest. So the decision tree is actually a part of the random forest. But today we're just going to focus on the decision tree. What is a decision tree? Let's go through a very simple example before we dig in deep. Decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. Let's start with a simple question. How to identify a random vegetable from a shopping bag? So we have this group of vegetables in here, and we can start off by asking a simple question, is it red? And if it's not, then it's going to be the purple fruit to the left, probably an eggplant. If it's true, it's going to be one of the red fruits. Is the diameter greater than 2? If false, it's going to be what looks to be a red chili. And if it's true, it's going to be a bell pepper from the capsicum family. So it's a capsicum. Problems that decision tree can solve. So let's look at the two different categories the decision tree can be used on. It can be used on the classification, the true, false, yes, no, and it can be used on regression, where we figure out what the next value is in a series of numbers or a group of data. In classification, the classification tree will determine a set of logical if-then conditions to classify problems. For example, discriminating between 3 types of flowers based on certain features. In regression, a regression tree is used when the target variable is numerical or continuous in nature. We fit the regression model to the target variable using each of the independent variables. Each split is made based on the sum of squared error. Before we dig deeper into the mechanics of the decision tree, let's take a look at the advantages of using a decision tree, and we'll also take a glimpse at the disadvantages. The first thing you'll notice is that it's simple to understand, interpret, and visualize. It really shines here because you can see exactly what's going on in a decision tree. Little effort is required for data preparation, so you don't have to do special scaling. There's a lot of things you don't have to worry about when using a decision tree. It can handle both numerical and categorical data, as we discovered earlier, and nonlinear parameters don't affect its performance. So even if the data doesn't fit an easy curved graph, you can still use it to create an effective decision or prediction. If we're going to look at the advantages of a decision tree, we also need to understand the disadvantages of a decision tree. The first disadvantage is overfitting. Overfitting occurs when the algorithm captures noise in the data. That means you're solving for one specific instance instead of a general solution for all the data. High variance. The model can get unstable due to small variation in data. Low bias tree. A highly complicated decision tree tends to have a low bias, which makes it difficult for the model to work with new data. Decision tree, important terms. Before we dive in further, we need to look at some basic terms. We need to have some definitions to go with our decision tree and the different parts we're going to be using. We'll start with entropy. Entropy is a measure of randomness or unpredictability in the data set. For example, we have a group of animals. In this picture, there's 4 different kinds of animals, and this data set is considered to have a high entropy. You really can't pick out what kind of animal it is based on looking at just the 4 animals as a big clump of entities. So as we start splitting it into subgroups, we come up with our second definition, which is information gain. Information gain. It is a measure of decrease in entropy after the data set is split. So in this case, based on the color yellow, we've split one group of animals on one side as true and those who aren't yellow as false. As we continue down the yellow side, we split based on the height, true or false equals 10, and on the other side, height is less than 10, true or false. And as you see, as we split it, the entropy continues to be less and less and less, and so our information gain is simply the entropy E1 from the top and how it's changed to E2 in the bottom. And we'll look at the deeper math, although you really don't need to know a huge amount of math when you actually do the programming in Python, because it'll do it for you. But we'll look on the actual math at how they compute entropy. Finally, we went over the different parts of our tree, and they call the leaf node. Leaf node carries the classification or the decision, so it's the final end at the bottom. The decision node has 2 or more branches. This is where we're breaking the group up into different parts. And finally, you have the root node. The topmost decision node is known as the root node. How does a decision tree work? Wonder what kind of animals I'll get in the jungle today? Maybe you're the hunter with a gun, or if you're more into photography, you're a photographer with a camera. So let's look at this group of animals and let's try to classify different types of animals based on their features using a decision tree. So the problem statement is to classify the different types of animals based on their features using a decision tree. The data set is looking quite messy and the entropy is high in this case. So let's look at a training set or a training data set. set. And we're looking at color, we're looking at height, and then we have our different animals. We have our elephants, our giraffes, our monkeys, and our tigers. And they're of different colors and shapes. Let's see what that looks like, and how do we split the data? We have to frame the conditions that split the data in such a way that the information gain is the highest. Note, gain is the measure of decrease in entropy after splitting. So the formula for entropy is the sum, that's what this symbol looks like, that looks like kind of like a funky E, of K, where I equals 1 to K. K would represent the number of the different animals in there, where value, or P, value of I, would be the percentage of that animal, times the log base 2 of the same, the percentage of that animal. Let's try to calculate the entropy for the current data set and take a look at what that looks like. And don't be afraid of the math. You don't really have to memorize this math. Just be aware that it's there and this is what's going on in the background. And so we have 3 giraffes, 2 tigers, 1 monkey, 2 elephants, a total of 8 animals gathered. And if we plug that into the formula, we get an entropy that equals 3 over 8. So we have 3 giraffes, a total of 8, times the log. Usually they use base 2 on the log. So log base 2 of 3 over 8 plus, in this case let's say it's the elephants, 2 over 8, 2 elephants over a total of 8 times log base 2, 2 over 8, plus 1 monkey over a total of 8, log base 2, 1 over 8, and plus 2 over 8 of the tigers, log base 2 over 8. And if we plug that into our computer or calculator, I obviously can't do logs in my head, we get an entropy equal to 0.571. The program will actually calculate the entropy of the data set similarly after every split to calculate the gain. Now we're not going to go through each set one at a time to see what those numbers are. We just want you to be aware that this is a formula or the mathematics behind it. Gain can be calculated by finding the difference of the subsequent entropy values after a split. Now we will try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking that the gain we get out of them. The condition that gives us the highest gain will be used to make the first split. Can you guess what that first split will be just by looking at this image? As a human, it's probably pretty easy to split it. Let's see if you're right. If you guessed the color yellow, you're correct. Let's say the condition that gives us the maximum gain is yellow. So we will split the data based on the color yellow. If it's true, that group of animals goes to the left. If it's false, it goes to the right. The entropy after the splitting has decreased considerably. However, we still need some splitting at both the branches to attain an entropy value equal to 0. So we decide to split both the nodes using height as a condition. Since every branch now contains single label type, we can say that entropy in this case has reached the least value. And here you see we have the giraffes, the tigers, the monkey, and the elephants all separated into their own groups. This tree can now predict all the classes of animals present in the dataset with 100% accuracy. That was easy. Use case, loan repayment prediction. Let's get into my favorite part and open up some Python and see what the programming code and the scripting looks like. In here, we're going to want to do a prediction. And we start with this individual here who's requesting to find out how good his customers are going to be, whether they're going to repay their loan or not for his bank. And from that, we want to generate a problem statement to predict if a customer will repay loan amount or not, and then we're going to be using the decision tree algorithm in Python. Let's see what that looks like, and let's dive into the code. In our first few steps of implementation, we're going to start by importing the necessary packages that we need from Python, and we're going to load up our data and take a look at what the data looks like. So the first thing I need is I need something to edit my Python and run it in. So let's flip on over, and here I'm using the Anaconda Jupyter Notebook. Now you can use any Python IDE you like to run it in, but I find the Jupyter Notebook's really nice for doing things on the fly. And let's go ahead and just paste that code in the beginning. And before we start, let's talk a little bit about what we're bringing in. And then we're going to do a couple things in here. We have to make a couple changes as we go through this first part of the import. The first thing we bring in is numpy as np. That's very standard. When we're dealing with mathematics, especially with very complicated machine learning tools, you almost always see the numpy come in for your numbers. It's called NumPy. It has your mathematics in there. In this case, we actually could take it out, but generally you'll need it for most of your different things you work with. And then we're going to use pandas as PD. That's also a standard. The pandas is a data frame setup, and you can liken this to taking your basic data and storing it in a way that looks like an Excel spreadsheet. So as we come back to this, when you see NP or PD, those are very standard uses, you'll know that that's the pandas, and I'll show you a little bit more when we explore the data in just a minute. Then we're going to need to split the data, so I'm going to bring in our train, test, and split, and this is coming from the sklearn package cross-validation. In just a minute, we're going to change that, and we'll go over that too. And then there's also the sk.tree import decision tree classifier. That's the actual tool we're using. Remember I told you don't be afraid of the mathematics, it's going to be done for you. Well, the decision tree classifier has all that mathematics in there for you, so you don't have to figure it back out again. And then we have sklearn.metrics for accuracy score. We need to score our setup. That's the whole reason we're splitting it between the training and testing data. And finally, we still need the sklearn import tree. And that's just the basic tree function is needed for the decision tree classifier. And finally, we're going to load our data down here. And I'm going to run this, and we're going to get two things on here. One, we're going to get an error, and two, we're going to get a warning. Let's see what that looks like. So the first thing we had is we have an error. Why is this error here? Well, it's looking at this and it says, I need to read a file. And when this was written, the person who wrote it, this is their path where they stored the file. So let's go ahead and fix that. And I'm going to put in here my file path. I'm just going to call it full file name. And you'll see it's on my C drive, and there's this very lengthy setup on here where I stored the data2.csv file. Don't worry too much about the full path because on your computer it'll be different. The data.2csv file was generated by Simplilearn. If you want a copy of that, you can comment down below and request it here in the YouTube. And then if I'm going to give it a name, full file name, I'm going to go ahead and change it here to full file name. So let's go ahead and run it now and see what happens. And we get a warning. When you're coding, understanding these different warnings and these different errors that come up is probably the hardest lesson to learn. So let's just go ahead and take a look at this and use this as an opportunity to understand what's going on here. If you read the warning, it says the cross-validation is depreciated. So it's a warning on it's being removed. And it's going to be moved in favor of the model selection. So if we go up here, we have sklearn.cross-validation. And if you research this and go to the sklearn site, you'll find out that you can actually just swap it right in there with model selection. And so when I come in here and I run it again, that removes a warning. What they've done is they've had two different developers develop it in two different branches. And then they decided to keep one of those and eventually get rid of the other one. That's all that is. And very easy and quick to fix. Before we go any further, I went ahead and opened up the data from this file. Remember the data file we just loaded on here, the data_2.csv. Let's talk a little bit more about that and see what that looks like both as a text file, because it's a comma-separated variable file, and in a spreadsheet. This is what it looks like as a basic text file. You can see at the top they've created a header, and it's got 1, 2, 3, 4, 5 columns, and each column has data in it. And let me flip this over because we're also going to look at this in an actual spreadsheet so you can see what that looks like. And here I've opened it up in the OpenOffice Calc, which is pretty much the same as Excel, and zoomed in, and you can see we've got our columns and our rows of data. A little easier to read in here. We have a result, yes, yes, no. We have initial payment, last payment, credit score, house number. If we scroll way down, we'll see that this occupies 1,001 lines of code, or lines of data, with the first one being a column and then 1,000 lines of data. Now, as a programmer, if you're looking at a small amount of data, I usually start by pulling it up in different sources so I can see what I'm working with. But in larger data, you won't have that option. It'll just be too large. So you need to either bring in a small amount that you can look at it like we're doing right now, or we can start looking at it through the Python code. So let's go ahead and move on and take the next couple steps to explore the data using Python. Let's go ahead and see what it looks like in Python to print the length and the shape of the data. So let's start by printing the length of the database. We can use a simple len function from Python. And when I run this, you'll see that it's 1,000 long. And that's what we expected. There's 1,000 lines of data in there if you subtract the column head. This is one of the nice things when we did the balance data from the Panda Read CSV. You'll see that the header is row 0, so it automatically removes a row and then shows the data separate. It does a good job sorting that data out for us. And then we can use a different function, and let's take a look at that. And again, we're going to utilize the tools in Panda. And since the balance underscore data was loaded as a Panda data frame, we can do a shape on it. And let's go ahead and run the shape and see what that looks like. What's nice about this shape is not only does it give me the length of the data, we have 1,000 lines, it also tells me there's 5 columns. So when we were looking at the data, we had 5 columns of data. And then let's take one more step to explore the data using Python. And now that we've taken a look at the length and the shape, let's go ahead and use the pandas module for head, another beautiful thing in the data set that we can utilize. So let's put that on our sheet here, and we have print data set and balance data.head. And this is a pandas print statement of its own. So it has its own print feature in there. And then we went ahead and gave a label for our print job here of data set, just a simple print statement. And when we run that, and let's just take a closer look at that. Let me zoom in here. There we go. Pandas does such a wonderful job of making this a very clean, readable data set. So you can look at the data, you can look at the column headers, you can have it, when you put it as the head, it prints the first 5 lines of the data. And we always start with 0. So we have 5 lines, we have 0, 1, 2, 3, 4 instead of 1, 2, 3, 4, 5. That's a standard scripting and programming set, as you want to start with the 0 position. And that is what the data head does. It pulls the first 5 rows of data, puts it in a nice format that you can look at and view. Very powerful tool to view the data. So instead of having to flip and open up an Excel spreadsheet or open Office Calc or trying to look at a Word doc where it's all scrunched together and hard to read, you can now get a nice open view of what you're working with. We're working with a shape of 1,000 long, 5 wide, so we have 5 columns, and we do the full data head. You can actually see what this data looks like. The initial payment, last payment, credit scores, house number. So let's take this, now that we've explored the data, and let's start digging into the decision tree. So in our next step, we're going to train and build our data tree. And to do that, we need to first separate the data out. We're going to separate it into 2 groups so that we have something to actually train the data with, and then we have some data on the side to test it, to see how good our model is. Remember, with any of the machine learning, you always want to have some kind of test set to weigh it against, so you know how good your model is when you distribute it. Let's go ahead and break this code down and look at it in pieces. So first we have our X and Y. Where do X and Y come from? Well, X is going to be our data, and Y is going to be the answer or the target. You can look at it source and target. In this case, we're using X and Y to denote the data in and the data that we're actually trying to guess what the answer is going to be. And so to separate it, we can simply put in X equals the balance of the data dot values. The first brackets means that we're going to select all the lines in the database. So it's all the data. And the second one says we're only going to look at columns 1 through 5. Remember, we always start with 0. 0 is a yes or no, and that's whether the loan went default or not. So we want to start with 1. If we go back up here, that's the initial payment, and it goes all the way through the house number. Well, if we want to look at 1 through 5, we can do the same thing for Y, which is the answers, and we're going to set that just equal to the 0 row. So it's just the 0 row, and then it's all rows going in there. So now we've divided this into 2 different data sets. One of them with the data going in, and one with the answers. Next, we need to split the data. And here you'll see that we have it split into 4 different parts. The first one is your X training, your X test, your Y train, your Y test. Simply put, we have X going in, where we're going to train it, and we have to know the answer to train it with. And then we have X test, where we're going to test that data. And we have to know in the end what the Y was supposed to be. And that's where this train test split comes in, that we loaded earlier in the modules. This does it all for us. And you can see they set the test size equal to 0.3, so that's roughly 30% will be used in the test. And then we use a random state, so it's completely random which rows it takes out of there. And then finally we get to actually build our decision tree. And they've called it here CLF_entropy. That's the actual decision tree, or decision tree classifier. And in here they've added a couple variables which we'll explore in just a minute. And then finally we need to fit the data to that. So we take our CLF entropy that we created and we fit the X train, and since we know the answers for X train or the Y train, we go ahead and put those in. And let's go ahead and run this. And what most of these sklearn modules do is when you set up the variable, in this case when we set the CLF entropy equal to decision tree classifier, it automatically prints out what's in that decision tree. There's a lot of variables you can play with in here, and it's quite beyond the scope of this tutorial to go through all of these and how they work. But we're working on entropy, that's one of the options. We've added that it's completely a random state of 100, so 100%. And we have a max depth of 3. Now the max depth, if you remember above when we were doing the different graphs of animals, means it's only going to go down 3 layers before it stops. And then we have minimal samples of leaves as 5. So it's going to have at least 5 leaves at the end. So I'll have at least 3 splits, or I'll have no more than 3 layers, and at least 5 end leaves with the final result at the bottom. Now that we've created our decision tree classifier, not only created it but trained it, let's go ahead and apply it and see what that looks like. So let's go ahead and make a prediction and see what that looks like. We're going to paste our predict code in here. And before we run it, let's just take a quick look at what it's doing here. We have a variable yPredict that we're going to do. And we're going to use our variable CLF entropy that we created. And then you'll see .predict. And it's very common in the sklearn modules that their different tools have the predict when you're actually running a prediction. In this case, we're going to put our X test data in here. Now, if you delivered this for use, an actual commercial use, and distributed it, this would be the new loans you're putting in here to guess whether the person's going to be pay them back or not. In this case, though, we need to test out the data and just see how good our sample is, how good of our tree does at predicting the loan payments. And finally, since Anaconda Jupyter Notebook works as a command line for Python, we can simply put the yPredict in to print it. I could just as easily have put the print and put brackets around yPredict in to print it out. We'll go ahead and do that. It doesn't matter which way you do it. And you'll see right here that it runs a prediction. This is roughly 300 in here. Remember, it's 30% of 1,000, so you should have about 300 answers in here. And this tells you which each one of those lines of our test went in there, and this is what our yPredict came out. So let's move on to the next step, where we're going to take this data and try to figure out just how good a model we have. So here we go. Since sklearn does all the heavy lifting for you and all the math, we have a simple line of code to let us know what the accuracy is. And let's go ahead and go through that and see what that means and what that looks like. Let's go ahead and paste this in, and let me zoom in a little bit. There we go. So you have a nice full picture. And we'll see here we're just going to do a print accuracy is, and then we do the accuracy score. And this was something we imported earlier, if you remember at the very beginning. Let me just scroll up there real quick so you can see where that's coming from. That's coming from here, down here, from sklearn.metrics import accuracy score. And you could probably run a script, make your own script to do this very easily. How accurate is it? How many out of 300 do we get right? And so we put in our y test, that's the one we ran the predict on. And then we put in our yPredict in, that's the answers we got. And we're just going to multiply that by 100, because this is just going to give us an answer as a decimal. And we want to see it as a percentage. And let's run that and see what it looks like. And if you see here, we got an accuracy of 93.66667. So when we look at the number of loans and we look at how good our model fit, we can tell people it has about a 93.6 fitting to it. So just a quick recap on that. We now have accuracy set up on here. And so we have created a model that uses the decision tree algorithm to predict whether a customer will repay the loan or not. The accuracy of the model is about 94.6%. The bank can now use this model to decide whether it should approve the loan request from a particular customer or not. And so this information is really powerful. We may not be able to, as individuals, understand all these numbers because they have thousands of numbers that come in. But you can see that this is a smart decision for the bank to use a tool like this to help them to predict how good their profit's going to be off of the loan balances and how many are going to default or not. So we've had a lot of fun learning about decision trees. So let's take a look at the key takeaways that we've covered today. What is machine learning? We covered up some different aspects of machine learning and what that is utilized in your everyday life and what you can use it for predicting, for describing, for guessing what the next outcome is, for storing information. We looked at the three main types of machine learning: supervised learning, unsupervised learning, and reinforced learning. We looked at problems in machine learning and what it solves: classification, regression, and clustering. Finally, we went through how does the decision tree work, where we looked at the hunter and he's trying to sort out the different animals and what kind of animals they are. And then we rolled up our sleeves and did our Python coding and actually applied it to a data set for random forest. Currently today it's used in remote sensing. For example, they're used in the ETM devices. If you're a space buff, that's the enhanced thematic mapper they use on satellites, which see far outside the human spectrum for looking at land masses. And they acquire images of the Earth's surface. The accuracy is higher and training time is less than many other machine learning tools out there. Also, object detection, multi-class object detection, is done using random forest algorithms. A good example is traffic, where you're trying to sort out the different cars, buses, and things. And it provides a better detection in complicated environments. They're very complicated up there. And then we have another example, Connect. And let's take a little closer look at Connect. Connect, they use a random forest as part of the game console. And what it does is it tracks the body movements and it recreates it in the game. And let's see what that looks like. We have a user who performs a step. In this case, it looks like Elvis Presley going there. That is then recorded, so that Connect registers the movement, and then it marks the user based on accuracy. And it looks like we have Prince going on this one, from Elvis Presley to Prince. It's great. So it marks the user based on the accuracy. If we look at that a little closer, we have a training set to identify body parts. Where are the hands? Where are the feet? What's going on with the body? That then goes into a random forest classifier that learns from it. Once we've trained the classifier, it then identifies the body parts while the person's dancing. And it's able to represent that in a computer format, and then based on that, it scores the game and how accurate you are as being Elvis Presley or Prince in your dancing. Let's take an overview of what we're going to cover today. What's in it for you? What we're going to start with is what is machine learning. We're not going to go into detail on that. We're going to specifically look at how the random forest fits in the machine learning hierarchy. Then we're going to look at some applications of random forest. What is classification, which is its primary use? Why use random forest? What's the benefits of it? And how does it actually come together? What is random forest? And then we'll get into random forest and the decision tree, that's like the final step and how it works. And finally, we'll get some Python code in there, and we'll use the case, the iris flower analysis. Now, if you don't know what any of these terms mean or where we're going with this, don't worry. We're going to cover all the basics and have you up and running, and even doing some basic script in Python by the end. Let's take a closer look at types of machine learning. Specifically, we're going to look at where the decision tree fits in with the different machine learning packages out there. We'll start with the basic types of machine learning. There's supervised learning, where you have lots of data and you're able to train your models. There's unsupervised learning, where it has to look at the data and then divide it based on its own algorithms without having any training. And then there's reinforcement learning, where you get a plus or negative if you have the answer correct. This particular tool belongs to the supervised learning. Let's take a closer look at that, what that means in supervised learning. Supervised learning falls into two groups, classification and regression. We'll talk about regression a little later and how that differs. This particular format goes underneath classification. So we're looking at supervised learning and classification in the machine learning tools. Classification is a kind of problem wherein the outputs are categorical in nature, like yes or no, true or false, or 0 or 1. In that particular framework, there's the KNN, where the NN stands for nearest neighbor, naive Bayes, the decision tree, which is part of the random forest that we're studying today. So why random forest? It's always important to understand why we use this tool over the other ones. What are the benefits here? And so with the random forest, the first one is there's no overfitting. If you use of multiple trees, reduce the risk of overfitting. Training time is less. Overfitting means that we have fit the data so close to what we have as our sample that we pick up on all the weird parts. And instead of predicting the overall data, you're predicting the weird stuff, which you don't want. High accuracy. Runs efficiently on large database. For large data, it produces highly accurate predictions. In today's world of big data, this is really important. And this is probably where it really shines. This is where why random forest really comes in. It estimates missing data. Data in today's world is very messy. So when you have a random forest, it can maintain the accuracy when a large proportion of the data is missing. What that means is if you have data that comes in from 5 or 6 different areas, and maybe they took one set of statistics in one area, and they took a slightly different set of statistics in the other, so they have some of the same shared data, but one is missing like the number of children in the house if you're doing something over demographics, and the other one is missing the size of the house. It will look at both of those separately and build 2 different trees, and then it can do a very good job of guessing which one fits better even though it's missing that data. Let us dig deep into the theory of exactly how it works. And let's look at what is random forest. Random forest, or random decision forest, is a method that operates by constructing multiple decision trees. The decision of the majority of the trees is chosen by the random forest as the final decision. And let's we have some nice graphics here. We have a decision tree, and they actually use a real tree to denote the decision tree, which I love. And given a random, some kind of picture of a fruit, this decision tree decides that the output is it's an apple. And we have a decision tree 2 where we have that picture of the fruit goes in, and this one decides that it's a lemon. And the decision 3 tree gets another image and it decides it's an apple. And then this all comes together in what they call the random forest. And this random forest then looks at it and says, okay, I got 2 votes for apple, 1 vote for lemon. The majority is apples, so the final decision is apples. To understand how the random forest works, we first need to dig a little deeper and take a look at the random forest and the actual decision tree and how it builds that decision tree. In looking closer at how the individual decision trees work, we'll go ahead and continue to use the fruit example, since we're talking about trees and forests. A decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. So in here we have a bowl of fruit, and if you look at that, it looks like they switched from lemons to oranges. So we have oranges, cherries, and apples. And the first decision of the decision tree might be, is the diameter greater than or equal to 3? And if it says false, it knows that they're cherries because everything else is bigger than that. So all the cherries fall into that decision. So we have all that data we're training. We can look at that. We know that that's what's going to come up. Is the color orange? Well, it goes, orange or red? Well, if it's true, then it comes out as the orange. And if it's false, that leaves apples. So in this example, it sorts out the fruit in the bowl, or the images of the fruit. A decision tree, these are very important terms to know because these are very central to understanding the decision tree and when working with them. The first is entropy. Everything on the decision tree and how it makes a decision is based on entropy. Entropy is a measure of randomness or unpredictability in the data set. Then they also have information gain, the leaf node, the decision node, and the root node. We'll cover these other 4 terms as we go down the tree. But let's start with entropy. So starting with entropy, we have here a high amount of randomness. What that means is that whatever's coming out of this decision, if it was going to guess based on this data, it wouldn't be able to tell you whether it's a lemon or an apple. It would just say it's a fruit. So the first thing we want to do is we want to split this apart. And we take the initial data set, and we're going to create a data set 1 and a data set 2. We just split it in 2. And if you look at these new data sets, after splitting them, the entropy of each of those sets is much less. So for the first one, whatever comes in there, it's going to sort that data and it's going to say, okay, if this data goes this direction, it's probably an apple. And if it goes into the other direction, it's probably a lemon. So that brings us up to information gain. It is the measure of decrease in the entropy after the data set is split. What that means in here is that we've gone from one set which has a very high entropy to two lower sets of entropy. And we've added in the values of E1 for the first one and E2 for the second two, which are much lower. And so that information gain is increased greatly in this example. And so you can find that the information gain simply equals decision E1 minus E2. As we're going down our list of definitions, we'll look at the leaf node. And the leaf node carries the classification or the decision. So we look down here to the leaf node. We finally get to our set 1 or our set 2. When it comes down there and it says, okay, this object's gone into set 1, if it's gone into set 1, it's going to be split by some means, and we'll either end up with apples on the leaf node or a lemon on the leaf node, and on the right it'll either be an apple or lemons. Those leaf nodes, or those final decisions or classifications, that's the definition of leaf node in here. If we're going to have a final leaf where we make the decision, we should have a name for the nodes above it, and they call those decision nodes. A decision node has two or more branches. And you can see here where we have the 5 apples and 1 lemon, and in the other case the 5 lemons and 1 apple. They have to make a choice of which tree it goes down based on some kind of measurement or information given to the tree. And that brings us to our last definition. The root node, the topmost decision node, is known as the root node. And this is where you have all of your data and you have your first decision it has to make, or the first split in information. So far we've looked at a very general image with the fruit being split. Let's look and see exactly what that means to split the data and how do we make those decisions on there. Let's go in there and find out how does a decision tree work. So let's try to understand this, and let's use a simple example, and we'll stay with the fruit. We have a bowl of fruit, and so let's create a problem statement, and the problem is we want to classify the different types of fruits in the bowl based on different features. The data set in the bowl is looking quite messy, and the entropy is high in this case. So if this bowl was our decision maker, it wouldn't know what choice to make. It has so many choices. Which one do you pick? Apple, grapes, or lemons? And so we look in here, we're going to start with a training set. So this is our data that we're training our data with. And we have a number of options here. We have the color, and under the color we have red, yellow, purple. We have a diameter, 331, 331, and we have a label, apple, lemon, grapes, apple, lemon, grapes. And how do we split the data? We have to frame the conditions to split the data in such a way that the information gain is the highest. And it's very key to note that we're looking for the best gain. We don't want to just start sorting out the smallest piece in there. We want to split it the biggest way we can. And so we measure this decrease in entropy, that's what they call it, entropy, there's our entropy, after splitting. And now we'll try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking the gain that we get out of them. The conditions that give us the highest gain will be used to make the first split. So let's take a look at these different conditions. We have color, we have diameter, and if we look underneath that, we have a couple different values. We have diameter equals 3, color equals yellow, red, diameter equals 1. And when we look at that, you'll see over here we have 1, 2, 3, 4 threes. That's a pretty high selection. So let's say the condition gives us a maximum gain of 3. So we have the most pieces fall into that range. So our first split from our decision node is we split the data based on the diameter. Is it greater than or equal to 3? If it's not, that's false, it goes into the grape bowl. And if it's true, it goes into a bowl full of lemon and apples. The entropy after splitting has decreased considerably. So now we can make two decisions. If you look at, there's very much less chaos going on there. This node has already attained an entropy value of 0, as you can see. There's only one kind of label left for this branch. So no further splitting is required for this node. However, this node on the right still requires a split to decrease the entropy further. So we split the right node further based on color. If you look at this, if I split it on color, that pretty much cuts it right down the middle, and it's the only thing we have left in our choices of color and diameter too. And if the color is yellow, it's going to go to the right bowl, and if it's false, it's going to go to the left bowl. So the entropy in this case is now 0. So now we have 3 bowls with 0 entropy. There's only one type of data in each one of those bowls. So we can predict a lemon with 100% accuracy. And we can predict the apple also with 100% accuracy, along with our grapes up there. So we've looked at kind of a basic tree in our forest, but what we really want to know is how does a random forest work as a whole? So to begin our random forest classifier, let's say we already have built 3 trees. And we're going to start with the first tree that looks like this. Just like we did in the example, this tree looks at the diameter. If it's greater than or equal to 3, it's true, otherwise it's false. So one side goes to the smaller diameter, one side goes to larger diameter. And if the color is orange, it's going to go to the right, true. We're using oranges now instead of lemons. And if it's red, it's going to go to the left, false. We build a second tree very similar, but it's split differently. Instead of the first one being split by diameter, this one, when they created it, if you look at that first bowl, it has a lot of red objects. So it says, is the color red? Because that's going to bring our entropy down the fastest. And so, of course, if it's true, it goes to the left. If it's false, it goes to the right. And then it looks at the shape, false or true, and so on and so on. And tree 3 is the diameter equal to 1. And it came up with this because there's a lot of cherries in this bowl. So that would be the biggest split on there is the diameter equal to 1. That's going to drop the entropy the quickest. And as you can see, it splits it into true. If it goes false, and they've added another category, does it grow in the summer? And if it's false, it goes off to the left. If it's true, it goes off to the right. Let's go ahead and bring these 3 trees so you can see them all in one image. So this would be 3 completely different trees categorizing a fruit. And let's take a fruit. Now let's try this. And this fruit, if you look at it, we've blackened it out. You can't see the color on it, so it's missing data. Remember, one of the things we talked about earlier is that a random forest works really good if you're missing data, if you're missing pieces. So this fruit has an image, but maybe the person had a black and white camera when they took the picture. And we're going to take a look at this, and it's going to have, they put the color in there, so ignore the color down there. But the diameter equals 3. We find out it grows in the summer equals yes, and the shape is a circle. And if you go to the right, you can look at what one of the decision trees did. This is the third one. Is the diameter greater than or equal to 3? Is the color orange? Well, it doesn't really know on this one, but if you look at the value, it'd say true, and it'd go to the right. Tree 2 classifies it as cherries. Is the color equal red? Is the shape a circle? True, it is a circle. So this would look at it and say, oh, that's a cherry. And then we go to the other classifier, and it says, is the diameter equal 1? Well, that's false. Does it grow in the summer? True. So it goes down and looks at as oranges. So how does this random forest work? The first one says it's an orange. The second one said it was a cherry. And the third one says, it's an orange. And you can guess that if you have 2 oranges and one says it's a cherry, when you add that all together, the majority of the vote says orange. So the answer is, it's classified as an orange, even though we didn't know the color and we're missing data on it. I don't know about you, but I'm getting tired of fruit. So let's switch, and I did promise you we'd start looking at a case example and get into some Python coding. Today we're going to use the case, the iris flower analysis. Ooh, this is the exciting part as we roll up our sleeves and actually look at some Python coding. Before we start the Python coding, we need to go ahead and create a problem statement. Wonder what species of iris do these flowers belong to? Let's try to predict the species of the flowers using machine learning in Python. Let's see how it can be done. So here we begin to go ahead and implement our Python code. And you'll find that the first half of our implementation is all about organizing and exploring the data coming in. Let's go ahead and take this first step, which is loading the different modules into Python, and let's go ahead and put that in our favorite editor, whatever your favorite editor is. In this case, I'm going to be using the Anaconda Jupyter Notebook, which is one of my favorites. Certainly there's Notepad++ and Eclipse and dozens of others, or just even using the Python terminal window. Any of those will work just fine to go ahead and explore this Python coding. So here we go. Let's go ahead and flip over to our Jupyter Notebook. And I've already opened up a new page for Python 3 code, and I'm just going to paste this right in there. And let's take a look and see what we're bringing into our Python. The first thing we're going to do is from the sklearn.datasets import load iris. Now this isn't the actual data, this is just the module that allows us to bring in the data. the load iris. And the iris is so popular, it's been around since 1936 when Ronald Fisher published a paper on it. And they're measuring the different parts of the flower, and based on those measurements, predicting what kind of flower it is. And then if we're going to do a random forest classifier, we need to go ahead and import a random forest classifier from the sklearn module. So sklearn.ensemble, import random forest classifier. And then we want to bring in two more modules. And these are probably the most commonly used modules in Python and data science with any of the other modules that we bring in. And one is going to be pandas. So we're going to import pandas as PD. PD is the common term used for pandas. And pandas is basically creates a data format for us where when you create a pandas data frame, it looks like an Excel spreadsheet. And you'll see that in a minute when we start digging deeper into the code. Panda is just wonderful because it plays nice with all the other modules in there. And then we have NumPy, which is our numbers Python. And the numbers Python allows us to do different mathematical sets on here. We'll see right off the bat, we're going to take our NP and we're going to go ahead and seed the randomness with it with 0. So np.random.seed is seeding that as 0. This code doesn't actually show anything. We're going to go ahead and run it because I need to make sure I have all those loaded. And then let's take a look at the next module on here. The next 6 slides, including this one, are all about exploring the data. Remember I told you half of this is about looking at the data and getting it all set. So let's go ahead and take this code right here, the script, and let's get that over into our Jupyter notebook. And here we go. We've gone ahead and run the imports. And I'm going to paste the code down here. And let's take a look and see what's going on. The first thing we're doing is we're actually loading the iris data. And if you remember up here, we loaded the module that tells it how to get the iris data. Now we're actually assigning that data to the variable iris. And then we're going to go ahead and use the df to define data frame. And that's going to equal PD. And if you remember, that's pandas as PD. So that's our pandas. And panda data frame. And then we're looking at iris data. And columns equals iris feature names. And we're going to do the df head. And let's run this so you can understand what's going on here. The first thing you want to notice is that our df has created what looks like an Excel spreadsheet. And in this Excel spreadsheet we have set the columns. So up on the top you can see the 4 different columns. And then we have the data, iris.data, down below. It's a little confusing without knowing where this data is coming from. So let's look at the bigger picture. And I'm going to go print. I'm just going to change this for a moment. And we're going to print all of iris and see what that looks like. So when I print all of iris, I get this long list of information. And you can scroll through here and see all the different titles on there. What's important to notice is that first off, there's a brackets at the beginning. So this is a Python dictionary. And in a Python dictionary, you'll have a key or a label. And this label pulls up whatever information comes after it. So feature names, which we actually used over here under columns, is equal to an array of sepal length, sepal width, petal length, petal width. These are the different names they have for the 4 different columns. And if you scroll down far enough, you'll also see data down here. Oh goodness, it came up right towards the top. And data is equal to the different data we're looking at. Now there's a lot of other things in here like target. We're going to be pulling that up in a minute. And there's also the names, the target names, which is further down. And we'll show you that also in a minute. Let's go ahead and set that back to the head. And this is one of the neat features of pandas and panda data frames is when you do df.head or the panda data frame.head, it'll print the first 5 lines of the data set in there, along with the headers if you have it. In this case, we have the column headers set to iris features. And in here, you'll see that we have 0, 1, 2, 3, 4. In Python, most arrays always start at 0. So when you look at the first 5, it's going to be 0, 1, 2, 3, 4, not 1, 2, 3, 4, 5. So now we've got our iris data imported into a data frame. Let's take a look at the next piece of code in here. And so in this section here of the code, we're going to take a look at the target. And let's go ahead and get this into our notebook, this piece of code, so we can discuss it a little bit more in detail. So here we are in our Jupyter notebook. I'm going to put the code in here. And before I run it, I want to look at a couple things going on. So we have df species. And this is interesting because right here you'll see where I have df species in brackets, which is the key code for creating another column. And here we have iris.target. Now these are both in the pandas setup on here. So in pandas we can do either one. I could have just as easily done iris and then in brackets target, depending on what I'm working on. Both are acceptable. Let's go ahead and run this code and see how this changes. And what we've done is we've added the target from the iris data set as another column on the end. Now what species is, this is what we're trying to predict. So we have our data, which tells us the answer for all these different pieces, and then we've added a column with the answer. That way when we do our final setup, we'll have the ability to program our neural network to look for this different data and know what a setosa is, or a varicolor, which we'll see in just a minute, or virginica. Those are the three that are in there. And now we're going to add one more column. I know, we're organizing all this data over and over again. It's kind of fun. There's a lot of ways to organize it. What's nice about putting everything onto one data frame is I can then do a printout and it shows me exactly what I'm looking at. And I'll show you where that's different, where you can alter that and do it slightly differently. But let's go ahead and put this into our script up to date now. And here we go. We're going to put that down here. And we're going to run that. And let's talk a little bit about what we're doing. Now, we're exploring data, and one of the challenges is knowing how good your model is. Did your model work? And to do this, we need to split the data. And we split it into two different parts. They usually call it the training and the testing. And so in here, we're going to go ahead and put that in our database so you can see it clearly. And we've set it df. And remember, you can put brackets. This is creating another column. Is train, so we're going to use part of it for training. And this equals np, remember that stands for numpy, .random.uniform. So we're generating a random number between 0 and 1. And we're going to do it for each of the rows. That's where the length df comes from. So each row gets a generated number. And if it's less than 0.75, it's true. And if it's greater than 0.75, it's false. This means we're going to take 75% of the data, roughly, because there's a randomness involved, and we're going to use that to train it. And then the other 25% we're going to hold off to the side and use that to test it later on. So let's flip back on over and see what the next step is. So now that we've labeled our database for which is training and which is testing, let's go ahead and sort that into two different variables, train and test. And let's take this code and let's bring it into our project. And here we go, let's paste it on down here. And before I run this, let's just take a quick look at what's going on here. Is we have up above, we created, remember there's our def.head, which prints the first 5 rows. And we've added a column is train at the end. And so we're going to take that, we're going to create two variables. We're going to create two new data frames. One's called train. One's called test, 75% in train, 25% in test. And then to sort that out, we're going to do that by doing df, our main original data frame with the iris data in it. And if df is train equals true, that's going to go in the train. And if df is train equals false, it goes in the test. And so when I run this, we're going to print out the number in each one. Let's see what that looks like. And you'll see that it puts 118 in the training module, and it puts 32 in the testing module, which lets us know that there was 150 lines of data in here. So if you went and looked at the original data, you could see that there's 150 lines. And that's roughly 75% in one and 25% for us to test our model on afterward. So let's jump back to our code and see where this goes. In the next two steps, we want to do one more thing with our data, and that's make it readable to humans. I don't know about you, but I hate looking at zeros and ones. So let's start with the features, and let's go ahead and take those and make those readable to humans. And let's put that in our code. Let's see, here we go, paste it in. And you'll see here we've done a couple very basic things. We know that the columns in our data frame, again this is a panda thing, the df columns, and we know the first 4 of them, 0, 1, 2, 3, that'd be the first 4, are going to be the features or the titles of those columns. And so when I run this, you'll see down here that it creates an index, SEPA length, SEPA width, petal length, and petal width. And this should be familiar because if you look up here, here's our column titles going across, and here's the first 4. One thing I want you to notice here is that when you're in a command line, whether it's Jupyter Notebook or you're running command line in the terminal window, if you just put the name of it, it'll print it out. This is the same as doing print features. And the shorthand is you just put features in here. If you're actually writing a code and saving the script and running it by remote, you really need to put the print in there. But for this, when I run it, you'll see it gives me the same thing. But for this, we want to go ahead and we'll just leave it as features because it doesn't really matter. And this is one of the fun thing about Jupyter Notebooks is I'm just building the code as we go. And then we need to go ahead and create the labels for the other part. So let's take a look and see what that. For our final step in prepping our data, before we actually start running the training and the testing, is we're going to go ahead and convert the species on here into something the computer understands. So let's put this code into our script and see where that takes us. Alright, here we go. We set y equal to pd.factorize train species of 0. So let's break this down just a little bit. We have our pandas right here, pd. Factorize. What's factorize doing? I'm going to come back to that in just a second. Let's look at what train species is and why we're looking at the group 0 on there. And let's go up here, and here is our species. Remember this that we created this whole column here for species? And then it has Setosa, 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 and if you scroll down enough, you'd also see Virginica and Varicolor. We need to convert that into something the computer understands, zeros and ones. So the trained species of 0, because this is in the format of an array of arrays, so you have to have the 0 on the end. And then species is just that column. Factorize goes in there and looks at the fact that there's only 3 of them. So when I run this, you'll see that y generates an array that's equal to, in this case it's the training set, and it's zeros, ones, and twos representing the 3 different kinds of flowers we have. So now we have something the computer understands, and we have a nice table that we can read and understand. And now, finally, we get to actually start doing the predicting. So here we go. We have 2 lines of code. Oh my goodness, that was a lot of work to get to 2 lines of code. But there is a lot in these 2 lines of code. So let's take a look and see what's going on here and put this into our full script that we're running. And let's paste this in here. And let's take a look and see what this is. We're creating a variable CLF, and we're going to set this equal to the random forest classifier. And we're passing 2 variables in here, and there's a lot of variables you can play with. As far as these 2 are concerned, they're very standard. In jobs, all that does is to prioritize it. Not something to really worry about. Usually when you're doing this on your own computer, you do in jobs equals 2. If you're working in a larger or big data and you need to prioritize it differently, this is what that number does, is it changes your priorities and how it's going to run across the system and things like that. And then the random state is just how it starts. 0 is fine for here. But let's go ahead and run this. We also have clf.fit train features, y. And before we run it, let's talk about this a little bit more. clf.fit. So we're training it. We are actually creating our random forest classifier right here. This is the code that does everything. And we're going to take our training set. Remember, we kept our test off to the side. And we're going to take our training set with the features, and then we're going to go ahead and put that in, and here's our target, the y. So the y is 0, 1, and 2 that we just created, and the features is the actual data going in that we put into the training set. And let's go ahead and run that. And this is kind of an interesting thing because it printed out the random forest classifier and everything around it. And so when you're running this in your terminal window or in a script like this, this automatically treats this just like when we were up here and I typed in y and it printed out y instead of print y. This does the same thing. It treats this as a variable and prints it out. But if you were actually running your code, that wouldn't be the case. And what is printed out is it shows us all the different variables we can change. And if we go down here, you can actually see in jobs equals 2. You can see the random state equals 0. Those are the 2 that we sent in there. You would really have to dig deep to find out all these different meanings of all these different settings on here. Some of them are self-explanatory if you kind of think about it a little bit, like max features is auto. So all the features that we're putting in there is just going to automatically take all 4 of them. Whatever we send it, it'll take. Some of them might have so many features because you're processing words. There might be like 1.4 million features in there because you're doing legal documents, and that's how many different words are in there. At that point, you probably want to limit the maximum features that you're going to process. And leaf nodes, that's the end nodes. Remember we had the fruit and we're talking about the leaf nodes. Like I said, there's a lot in this. We're looking at a lot of stuff here. So you might have, in this case, there's probably only 3 leaf nodes, maybe 4. You might have thousands of leaf nodes, at which point you do need to put a cap on that and say, okay, you can only go so far, and then we're going to use all of our resources on processing this. And that really is what most of these are about, is limiting the process and making sure we don't overwhelm a system. And there's some other settings in here. Again, we're not going to go over all of them. Warm start equals false. Warm start is if you're programming it one piece at a time externally. Since we're not going to have, we're not going to continually to train this particular learning tree. And again, like I said, there's a lot of things in here that you'll want to look up more detail from the sklearn. And if you're digging in deep and running a major project on here. For today though, all we need to do is fit or train our features and our target Y. So now we have our training model. What's next? If we're going to create a model, we now need to test it. Remember, we set aside the test feature, test group, 25% of the data. So let's go ahead and take this code and let's put it into our script and see what that looks like. Okay, here we go. And we're going to run this, and it's going to come out with a bunch of 0s, 1s, and 2s, which represents the 3 types of flowers, the setosa, the virginica, and the versicolor. And what we're putting into our predict is the test features, and I always kind of like to know what it is I am looking at. So real quick, we're going to do test features. And remember, features is an array of sepal length, sepal width, petal width. So when we put it in this way, it actually loads all these different columns that we loaded into features. So if we did just features, let me just do features in here so you can see what features looks like. This is just playing with pandas data frames. You'll see that it's an index. So when you put an index in like this into test features, into test, it then takes those columns and creates a panda data frames from those columns. And in this case, we're going to go ahead and put those into our predict. So we're going to put each one of these lines of data, the 5.0, 3.4, 1.5, 0.2, and we're going to put those in and we're going to predict what our new forest classifier is going to come up with. And this is what it predicts. It predicts 0, 0, 0, 1, 2, 1, 1, 2, 2, 2. And again, this is the flower type, setosa, virginica, and versicolor. So now that we've taken our test features, let's explore that. Let's see exactly what that data means to us. So the first thing we can do with our predicts is we can actually generate a different prediction model. When I say different, we're going to view it differently. It's not that the data itself is different. So let's take this next piece of code and put it into our script. So we're pasting it in here, and you'll see that we're doing predict, and we've added underscore proba for probability. So there's our clf.predict probability. So we're running it just like we ran it up here, but this time with this we're going to get a slightly different result, and we're only going to look at the first 10. So you'll see down here, instead of looking at all of them, which was 27, you'll see right down here that this generates a much larger field on the probability. And let's take a look and see what that looks like and what that means. So when we do the predict underscore proba for probability, it generates 3 numbers. So we had 3 leaf nodes at the end. And if you remember from all the theory we did, this is the predictors. The first one is predicting a 1 for setosa. It predicts a 0 for virginica, and it predicts a 0 for versicolor, and so on and so on and so on. And let's, you know what, I'm going to change this just a little bit. Let's look at 10 to 20, just because we can. And we start to get in a little different of data, and you'll see right down here, it gets to this one, this line right here. And this line has 0, 0.5, 0.5. And so if we're going to vote, and we have 2 equal votes, it's going to go with the first one. So it says Setosa gets 0 votes, Virginica gets 0.5 votes, Versicolor gets 0.5 votes, but let's just go with the Virginica since these 2 are equal, and so on down the list. You can see how they vary on here. So now we've looked at both how to do a basic predict of the features, and we've looked at the predict probability. Let's see what's next on here. So now we want to go ahead and start mapping names for the plants. We want to attach names so that it makes a little more sense for us. And that's what we're going to do in these next 2 steps. We're going to start by setting up our predictions and mapping them to the names. So let's see what that looks like. And let's go ahead and paste that code in here and run it. And this goes along with the next piece of code. So we'll skip through this quickly and then come back to it a little bit. So here's iris.targetNames. And if you remember correctly, this was the names that we've been talking about this whole time, the Setosa, Virginica, Versicolor. And then we're going to go ahead and do the prediction again. We could have just set a variable equal to this instead of rerunning it each time. But we're going to go ahead and run it again, clf.predict test features. Remember that returns the 0s, the 1s, and the 2s. And then we're going to set that equal to predictions. So this time we're actually putting it in a variable. And when I run this, it distributes, it comes out as an array, and the array is Setosa, 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 Setosa. We're only looking at the first 5. We could actually let's do the first 25 just so we can see a little bit more on there. And you'll see that it starts mapping it to all the different flower types, the Versicolor and the Virginica in there. And let's see how this goes with the next one. So let's take a look at the top part of our species in here, and we'll take this code and put it in our script. And let's put that down here and paste it. There we go. And we'll go ahead and run it. And let's talk about both these sections of code here and how they go together. The first one is our predictions. And I went ahead and did predictions through 25. Let's just do 5. And so we have Setosa, Setosa, Setosa. That's what we're predicting. And then we come down here and we look at test species. I remember I could have just done test.species.head. And you'll see it says Setosa, 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 Setosa. And they match. So the first one is what our forest is doing. And the second one is what the actual data is. Now, we need to combine these so that we can understand what that means. We need to know how good our forest is, how good it is at predicting the features. So that's where we come up to the next step, which is lots of fun. We're going to use a single line of code to combine our predictions and our actuals so we have a nice chart to look at. And let's go ahead and put that in our script in our Jupyter notebook here. Let's see, let's go ahead and paste that in, and then because I'm on the Jupyter notebook, I can do a Control-, so you can see the whole line there. There we go, resize it. And let's take a look and see what's going on here. We're going to create in pandas, remember PD stands for pandas, and we're doing a crosstab. This function takes 2 sets of data and creates a chart out of them. So when I run it, you'll get a nice chart down here. And we have the predicted species. So across the top, you'll see the Setosa, Versicolor, Virginica, and the actual species, Setosa, Versicolor, Virginica. And so the way to read this chart, and let's go ahead and take a look on how to read this chart here. When you read this chart, you have Setosa where they meet, you have Versicolor where they meet, and you have Virginica where they meet. And they're meeting where the actual and the predicted agree. So this is the number of accurate predictions. So in this case, it equals 30. If you add 13 plus 5 plus 12, you get 30. And then we notice here where it says Virginica, but it was supposed to be Versicolor. This is inaccurate. So now we have two inaccurate predictions and 30 accurate predictions. So we'll say that the model accuracy is 93. That's just 30 divided by 32. And if we multiply it by 100, we can say that it is 93% accurate. So we have a 93% accuracy with our model. I did want to add one more quick thing in here on our scripting before we wrap it up. So let's flip back on over to my script. In here, we're going to take this line of code from up above. I don't know if you remember it, but predicts equals the iris.target_names. So we're going to map it to the names. And we're going to run the prediction, and we read it on test features. But, we're not just testing it, we want to actually deploy it. So at this point, I would go ahead and change this And this is an array of arrays. This is really important when you're running these to know that. So you need the double brackets, and I could actually create data. Maybe let's just do 2 flowers. So maybe I'm processing more data coming in, and we'll put 2 flowers in here. And then I actually want to see what the answer is. So let's go ahead and type in preds and print that out. And when I run this, you'll see that I've now predicted 2 flowers that maybe I measured in my front yard as versicolor and versicolor. Not surprising since I put the same data in for each one. This would be the actual end product going out to be used on data that you don't know the answer for. So that's going to conclude our scripting part of this. And let's just go ahead and take a look at the key takeaways with today's tutorial. We have solutions under classification. So we looked at where the random forest fits in the bigger model as far as supervised learning and part of the machine learning class, and in this case it's in classification. And why a random forest? The 3 main points: it has very little overfitting, if any. It has a high accuracy, and in my opinion one of the most powerful tools is it estimates missing data. We saw that with the missing color of the fruit. We talked about what is a random forest versus a tree. And then we went into how does a decision tree work, how does a random forest work, we put all those trees together, and then we took a look at some basic Python coding in the iris example.
So what is k-means clustering? K-means clustering is an unsupervised learning algorithm. In this case, you don't have labeled data, unlike in supervised learning. So you have a set of data and you want to group them. And as the name suggests, you want to put them into clusters, which means objects that are similar in nature, similar in characteristics, need to be put together. So that's what k-means clustering is all about. The term k is basically a number. So we need to tell the system how many clusters we need to perform. So if k is equal to 2, there will be 2 clusters. If k is equal to 3, it's 3 clusters, and so on and so forth. That's what the k stands for. And of course, there is a way of finding out what is the best or optimum value of k for a given data. We will look at that. So that is k-means clustering. So let's take an example. K-means clustering is used in many scenarios, but let's take an example of cricket, the game of cricket. Let's say you received data of a lot of players from maybe all over the country or all over the world, and this data has information about the runs scored by the people or by the player and the wickets taken by the player. And based on this information, we need to cluster this data into 2 clusters, batsmen and bowlers. So this is an interesting example. Let's see how we can perform this. So we have the data which consists of primarily 2 characteristics, which is the runs and the wickets. So the bowlers basically take wickets and the batsmen score runs. There will be, of course, a few bowlers who can score some runs, and similarly there will be some batsmen who would have taken a few wickets. But with this information, we want to cluster those players into batsmen and bowlers. So how does this work? Let's say this is how the data is. So there is information on the y-axis about the runs scored, and on the x-axis about the wickets taken by the players. So if we do a quick plot, this is how it would look. And when we do the clustering, we need to have the clusters like shown in the third diagram out here. So we need to have a cluster which consists of people who have scored high runs, which is basically the batsmen, and then we need a cluster with people who have taken a lot of wickets, which is typically the bowlers. There may be a certain amount of overlap, but we will not talk about it right now. So with k-means clustering, we will have here, that means k is equal to 2, and we will have 2 clusters, which is batsmen and bowlers. So how does this work? The way it works is, the first step in k-means clustering is the allocation of 2 centroids randomly. So 2 points are assigned as so-called centroids. So in this case, we want 2 clusters, which means k is equal to 2. So 2 points have been randomly assigned as centroids. Keep in mind, these points can be anywhere. They are random points. They are not really the centroids. Centroid means it's a central point of a given data set, but in this case, when it starts off, it's not really the centroid. Okay, so these points, though in our presentation here we have shown them one point closer to these data points and another closer to these data points, they can be assigned randomly anywhere. Okay, so that's the first step. The next step is to determine the distance of each of the data points from each of the randomly assigned centroids. So for example, we take this point and find the distance from this centroid and the distance from this centroid. This point is taken and the distance is found from this centroid and this centroid, and so on and so forth. So for every point, the distance is measured from both the centroids, and then whichever distance is less, that point is assigned to that centroid. So for example, in this case, visually it is very obvious that all these data points are assigned to this centroid and all these data points are assigned to this centroid. And that's what is represented here in blue color and in this yellow color. The next step is to actually determine the central point or the actual centroid for these two clusters. So we have this one initial cluster, this one initial cluster, but as you can see, these points are not really the centroid. Centroid means it should be the central position of this data set, central position of this data set. So that is what needs to be determined as the next step. So the central point or the actual centroid is determined and the original randomly allocated centroid is repositioned to the actual centroid of this new clusters. And this process is actually repeated. Now what might happen is some of these points may get reallocated. In our example, that is not happening probably, but it may so happen that the distance is found between each of these data points once again with these centroids. And if it is required, some points may be reallocated. We will see that in a later example, but for now we will keep it simple. So this process is continued till the centroid repositioning stops, and that is our final cluster. So this is so after iteration, we come to this position, this situation where the centroid doesn't need any more repositioning, and that means our algorithm has converged. Convergence has occurred, and we have the cluster, two clusters, we have the clusters with a centroid. So this process is repeated. The process of calculating the distance and repositioning the centroid is repeated till the repositioning stops, which means that the algorithm has converged and we have the final cluster with the data points and the centroids. So this is what you're going to learn from this session. We will talk about the types of clustering, what is k-means clustering, application of k-means clustering. K-means clustering is done using distance measure, so we will talk about the common distance measures, and then we will talk about how k-means clustering works and go into the details of k-means clustering algorithm, and then we will end with a demo and a use case for k-means clustering. So let's begin. First of all, what are the types of clustering? There are primarily two categories of clustering: hierarchical clustering and then partitional clustering. And each of these categories are further subdivided into agglomerative and divisive clustering and k-means and fuzzy c-means clustering. Let's take a quick look at what each of these types of clustering are. In hierarchical clustering, the clusters have a tree-like structure, and hierarchical clustering is further divided into agglomerative and divisive. Agglomerative clustering is a bottom-up approach. We begin with each element as a separate cluster and merge them into successively larger clusters. So for example, we have A, B, C, D, E, F. We start by combining B and C, form one cluster, D and E, form one more. Then we combine D, E, and F, one more bigger cluster, and then add BC to that, and then finally A to it. Compared to that, divisive clustering or divisive clustering is a top-down approach. We begin with the whole set and proceed to divide it into successively smaller clusters. So we have A, B, C, D, E, F. We first take that as a single cluster and then break it down into A, B, C, D, E, and F. Then we have partitional clustering split into two subtypes, k-means clustering and fuzzy c-means. In k-means clustering, the objects are divided into the number of clusters mentioned by the number k. That's where the k comes from. So if we say k is equal to 2, the objects are divided into two clusters, C1 and C2. And the way it is done is the features or characteristics are compared, and all objects having similar characteristics are clubbed together. So that's how k-means clustering is done. We will see it in more detail as we move forward. And fuzzy c-means is very similar to k-means in the sense that it clubs objects that have similar characteristics together, but while in k-means clustering, two objects cannot belong to, or any object, a single object cannot belong to two different clusters, in c-means objects can belong to more than one cluster. So that is the primary difference between k-means and fuzzy c-means. So what are some of the applications of k-means clustering? K-means clustering is used in a variety of examples or variety of business cases in real life, starting from academic performance, diagnostic systems, search engines, and wireless sensor networks, and many more. So let us take a little deeper look at each of these examples. Academic performance. So based on the scores of the students are categorized into A, B, C, and so on. Clustering forms a backbone of search engines. When a search is performed, the search results need to be grouped together. The search engines very often use clustering to do this. And similarly, in case of wireless sensor networks, the clustering algorithm plays the role of finding the cluster heads, which collects all the data in its respective cluster. So clustering, especially k-means clustering, uses distance measure. So let's take a look at what is distance measure. So while these are the different types of clustering, in this video we will focus on k-means clustering. So distance measure tells how similar some objects are. So the similarity is measured using what is known as distance measure. And what are the various types of distance measures? There is Euclidean distance, there is Manhattan distance, then we have squared Euclidean distance measure and cosine distance measure. These are some of the distance measures supported by k-means clustering. Let's take a look at each of these. What is Euclidean distance measure? This is nothing but the distance between 2 points. So we have learnt in high school how to find the distance between 2 points. This is a little sophisticated formula for that, but we know a simpler one is square root of y2 minus y1 whole square plus x2 minus x1 whole square. So this is an extension of that formula. So that is the Euclidean distance between 2 points. What is the squared Euclidean distance measure? It's nothing but the square of the Euclidean distance, as the name suggests. So instead of taking the square root, we leave the square as it is. And then we have Manhattan distance measure. In case of Manhattan distance, it is the sum of the distances across the x-axis and the y-axis. And note that we are taking the absolute value so that the negative values don't come into play. So that is the Manhattan distance measure. Then we have cosine distance measure. In this case, we take the angle between the two vectors formed by joining the points from the origin. So that is the cosine distance measure. Okay, so that was a quick overview about the various distance measures that are supported by k-means. Now let's go and check how exactly k-means clustering works. Okay, so this is how k-means clustering works. This is like a flowchart of the whole process. There is a starting point, and then we specify the number of clusters that we want. Now there are a couple of ways of doing this. We can do by trial and error. So we specify a certain number, maybe k is equal to 3 or 4 or 5 to start with, and then as we progress we keep changing until we get the best clusters. Or there is a technique called elbow technique, whereby we can determine the value of k. What should be the best value of k? How many clusters should be formed? So once we have the value of k, we specify that, and then the system will assign that many centroids. So it picks randomly that to start with randomly that many points that are considered to be the centroids of these clusters. And then it measures the distance of each of the data points from these centroids and assigns those points to the corresponding centroid from which the distance is minimum. So each data point will be assigned to the centroid which is closest to it. And thereby we have k number of initial clusters. However, this is not the final clusters. The next step it does is for the new groups, for the clusters that have been formed, it calculates the mean position, thereby calculates the new centroid position. The position of the centroid moves compared to the randomly allocated one. So it's an iterative process. Once again, the distance of each point is measured from this new centroid point, and if required, the data points are reallocated to the new centroids, and the mean position or the new centroid is calculated once again. If the centroid moves, then the iteration continues, which means the convergence has not happened. The clustering has not converged. So as long as there is a movement of the centroid, this iteration keeps happening. But once the centroid stops moving, which means that the cluster has converged or the clustering process has converged, that will be the end result. So now we have the final position of the centroid, and the data points are allocated accordingly to the closest centroid. I know it's a little difficult to understand from this simple flowchart, so let's do a little bit of visualization and see if we can explain it better. Let's take an example. If we have a data set for a grocery shop. So let's say we have a data set for a grocery shop, and now we want to find out how many clusters this has to be spread across. So how do we find the optimum number of clusters? There is a technique called the elbow method. So when these clusters are formed, there is a parameter called within sum of squares. And the lower this value is, the better the cluster is. That means all these points are very close to each other. So we use this within sum of squares as a measure to find the optimum number of clusters that can be formed for a given data set. So we create clusters, or we let the system create clusters of a variety of numbers, maybe of 10 clusters, and for each value of k, the within SS is measured, and the value of k which has the least amount of within SS or WSS, that is taken as the optimum value of k. So this is the diagrammatic representation. So we have on the y-axis the within sum of squares or WSS, and on the x-axis we have the number of clusters. So as you can imagine, if you have k is equal to 1, which means all the data points are in a single cluster, the within SS value will be very high because they are probably scattered all over. The moment you split it into 2, there will be a drastic fall in the within SS value. And that's what is represented here. But then as the value of k increases, the rate of decrease will not be so high. It will continue to decrease, but probably the rate of decrease will not be high. So that gives us an idea. So from here, we get an idea, for example, the optimum value of k should be either 2 or 3 or at the most 4. But beyond that, increasing the number of clusters is not dramatically changing the value in WSS because that pretty much gets stabilized. Okay, now that we have got the value of k, and let's assume that these are our delivery points, the next step is basically to assign two centroids randomly. So let's say C1 and C2 are the centroids assigned randomly. Now the distance of each location from the centroid is measured, and each point is assigned to the centroid which is closest to it. So for example, these points are very obvious that these are closest to C1, whereas this point is far away from C2. So these points will be assigned, which are close to C1 will be assigned to C1, and these points or locations which are close to C2 will be assigned to C2. And then, so this is how the initial grouping is done. This is part of C1 and this is part of C2. Then the next step is to calculate the actual centroid of this data, because remember, C1 and C2 are not the centroids. They've been randomly assigned points, and only thing that has been done was the data points which are closest to them have been assigned to them. But now in this step, the actual centroid will be calculated, which may be for each of these data sets somewhere in the middle. So that's like the mean point that will be calculated. And the centroid will actually be positioned or repositioned there. Same with C2. So the new centroid for this group is C2 in this new position, and C1 is in this new position. Once again, the distance of each of the data points is calculated from these centroids. Now remember, it's not necessary that the distance still remains or each of these data points still remain in the same group. By recalculating the distance, it may be possible that some points get reallocated. Like so. You see this? So this point earlier was closer to C2 because C2 was here. But after recalculating, repositioning, it is observed that this is closer to C1 than C2. So this is the new grouping. So some points will be reassigned. And again, the centroid will be calculated, and if the centroid doesn't change, so that is a repetitive process, iterative process. And if the centroid doesn't change, once the centroid stops changing, that means the algorithm has converged. And this is our final cluster with this as the centroid, C1 and C2 as the centroids, these data points as a part of each cluster. So I hope this helps in understanding the whole process, iterative process of k-means clustering. So let's take a look at the k-means clustering algorithm. Let's say we have x1, x2, x3, n number of points as our inputs, and we want to split this into k clusters, or we want to create k clusters. So the first step is to randomly pick k points and call them centroids. They are not real centroids because centroid is supposed to be a center point, but they are just called centroids. And we calculate the distance of each and every input point from each of the centroids. So the distance of x1 from C1, from C2, C3, each of the distances we calculate. And then find out which distance is the lowest and assign x1 to that particular random centroid. Repeat that process for x2. Calculate its distance from each of the centroids C1, C2, C3 up to Ck, and find which is the lowest distance and assign x2 to that particular centroid. Same with x3 and so on. So that is the first round of assignment that is done. Now we have k groups because we have assigned the value of k. So there are k centroids, and so there are k groups. All these inputs have been split into k groups. However, remember, we pick the centroids randomly, so they are not real centroids. So now what we have to do? We have to calculate the actual centroids for each of these groups, which is like the mean position. Which means that the position of the randomly selected centroids will now change, and they will be the mean positions of these newly formed k groups. And once that is done, we once again repeat this process of calculating the distance, right? So this is what we are doing as a part of step 4. We repeat step 2 and 3. So we again calculate the distance of x1 from the centroid C1, C2, C3, and then see which is the lowest value and assign x1 to that. Calculate the distance of x2 from C1, C2, C3 or whatever up to Ck, and find whichever is the lowest distance and assign x2 to that centroid, and so on. In this process, there may be some reassignment. x1 was probably assigned to cluster C2, and after doing this calculation, maybe now x1 is assigned to C1. So that kind of reallocation may happen. So we repeat the steps 2 and 3 till the position of the centroids don't change or stop changing. And that's when we have convergence. So let's take a detailed look at each of these steps. So we randomly pick k cluster centers. We call them centroids because they are not really the centroids. So let us name them C1, C2 up to Ck. And then step 2, we assign each data point to the closest center. So what we do, we calculate the distance of each x value from each c value. So the distance between x1, c1, distance between x1, c2, x1, c3, and then we find which is the lowest value, right? That's the minimum value we find, and assign x1 to that particular centroid. Then we go next to x2. Find the distance of x2 from C1, x2 from C2, x2 from C3, and so on up to ck, and then assign it to the point or to the centroid which has the lowest value, and so on. So that is step number 2. In step number 3, we now find the actual centroid for each group. So what has happened? As a part of step number 2, we now have all the points, all the data points grouped into k groups, because we wanted to create k clusters, right? So we have k groups, each one may be having a certain number of input values. They need not be equally distributed, by the way. Based on the distance, we will have k groups. But remember, the initial values of the C1, C2 were not really the centroids of these groups, right? We assigned them randomly. So now in step 3, we actually calculate the centroid of each group, which means the original point which we thought was the centroid will shift to the new position, which is the actual centroid for each of these groups. Okay, and we again calculate the distance. So we go back to step 2, which is what? We calculate again the distance of each of these points from the newly positioned centroids, and if required, we reassign these points to the new centroids. So as I said earlier, there may be a reallocation. So we now have a new set or a new group. We still have k groups, but the number of items and the actual assignment may be different from what was in step 2 here. Okay, so that might change. Then we perform step 3 once again to find the new centroid of this new group. So we have again a new set of clusters, new centroids, and new assignments. We repeat this step 2 again. Once again we find, and then it is possible that after iterating through 3 or 4 or 5 times, the centroid will stop moving, in the sense that when you calculate the new value of the centroid, that will be same as the original value, or there will be very marginal change. So that is when we say convergence has occurred, and that is our final cluster. That's the formation of the final cluster. Alright, so let's see a couple of demos of k-means clustering. We will actually see some live demos in Python Notebook, using Python Notebook. But before that, let's find out what's the problem that we are trying to solve. The problem statement is, let's say Walmart wants to open a chain of stores across the state of Florida, and it wants to find the optimal store locations. Now the issue here is, if they open too many stores close to each other, obviously they will not make profit. But if the stores are too far apart, then they will not have enough sales. So how do they optimize this? Now, for an organization like Walmart, which is an e-commerce giant, they already have the addresses of their customers in their database. So they can actually use this information or this data and use k-means clustering to find the optimal location. Now, before we go into the Python Notebook and show you the live code, I wanted to take you through very quickly a summary of the code in the slides, and then we will go into the Python Notebook. So in this block, we are basically importing all the required libraries like NumPy, Matplotlib, and so on. And we are loading the data that is available in the form of, let's say, the addresses. For simplicity's sake, we will just take them as some data points. Then the next thing we do is quickly do a scatter plot to see how they are related to each other with respect to each other. So in the scatter plot, we see that there are a few distinct groups already being formed. So you can actually get an idea about how the cluster would look and how many clusters, what is the optimal number of clusters. And then starts the actual k-means clustering process. So we will assign each of these points to the centroids and then check whether they are the optimal distance, which is the shortest distance, and assign each of the data points to the centroids, and then go through this iterative process till the whole process converges. And finally, we get an output like this. So we have 4 distinct clusters, and which is, we can say that this is how the population is probably distributed across Florida state, and the centroids are like the location where the store should be, the optimum location where the store should be. So that's the way we determine the best locations for the store, and that's how we can help Walmart find the best locations for their stores in Florida. So now let's take this into Python notebook. Let's see how this looks when we are running the code live. Alright, so this is the code for k-means clustering in Jupyter Notebook. We have a few examples here which we will demonstrate how k-means clustering is used, and even there is a small implementation of k-means clustering as well. Okay, so let's get started. Okay, so this block is basically importing the various libraries that are required, like matplotlib and numpy and so on and so forth, which would be used as a part of the code. Then we are going and creating blobs which are similar to clusters. Now this is a very neat feature which is available in scikit-learn. Make blobs is a nice feature which creates clusters of data sets. So that's a wonderful functionality that is readily available for us to create some test data kind of thing. Okay, so that's exactly what we are doing here. We are using make blobs, and we can specify how many clusters we want. So centers we are mentioning here. So it will go ahead, and so we just mentioned 4. So it will go ahead and create some test data for us. And this is how it looks. As you can see, visually also we can figure out that there are 4 distinct classes or clusters in this data set. And that is what make blobs actually provides. Now, from here onwards, we will basically run the standard k-means functionality that is readily available. So we really don't have to implement k-means itself. The k-means functionality or the function is readily available. You just need to feed the data and we'll create the clusters. So this is the code for that. We import k-means, and then we create an instance of k-means, and we specify the value of k. This n underscore clusters is the value of k. Remember, k-means, in k-means, k is basically the number of clusters that you want to create, and it is a integer value. So this is where we are specifying that. So we have k is equal to 4, and so that instance is created. We take that instance, and as with any other machine learning functionality, fit is what we use. The function, or the method rather, fit is what we use to train the model. Here there is no real training kind of thing, but that's the call. Okay, so we are calling fit, and what we are doing here, we are just passing the data. So x has these values, the data that has been created, right? So that is what we are passing here. And this will go ahead and create the clusters, and then we are using, after doing fit, we run the predict, which basically assigns for each of these observations which cluster it belongs to. All right, so it will name the clusters. Maybe this is cluster 1, this is 2, 3, and so on, or I will actually start from 0. Cluster 0, 1, 2, and 3 maybe, and then for each of the observations, it will assign based on which cluster it belongs to, it will assign a value. So that is stored in y underscore k-means. When we call predict, that is what it does. And we can take a quick look at these y underscore k-means, or the cluster numbers that have been assigned for each observation. So this is the cluster number assigned for observation 1, maybe this is for observation 2, observation 3, and so on. So we have how many? About, I think, 300 samples, right? So all the 300 samples, there are 300 values here. Each of them, the cluster number is given, and the cluster number goes from 0 to 3. So there are 4 clusters, so the numbers go from 0, 1, 2, 3. So that's what is seen here. Okay, now, so this was a quick example of generating some dummy data and then clustering that.
Okay, and this can be applied if you have proper data. You can just load it up into X, for example, here, and then run the k-means. So this is the central part of the k-means clustering program example. So you basically create an instance and you mention how many clusters you want by specifying this parameter n_clusters, and that is also the value of k, and then pass the data to get the values. Now, the next section of this code is the implementation of a k-means. Now, this is kind of a rough implementation of the k-means algorithm. So we will just walk you through. I will walk you through the code at each step what it is doing, and then we will see a couple of more examples of how k-means clustering can be used in maybe some real life examples, real life use cases. All right. So in this case here, what we are doing is basically implementing the k-means clustering, and there is a function or a library calculates for a given two pairs of points. It will calculate the distance between them and see which one is the closest and so on. So this is pretty much like what k-means does, right? So it calculates the distance of each point or each data set from predefined centroid, and then based on whichever is the lowest, this particular data point is assigned to that centroid. So that is basically available as a standard function, and we will be using that here. So as explained in the slides, the first step that is done in case of k-means clustering is to randomly assign some centroids. So as a first step, we randomly allocate a couple of centroids, which we are calling as centers. And then we put this in a loop and we take it through an iterative process. For each of the data points, we first find out using this function pairwise distance argument. For each of the points, we find out which center or which randomly selected centroid is the closest, and accordingly we assign that data or the data point to that particular centroid or cluster. And once that is done for all the data points, we calculate the new centroid by finding out the mean position with the center position, right? So we calculate the new centroid, and then we check if the new centroid is the coordinates or the position is the same as the previous centroid. The positions we will compare, and if it is the same, that means the process has converged. So remember, we do this process till the centroids or the centroid doesn't move anymore, right? So the centroid gets relocated each time this reallocation is done. So the moment it doesn't change anymore, the position of the centroid doesn't change anymore, we know that convergence has occurred. So till then, so you see here, this is like an infinite loop. While true is an infinite loop. It only breaks when the centers are the same. The new center and the old center positions are the same. And once that is done, we return the centers and the labels. Now, of course, as explained, this is not a very sophisticated and advanced implementation, very basic implementation, because one of the flaws in this is that sometimes what happens is the centroid, the position will keep moving, but the change will be very minor. So in that case, also that is actually convergence, right? So for example, the change is 0.0001. We can consider that as convergence. Otherwise, what will happen is this will either take forever or it will be never ending. So that's a small flaw here. So that is something, additional checks may have to be added here. But again, as mentioned, this is not the most sophisticated implementation. This is like a kind of a rough implementation of the k-means clustering. Okay, so if we execute this code, this is what we get as the output. So this is the definition of this particular function, and then we call that find_clusters, and we pass our data x and the number of clusters, which is 4. And if we run that and plot it, this is the output that we get. So this is, of course, each cluster is represented by a different color. So we have a cluster in green color, yellow color, and so on and so forth. And these big points here, these are the centroids. This is the final position of the centroids. And as you can see visually also, this appears like a kind of a center of all these points here, right? Similarly, this is like the center of all these points here, and so on. So this is the example, or this is an example of an implementation of k-means clustering. And next we will move on to see a couple of examples of how k-means clustering is used in maybe some real life scenarios or use cases. In the next example or demo, we are going to see how we can use k-means clustering to perform color compression. We will take a couple of images, so there will be two examples, and we will try to use k-means clustering to compress the colors. This is a common situation in image processing when you have an image with millions of colors, but then you cannot render it on some devices which may not have enough memory. So that is the scenario where something like this can be used. So before again we go into the Python notebook, let's take a look at quickly the code. As usual, we import the libraries and then we import the image, and then we will flatten it. So the reshaping is basically we have the image information is stored in the form of pixels, and if the image is like, for example, 427 by 640 and it has 3 colors, so that's the overall dimension of the initial image. We just reshape it and then feed this to our algorithm, and this will then create clusters of only 16 clusters. So this colors, there are millions of colors, and now we need to bring it down to 16 colors. So we use k is equal to 16, and this is how, when we visualize, this is how it looks. These are all about 16 million possible colors. The input color space has 16 million possible colors, and we just compress it to 16 colors. So this is how it would look when we compress it to 16 colors, and this is how the original image looks, and after compression to 16 colors, this is how the new image looks. As you can see, there is not a lot of information that has been lost, though the image quality is definitely reduced a little bit. So this is an example which we are going to now see in Python notebook. Let's go into the Python notebook. And once again, as always, we will import some libraries and load this image called flower.jpg. Okay, so we'll load that, and this is how it looks. This is the original image, which has, I think, 16 million colors, and this is the shape of this image, which is basically, what is the shape is nothing but the overall size, right? So this is 427 pixel by 640 pixel, and then there are 3 layers, which is this 3 basically is for RGB, which is red, green, blue. So color image will have that, right? So that is the shape of this. Now what we need to do is data. Let's take a look at how data is looking. So let me just create a new cell and show you what is in data. Basically, we have captured this information. So data is what, let me just show you here. All right, so let's take a look at China. What are the values in China? And if we see here, this is how the data is stored. This is nothing but the pixel values. Okay, so this is like a matrix, and each one has about for this 427 by 640 pixels. All right, so this is how it looks. Now the issue here is these values are large, the numbers are large, so we need to normalize them to between 0 and 1. Right, so that's why we will basically create one more variable, which is data, which will contain the values between 0 and 1, and the way to do that is divide by 255. So we divide China by 255 and we get the new values in data. So let's just run this piece of code, and this is the shape. So we now have also, what we have done is we changed using reshape, we converted into the 3-dimensional into a 2-dimensional data set. And let us also take a look at how, let me just insert probably a cell here and take a look at how data is looking. All right, so this is how data is looking, and now you see this is the values are between 0 and 1. right? So if you earlier noticed, in case of China, the values were large numbers. Now everything is between 0 and 1. This is one of the things we need to do. All right, so after that, the next thing that we need to do is to visualize this, and we can take random set of maybe 10,000 points and plot it and check and see how this looks. So let us just plot this. And so this is how the original, the color, the pixel distribution is. These are two plots. One is red against green and another is red against blue, and this is the original distribution of the color. So then what we will do is we will use k-means clustering to create just 16 clusters for the various colors and then apply that to the image. Now what will happen is, since the data is large because there are millions of colors, using regular k-means may be a little time consuming. So there is another version of k-means which is called mini batch k-means. So we will use that, which processes in, the overall concept remains the same, but this basically processes it in smaller batches. That's the only thing. Okay, so the results will pretty much be the same. So let's go ahead and execute this piece of code and also visualize this so that we can see that there are these. This is how the 16 colors would look. So this is red against green and this is red against blue. There is quite a bit of similarity between this original color schema and the new one, right? So it doesn't look very completely different or anything like that. Now we apply the newly created colors to the image, and we can take a look how this is looking now. We can compare both the images. So this is our original image and this is our new image. So as you can see, there is not a lot of information that has been lost. It pretty much looks like the original image. Yes, we can see that, for example, here there is a little bit, it appears a little dullish compared to this one, right? Because we kind of took off some of the finer details of the color, but overall the high level information has been maintained. At the same time, the main advantage is that now this is an image which can be rendered on a device which may not be that very sophisticated. Now let's take one more example with a different image. In the second example, we will take an image of the Summer Palace in China, and we repeat the same process. This is a high definition color image with millions of colors and also three-dimensional. Now we will reduce that to 16 colors using k-means clustering, and we do the same process like before. We reshape it and then we cluster the colors to 16, and then we render the image once again, and we will see that the quality of the image slightly deteriorates. As you can see here, this has much finer details in this which are probably missing here, but then that's the compromise because there are some devices which may not be able to handle this kind of high density images. So let's run this code in Python notebook. Alright, so let's apply the same technique for another picture which is even more intricate and has probably much complicated color schema. So this is the image. Now once again, we can take a look at the shape, which is 427 by 640 by 3. And this is the new data would look somewhat like this compared to the flower image. So we have some new values here, and we will also bring this. As you can see, the numbers are much big, so we will much bigger, so we will now have to scale them down to values between 0 and 1, and that is done by dividing by 255. So let's go ahead and do that and reshape it. Okay, so we get a two-dimensional matrix, and we will then, as a next step, we will go ahead and visualize this, how it looks, the 16 colors, and this is basically how it would look, 16 million colors. And now we can create the clusters out of this. The 16 k-means clusters we will create. So this is how the distribution of the pixels would look with 16 colors. And then we go ahead and apply this and visualize how it is looking for with the new just the 16 colors. So once again, as you can see, this looks much richer in color, but at the same time, and this probably doesn't have, as we can see, it doesn't look as rich as this one, but nevertheless the information is not lost, the shape and all that stuff. And this can be also rendered on a device which is probably not that sophisticated. Okay, so that's pretty much it. So we have seen two examples of how color compression can be done using k-means clustering, and we have also seen in the previous examples of how to implement k-means, the code to roughly how to implement k-means clustering, and we use some sample data using blob to just execute the k-means clustering. All right, so with that, let's move on. So let's summarize what we have learned in this video. We started with an example of how we can apply k-means clustering, taking the cricket example. Then we understood what are the types of clustering, two major categories, hierarchical clustering and partitional clustering, which in turn had two subcategories, agglomerative and divisive, and then k-means and fuzzy C. Then we understood the distance measures, what are the different types of distance measures supported by k-means clustering, and we focused on k-means clustering. We talked about its applications and how exactly the process flow works for the k-means clustering, and then finally we ended up with a demo and a couple of use cases.
If you are an aspiring data scientist who's looking out for online training and certification in data science from the best universities and industry experts, then search no more. Simplilearn's postgraduate program in data science from Caltech University in collaboration with IBM should be the right choice. For more details on this program, please use the link in the description box below.
Have you ever wondered how your mail provider implements spam filtering, or how online news channels perform news text classification, or how companies perform sentimental analysis of their audience on social media? All of this and more is done through a machine learning algorithm called Naive Bayes Classifier. Welcome to Naive Bayes Tutorial. My name is Richard Kirshner. I'm with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. What's in it for you? We'll start with what is Naive Bayes, a basic overview of how it works. We'll get into Naive Bayes and machine learning, where it fits in with our other machine learning tools. Why do we need Naive Bayes? And understanding Naive Bayes Classifier, a much more in-depth of how the math works in the background. Finally, we'll get into the advantages of the Naive Bayes Classifier in the machine learning setup. And then we'll roll up our sleeves and do my favorite part. We'll actually do some Python coding and do some text classification using the Naive Bayes. What is Naive Bayes? Let's start with a basic introduction to the Bayes theorem, named after Thomas Bayes from the 1700s, who first coined this in the Western literature. Naive Bayes classifier works on the principle of conditional probability as given by the Bayes theorem. Before we move ahead, let us go through some of the simple concepts in the probability that we will be using. Let us consider the following example of tossing two coins. Here we have two quarters, and if we look at all the different possibilities of what they can come up as, we get that they can come up as head-heads, they can come up as head-tail, tail-head, and tail-tail. When doing the math on probability, we usually denote probability as a P, a capital P. So the probability of getting two heads equals 1/4. You can see on our data set we have two heads, and this occurs once out of the four possibilities. And then the probability of at least one tail occurs 3/4 of the time. You'll see on 3 of the coin tosses we have tails in them, and out of 4 that's 3/4. And then the probability of the second coin being head given the first coin is tail is 1/2, and the probability of getting two heads given the first coin is a head is 1/2. We'll demonstrate that in just a minute and show you how that math works. Now when we're doing it with two coins it's easy to see, but when you have something more complex you can see where these formulas really come in and work. So the Bayes theorem gives us the conditional probability of an event A given another event B has occurred. In this case, the first coin toss will be B and the second coin toss A. This could be confusing because we've actually reversed the order of them and go from B to A instead of A to B. You'll see this a lot when you work in probabilities. The reason is we're looking for event A. We want to know what that is. So we're going to label that A since that's our focus. And then given another event B has occurred. In the Bayes theorem, as you can see on the left, the probability of A occurring given B has occurred equals the probability of B occurring given A has occurred times the probability of A over the probability of B. This simple formula can be moved around just like any algebra formula. And we could do the probability of A after a given B times probability of B equals the probability of B given A times probability of A. You can easily move that around and multiply it and divide it out. Let us apply Bayes' theorem to our example. Here we have our 2 quarters, and we'll notice that the first 2 probabilities of getting 2 heads and at least 1 tail we compute directly off the data. So you can easily see that we have one example, HH, out of 4, 1/4, and we have 3 with tails in them, giving us 3/4, or 3/4, 75%. The second condition, the second set, 3 and 4, we're going to explore a little bit more in detail. Now we stick to a simple example with 2 coins because you can easily understand the math. The probability of throwing a tail doesn't matter what comes before it, and the same with the heads. So it's still going to be 50% or 1/2. But when that probability gets more complicated, let's say you have a D6 dice or some other instance, then this formula really comes in handy. But let's stick to the simple example for now. In this sample space, let A be the event that the second coin is head and B be the event that the first coin is tails. Again, we reversed it because we want to know what the second event's going to be, so we're going to be focusing on A. And we write that out as the probability of A given B. And we know this from our formula that equals the probability of B given A times the probability of A over the probability of B. And when we plug that in, we plug in the probability of the first coin being tails given the second coin is heads, and the probability of the second coin being heads given the first coin being over the probability of the first coin being tails. When we plug that data in, and we have the probability of the first coin being tails given the second coin is heads times the probability of the second coin being heads over the probability of the first coin being tails. You can see it's a simple formula to calculate. We have 1/2 times 1/2 over 1/2, or 1/2 equals 0.5, or 1/4. So the Bayes' theorem basically calculates the conditional probability of the occurrence of an event based on prior knowledge of conditions that might be related to the event. We will explore this in detail when we take up an example of online shopping further in this tutorial. Understanding naive Bayes and machine learning. Like with any of our other machine learning tools, it's important to understand where the naive Bayes fits in the hierarchy. So under the machine learning, we have supervised learning, and there is other things like unsupervised learning. There's also a reward system. This falls under the supervised learning. And then under the supervised learning, there's classification. There's also regression, but we're going to be in the classification side. And then under classification is your naive Bayes. Let's go ahead and glance into where is naive Bayes used. Let's look at some of the use scenarios for it. As a classifier, we use it in face recognition. Is this Cindy or is it not Cindy or whoever? Or it might be used to identify parts of the face that they then feed into another part of the face recognition program. This is the eye, this is the nose, this is the mouth. Weather prediction, is it going to be rainy or sunny? Medical recognition, news prediction. It's also used in medical diagnosis. We might diagnose somebody as either as high risk or not as high risk for cancer or heart disease or other ailments. And news classification. When you look at the Google News and it says, well, is this political or is this world news? Or a lot of that's all done with the naive Bayes. Understanding naive Bayes classifier. Now, we already went through a basic understanding with the coins and the 2 heads and 2 tails and head tail, tail heads, etc. We're going to do just a quick review on that and remind you that the naive Bayes classifier is based on the Bayes theorem, which gives a conditional probability of event A given event B. And that's where the probability of A given B equals the probability of B given A times probability of A over probability of B. Remember, this is an algebraic function, so we can move these different entities around. We can multiply by the probability of B, so it goes to the left-hand side, and then we could divide by the probability of A given B, and just as easily come up with a new formula for the probability of B. To me, staring at these algebraic functions kind of gives me a slight headache. It's a lot better to see if we can actually understand how this data fits together in a table. And let's go ahead and start applying it to some actual data so you can see what that looks like. So we're going to start with the shopping demo problem statement. And remember, we're going to solve this first in table form so you can see what the math looks like, and then we're going to solve it in Python. And in here we want to predict whether the person will purchase a product. Are they going to buy or don't buy? Very important if you're running a business, you want to know how to maximize your profits, or at least maximize the purchase of the people coming into your store. And we're going to look at a specific combination of different variables. In this case, we're going to look at the day, the discount, and the free delivery. And you can see here under the day, we want to know whether it's on the weekday. You know, somebody's working, they come in after work, or maybe they don't work. Weekend, you can see the bright colors coming down there, celebrating not being in work, or holiday. And did we offer a discount that day? Yes or no? Did we offer free delivery that day? Yes or no? And from this, we want to know whether the person's going to buy based on these traits so we can maximize them and find out the best system for getting somebody to come in and purchase our goods and products from our store. Now, having a nice visual is great, but we do need to dig into the data. So let's go ahead and take a look at the data set. We have a small sample data set of 30 rows. We're showing you the first 15 of those rows for this demo. Now, the actual data file you can request. Just type in below under the comments on the YouTube video, and we'll send you some more information and send you that file. As you can see here, the file is very simple, columns and rows. We have the day, the discount, the free delivery, and did the person purchase or not. And then we have under the day whether it was a weekday, a holiday, was it the weekend. This is a pretty simple set of data, and long before computers, people used to look at this data and calculate this all by hand. So let's go ahead and walk through this and see what that looks like when we put that into tables. Also note, in today's world, we're not usually looking at 3 different variables in 30 rows. Nowadays, because we're able to collect data so much, we're usually looking at 27, 30 variables across hundreds of rows. The first thing we want to do is we're going to take this data and based on the data set containing our 3 inputs, day, discount, and free delivery, we're going to go ahead and populate that to frequency tables for each attribute. So we want to know if they had a discount, how many people buy and did not buy. Did they have a discount, yes or no? Did we have a free delivery, yes or no? On those days, how many people made a purchase, how many people didn't? And the same with the 3 days of the week. Was it a weekday, a weekend, a holiday? And did they buy, yes or no? As we dig in deeper to this table for our Bayes theorem, let the event buy be A. Now remember, when we looked at the coins, I said we really want to know what the outcome is. Did the person buy or not? And that's usually event A is what you're looking for. And the independent variables, discount, free delivery, and day, be B. So we'll call that probability of B. Now let us calculate the likelihood table for one of the variables. Let's start with day, which includes weekday, weekend, and holiday. And let us start by summing all of our rows. So we have the weekday row, and out of the weekdays there's 9 plus 2, so it's 11 weekdays. There's 8 weekend days and 11 holidays. Wow, that's a lot of holidays. And then we want to sum up the total number of days. So we're looking at a total of 30 days. Let's start pulling some information from our chart and see where that takes us. And when we fill in the chart on the right, you can see that 9 out of 24 purchases are made on the weekday, 7 out of 24 purchases on the weekend, and 8 out of 24 purchases on a holiday. And out of all the people who come in, 24 out of 30 purchase. You can also see how many people do not purchase. On the weekday, it's 2 out of 6 didn't purchase, and so on and so on. We can also look at the totals, and you'll see on the right we put together some of the formulas. The probability of making a purchase on the weekend comes out at 11 out of 30. So out of the 30 people who came into the store throughout the weekend, weekday, and holiday, 11 of those purchases were made on the weekday. And then you can also see the probability of them not making a purchase. And this is done for, doesn't matter which day of the week. So we call that probability of no buy. It would be 6 over 30 or 0.2. So there's a 20% chance that they're not going to make a purchase no matter what day of the week it is. And finally, we look at the probability of B if A. In this case, we're going to look at the probability of the weekday and not buying. 2 of the no buys were done out of the weekend out of the 6 people who did not make purchases. So when we look at that, probability of the weekday without a purchase is going to be 0.33 or 33%. Let's take a look at this at different probabilities, and based on this likelihood table, let's go ahead and calculate conditional probabilities as below. The first 3 we just did. The probability of making a purchase on the weekday is 11 out of 30, or roughly 36 or 37%, 0.367. The probability of not making a purchase at all, doesn't matter what day of the week, is roughly 0.2 or 20%. And the probability of a weekday no purchase is roughly 2 out of 6. So 2 out of 6 of our no purchases were made on the weekday. And then finally we take our P of AB. If you look, we've kept the symbols up there. We got P of probability of B, probability of A, probability of B if A. We should remember that the probability of A if B is equal to the first one times the probability of no buys over the probability of the weekday. So we could calculate it both off the table we created. We can also calculate this by the formula, and we get the 0.367 which equals, or 0.33 times 0.2 over 0.367, which equals 0.179, or roughly 17 to 18%. And that'd be the probability of no purchase done on the weekday. And this is important because we can look at this and say, as the probability of buying on the weekday is more than the probability of not buying on the weekday, we can conclude that customers will most likely buy the product on a weekday. Now, we've kept our chart simple and we're only looking at one aspect. So you should be able to look at the table and come up with the same information or the same conclusion. That should be kind of intuitive at this point. Next, we can take the same setup. We have the frequency tables of all three independent variables. Now we can construct the likelihood tables for all three of the variables we're working with. We can take our day like we did before. We have weekday, weekend, and holiday. We filled in this table. And then we can come in and also do that for the discount, yes or no. Did they buy, yes or no? And we fill in that full table. So now we have our probabilities for a discount and whether the discount leads to a purchase or not, and the probability for free delivery. Does that lead to a purchase or not? And this is where it starts getting really exciting. Let us use these three likelihood tables to calculate whether a customer will purchase a product on a specific combination of day, discount, and free delivery, or not purchase. Here, let us take a combination of these factors. Day equals holiday, discount equals yes, free delivery equals yes. Let's dig deeper into the math and actually see what this looks like. And we're going to start with looking for the probability of them not purchasing on the following combinations of days. We're actually looking for the probability of A equal no buy, no purchase. And our probability of B we're going to set equal to, is it a holiday? Did they get a discount? Yes. And was it a free delivery? Yes. Before we go further, let's look at the original equation. The probability of A if B equals the probability of B given the condition A and the probability times the probability of A over the probability of B occurring. Now this is basic algebra, so we can multiply this information together. So when you see the probability of A given B, in this case the condition is B, C, and D, or the three different variables we're looking at. And when you see the probability of B, that would be the conditions. We're actually going to multiply those three separate conditions out. Probability of, you'll see that in just a second in the formula, times the full probability of A over the full probability of B. So here we are back to this, and we're going to have let A equal no purchase, and we're looking for the probability of B on the condition A, where A sets for three different things. Remember that equals the probability of A given the condition B. And in this case, we just multiply those three different variables together. So we have the probability of the discount times the probability of free delivery times the probability is the day equal a holiday. Those are our three variables of the probability of A if B. And then that is going to be multiplied by the probability of them not making a purchase. And then we want to divide that by the total probabilities, and they're multiplied together. So we have the probability of a discount, the probability of a free delivery, and the probability of it being on a holiday. When we plug those numbers in, we see that 1 out of 6 were no purchase on a discounted day, 2 out of 6 were a no purchase on a free delivery day, and 3 out of 6 were a no purchase on a holiday. Those are our three probabilities of A if B multiplied out. And then that has to be multiplied by the probability of a no purchase. And remember, the probability of a no buy is across all the data. So that's where we get the 6 out of 30. We divide that out by the probability of each category over the total number. So we get the 20 out of 30 had a discount, 23 out of 30 had a yes for free delivery, and 11 out of 30 were on a holiday. We plug all those numbers in, we get 0.178. So in our probability math, we have a 0.178 if it's a no buy for a holiday, a discount, and a free delivery. Let's turn that around and see what that looks like if we have a purchase. I promise this is the last page of math before we dig into the Python script. So here we're calculating the probability of the purchase using the same math we did to find out if they didn't buy. Now we want to know if they did buy. And again, we're going to go by the day equals a holiday, discount equals yes, free delivery equals yes, and let A equal buy. Now right about now you might be asking, why are we doing both calculations? Why would we want to know the no buys and buys for the same data going in? Well, we're going to show you that in just a moment, but we have to have both of those pieces of information so that we can figure it out as a percentage as opposed to a probability equation. And we'll get to that normalization here in just a moment. Let's go ahead and walk through this calculation. And as you can see here, the probability of A on the condition of B being all three categories. Did we have a discount with a purchase? Did we have a free delivery with a purchase? And is a day equal to holiday? And when we plug this all into that formula and multiply it all out, we get our probability of a discount, probability of a free delivery, probability of the day being a holiday, times the overall probability of it being a purchase, divided by, again multiplying the three variables out, the full probability of there being a discount, the full probability of being a free delivery, and the full probability of there being a day equal holiday. And that's where we get this 19 over 24 times 21 over 24 times 8 over 24 times the P of A, 24 over 30, divided by the probability of the discount, the free delivery times the day, or 20 over 30, 23 over 30 times 11 over 30, and that gives us our 0.986. So, what are we going to do with these two pieces of data we just generated? Well, let's go ahead and go over them. We have a probability of purchase equals 0.986. We have a probability of no purchase equals 0.178. So, finally, we have a conditional probabilities of purchase on this day. Let us take that, we're going to normalize it, and we're going to take these probabilities and turn them into percentages. This is simply done by taking the sum of probabilities, which equals 0.986 plus 0.178, and that equals the 1.164. If we divide each probability by the sum, we get the percentage. And so the likelihood of a purchase is 84.71%, and the likelihood of no purchase is 15.29%, given these three different variables. So if it's on a holiday, if it's with a discount and has free delivery, then there's an 84.71% chance that the customer is going to come in and make a purchase. Hooray! They purchased our stuff. We're making money. If you're owning a shop, that's is the bottom line, is you want to make some money so that you can keep your shop open and have a living. Now, I promised you that we were going to be finishing up the math here with a few pages. So we're going to move on and we're going to do two steps. The first step is I want you to understand why you want to use the naive Bayes. What are the advantages of naive Bayes? And then once we understand those advantages, we'll just look at that briefly, then we're going to dive in and do some Python coding. Advantages of naive Bayes classifier. So let's take a look at the 6 advantages of the naive Bayes classifier, and we're going to walk around this lovely wheel. It looks like an origami folded paper. The first one is very simple and easy to implement. Certainly you could walk through the tables and do this by hand. You got to be a little careful because the notations can get confusing. You have all these different probabilities, and I certainly mess those up as I put them on, is it on the top or the bottom? You got to really pay close attention to that. When you put it into Python, it's really nice because you don't have to worry about any of that. You let the Python handle that, the Python module. But understanding it, you can put it on a table and you can easily see how it works, and it's a simple algebraic function. It needs less training data, so if you have smaller amounts of data, this is a great, powerful tool for that. Handles both continuous and discrete data. It's highly scalable with number of predictors and data points. So as you can see, you can just keep multiplying different probabilities in there, and you can cover not just 3 different variables or sets. You can now expand this to even more categories. Number 5, it's fast. It can be used in real-time predictions. This is so important. This is why it's used in a lot of our predictions on online shopping carts, referrals, spam filters, is because there's no time delay as it has to go through and figure out a neural network, or one of the other many setups where you're doing classification. And certainly there's a lot of other tools out there in the machine learning that can handle these, but most of them are not as fast as the naive Bayes. And then finally, it's not sensitive to irrelevant features. So it picks up on your different probabilities, and if you're short on data on one probability, you can it automatically adjusts for that. Those formulas are very automatic, and so you can still get a very solid predictability even if you're missing data or you have overlapping data for 2 completely different areas. We see that a lot in doing census and studying of people and habits, where they might have one study that covers one aspect and another one that overlaps, and because the 2 overlap, they can then predict the unknowns for the group that they haven't done the second study on, or vice versa. So it's very powerful in that it is not sensitive to the irrelevant features, and in fact you can use it to help predict features that aren't even in there. So now we're down to my favorite part. We're going to roll up our sleeves and do some actual programming. We're going to do the use case text classification. Now, I would challenge you to go back and send us a note on the notes below underneath the video and request the data for the shopping cart. So you can plug that into Python code and do that on your own time so you can walk through it, since we walk through all the information on it. But we're going to do a Python code doing text classification, very popular for doing the naive Bayes. So we're going to use our new tool to perform a text classification of news headlines and classify news into different topics for a news website. As you can see here, we have a nice image of the Google News, and then related on the right, subgroups. I'm not sure where they actually pulled the actual data we're going to use from. It's one of the standard sets. But certainly this can be used on any of our news headlines and classification. So let's see how it can be done using the naive Bayes classifier. Now we're at my favorite part. We're actually going to write some Python script. Roll up our sleeves. And we're going to start by doing our imports. These are very basic imports, including our news group. And we'll take a quick glance at the target names. Then we're going to go ahead and start training our data set and putting it together. We'll put together a nice graph, because it's always good to have a graph to show what's going on. And once we've trained it and we've shown you a graph of what's going on, then we're going to explore how to use it and see what that looks like. Now, I'm going to open up my favorite editor, inline editor for Python. You don't have to use this. You can use whatever your editor that you like, whatever interface IDE you want. This just happens to be the Anaconda Jupyter Notebook. And I'm going to paste that first piece of code in here so we can walk through it. Let's make it a little bigger on the screen so you have a nice view of what's going on. And we're using Python 3, in this case 3.5. So this would work in any of your 3x. If you have it set up correctly, it should also work in a lot of the 2x. You just have to make sure all of the versions of the modules match your Python version. And in here, you'll notice the first line is your percentage matplot library in line. Now, 3 of these lines of code are all about plotting the graph. This one lets the notebook know, since it's an inline setup, that we want the graphs to show up on this page. Without it in a notebook like this, which is an Explorer interface, it won't show up. Now, a lot of IDEs don't require that. A lot of them, like if I'm working on one of my other setups, it just has a pop-up and the graph pops up on there. So you have that setup also. But for this, we want the matplot library inline. And then we're going to import NumPy as NP. That's NumberPython, which has a lot of different formulas in it that we use for both of our sklearn module. And we also use it for any of the upper math functions in Python. And it's very common to see that as NP, NumPy as NP. The next 2 lines are all about our graphing. Remember I said 3 of these were about graphing? Well, we need our matplotlibary.pyplot as PLT, and you'll see that PLT is a very common setup, as is the SNS, and just like the NP. And we're going to import Seaborn as SNS, and we're going to do the SNS.set. Now, Seaborn sits on top of pyplot, and it just makes a really nice heat map. It's really good for heat maps. And if you're not familiar with heat maps, that just means we give it a color scale. The term comes from the brighter red it is, the hotter it is in some form of data, and you can set it to whatever you want. And we'll see that later on. So you'll see that those 3 lines of code here are just importing the graph function so we can graph it. And as a data scientist, you always want to graph your data and have some kind of visual. It's really hard just to shove numbers in front of people and they look at it and it doesn't mean anything. And then from the sklearn.datasets, we're going to import the fetch 20 news groups. Very common one for analyzing, tokenizing words and setting them up and exploring how the words work and how do you categorize different things when you're dealing with documents. And then we set our data equal to fetch 20 news groups. So our data variable will have the data in it. And we're going to go ahead and just print the target names, data.target names. And let's see what that looks like. And you'll see here we have alt atheism, comp graphics, comp os ms windows.miscellaneous. And it goes all the way down to talkpolitics.miscellaneous, talkreligion.miscellaneous. These are the categories they've already assigned to this news group. And it's called Fetch 20 because you'll see I believe there's 20 different topics in here, or 20 different categories as we scroll down. Now, we've gone through the 20 different categories, and we're going to go ahead and start defining all the categories and set up our data. So we're actually going to go ahead and get the data all set up and take a look at our data. And let's move this over to our Jupyter Notebook, and let's see what this code does. First, we're going to set our categories. Now, if you noticed up here, I could have just as easily set this equal to data.target_names, because it's the same thing. But we want to kind of spell it out for you so you can see the different categories. It kind of makes it more visual so you can see what your data is looking like in the background. Once we've created the categories, we're going to open up a train set. So this training set of data is going to go into fetch 20 news groups, and it's a subset in there called train, and categories equals categories. So we're pulling out those categories that match. And then if you have a train set, you should also have the testing set. We have test equals fetch 20 news groups, subset equals test, and categories equals categories. Let's go down one size so it all fits on my screen. There we go. And just so we can really see what's going on, let's see what happens when we print out one part of that data. So it creates train, and under train it creates train.data, and we're just going to look at data piece number 5. And let's go ahead and run that and see what that looks like. And you can see when I print train.data number 5 under train, it prints out one of the articles. This is article number 5. You can go through and read it on there. And we can also go in here and change this to test, which should look identical because it's splitting the data up into different groups, train and test. And we'll see test number 5 is a different article, but it's another article in here. And maybe you're curious and you want to see just how many articles are in here. We could do length of train.data. And if we run that, you'll see that the training data has 11,314 articles. So we're not going to go through all those articles. That's a lot of articles. But we can look at one of them just so you can see what kind of information is coming out of it and what we're looking at. And we'll just look at number 5 for today. And here we have it. Rewording the Second Amendment IDs, VTT, lines 58 in article, etc. And you can scroll all the way down and see all the different parts to there. Now we've looked at it, and that's pretty complicated when you look at one of these articles to try to figure out how do you weight this. If you look down here, we have different words, and maybe the word from. Well, from is probably in all the articles, so it's not going to have a lot of meaning as far as trying to figure out whether this article fits one of the categories or not. So trying to figure out which category it fits in based on these words is where the challenge comes in. Now that we've viewed our data, we're going to dive in and do the actual predictions. This is the actual naive Bayes. And we're going to throw another model at you, or another module at you here in just a second. We can't go into too much detail, but it deals specifically working with words and text and what they call tokenizing those words. So let's take this code and let's skip on over to our Jupyter Notebook and walk through it. And here we are in our Jupyter Notebook. Let's paste that in there. And I can run this code right off the bat. It's not actually going to display anything yet, but it has a lot going on in here. So at the top we had the print module from the earlier one. I didn't know why that was in there. So we're going to start by importing our necessary packages. And from the sklearn features extraction.txt, we're going to import tf-idf vectorizer. I told you we're going to throw a module at you. We can't go too much into the math behind this or how it works. You can look it up. The notation for the math is usually tf.idf. And that's just a way of weighing the words. And it weighs the words based on how many times they're used in a document, how many times or how many documents they're used in. And it's a well-used formula. It's been around for a while. It's a little confusing to put this in here, but let's let it know that it just goes in there and weights the different words in the document for us. That way we don't have to wait. And if you put a weight on it, if you remember I was talking about that up here earlier, if these are all emails, they probably all have the word from in them. From probably has a very low weight. It has very little value in telling you what this document's about. Same with words like in article, in articles, in, cost of, un, maybe cost might, or where words like criminal, weapons, destruction, these might have a heavier weight because they describe a little bit more what the article's doing. Well, how do you figure out all those weights in the different articles? That's what this module does. That's what the tf-idf vectorizer is going to do for us. And then we're going to import our sklearn.naive Bayes, and that's our multinomial NB. Multinomial naive Bayes. Pretty easy to understand that, where that comes from. And then finally we have the sklearn pipeline import make pipeline. Now the make pipeline is just a cool piece of code because we're going to take the information we get from the tf-idf vectorizer and we're going to pump that into the multinomial NB. So a pipeline is just a way of organizing how things flow. It's used commonly. You probably already guessed what it is if you've done any businesses. They talk about the sales pipeline. If you're on a work crew or a project manager, you have your pipeline of information that's going through, or your projects and what has to be done in what order. That's all this pipeline is. We're going to take the TF-ID vectorizer and then we're going to push that into the multinomial NB. Now, we've designated that as the variable model. We have our pipeline model. And we're going to take that model, and this is just so elegant. This is done in just a couple lines of code. Model.fit. And we're going to fit the data, and first the trained data, and then the trained target. Now, the trained data has the different articles in it. You can see the one we were just looking at. And the trained.target is what category they already categorized that particular article as. And what's happening here is the trained data is going into the TF-ID vectorizer. So when you have one of these articles, it goes in there, it weights all the words in there. So there's thousands of words with different weights on them. I remember once running a model on this, and I literally had 2.4 million tokens go into this. So when you're dealing like large document bases, you can have a huge number of different words. It then takes those words, gives them a weight, and then based on that weight, based on the words and the weights, it then puts that into the multinomial NB. And once we go into our naive Bayes, we want to put the trained target in there. So the trained data that's been mapped to the TF-ID vectorizer is now going through the multinomial NB, and then we're telling it, well, these are the answers. These are the answers to the different documents. So this document that has all these words with these different weights from the first part is going to be whatever category it comes out of. Maybe it's the talk show or the article on religion, miscellaneous. Once we fit that model, we can then take labels, and we're going to set that equal to model.predict. Most of the sklearn use the term .predict to let us know that we've now trained the model, and now we want to get some answers. And we're going to put our test data in there, because our test data is the stuff we held off to the side. We didn't train it on there, and we don't know what's going to come up out of it, and we just want to find out how good our labels are. Do they match what they should be? Now, I've already run this through. There's no actual output to it to show. This is just setting it all up. This is just training our model, creating the labels so we can see how good it is, and then we move on to the next step to find out what happened. To do this, we're going to go ahead and create a confusion matrix and a heat map. So the confusion matrix, which is confusing just by its very name, is basically going to ask how confused is our answer. Did it get it correct, or did it miss some things in there, or have some missed labels? And then we're going to put that on a heat map, so we'll have some nice colors to look at to see how that plots out. Let's go ahead and take this code and see how that, take a walk through it and see what that looks like. So back to our Jupyter notebook, I'm going to put the code in there, and let's go ahead and run that code. Take it just a moment. And remember, we had the inline, that way my graph shows up on the inline here. And let's walk through the code, and then we'll look at this and see what that means. So make it a little bit bigger. There we go. No reason not to use the whole screen. Too big. So we have here from sklearn metrics import confusion matrix. And that's just going to generate a set of data that says the prediction was such, the actual truth was either agreed with it or is something different. And it's going to add up those numbers so we can take a look and just see how well it worked. And we're going to set a variable mat equal to confusion matrix. And we have our test target, our test data that was not part of the training. Very important in data science, we always keep our test data separate. Otherwise, it's not a valid model if we can't properly test it with new data. And this is the labels we created from that test data. These are the ones that we predict it's going to be. So we go in and we create our SN heat map. The SNS is our seaborn, which sits on top of the pie plot. So when we create a SNS.heatmap, we take our confusion matrix, and it's going to be mat.t. And do we have other variables that go into the SNS.heatmap? We're not going to go into detail what all the variables mean. The annotation equals true. That's what tells it to put the numbers here. So you have the 166, the 1, the 0001. Format D and C bar equals false have to do with the format. If you take those out, you'll see that some things disappear. And then the X tick labels and the Y tick labels, those are our target names. And you can see right here, that's the alt atheism, comp graphics, comp OS, MS, Windows, miscellaneous. And then finally, we have our plt.x label. Remember, the SNS, or the seaborn, sits on top of our matplot library, our PLT. And so we want to just tell it x label equals a true is true. The labels are true. And then the y label is prediction label. So when we say a true, this is what it actually is, and the prediction is what we predicted. And let's look at this graph, because that's probably a little confusing the way I rattled through it. And what I'm going to do is I'm going to go ahead and flip back to the slides because they have a black background they put in there that helps it shine a little bit better so you can see the graph a little bit easier. So in reading this graph, what we want to look at is how the color scheme has come out. And you'll see a line right down the middle, diagonally, from upper left to bottom right. What that is if you look at the labels, we have our predicted label on the left and our true label on the right. Those are the numbers where the prediction and the true come together. And this is what we want to see, is we want to see those lit up. That's what that heat map does, is you can see that it did a good job of finding those data. And you'll notice that there's a couple of red spots on there where it missed. You know, it's a little confused when we talk about talk religion miscellaneous versus talk politics miscellaneous, social religion Christian versus alt atheism. It mislabeled some of those. And those are very similar topics, so you could understand why it might mislabel them. But overall, it did a pretty good job. If we're going to create these models, we want to go ahead and be able to use them. So let's see what that looks like. To do this, let's go ahead and create a definition, a function to run. And we're going to call this function, let me just expand that just a notch here. There we go. I like mine in big letters. Predict categories. We want to predict the category. We're going to send it S, a string. And then we're sending it train equals train. We have our training model. And then we had our pipeline, model equals model. This way we don't have to resend these variables each time. The definition knows that because I said train equals train, and I put the equal for model. And then we're going to set the prediction equal to the model.predict S. So it's going to send whatever string we send to it. It's going to push that string through the pipeline, the model pipeline. It's going to go through and tokenize it and put it through the TF, IDF, convert that into numbers and weights for all the different documents and words, and then it'll put that through our naive Bayes. And from it, we'll go ahead and get our prediction. We're going to predict what value it is. And so we're going to return train.targetNamesPredict of 0. And remember that the train.targetNames, that's just categories. I could have just as easily put categories in there .predict of 0. So we're taking the prediction, which is a number, and we're converting it to an actual category. We're converting it from, I don't know what the actual numbers are, but let's say 0 equals alt atheism. So we're going to convert that 0 to the word, or 1, maybe it equals comp graphics. So we're going to convert number 1 into comp graphics. That's all that is. And then we got to go ahead and then we need to go ahead and run this. So I load that up. And then once I run that, we can start doing some predictions. I'm going to go ahead and type in predict category. And let's just do predict category Jesus Christ. And it comes back and says it's social, religion, Christian. That's pretty good. Now, note I didn't put print on this. One of the nice things about the Jupyter Notebook Editor and a lot of inline editors is if you just put the name of the variable out as returning the variable train.target_names, it'll automatically print that for you. In your own IDE, you might have to put in print. Let's see where else we can take this. And maybe you're a space science buff. So how about sending load to International Space Station? And if we run that, we get science space. Or maybe you're a automobile buff. And let's do, they were going to tell me Audi is better than BMW, but I'm going to do BMW is better than an Audi. So maybe you're a car buff. And we run that, and you'll see it says recreational. I'm assuming that's what REC stands for. Autos. So I did a pretty good job labeling that one. How about if we have something like a caption running through there? President of India. And if we run that, it comes up and says talk, politics, miscellaneous. So when we take our definition or our function and we run all these things through, kudos, we made it. We were able to correctly classify texts into different groups based on which category they belong to using the naive Bayes classifier. Now, we did throw in the pipeline, the TF, IDF vectorizer. We threw in the graphs. Those are all things that you don't necessarily have to know to understand the naive Bayes setup or classifier. But they're important to know. One of the main uses for the naive Bayes is with the TF, IDF tokenizer or vectorizer, where it tokenizes the word and adds labels. And we use the pipeline because you need to push all that data through, and it makes it really easy and fast. You don't have to know those to understand naive Bayes, but they certainly help for understanding the industry and data science. And we can see our categorizer, our naive Bayes classifier. We were able to predict the category religion, space, motorcycles, autos, politics, and properly classify all these different things we pushed into our prediction and our trained model. Let's go ahead and wrap it up. And let's just go through what we covered. We gave you an introduction to naive Bayes and how it's used to perform basic classification as a classifier. We went through the basic formula, the probability of A given B and the probability of B given A, the basics of the naive Bayes. We touched a little bit on some of the different uses for the naive Bayes. We also went over the advantages of it and where it really shines, especially when we talk about real-time processing. Naive Bayes is very fast. We talked about the shopping demo. Remember that if you want to try that on your own, send a note down below. Let us know and we'll get you that data set. And we also went through the Python, my favorite part, the text classification. So we learned all kinds of things in there and walking through a real life scenario where you'd use the naive Bayes at.
Welcome to this session on deep learning. My name is Mohan, and in this video we are going to talk about what deep learning is all about. Some of you may be already familiar with image recognition. How does image recognition work? You can train an application or your machine to recognize whether a given image is a cat or a dog. And this is how it works at a very high level. It uses artificial neural network. It is trained with some known images, and during the training it is told if it is recognizing correctly or not. And then when new images are submitted, it recognizes correctly based on the accuracy, of course. So a little quick understanding about artificial neural networks. So this is the way it does is you provide a lot of training data, also known as labeled data. For example, in this case, these are the images of dogs, and the network extracts some features that makes a dog, right? So that is known as feature extraction. And based on that, when you submit a new image of dog, the basic features remain pretty much the same. It may be a completely different image, but the features of a dog still remain pretty much the same in various different images, let's say compared to a cat. And that's the way artificial neural network works. We'll go into details of this very shortly. And once the training is done with training data, we then test it with some test data which is basically completely new data which the system has not seen before, unlike the training data. And then we find out whether it is predicting correctly or not. Thereby we know whether the training is complete or it needs more training. So that's how at a very high level artificial neural network works. So this is what we are going to talk about today. Our agenda looks something like this. What is deep learning? Why do we need deep learning? And then what are the applications of deep learning? One of the main components, the secret sauce in deep learning, is neural networks. So we're going to talk about what is neural network and how it works, and some of its components, like for example the activation function, the gradient descent, and so on and so forth. So that as a part of working of a neural network, we will go into a little bit more details how this whole thing works. So without much further ado, let's get started. So deep learning is considered to be a part of machine learning. So this diagram very nicely depicts what deep learning is. At a very high level, you have the all-encompassing artificial intelligence, which is more a concept rather than a technology or a technical concept, right? So it is more of a concept at a very high level, artificial intelligence. Under the hood is actually machine learning and deep learning. And machine learning is a broader concept, you can say, or a broader technology, and deep learning is a subset of machine learning. The primary difference between machine learning and deep learning is that deep learning uses neural networks and it is suitable for handling large amounts of unstructured data. And the last but not least, one of the major differences between machine learning and deep learning is that in machine learning, the feature extraction or the feature engineering is done by the data scientists manually. But in deep learning, since we use neural networks, the feature engineering happens automatically. So that's a little bit of a quick difference between machine learning and deep learning. And this diagram very nicely depicts the relation between artificial intelligence, machine learning, and deep learning. Now, why do we need deep learning? Machine learning was there for quite some time, and it can do a lot of stuff that probably what deep learning can do, but it's not very good at handling large amounts of unstructured data, like images, voice, or even text for that matter. So traditional machine learning is not that very good at doing this. Traditional machine learning can handle large amounts of structured data, but when it comes to unstructured data, it's a big challenge. So that is one of the key differentiators for deep learning. So that is number one. And increasingly for artificial intelligence, we need image recognition, and we need to process, analyze images and voice. That's the reason deep learning is required compared to, let's say, traditional machine learning. It can also perform complex algorithms, more complex than, let's say, what machine learning can do, and it can achieve best performance with the large amounts of data. So the more you have the data, let's say reference data or labeled data, the better the system will do, because the training process will be that much better. And last but not least, with deep learning, you can really avoid the manual process of feature extraction. Those are some of the reasons why we need deep learning. Some of the applications of deep learning. Deep learning has made major inroads, and it is a major area in which deep learning is applied is healthcare. And within healthcare, particularly oncology, which is basically cancer related stuff. One of the issues with cancer is that a lot of cancers today are curable. They can be cured. They are detected early on. And the challenge with that is when a diagnostics is performed, let's say an image has been taken of a patient, to detect whether there is cancer or not, you need a specialist to look at the image and determine whether the patient is fine or there is any onset of cancer. And the number of specialists are limited. So if we use deep learning, if we use automation here, or if we use artificial intelligence here, then the system can, with a certain amount of the good amount of accuracy, determine whether a particular patient is having cancer or not. So the prediction or the detection process of a disease like cancer can be expedited. The detection process can be expedited, can be faster without really waiting for a specialist. We can obviously then, once the artificial intelligence detects or predicts that there is an onset of a cancer, this can be cross-checked by a doctor. But at least the initial screening process can be automated, and that is where the current focus is with respect to deep learning in healthcare. What else? Robotics is another area. Deep learning is majorly used in robotics, and you must have seen nowadays robots are everywhere. Humanoids, the industrial robots which are used for manufacturing process. You must have heard about Sophia, who got citizenship with Saudi Arabia, and so on. There are multiple such robots which are knowledge oriented, but there are also industrial robots that are used in industries, in the manufacturing process, and increasingly in security and also in defense. For example, image processing. Video is fed to them and they need to be able to detect objects, obstacles, and so on and so forth. So that's where deep learning is used. They need to be able to hear and make sense of the sounds that they are hearing. That needs deep learning as well. So robotics is a major area where deep learning is applied. Then we have self-driving cars or autonomous cars. You must have heard of Google's autonomous car, which has been tested for millions of miles and pretty much incident-free. There were, of course, a couple of incidents here and there, but it is considered to be fairly safe. And there are today a lot of automotive companies. In fact, pretty much every automotive company worth its name is investing in self-driving cars or autonomous cars. And it is predicted that in the next probably 10 to 15 years, these will be in production and they will be used extensively in real life. Right now, they are all in R&D and in test phases, but pretty soon these will be on the road. So this is another area where deep learning is used. And how is it used? Where is it used? Within autonomous driving, the car actually is fed with video of surroundings, and it is supposed to process that information, process that video, and determine if there are any obstacles. It has to determine if there are any cars in the side. It will detect whether it is driving in the lane. Also, it has to determine whether the signal is green or red, so that accordingly it can move forward or wait. So for all these video analysis, deep learning is used. In addition to that, the training, overall training to drive the car happens in a deep learning environment. So again, a lot of scope here to use deep learning. A couple of other applications are machine translation. So today we have a lot of information, and very often this information is in one particular language, and more specifically in English. And people need information in various parts of the world. It is pretty difficult for human beings to translate each and every piece of information or every document into all possible languages. There are probably at least hundreds of languages, or if not more. To translate each and every document into every language is pretty difficult. Therefore, we can use deep learning to do pretty much like a real-time translation mechanism. So we don't have to translate everything and keep it ready, but we train applications or artificial intelligence systems that will do the translation on the fly. For example, you go to somewhere like China and you want to know what is written on a signboard. Now, it is impossible for somebody to translate that and put it on the web or something like that. So you have an application which is trained to translate stuff on the fly. So this can be running on your mobile phone, on your smartphone. You scan this, the application will instantly translate that from Chinese to English. That is one. Then there could be web applications where there may be a research document which is all in maybe Chinese or Japanese, and you want to translate that to study that document, or in that case you need to translate that. So therefore, deep learning is used in such situations as well, and that is again on demand. So it is not like you have to translate all these documents from other languages into English in one shot and keep it somewhere. That is again pretty much an impossible task, but on a need basis. So you have systems that are trained to translate on the fly. So machine translation is another major area where deep learning is used. Then there are a few other upcoming areas where synthesizing is done by neural nets. For example, music composition and generation of music. So you can train a neural net to produce music, even to compose music. So this is a fun thing. This is still upcoming. It needs a lot of effort to train such neural net. It has been proved that it is possible. So this is a relatively new area. And on the same lines, colorization of images. So these two images on the left hand side is a grayscale image or a black and white image. This was colored by a neural net or a deep learning application. As you can see, it's done a very good job of applying the colors, and obviously this was trained to do this colorization. But yes, this is one more application of deep learning. Now, one of the major secret sauce of deep learning is neural network. Deep learning works on neural network or consists of neural network. So let us see, what is neural network. Neural network or artificial neural network is designed or based on the human brain. Now, human brain consists of billions of small cells that are known as neurons. Artificial neural networks is, in a way, trying to simulate the human brain. So, this is a quick diagram of biological neuron. A biological neuron consists of the major part, which is the cell nucleus, and then it has some tentacles kind of stuff on the top called dendrite, and then there is like a long tail which is known as the axon. Further again, at the end of this axon are what are known as synapses. These in turn are connected to the dendrites of the next neuron, and all these neurons are interconnected with each other. Therefore, they are like billions of them sitting in our brain, and they're all active, they're working. Based on the signals, they receive signals as inputs from other neurons or maybe from other parts of the body, and based on certain criteria, they send signals to the neurons at the other end. So they they get either activated or they don't get activated based on, so it is like a binary gates, so they get activated or not activated based on the inputs that they receive and so on. So we will see a little bit of those details as we move forward in our artificial neuron. But this is a biological neuron. This is the structure of a biological neuron. And artificial neural network is based on the human brain. The smallest component of artificial neural network is an artificial neuron, as shown here. Sometimes is also referred to as a perceptron. Now, this is a very high-level diagram. The artificial neuron has a small central unit which will receive the input. If it is doing, let's say, image processing, the inputs could be pixel values of the image, which is represented here as x1, x2, and so on. Each of the inputs are multiplied by what is known as weights, which are represented as w1, w2, and so on. There is, in the central unit, basically, there is a summation of these weighted inputs, which is like x1 into w1 plus x2 into w2 and so on. The products are then added, and then there is a bias that is added to that. In the next slide we will see that passes through an activation function, and the output comes as a y, which is the output, and based on certain criteria the cell gets either activated or not activated. So this output would be like a 0 or a 1 binary format. Okay, so we will see that in a little bit more detail, but let's do a quick comparison between biological and artificial neuron. Just like a biological neuron, there are dendrites, and then there is a cell nucleus and synapse and an axon. We have in the artificial neuron as well. These inputs come like the dendrite, if you will, act like the dendrites. There is like a central unit which performs the summation of these weighted inputs, which is basically w1, x1, w2, x2, and so on. And then a bias is added here, and then that passes through what is known as an activation function. Okay, so these are known as the weights, w1, w2, and then there is a bias which will come out here, and that is added. The bias is, by the way, common for a particular neuron, so there won't be like b1, b2, b3, and so on. Only weights will be 1 per input. The bias is common for the entire neuron. It is also common for, or the value of the bias remains the same for all the neurons in a particular layer. We will also see this as we move forward and we see deep neural network where there are multiple neurons. So that's the output. Now, the whole exercise of training a neuron is about changing these weights and biases. As I mentioned, this artificial neural network will consist of several such neurons, and as a part of the training process, these weights keep changing. Initially they are assigned some random values. Through the training process, the weights, the whole process of training is to come up with the optimum values of w1, w2, and wn, and then the b for, or the bias for this particular neuron, such that it gives an accurate output as required. So let's see what exactly that means. So the training process, this is how it happens. It takes the inputs. Each input is multiplied by a weight, and these weights during training keep changing. So initially they are assigned some random values, and based on the output, whether it is correct or wrong, there is a feedback coming back, and that will basically change these weights until it starts giving the right output. That is represented in here as sigma I going from 1 to n. If there are n inputs, wi into xi. So this is the product of w1, x1, w2, x2, and so on, right? And there is a bias that gets added here, and that entire thing goes to what is known as an activation function. So essentially this is sigma of wixi plus a value of bias, which is a b. So that entire thing goes as an input to an activation function. Now this activation function takes this as an input, gives the output as a binary output. It could be a 0 or a 1. There are, of course, to start with, let's assume it's a binary output. Later we will see that there are different types of activation functions, so it need not always be binary output. But to start with, let's keep simple. So it decides whether the neuron should be fired or not. So that is the output, like a binary output, 0 or 1. All right. So again, let me summarize this. So it takes the inputs. So if you're processing an image, for example, the inputs are the pixel values of the image, x1, x2 up to xn. There could be hundreds of these. So all of those are fed as, so these are some values, and these pixel values again can be from 0 to 256. Each of those pixel values are then multiplied with what is known as a weight. This is a numeric value, can be any value. So this is a number, W1. Similarly, W2 is a number. So initially some random values will be assigned, and each of these weights are multiplied with the input value and their sum. This is known as the weighted sum. So that is performed in this kind of the central unit, and then a bias is added. Remember, the bias is common for each neuron. So this is not, the bias value is not one bias value for per input. So just keep that in mind. The bias value, there is one bias per neuron. So it is like this summation plus bias is the output from this section. This is not the complete output of the neuron, but this is the bias for output for step 1. That goes as an input to what is known as an activation function, and that activation function results in an output, usually a binary output like a 0 or a 1, which is known as the firing of the neuron. Okay, good. So we talked about activation function. So what is an activation function? An activation function basically takes the weighted sum, which is, we saw, W1, X1, W2, X2, the sum of all that, plus the bias. So it takes that as an input and it generates a certain output. Now, there are different types of activation functions, and the output is different for different types of activation functions. Moreover, why is an activation function required? It is basically required to bring in non-linearity. That's the main reason why an activation function is required. So, what are the different types of activation functions? There are several types of activation functions, but these are the most common ones. These are the ones that are currently in use. Sigmoid function was one of the early activation functions, but today ReLU has kind of taken over. So ReLU is by far the most popular activation function that is used today. But still, sigmoid function is still used in many situations. These different types of activation functions are used in different situations based on the kind of problem we are trying to solve. So what exactly is the difference between these two? Sigmoid gives the values of the output will be between 0 and 1. Threshold function is the value will be 0 up to a certain value, and beyond that, this is also known as a step function, and beyond that it will be 1. In case of sigmoid, there is a gradual increase, but in case of threshold, it's like also known as a step function. There is a rapid or instantaneous change from 0 to 1. Whereas in sigmoid, we will see in the next slide, there is a gradual increase, but the value in this case is between 0 and 1 as well. Now, ReLU function, on the other hand, it is equal to, basically, if the input is 0 or less than 0, then the output is 0. Whereas if the input is greater than 0, then the output is equal to the input. I know it's a little confusing, but in the next slides where we show the ReLU function, it will become clear. Similarly, hyperbolic tangent. This is similar to sigmoid in terms of the shape of the function. However, while sigmoid goes from 0 to 1, hyperbolic tangent goes from -1 to 1. And here again, the increase or the change from -1 to 1 is gradual and not like threshold or step function where it happens instantaneously. So let's take a little detailed look at some of these functions. So let's start with the sigmoid function. So this is the equation of a sigmoid function, which is 1 by 1 plus e to the power of minus x. So x is the value, that is the input. It goes from 0 to -1. So this is sigmoid function. The equation is phi x is equal to 1 by 1 plus e to the power of minus x. And as you can see here, this is the input on the x-axis. As x is the value is coming from, in fact, it can also go negative. This is negative actually. So this is the 0. So this is the negative value of x. So as x is coming from negative value towards 0, the value of the output slowly, as it is approaching 0, it slowly and very gently increases. And actually at the point, let me just use a pen, at the point here, it is 0.5. It is actually 0.5. Okay. And slowly, gradually it increases to 1 as the value of x increases. But then as the value of x increases, it tapers off. It doesn't go beyond 1. So that is the speciality of sigmoid function. So the output value will remain between 0 and 1. It will never go below 0 or above 1. Okay, so that is sigmoid function. Now this is threshold function, or this is also referred to as a step function. And here we can also set the threshold. In this case that's why it's called the threshold function. Normally it is 0, but you can also set a different value for the threshold. Now the difference between this and the sigmoid is that here the change is rapid or instantaneous. As the x value comes from negative up to 0, it remains 0, and at 0 it pretty much immediately increases to 1. Okay, so this is a mathematical representation of threshold function. Phi x is equal to 1 if x is greater than or equal to 0, and 0 if x is less than 0. So for all negative values it is 0, since we have set the threshold to be 0. So as soon as it reaches 0, it becomes 1. You see the difference between this and the previous one, which is basically the sigmoid, where the increase from 0 to 1 is gradual, and here it is instantaneous. And that's why this is also known as a step function, threshold function or step function. This is a ReLU. A ReLU is one of the most popular activation functions today. This is the definition of ReLU. Phi x is equal to max of x, 0. What it says is if the value of x is less than 0, then phi x is 0. The moment it increases, goes beyond 0, the value of phi x is equal to x. So it doesn't stop at 1. Actually, it goes all the way. So as the value of x increases, the value of y will also increase infinitely. So there is no limit here, unlike your sigmoid or threshold or the next one, which is basically hyperbolic tangent. Okay, so in case of ReLU, remember there is no upper limit. The output is equal to either 0 in case the value of x is negative, or it is equal to the value of x. So for example, here if the value of x is 10, then the value of y is also 10. Right? Okay, so that is ReLU, and there are several advantages of ReLU, and it is much more efficient and provides much more accuracy compared to other activation functions like sigmoid and so on. So that's the reason it is very popular. Alright, so this is hyperbolic tangent activation function. The function looks similar to sigmoid function. The curve, if you see the shape, it looks similar to sigmoid function. But the difference between hyperbolic tangent and sigmoid function is that in case of sigmoid, the output goes from 0 to 1. Whereas in case of hyperbolic tangent, it goes from -1 to 1. So that is the difference between hyperbolic tangent and sigmoid function. Otherwise, the shape looks very similar. There is a gradual increase, unlike the step function where there was an instant increase or instant change. Here again, very similar to sigmoid function, the value changes gradually from -1 to 1. So this is the equation of hyperbolic tangent activation function. Yeah, so then let's move on. This is a diagrammatic representation of the activation function and how the overall data or how the overall progression happens from input to the output. So we get the input from the input layer. By the way, the neural network has 3 layers. Typically there will be 3 layers. There is an input layer, there is an output layer, and then you have the hidden layer. So the inputs come from the input layer and they get processed in the hidden layer, and then you get the output in the output layer. So let's take a little bit of a detailed look into the working of a neural network. So let's say we want to classify some images between dogs and cats. How do we do this? This is known as a classification process, and we are trying to use neural networks and deep learning to implement this classification. So how do we do that? So this is how it works. So you have 4-layer neural network. There is an input layer, there is an output layer, and then there are 2 hidden layers. And what we do is we provide labeled training data, which means these images are fed to the network with the label saying that, okay, this is a cat. The neural network is allowed to process it and come up with a prediction saying whether it is a cat or a dog. And obviously in the beginning, there may be mistakes. A cat may be classified as a dog. So we then say that, okay, this is wrong. This output is wrong. But every time it predicts correctly, we say, yes, this output is correct. So that learning process, so it will go back, make some changes to its weights and biases. We again feed these inputs and it will give us the output. We will check whether it is correct or not, and so on. So this is a iterative process which is known as the training process. So we are training the neural network. And what happens in the training process? These weights and biases, you remember there were weights like W1, W2 and so on. So these weights and biases keep changing every time you feed these, which is known as an epoch. So there are multiple iterations. Every iteration is known as an epoch, and each time the weights are updated to make sure that the maximum number of images are classified correctly. So once again, what is the input? This input could be like 1,000 images of cats and dogs, and they are labeled because we know which is a cat and which is a dog, and we feed those 1,000 images. The neural network will initially assign some weights and biases for each neuron, and it will try to extract the features from the images, and it will try to come up with a prediction for each image. And that prediction that is calculated by the network is compared with the actual value, whether it is a cat or a dog, and that's how the error is calculated. So let's say there are 1,000 images, and in the first run only 500 of them have been correctly classified. That means we are getting only 50% accuracy. So we feed that information back to the network, further update these weights and biases for each of the neurons, and we run these inputs once again. It will try to calculate, extract the features, and it will try to predict which of these is cats and dogs. And this time, let's say out of 1,000, 700 of them have been predicted correctly. So that means in the second iteration, the accuracy has increased from 50% to 70%. Alright. Then we go back again, we feed this maybe for a third iteration, fourth iteration, and so on, and slowly and steadily the accuracy of this network will keep increasing, and it may reach probably, you never know, 90%, 95%. And there are several parameters that are known as hyperparameters that need to be changed and tweaked. And that is the overall training process. And ultimately, at some point we say, okay, you will probably never reach 100% accuracy, but then we set a limit saying that, okay, if we receive 95% accuracy, that is good enough for our application. And then we say, okay, our training process is done. So that is the way training happens. And once the training is done, now with the training data set, the system has, let's say, seen all these 1,000 images. Therefore, what we do is the next step, like in any normal machine learning process, we do the testing, where we take a fresh set of images and we feed it to the network, the fresh set which it has not seen before as a part of the training process. And this is again nothing new in deep learning. This was there in machine learning as well. So you feed the test images and then find out whether we are getting similar accuracy or not. So maybe that accuracy may reduce a little bit. While training you may get 98%, and then for test you may get 95%. But there shouldn't be a drastic drop, like for example you get 98% in training and then you get 50% or 40% with the test. That means your network has not learned. You may have to retrain your network. So that is the way neural network training works. And remember, the whole process is about changing these weights and biases and coming up with the optimal values of these weights and biases so that the accuracy is the maximum possible. Alright, so a little bit more detail about how this whole thing works. So this is known as forward propagation, which is the data or the information is going in the forward direction. The inputs are taken, weighted summation is done, bias is added here, and then that is fed to the activation function, and then that comes out as an output. So that is forward propagation, and the output is compared with the actual value, and that will give us the error. The difference between them is the error, and in technical terms that is also known as our cost function. And this is what we would like to minimize. There are different ways of defining the cost function, but one of the simplest ways is mean square error. So it is nothing but the square of the difference of the errors, or the sum of the squares of the difference of the errors. And this is also nothing new. We have probably, if you're familiar with machine learning, you must have come across this mean square error. Now, there are different ways of defining cost function. It need not always be the mean square error, but the most common one is this. So you define this cost function and you ask the system to minimize this error. So we use what is known as an optimization function to minimize this error, and the error itself sent back to the system as feedback, and that is known as backpropagation. And so this is the cost function. And how do we optimize the cost function? We use what is known as gradient descent. So the gradient descent mechanism identifies how to change the weights and biases so that the cost function is minimized. And there is also what is known as the rate or the learning rate. That is what is shown here as slower and faster. So you need to specify what should be the learning rate. Now, if the learning rate is very small, then it will probably take very long to train. Whereas if the learning rate is very high, then it will appear to be faster, but then it will probably never what is known as converge. Now, what is convergence? Now, we are talking about a few terms here. Convergence is like this. This is a representation of convergence. So the whole idea of gradient descent is to optimize the cost function or minimize the cost function. In order to do that, we need to represent the cost function as this curve. We need to come to this minimum value. That is what is known as the minimization of the cost function. Now, what happens if we have the learning rate very small is that it will take very long to come to this point. On the other hand, if you have higher learning rate, what will happen is instead of stopping here, it will cross over because the learning rate is high, and then it has to come back. So it will result in what is known as like an oscillation. So it will never come to this point, which is known as convergence. Instead, it will go back and forth. So these are known as hyperparameters, the learning rate and so on. And these have to be those numbers or those values we can determine typically using trial and error. Out of experience, we try to find out these values. So that is the gradient descent mechanism to optimize the cost function, and that is what is used to train our neural network. This is another representation of how the training process works. And here in this example, we are trying to classify these images, whether they are cats or dogs. And as you can see, actually each image is fed, in each time one image is fed rather. And these values of x1, x2 up to xn are the pixel values within this image. Okay, so those values are then taken, and for each of those values a weight is multiplied, and then it goes to the next layer and then to the next layer and so on. Ultimately it comes as the output layer, and it gives an output as whether it is a dog or a cat. Remember, the output will never be a named output, so these would be like a 0 or a 1, and we say okay, 0 corresponds to dogs and 1 corresponds to cats. So that is the way it typically happens. This is a binary classification. We have similar situations where there can be multiple classes, which means that there will be more neurons in the output layer. Okay, so this is once again a quick representation of how the forward propagation and the backward propagation works. So the information is going in this direction, which is basically the forward propagation, and at the output level we find out what is the cost function. The difference is basically sent back as part of the backward propagation, and gradient descent then adjusts the weights and biases for the next iteration. This happens iteratively till the cost function is minimized. And that is when we say the network has converged, or the training process has converged. And there can be situations where convergence may not happen in rare cases, but by and large the network will converge, and after maybe a few iterations, it could be tens of iterations or hundreds of iterations, depending on what exactly the number of iterations can vary. And then we say, okay, we are getting a certain accuracy, and we say that is our threshold, maybe 90% accuracy. We stop at that, and we say that the system is trained. The trained model is then deployed for production and so on. So that is the way the neural network training happens. Okay, so that is the way classification works in deep learning using neural network. And this slide is an animation of this whole process. As you can see, the forward propagation, the data is going forward from the input layer to the output layer, and there is an output. And the error is calculated, the cost function is calculated, and that is fed back as a part of backward propagation. And that whole process repeats once again. Okay, so remember, in neural networks, the training process is nothing but finding the best values of the weights and biases for each and every neuron in the network. That's all training of neural network consists of. Finding the optimal values of the weights and biases so that the accuracy is maximum.
Star Wars fans would be familiar with the golden, life-sized hospitality robot C-3PO. While Star Wars might be set in a galaxy far, far away, the reality of having machines talk and respond to us in a human-like manner is already a reality, which keeps getting more and more realistic with every passing day. The people you ask for queries on websites, your smart assistants, even calls made over the internet, all of them have one thing in common. None of them are actually human. Now, you must be thinking, if they are not human, how do they manage to sound and seem so human-like? How do they respond to me so intelligently? And how are they so articulate? This, my friends, is the magic of natural language processing. What is NLP? Natural language processing, or NLP, refers to the branch of artificial intelligence that gives the machines the ability to read, understand, and derive meaning from human languages. NLP combines the field of linguistics and computer science to decipher language structure and guidelines, and to make models which can comprehend, break down, and separate significant details from text and speech. Every day, humans interact with each other through public social media, transferring vast quantities of freely available data to each other. This data is extremely useful in understanding human behavior and customer habits. Data analysts and machine learning experts utilize this data to give machines the ability to mimic human linguistic behavior. This helps save millions in terms of manpower and time, as you don't need to always have a person present at the other end of a phone. NLP is also a lot more widespread than you may realize. You use it every day in seemingly normal and insignificant situations. Don't know how to correctly spell a word? Autocorrect has you covered. Need to see if your article or thesis will get flagged for copyright violations? That's okay. A plagiarism checker will search through the web and find any cases of published documents which may match your work line by line. While NLP seems really cool, yet a cutting-edge and complicated technology concept, it is actually pretty easy to learn. You start off with a document or an article. To make your algorithm understand what is going on in it, you need to process it into a form which is easily comprehensible by the machine. This is no different than making a child learn to read for the first time. You start off by performing segmentation, which is to break the entire document down into its constituent sentences. You can do this by segmenting the article along its punctuations, like full stops and commas. For the algorithm to understand these sentences, we get the words in a sentence and to explain them individually to our algorithm. So, we break down our sentence into its constituent words and store them. This is called tokenizing, where each word is called a token. We can make the learning process faster by getting rid of non-essential words which do not add much meaning to our statement and are just there to make our statement sound more cohesive. These words, such as are, and, the, are called stop words. Now that we have the basic form of our document, we need to explain it to our machine. We first start off by explaining that some words like skipping, skips, skipped are the same word with added prefixes and suffixes. This is called stemming. We also identify the base words for different word tense, mood, gender, etc. This is called lemmatization, stemming from the base word lemma. Now we explain the concept of nouns, verbs, articles, and other parts of speech to the machine by adding these tags to our words. This is called part of speech tagging. Next, we introduce our machine to pop culture references and everyday names by flagging names of movies, important personalities or locations, etc. that may occur in the document. This is called named entity tagging. Once we have our base words and tags, we use a machine learning algorithm like naive Bayes to teach our model humans sentiment and speech. At the end of the day, most of the techniques used in NLP are simple grammar techniques that we have been taught in school. Here is a question for you. Which of these NLP techniques is used to obtain words from sentences? A. Stemming. B. Tokenization.
C. Lemmatization. D. Segmentation. Give it a thought and leave your answers in the comments section below. 3 lucky winners will receive Amazon gift vouchers. With the increasing demand for automated language solutions, companies are looking for NLP experts to join them and are prepared to offer highly lucrative salaries as well. If you want to learn more about NLP, you can check out Simplilearn's postgraduate program in AI and machine learning in collaboration with IBM. In this program, you will learn about frameworks like Keras and TensorFlow and get hands-on experience in deep learning to become a truly experienced AI engineer.
Python is the most widely used programming language today. When it comes to solving data science tasks and challenges, Python never ceases to surprise its audience. Most data scientists out there are already leveraging the power of Python every day. Hi, I'm Apeksha from Simplilearn, and well, after some thought and a bit more research, I was finally able to narrow down my choice of top Python libraries for data science. What are they? Let's find out. So let's talk about this amazing library, TensorFlow, which is also one of my favorites. So TensorFlow is a library for high performance numerical computations with around 35,000 GitHub commits and a vibrant community of around 1,500 contributors, and it's used across various scientific domains. It's basically a framework where we can define and run computations which involves tensors. And tensors, we can say, are partially defined computational objects again, where they will eventually produce a value. That was about TensorFlow. Let's talk about the features of TensorFlow. So TensorFlow is majorly used in deep learning models and neural networks, where we have other libraries like Torch and Theano also. But TensorFlow has hands down better computational graphical visualizations when compared to them. Also, TensorFlow reduces the error largely by 50 to 60% in neural machine translations. It's highly parallel in a way where it can train multiple neural networks and multiple GPUs for highly efficient and scalable models. This parallel computing feature of TensorFlow is also called pipelining. Also, TensorFlow has the advantage of seamless performance. As it's backed by Google, it has quicker updates, frequent new releases with the latest of features. Now, let's look at some applications. TensorFlow is extensively used in speech and image recognition, text-based applications, time series analysis and forecasting, and various other applications involving video detection. So, favorite thing about TensorFlow that it's already popular among the machine learning community, and most are open to trying it, and some of us are already using it. Now, let's look at an example of a TensorFlow model. In this example, we will not dive deep into the explanation of the model as it is beyond the scope of this video. So here we're using Analyst dataset, which consists of images of handwritten digits. Handwritten digits can be easily recognized by building a simple TensorFlow model. Let's see how. When we visualize our data using Matplotlib library, the inputs will look something like this. Then we create our TensorFlow model. To create a basic TensorFlow model, we need to initialize the variables and start a session. Then after training the model, we can validate the data and then predict the accuracy. This model has predicted 92% accuracy. Let's see, which is pretty well for this model. So that's all for TensorFlow. If you need to understand this tutorial in detail, then you can go ahead and watch our deep learning tutorial from Simplilearn as shown in the right corner. Interesting, right? Let's move on to the next library. Now let's talk about a common yet a very powerful Python library called NumPy. NumPy is a fundamental package for numerical computation in Python. It stands for Numerical Python as the name suggests. It has around 18,000 commits on GitHub with an active community of 700 contributors. It's a general purpose array processing package in a way that it provides high performance multi-dimensional objects called arrays and tools for working with them. Also, NumPy addresses the slowness problem partly by providing these multi-dimensional arrays that we talked about, and then functions and operators that operate efficiently on these arrays. Interesting, right? Now let's talk about the features of NumPy. It's very easy to work with large arrays and matrices using NumPy. NumPy fully supports object-oriented approach. For example, coming back to ND array once again, it's a class possessing numerous methods and attributes. ND-array provides for larger and repeated computations. NumPy offers vectorization. It's more faster and compact than traditional methods. I always wanted to get rid of loops, and vectorization of NumPy clearly helps me with that. Now let's talk about the applications of NumPy. NumPy, along with pandas, is extensively used in data analysis, which forms the basis of data science. It helps in creating the powerful n-dimensional array. Whenever we talk about NumPy, the mention of the array, we cannot do it without the mention of the powerful n-dimensional array. Also, NumPy is extensively used in machine learning when we are creating machine learning models, as in where it forms the base of other libraries like SciPy, scikit-learn, etc. When you start creating the machine learning models in data science, you will realize that all the models will have their base as NumPy or pandas. Also, when NumPy is used with SciPy and Matplotlib, it can be used as a replacement of MATLAB. Now let's look at a simple example of an array in NumPy. As you can see here, there are multiple array manipulation routines. Like there are basic examples where we can copy the values from one array to another. We can give a new shape to an array from maybe one-dimensional to we can make it as a two-dimensional array. We can return a copy of the array collapsed into one dimension. Now let's look at an example where this is a Jupyter notebook, and we will just create a basic array, and for detailed explanation you can watch our other videos which targets on these explanations of each libraries. So first of all, whenever we are using any library in Python, we have to import it. So now this np is the alias which we will be using. Let's create a simple array. Let's look what is the type of this array. So this is an ND array type of array. Also, let's look what's the shape of this array. So this is a shape of the array. Now here we saw that we can expand the shape of the array. So this is where you can change the shape of the array using all those functions. Now let's create an array using arrange functions. If I give arrange 12, it will give me a 1D array of 12 numbers like this. Now we can reshape this array to 3, 4, or we can write it here itself. So this is how arrange function and the reshape function works for NumPy. Now let's discuss the next library, which is SciPy. So this is another free and open source Python library extensively used in data science for high-level computations. So this library, as the name suggests, stands for Scientific Python, and it has around 19,000 commits on GitHub with an active community of 600 contributors. It is extensively used for scientific and technical computations. Also, as it extends NumPy, it provides many user-friendly and efficient routines for scientific calculations. Now, let's discuss about some features of SciPy. So SciPy has this collection of algorithms and functions which is built on the NumPy extension of Python. Secondly, it has various high-level commands for data manipulation and visualization. Also, the NDImage function of SciPy is very useful in multi-dimensional image processing, and it includes built-in functions for solving differential equations, linear algebra, and many more. So that was about the features of SciPy. Now let's discuss its applications. So SciPy is used in multi-dimensional image operations. It has functions to read images from disk into NumPy arrays, to write arrays to disk as images, resize images, etc., solving differential equations, Fourier transforms, then optimization algorithms, linear algebra, etc. Let's look at a simple example to learn what kind of functions are there in SciPy. Here I'm importing the constants package of SciPy library. So in this package, it has all the constants. So here I'm just mentioning C or H or NA, and this library already knows what it has to fetch, like speed of light, Planck's constant, etc. So this can be used in further calculations. Data analysis is an integral part of data science. Data scientists spend most of the day in data munging and then cleaning the data also. Hence, mention of pandas is a must in data science lifecycle. Yes, pandas is the most popular and widely used Python library for data science, along with NumPy and Matplotlib. The name itself stands for Python Data Analysis, with around 17,000 commits on GitHub GitHub and an active community of 1200 contributors. It is heavily used for data analysis and cleaning as it provides fast, flexible data structures like data frames, series, which are designed to work with structured data very easily and intuitively. Now let's talk about some features of Pandas. So Pandas offers this eloquent syntax and rich functionalities. Like there are various methods in Pandas like drop NA, fill NA, which gives you the freedom to deal with missing data. Also, Pandas provides a powerful apply function, which lets you create your own function and run it across a series of data. Now forget about writing those for loops while using Pandas. Also, this library's high-level abstraction over low-level NumPy, which is written in pure C. Then it also contains these high-level data structures and manipulation tools, which makes it very easy to work with Pandas, like their data structures and series. Now let's discuss the applications of Pandas. So Pandas is extensively used in general data wrangling and data cleaning. Then Pandas also finds its usage in ETL jobs for data transformation and data storage, as it has excellent support for loading CSV files into its data frame format. Then Pandas is used in a variety of academic and commercial domains, including statistics, finance, neuroscience, economics, web analytics, etc. Then Pandas is also very useful in time series specific functionality like date range generation, moving window linear regression, date shifting, etc. Now let's look at a very simple example of how to create a data frame. So data frame is a very useful data structure in Pandas and it has very powerful functionalities. So here I'm only enlisting important libraries in data science. You can explore more of our videos to learn about these libraries in detail. So let's just go ahead and create a data frame. I'm using Jupyter Notebook again, and in this, before using Pandas, here I'm importing the Pandas library. Let me go and run this. So in data frame, we can import a file, a CSV file, Excel files. There are many functions doing these things, and we can also create our own data and put it into data frame. So here I am taking random data and putting in a data frame. Also I'm creating an index and then also giving the column names. So PD is the alias we've given for Pandas, random data of 6x4, index which is taking a range of 6 numbers, and column name I'm giving as ABCD. Now let's go ahead and look at it. So here it has created a data frame with my column names are ABCD, my list as 6 numbers 0 to 5, and a random data of 6x4. So data frame is just another table with rows and columns where you can do various functions over it. Also, I can go ahead and describe this data frame to see. So it's giving me all these functionalities where count and mean and standard deviation, etc. Okay, so that was about Pandas. Now let's talk about the next library and the last one. So Matplotlib for me is the most fun library out of all of them. Why? Because it has such powerful yet beautiful visualizations. We'll see in the coming slides. Plot and Matplotlib suggests that it's a plotting library for Python. It has around 26,000 commits on GitHub and a very vibrant community of 700 contributors. And because of such graphs and plots that it produces, it's majorly used for data visualization. And also because it provides an object-oriented API which can be used to embed those plots into our applications. Let's talk about the features of Matplotlib. The PyPlot module of Matplotlib provides MATLAB-like interface. So Matplotlib is designed to be as usable as MATLAB with an advantage of being free and open source. Also, it supports dozens of backends and output types, which means you can use it regardless of which operating system you're using or which output format you wish. Pandas itself can be used as wrappers around Matplotlib's API so as to drive Matplotlib via cleaner and more modern APIs. Also, when you start using this library, you will realize that it has a very little memory consumption and a very good runtime behavior. Now let's talk about the applications of Matplotlib. It's important to discover the unknown relationship between the variables in your dataset. So this library helps to visualize the correlation analysis of variables. Also in machine learning, we can visualize 95% confidence interval of the model just to communicate how well our model fits the data. Then Matplotlib finds its application in outlier detection using scatterplot, etc. and to visualize the distribution of data to gain instant insights. Now let's make a very simple plot to get a basic idea. I've already imported the libraries here. So this function Matplotlib inline will help you show the plots in the Jupyter Notebook. This is also called a magic function. I won't be able to display my plots in the Jupyter Notebook if I don't use this function. I'm using this function in NumPy to fix random state for reproducibility. Now I'll take my n as 30 and will assign random values to my variables. So this function is generating 30 random numbers. Here I'm trying to create a scatter plot. So I want to decide the area. Let's put this. So it's just multiplying 30 with random numbers to the power 2 so that we get the area of the plot, which we will see in just a minute. So using the scatter function and the alias of matplotlib as plt, I've created this. If I don't use this, then I have very small circles as my scatter plot. It's colorful, it's nice. So that's one very easy plot. I suggest that you explore more of matplotlib and I'm sure you will enjoy it. Let's create a histogram. So I'm using the style as ggplot and assigning some values to these variables, any random values. Now we are assigning bars and colors and alignment to the plot. And here we get the graph. So we can create different type of visualizations and plots and then work upon them using matplotlib, and it's just that simple. So that was about the leading Python libraries in the field of data science. But along with these libraries, data scientists are also leveraging the power of some other useful libraries. For example, like TensorFlow, Keras is another popular library which is extensively used for deep learning and neural network modules. Keras wraps both TensorFlow and Theano backends, so it is a good option if you don't want to dive into details of TensorFlow. Then Scikit-learn is a machine learning library. It provides almost all the machine learning algorithms that you need, and it is designed to interpolate with NumPy and SciPy. Then we have Seaborn, which is another library for data visualization. We can say that Seaborn is an enhancement of matplotlib as it introduces additional plot types.
If you are an aspiring data scientist who's looking out for online training and certification in data science from the best universities and industry experts, then search no more. Simplilearn's postgraduate program in data science from Caltech University in collaboration with IBM should be the right choice. For more details on this program, please use the link in the description box below.
Let's now start this lesson by defining what data visualization is. Data visualization is the technique to present the data in a pictorial or graphical format. It enables stakeholders and decision makers to analyze data visually. The data in graphical format allows them to identify new trends and patterns easily. Well, you might think, why data visualization is important? Let's explain with an example. You are a sales manager in a leading global organization. The organization plans to study the sales details of each product across all regions and countries. This is to identify the product which has the highest sales in a particular region and up the production. This research will enable the organization to increase the manufacturing of that product in the particular region. The data involved for this research might be huge and complex. The research on this large numeric data is difficult and time-consuming when it is performed manually. When this numeric data is plotted on a graph or converted to charts, it's easy to identify the patterns and predict the result accurately. The main benefits of data visualization are as follows. It simplifies the complex quantitative information. It helps analyze and explore big data easily. It identifies the areas that need attention or improvement. It identifies the relationship between data points and variables. It explores new patterns and reveals hidden patterns in the data. There are three major considerations for data visualization. They are clarity, accuracy, and efficiency. First, ensure the data set is complete and relevant. This enables the data scientist to use the new patterns yield from the data in the relevant places. Second, ensure using appropriate graphical representation to convey the right message. Third, use efficient visualization technique, which highlights all the data points. There are some basic factors that one would need to be aware of before visualizing the data. Visual effect, coordination system, data types and scale, informative interpretation. Visual effect includes the usage of appropriate shapes, colors, and size to represent the analyzed data. The coordinate system helps to organize the data points within the provided coordinates. The data types and scale choose the type of data, such as numeric or categorical. The informative interpretation helps create visuals in an effective and easily interpretable manner using labels, title, legends, and pointers. So far, you have learned what data visualization is and how it helps interpret results with large and complex data. With the help of the Python programming language, you can perform this data visualization. You'll learn more about how to visualize data using the Python programming language in the subsequent screens. Many new Python data visualization libraries are introduced recently, such as Matplot Library, Vispi, Bokeh, Seaborn, Pygel, Folium, and Networks. The Matplot library has emerged as the main data visualization library. Let's now learn about this Matplot library in detail. Matplot library is a Python two-dimensional plotting library for data visualization and creating interactive graphics or plots. Using Python's Matplot library, the data visualization of large and complex data becomes easy. There are several advantages of using Matplot library to visualize data. They are as follows. It's a multi-platform data visualization tool built on the NumPy and SciPy framework. Therefore, it's fast and efficient. It possesses the ability to work well with many operating systems and graphic backends. It possesses high-quality graphics and plots to print and view for a range of graphs, such as histograms, bar charts, pie charts, scatter plots, and heat maps. With Jupyter Notebook integration, the developers have been freed to spend their time implementing features rather than struggling with cross-platform compatibility. It has large community support and cross-platform support as it is an open-source tool. It has full control over graph or plot styles, such as line properties, fonts, and axis properties. Let's now try to understand a plot. A plot is a graphical representation of data, which shows relationship between two variables or the distribution of data. Look at the example shown on the screen. This is a two-dimensional line plot of the random numbers on the y-axis and the range on the x-axis. The background of the plot is called grid. The text first plot denotes the title of the plot, and text line 1 denotes the legend. You can create a plot using 4 simple steps. Import the required libraries, define or import the required dataset, set the plot parameters, display the created plot. Let's consider the same example plot used earlier. Follow the steps below to obtain this plot. The first step is to import the required libraries. Here we have imported NumPy and PyPlot and style from Matplot library. NumPy is used to generate the random numbers, and PyPlot, which is built in Python library, is used to plot numbers, and style class is used for setting the grid style. Matplot library inline is required to display the plot within Jupyter Notebook. The second step is to define or import the required dataset. Here we have defined the dataset random number using NumPy random method. Note that the range is 10. We have used the print method to view the created random numbers. The third step is to set the plot parameters. In this step, we set the style of the plot, labels of the coordinates, title of the plot, the legend, and the line width. In this example, we have used ggplot as the plot style. The plot method is used to plot the graph against the random numbers. In the plot method, the word G denotes the plot line color as green. Label denotes the legend label, and it's named as line 1. Also, the line width is set to 2. Note that we have labeled the x-axis as range and the y-axis as labels, and set the title as first plot. The last step is to display the created plot. Use the legend method to plot the graph based on the set conditions, and the show method to display the created plot. Let's now learn how to create a two-dimensional plot. Consider the following example. A Nutri worldwide firm wants to know how many people visit its website at a particular time. This analysis helps it control and monitor the website traffic. This example involves two variables, namely users and time. Therefore, this is a two-dimensional or 2D plot. Take a look at the program that creates a 2D plot. Object Web Customers is a list on the number of users, and time hours indicates the time. From this, we understand that there are 123 customers on the website at 7 a.m., 645 customers on the website at 8 a.m., and so on. The ggplot is used to set the grid style, and the plot method is used to plot the website customers against time. Don't forget to matplot library in line to display or view the plot on the Jupyter Notebook. The website traffic curve is plotted and the graph is shown on the screen. It's also possible to change the line style of the plot. To change the line style of the plot, use define the line style as dashed in the plot method. Observe the output graph changes to a dashed line. Also note that the color is defined as blue. Using matplot library, it's also possible to set the desired axis to interpret the required result. Use the axis method to set the axis. In this example shown on the screen, the x-axis is set to range from 6.5 to 17.5, and the y-axis is set to range from 50 to 2000. Let's now understand how to set the transparency level of the line and to annotate a plot. Alpha is an attribute which controls the transparency of the line. Lower the alpha value, more transparent the line. Here, the alpha value is defined as 0.4. The annotate method is used to annotate the graph. The syntax for annotate method is shown on the screen. The keyword max is the attribute that denotes the annotation text. HA indicates the horizontal alignment. VA indicates the vertical alignment. XY text indicates the text position, and XY indicates the arrow position. The keyword arrow props indicates the properties of the arrow. In this example, the arrow property is defined as the green color. The output graph is shown on the screen. So far, you've learned how to set line width, title, x-axis and y-axis label, title of the plot, legend, line color, and annotate the graph for a single plot. The plot we created for website traffic in the previous screens is for only 1 day. Let's now learn how to create multiple plots, say for 3 days, using the same example. The dataset number of user for Monday, Tuesday, and Wednesday is defined with respect to its time distribution. Use different color and line width for each day to distinguish the plot. In this example, we have used red for Monday, green for Tuesday, and blue for Wednesday. The output graph is shown on the screen. A subplot is used to display multiple plots in the same window. With a subplot, you can arrange plots in a regular grid. All you need to do is specify the number of rows, columns, and plot. The syntax for a subplot is shown on the screen. It divides the current window into an M by N grid and creates an axis for a subplot in the position specified by P. For example, subplot 2, 1, 2 creates two subplots, which are stacked vertically on a grid. If you want to plot 4 graphs in one window, then the syntax used should be subplot 2, 1, 4. Layout and spacing adjustment are two important factors to be considered while creating subplots. Use PLT subplots adjust method with the parameters hspace and wspace to adjust the distances between the subplot and move them around on the grid. In this demo, you can see how to create two subplots that will display side by side in a single frame. Two subplots stacked one on top of the other or vertically split in a single frame, and 4 subplots displayed in a single frame. First, import matplotlib pyplot and style. Type %matplotlib in line to view the plot in Jupyter Notebook. Define the parameters such as temperature, wind, humidity, precipitation data, and time data. You can see the data being typed here. Next, to create two subplots to be displayed side by side in a given frame for 1, 2, 1 and 1, 2, 2, specify the figure size, subplot space, title, the color for time and temperature data, which is blue here, and line style and width. Similarly, specify the color for wind, which is red, its line style, and width. You can see the temperature and wind subplot charts displayed side by side in a given frame here. To create subplots for 2, 1, 1 and 2, 1, 2, specify the parameters. This will create two subplots stacked one on top of the other or vertically split in a given frame. Let's use humidity and precipitation data to plot the graphs. Specify the title, color, line style, and line width for both the graphs. You can see the two subplots stacked one on top of the other with two different colors, indicating precipitation and humidity. Here, the two graphs are separate. Finally, let's draw four subplots for 2, 2, 1, 2, 2, 2, 2, 2, 3, and 2, 2, 4 that will display in a given frame. Specify the title, subplot data, color, line style, and line width for all four subplots. You can see the four subplots displayed in a single frame. In this demo, you learned how to create subplots displayed side by side, vertically split subplots, and four subplots displayed in a single frame using Matplotlib. You can create different types of plots using Matplot library: histogram, scatterplot, heat map, pie chart, error bar. Histograms. Histograms are graphical representations of a probability distribution. In fact, a histogram is a kind of bar chart. Using Matplot library and its bar chart function, you can create histogram charts. A histogram chart has several advantages. Some of them are as follows. It displays the number of values within a specified interval. It's suitable for large datasets as they can be grouped within the intervals. Scatterplots. A scatterplot is used to graphically display the relationship between variables. A basic plot can be created using the plot method. However, if you need more control of a plot, it's recommended that you use the scatter method provided by Matplot library. It has several advantages. It shows the correlation between variables. It's suitable for large datasets. It's easy to find clusters. It's possible to represent each piece of data as a point on the plot. In this demo, you'll learn how to generate a histogram and scatterplot using Matplotlib. Let's import a dataset called Boston Dataset, which we will use to create the histogram and scatterplot from the scikit-learn library. Let's import Matplotlib pyplot. Type %matplotlib in line to view the plot in Jupyter Notebook. Let's use the data in Boston Real Estate Dataset to create the histogram and scatterplot. Load this data. You can view this data by using the print command. Now define the x-axis for the data, which is Boston real estate data. Likewise, define the y-axis for the data, which is Boston real estate data, with the target extension. Specify the plot style, figure style, number of bins, and labels of the x-axis and y-axis. Use the show method to display the histogram created by you. Specify the style, size, datasets, and labels of the scatter plot that you want to create. Use the show method to display the scatter plot created by you. Heat maps. A heat map is a better way to visualize two-dimensional data. Using heat maps, you can gain deeper and quicker insight into data than those afforded by other types of plots. It has several advantages. It draws attention to the risky-prone area. It uses the entire dataset to draw bigger and more meaningful insights. It's used for cluster analysis and can deal with large datasets. In this demonstration, you'll learn how to generate a heat map for a dataset using Matplotlib. Let's import the required libraries, Matplotlib, pyplot, and Seaborn. Type percentage matplotlib inline to view the plot in Jupyter Notebook. Let's load the flights dataset from the built-in datasets of Seaborn library. Use head to view the top 5 records of the dataset. We have to arrange the columns to generate the heat map. Let's use the pivot method to arrange the columns, month, year, and passengers. Let's view the flight dataset that's now ready to generate the heat map. Let's use the heat map method and pass flight data as an argument. This will generate the heat map, which you can see here. In this demo, you learned how to create and display a heat map. Pie charts. Pie charts are typically used to show percentage or proportional data. Note that usually the percentage represented by each category is provided next to the corresponding slice of the pie. Matplotlib provides the pie method to make pie charts. It has several advantages. It summarizes a large data set in visual form. It displays the relative proportions of multiple classes of data. The size of the circle is made proportional to the total quantity. In this demonstration, you'll learn how to create a pie chart and display it. First, import matplotlib pieplot. Type percentage matplotlib inline to view the plot in Jupyter Notebook. Type the job data within parentheses using single quotes separated by commas. Specify the labels as IT, Finance, Marketing, Admin, HR, and Operations. Specify the slice IT to explode. Use the show method to display the pie chart. You can see the pie chart with the slices, labels, and IT, the largest slice. Error bars. An error bar is used to show the graphical representation of the variability of data. It's used mainly to point out errors. It builds confidence about the data analysis by unleashing the statistical differences between the two groups of data. It has several advantages. It shows the variability in data and indicates the errors. It depicts the precision in the data analysis. It demonstrates how well a function and a model are used in the data analysis. It defines the underlying data. Seaborn is a Python visualization library based on Matplotlib. It provides a high-level interface for drawing attractive statistical graphics. It was originally developed at Stanford University and is widely used for plotting and visualizing data. There are several advantages. It possesses built-in themes for better visualizations. It has tools built-in statistical functions which reveal hidden patterns in the dataset. It has functions to visualize matrices of data, which become very important when visualizing large datasets.
Now, in order to learn Tableau, the basic first step is to import a sample data. So in our case, what we have done is we have imported a sample superstore, which is in Excel format, a sample superstore.excel, which has 3 worksheets in it: orders, people, and returns. So by importing this data into Tableau, first of all, we will create relationships between these sheets in order to identify who all have placed orders and how many people have returned the orders. We will do some analysis on the orders placed by a certain set of people and order returned by a certain set of people. Now, as we have imported the sheet, we will make certain joins. So the first step is to drag the orders table, the order sheet on the relationship canvas here, okay, and you can see the data, sample data, the first 100 rows over here, okay. Then now we need to create an inner join with people's table between order and people, okay. So if you see, it has automatically detected the field names on which the inner join has to be created. So on the order side you have region, and on the right hand side, which is the people data, you have also a region, okay. So both these columns are common, and that's how we have made a join between orders and people data. So if I close this box and go and check the people's data, open, so see the region and the person, these two columns from the people table have now been joined with the orders table, right? So it means that these are the orders in a particular region which has been placed by in this region. Let me show you the sample superstore Excel file. Now this is the structure of the file. You have a sample list of transactions, basically the orders which are placed by customers across multiple regions, south, west of USA, south region, west region. Then you have a list of order IDs which have been returned. So basically the order ID in the returns sheet matches with those orders in the orders table. And then you have the people sheet in which you have region and a person associated with that region, the salesperson associated with that region. Okay, so basically when we are combining, joining orders with people, we are joining that which orders belongs to which region and who's the salesperson associated with it. So what we have done over here is we have made a inner join, means all the orders should belong to particular region, and that region is in the people's sheet. And then in the second step, now we will make a left join between returns and orders, not inner join. We will make a left join between returns and orders, and we will make a join using the order ID. Okay, so just edit this, click on left and select order ID as the join column. Now what does left join means? Left join means is that consider all the orders from the orders table and only consider the orders from the returns table which have data, means which are returned. Otherwise show null for the order IDs which are not returned. So if you see, these are the two columns from the returns table, and these are null because this is relevant to the order IDs which are not returned, okay, which has been accepted by the customer. But these are the orders for which you see data in the returned and order ID column. It means that these have been returned. Now with these joins in place, please save your book, and now we have our relations created in the Tableau. Now we are ready to create certain reports and extract certain KPIs using this relationship model. Now we'll move to sheet 1. Okay, and first we will place state and person on the rows sheet. Okay, then I'll go to my numbers and put the profit or so per state, per person, how much profit I am making as a company. Okay, this is my goal to check. Now sort by highest to lowest. So California is giving me the maximum profit of 76,381, then New York, then Washington. So this is the sorted order in which I have listed my profit in descending order. Now I can also check what are the number of orders placed and check the distinct count. So out of 120, out of the total orders of 127, okay, so this is the total number of orders which have been returned for California is 127. It's 16, 29. So the sorted order is as per the revenue, as per the profit, and this is the details of the orders which have been returned per state. So if you see for Connecticut, for Kansas, there are 0 returns. So you can also extract data. Table to refresh is orders and identify new rows using order date. So as and when new data is being added, you can refresh it. Now say extract, and now you can save this information, profit by state, and click save. So this is the extraction of this particular report which is possible in Tableau. So this is the first exercise which we have completed for reviewing and analyzing the profit per state, highest to lowest, and within that per state, what are the number of orders which have been returned by all the customers, the distinct count of order IDs which have been returned. Now let's start our second exercise on creating calculated fields in Tableau. Now in this exercise we will be doing certain activities, like we will be creating a set to show the states which have more than 100 customers. Then we will be creating a calculated field to show an average sales per customer. Okay, then we will create a calculated field to show the sales goals, and then show emerging and developing stage. So these are the 4 KPIs which we have to derive. Now the first thing, we have our sample superstore data already imported and the relationships created, inner join with people and left join with returns. Now we have our sheet 2 in which we will create the states, a list of states which has more than 100 customers. So what we have to do is we have to right click on the customer name and click create set. Okay. Now we have to give the name as states with 100 plus customers, and then go to the condition tab, select by field, and then apply condition as count of customer name greater than equal to 100 and click OK. Now we have this set created, states with 100 plus customers. Now to determine average sales by customer, we have to now create a calculated field. So go to the analysis and click on create calculate field. Okay. Now name it as average sales per customer, and now we will say average we will use a okay, so we are saying that per customer we are using a level of definition function include, which means that per customer what is my average sales, right? We've already used a function, aggregated function called average. So we are saying per customer give me the total and then give me the average per customer. So we're going to click OK. Now create another calculated field. You can also create from here and name it as sales goal. Now in this we are going to type the formula if minimum states with 100 plus customers equal to true, then sum of sales into 1.3, else average sales per customer into 100. So we are saying that if the customer belongs to the set of states with 100 plus customers, then the sales target should be 1.3 times the actual sales as of today, else it should be 100% of the average sales per customer. Now let's create another calculated field which we call as emerging or developing state. If distinct count of customer name is greater than equal to 100, then the state is tagged as developing state, else it is called as emerging state. Okay, so we have now 3 calculated fields: average sales per customer, emerging or developing state, and sales goals. Now we will use this in our reporting. So we will drag sales goal under the columns and then I'll drop my state. So now this is the state wise sales goal, depending whether the state has 100 plus customers or not. Then add your customer name. make the measure as count distinct and make it as discrete. Okay, so if you see this, we have the count of customers per state and the sales goal for that particular state. And now I'll put my sum of sales, the total sales which I want which is there per state. Now go to show me and select this particular chart, bullet graph. Now to bring sales goals to column, right click on the sales axis and select swap reference line fields. Now from your left hand panel, drag and drop emerging or developing state on the color panel. Okay, so emerging state is the orange one and the developing state is the blue one. And save the sheet as developing and the emerging states. So if you see this, it's an emerging state because its count is less than, the customer count is less than 100. Its sales goal is 57384, but the actual sales is 19511. Okay. So now this is a developing state. Its count is greater than equal to 100 and its sales goal and its sales is exactly the same. It matches. So that's why you are saying the bar and the blue bar is ending exactly where the vertical bar is. So what we are trying to depict is that whether the state is going beyond its target sales goal or it's behind it, and you can see that using this particular vertical bar. Like for example, Michigan, its sales goal is 71,952, but its actual sales is 76,270 average sales. So that's why it is above its target and it's a developing state because it has more than 100 customers. So you can even sort by the count of the customers higher to lower. So all your developing state will group from at the top and the emerging states will group at the bottom. Or you can sort by the sales goal. So the orange bar is the sales goal or the blue bar. So depending what sales goal is being derived for each state.
Let's go ahead and take a look at building a resume. Always exciting, putting ourselves out, selling ourselves. And if you looked at some of our other videos dealing with resumes, you'll see a trend here. The top part is so different than what resumes were in the 90s, in the 2000 to 2010. They've evolved. They've really evolved. It used to be 2000, 2010, maybe LinkedIn, maybe one other reference. Now you're going to see that we want those references. This is a sales tactic, which now has come into resumes. It used to be that if you were a real estate agent, every real estate agent I knew, I used to deal with real estate software for the real estate industry back in the 90s. Every real estate agent wanted their picture on their business card. They wanted their picture, if they could, put on their contracts. They want people to see the face. So that's really a big change, is to make sure that it stands out. You stand out. Here's a picture of somebody, so you're more than just a couple letters and a name. And of course, you need your contact information, should always be at the top. You have your summary. What are you focusing on? Be a little careful with your summary, because if you have everything in your summary and then they scroll down to experience and education and skills, they're going to stop. The second you repeat yourself in your resume, that usually means to the reader, hey, this person doesn't have anything more to offer me, I'm done. So be a little careful how you word your summary. Most companies appreciate when you come in here and you've adjusted this summary to be both about you and how you're going to serve that company. So it's worth researching that company to find out how those connect and put that in the summary. Take some time to do that. That's actually a pretty big deal. And the references are huge also, especially in data science. When you're talking about any of the programming or data science, data analytics, having a place to go where they can look it up and scroll down and see different things you're doing, whether it's LinkedIn in this case, which is the business profile most commonly used, GitHub where you have stuff published, Facebook. I'm always hesitant because that tends to push more towards social media type jobs and other jobs. But certainly there's people who have Facebook who do marketing and stuff like that. But these links, having these basic links here is important. People are starting to look for that for some other setup. Maybe you have a personal website. This is a good place to put that so that they now have a multitude of links that go back to you and highlight who you are. And then the next part, or next 4 parts, so for the next 4 parts, we have a combination of experience, education, skills, certifications. And you can see they're organized. If you have, a lot of people like to see what kind of degree you have. They want to know where it came from. And if you just got out of college, you're going to put education at the top. And then maybe you'll put skills after that, and then your experience at the bottom. If you've been in the field for years, my degree, just to give you my age, goes back to the early 90s. So I usually put education at the very bottom. And then because a lot of the stuff I'm trying to sell myself on right now is my skills, I actually put that at the top. And I'll put my education, my certifications at the bottom, my skills, and then my experience is, since it's a huge part of my resume, goes next. You can organize these in whatever order you want that's going to work best for you and sell you. So remember, you're selling yourself. This is your image. Probably don't wear an old tie-dye t-shirt with holes in it. Something nice because it is professional. And of course your summary. And then what do you have to offer the company? And again, when I put out resumes, and I haven't done a resume in a while, you go in there and you can take this and reorganize this. So if the company's looking for something specific, you might put the experiences specific to that company. You might even take experience, if you have like a long job history like I do, I've gone into a lot of different things, you might leave out those companies or those experiences that had nothing to do with data science because it just becomes overwhelming. Resume should only take about 30 seconds to glance over, maybe a minute tops, because after that point you've lost the person's interest. And if they want to dig deeper, they now have links, they have your website, they have LinkedIn, and they can now take this and they come back to it and they go, oh, okay, let's look at this person a little closer. So quick overview, this is your sell sheet selling you to the company. So always tie it to the company so that you have that, what am I going to give this company? What are they going to get from me?
If you are an aspiring data scientist who is looking out for online training and certification in data science from the best universities and industry experts, then search no more. Simplilearn's postgraduate program in data science from Caltech University in collaboration with IBM should be the right choice. For more details on this program, please use the link in the description box below.
Before we dive in and start going through the questions one at a time, we're going to start with some of the logical kind of concept that enters in a lot of interviews. In this one, you have 2 buckets, one of 3 liters and the other of 5 liters. You're expected to measure exactly 4 liters. How will you complete the task? And note, you only have the 2 buckets. You don't have a 3rd bucket or anything like that, just the 2 buckets. And the object of the question like this is to see how well you are thinking outside the box. In this case, you're in a larger box. You have 2 buckets. And also the pattern which you go on. And what that means is if you look at the 2 buckets, and we'll show you their answer in just a second, you have a bucket with 3 liters and a bucket with 5 liters. And the first thought is, what happens if you go from left to right? So we have a direction. And what happens if you pour the 3 liters into the 5 liter bucket? Well, if you pour the 3 liters into the 5 liter bucket, you have an empty bucket of 3 liters. And what's really important here is thinking outside the box, you realize that you have a 5 liter bucket that has 3 liters in it and 2 empty liters. So you have 2 additional liters you can fill up. If we continue that process, we can pour from the left to right, from the small bucket to the large bucket. You can now measure in 2 additional liters into the 5 liter bucket. And 3 minus 2 is 1, and you can keep doing that. You can empty the 5 liter bucket in, pour those 3 liters in, that 1 liter in, and then you can pour 3 liters in. What's cool about these questions as you explore them is you realize there's multiple ways usually to solve them. I went from small bucket to big bucket. The Simplilearn team, their solution that they pulled out was you fill the 5 liter bucket and empty it into the 3 liter bucket. Now you're left with 2 liters in the 5 liter bucket. So that's great. We can empty the 3 liter bucket. So now we're going from large to small. Remember, we went from small to large. So you can go both either way, but you have to go one way or the other, it turns out. And you can empty the 3 liter bucket and pour the contents of the 5 liter bucket in it. So the 3 liter bucket now has 2 liters. And if it has 2 liters, that means it has an empty 1 liter. And by now you probably have guessed that if you have that empty space, you can start using that empty space of 1 liter as a measuring. So we fill the 5 liter bucket again, and we pour the water in the 3 liter bucket. It already has the 2 liters, and so we're only pouring 1 liter in there, and 5 minus 1 is 4. So interview questions, they break up into all kinds of different patterns. We have logic like this one, which is a lot of fun. We have questions that come up that are more vocabulary. List the difference between supervised and unsupervised learning. Probably one of the fundamental breakdowns in data science. And supervised learning uses known and labeled data as input. Supervised learning has a feedback mechanism. Most commonly used supervised learning algorithms are decision tree, logistic regression, support vector machine. And you should know that those are probably the most common used right now, and there certainly are so many coming out. So that's a very evolving thing, and be aware of a lot of the different algorithms that are out there outside of the deep learning. Because a lot of these work faster on raw data and numbers than a deep neural network would. Unsupervised learning uses unlabeled data as input. Unsupervised learning has no feedback mechanism. Most commonly used unsupervised learning algorithms are k-means, clustering, hierarchical clustering, the Aporia algorithm. And there certainly are more. I'm going to say k-means definitely is at the top of the list, and the hierarchical clustering, those two are used so many times. So really important to understand what those are and how they're used. And most important is understand that supervised learning is you have your data set where you have training data and you have all those different pieces moving around, but you're able to train it. You know the answers. And unsupervised, we're just grouping things together that look like they go together. How is logistic regression done? Logistic regression measures the relationship between the dependent variable, our label, what we want to predict, and the one or more independent variables, our features, by estimating probability using its underlying logistic function, sigmoid. And whenever I draw these charts, I always end up drawing them the right-hand side first, because you want to know what your output is. What is you want out of here? And the left-hand side, what do you have going in? So you have your in and out. You can see we have a nice labeled image here to help you remember this. We have our inputs, we have our linear model, we have our probabilities. What are the probabilities of it being a certain way based on these features coming in? The sigmoid function, and it's important to note that the sigmoid function is maybe the most commonly used, but it's only one of a number of functions that are out there. And the sigmoid function turns our probabilities into a value between 0 and 1, or very close to 0 and very close to 1, between 0.1 and 0.009. And based on that, we generate an answer, in this case is 0 or 1. How is logistic regression done? So last time we talked about the sigmoid function. Generally, depending on what your interview and level of math and what expertise you're going in for the market, you'll have to understand that formula of the probability equals 1 over 1 plus e to the negative y. And that's e to the base 2. So you have your probability function or your sigmoid function, which pushes it. As you can see, we have a nice visual of that. And that helps a lot to have that visual on the sigmoid function. You definitely should know your y equals m times x plus c, your basic Euclidean geometry of forming a line, and the slope plus the intercept, the y-intercept. And then you have your natural log. And the natural log is to the e, as opposed to a base 2 or base 10. So your natural log to the e of the probability over 1 minus a probability equals your
m times x plus c, or your Euclidean line. That helps a lot as far as the graphing and understanding the sigmoid function. So we'll just keep pushing on to question number 3. Explain the steps in making a decision tree. And I noticed last time we brought up the decision tree and the forest, a lot of questions came up. What is the difference? So let's go through that. When you make a decision tree, you're going to take the entire data set as input. You're going to calculate entropy of the target variable as well as the predictor attributes. I remember entropy is just how chaotic is it. So if you have like, banana and grapes and oranges, if you're mixing in fruit and that's your data coming in, you have all these different objects that are so separate from each other, and the more they become uniform, the lower the entropy. And we call that information gain. So we gain information on sorting different objects from each other. So you have your entropy, you have to calculate your information gain of all attributes, and then you choose the attribute with the highest information gain as the root node. So if you can separate your group and each group chaos in each group is lowered, whichever split lowers the chaos the most, that's where you split it, and that's your root node. At that point you repeat the same procedure on every branch till the decision node of each branch finalized. So understanding that setup is pretty important as far as decision trees, and you can see here we have a nice visual of a decision tree. For example, if you want to build a decision tree to decide whether we should accept or decline a job offer, since these are interview questions, that's a good one to ask. And just as a tip, you should be pretty aware of the formula for entropy and information gain. So you need to look those up if you don't remember those. And the salary, if it's greater than 50,000, no, decline the offer. Yes, it's got a good salary. The commute is greater than an hour. Yes, decline the offer. No. Offers incentives. Yes, accept the offer. No incentives, decline the offer. So we use decision tree pretty much for everything if you want. And if you have a decision tree, then you also should understand how do you build a random forest model. And remember that a random forest is built up of a number of decision trees. So if you split your data up into a lot of different packages and you do a decision tree in each of those different groups of data, the random forest is bringing all those trees together. So how do you build a random forest model? Randomly select k features from a total of m features, where k is less than m. Among the k features, calculate the node D using the best split point. Split the node into daughter nodes using the best split. Repeat steps 2 and 3 steps until leaf nodes are finalized. Build forest by repeating steps 1 to 4 for n number times to create n number of trees. So you can see it's got the same build pattern as the tree, but instead you're building a number of different trees, little small trees, so it all have an n leaf node. Random forest has a vote at the end, and whoever gets the most votes wins. That's the answer. How can you avoid overfitting of your model? Very important question in any kind of mathematical, scientific, data science setup, in any of them. There are 3 main methods to avoid overfitting, and you should really understand overfitting. Overfitting means that your model is only set for a very small amount of data and ignores the bigger picture. Keep the model simple. Take into account fewer variables, thereby removing some of the noise in the training data. Good advice for any programming at all. Use cross-validation techniques such as k-folds cross-validation. Use regularization techniques such as lasso that penalize certain model parameters if they're likely to cause overfitting. And you should also be well aware that your cross-validation techniques, that's like a pre-data, or your lasso and your regularization techniques are usually during the process. So when you're prepping your data, that's when you're going to do a cross-validation, such as like splitting your data into 3 groups, and you train it on 2 groups and test it on 1, and then switch which 2 groups you test it on, that kind of thing. So can you solve, another one of these, I love these things. There are 9 balls, out of which 1 ball is heavy in weight, and the rest are of the same weight. In how many minimum weighings will you find the heavier ball? And when we say weighing, think of a scale where you can put objects on one side and the other, and you can see which side is heavier. And you want to minimize that. You want to split the balls up in such a way that you're going to do as few measurements as you can. You will need to perform 2 weighings. So you can get it down to just 2 weighings. And I always think if there's 9 balls, I'm going to divide them into 3 groups of 3. Place 3 balls on each side. So you can just randomly pick 6 of the balls and 3 on one side, 3 on the other. And if they balance out, both sides are equal, then you know the heavy weight isn't in any of those. So out of the remaining 3 balls from step 1, take 2 balls and place 1 ball on each side. A little tricky there because I always want to put all 3. I want to put 2 on one side and 1 on the other, but no, just randomly pick 2 of those, put 1 on each side. If they balance out, then the left out ball, the one you didn't measure, will be the heavier one. Otherwise, you'll see it in the balance. You'll see which one's heavier because you'll take one of the balls down. Now we go to scenario B. where they did not balance out. So now we know which side has a heavier ball in it. And it's just very similar to what we did before. If the balls in step 1 do not balance out, then take those 3 balls that had the heavier side on them and reproduce step 2 to find out the heavier ball. Difference between univariate, bivariate, and multivariate analysis. And hopefully, if you know a little Latin, it'll kick in there that you have uni and you have bi and you have multi, because the answer is in the words themselves. So the first one, this type of data contains only one variable, so that's the univariate. The purpose of the univariate analysis is to describe the data and find patterns that exist within it. So when you only see one variable coming in this case we're using height of students, you're limited as far as what you can do with that data. So you can come up and draw different patterns and conclusions from those patterns using the means, the median, the mode, dispersion, range, minimum, maximum. So we're describing the data. So all those words would describe the data, and that's about all you can do with data like that. There's no correlation, there's nothing to go beyond that as far as guessing or predicting anything. So we move into bivariate. Uni means 1, bi means 2. Bivariate, this type of data involves 2 different variables. The analysis of this type of data deals with causes and relationships, and the analysis is done to find out the relationship among the 2 variables. And this is always a favorite one because everybody loves ice cream in the summer when it's hot, and very few people go for ice cream in the winter when it's really cold, so it's easy to see the correlation in the data. The temperature and ice cream cells in summer season. And you can see here where the temperature goes from 20 to 35, and as the temperature goes up, so does the cells of ice cream. It goes from 2,000, I'm not sure 2,000 what, so I'm guessing it's a very large chain, because if they're selling 2,000 ice cream cones, and they have a lot of business, good for them. A little vendor on the corner selling 2,000 ice cream cones a day and 3,100 the next day. Here, the relationship is visible from the table that temperature and cells are directly proportional to each other. So the hotter the temperature, we can predict an increase in cells. So the word prediction should come up. So we have description and prediction. When the data involves 3 or more variables, it is categorized under multivariate. It is similar to bivariate, but contains more than one dependent variable. In this example, another really common one, the data for house price prediction, the patterns can be studied by drawing conclusions using mean, median, and mode, dispersion, or range minimum, maximum, etc. And so you can start describing the data, that's what all that was, and then using that description to guess what the price is going to be. So this is very good if you're in the market and you have already looked at the area and you already know that a 2-bedroom, 0-floor, 900 square foot house usually runs about $40,000. You can guess what the next one that looks similar to it is. And I'll just throw in another word in there I don't see very often unless you're really a hardcore data science. We talked about describing the data, descriptive. We talked about predictive, and there's also postscriptive. Postscriptive means we're going to change the variables to try to guess what the outcome is if we change what's going on. So that would be the next step. But that usually doesn't show up unless you're dealing with some really hardcore data science groups. What are the feature selection methods to select the right variables? There are 2 main methods for feature selection. There's filter methods and wrapper methods. And when you're filtering before we discuss the 2 methods real quick, the best analogy for selecting features is bad data in, bad answer out. So when we're limiting or selecting our features, it's all about cleaning up the data coming in so it's cleaner and is more representative of what we're trying to predict. Filter method. Filter methods as they come in, we have linear discrimination analysis, ANOVA, chi-squared. Chi-squared is probably the most common one. And these are all part of pre-processing. We're taking out all the outliers, all the things that have a difference that is very different from the data we're looking at, the odd ones. And sometimes you take the odd ones out and then you analyze them separately to see why they're odd. But remember your filter methods, you want to pull all that weird stuff out. Wrapper methods, on the other hand, are forward selection, backward selection, recursive feature elimination. And one of the most important things to remember about wrapper methods is they're very labor intensive. You have to have some pretty high-end computers if you're doing a lot of data analysis with the wrapper method. And just quickly, forward selection means you have all your different features. They're off to the side, and we test just one feature at a time, and we keep adding them in until we get a good fit. Backward is we have all the features, and we run a test on that to see how well it does, and then we start removing features to see what works. And recursive, which is the most processing-hungry algorithm out there, goes through and just recursively looks through all the different features and how they pair together. But again, we have filter method and wrapper method, and it's important to understand that we're sorting the data out and finding out which features are going to represent the data the best and which ones are not going to really add any value to our models. Let's jump to number 8. In your choice of language, write a program that prints the numbers from 1 to 50, but for multiples of 3, print fizz instead of the number, and for the multiples of 5, print buzz. For numbers which are multiples of both 3 and 5, print fizz buzz. And this really is testing your knowledge in iterating over data. Very important. My sister, who runs at the university the data science team, is in charge of their department. It's the first question she asks in her interview of anybody who comes in is, how do they iterate through data? So if this question comes up a lot and it's very important you have an understanding, and there's actually a slight error on this code, which I'll point out in just a second. The concept is we have fizz buzz in range, and you have range 51, which in this case goes from 0 to 51. And I'm going to challenge you to see if you can catch the error, and I'll tell you at the end of the code where the error is. What that means is that we're going to go through all the numbers 0, 1, 2, 3, 4, and we're going to process through this loop. If the remainder of fizz buzz divided by 3 equals 0, and fizz buzz divided by 5 also equals 0, then print fizz buzz. Continue. And else if fizz buzz divided by 3 equals 0, then print fizz, continue. Else if fizz buzz divided by 5 equals 0, print buzz, continue, and print fizz buzz. You print the answer. In this case, fizz buzz is either going to be the number we generated, which is 0, or it'll be the fizz buzz, fizz, or buzz. Whew, that's a mouthful. Now, if you didn't catch the error in the code, which is always a fun game, find the error. It has to do with the range. And it's important to remember the range here says range to 51. That's 0 to 51, which is correct. We want to go to 51 because it stops. It gets to 50 and it stops. So that's 0 to 50. But if you remember, the question asks from 1 to 50. So the range should be 1, 51, not just 51, which does 0 to 51. In this particular script, in Python, you could leave out the continue, but the continue in this script skips the next else if, so it doesn't keep processing it going down. And in programming, a lot of scripts you don't need the continue answer, so it would depend on what script you chose. And there's probably some other ways to do this. It's a lot of fun. And you can see here from the output, we end up with fizz buzz for 0, which shouldn't be there. 1, 2 fizz, 4 buzz, fizz, 7, 8 fizz buzz, 11 fizz, and so on. Sounds like a drinking game from my college days. So long ago, many decades ago. You are given a data set consisting of variables having more than 30% missing values. How will you deal with them? Oh, the joy of messy data coming in. Ways to handle missing data values. Data set is huge. We can just simply remove the rows with missing data values. It is the quickest way, i.e. we use the rest of the data to predict the values. You just go in there and say any row of our data that has a NA in it, get rid of it. That doesn't work with smaller data. So with smaller data, you start running into problems because you lose a lot of data. And so we can substitute missing values with the mean or average of the rest of the data using Pandas data frame in Python. There's different ways to do this, obviously, in different languages. And even in Python, there's different ways to do this. But in Python, it's real easy. You can do the df.mean, so you get the mean value. So if you set mean equal to that, then you can do a df.fillNA with the mean value. Very easy to do in a Python Pandas script. And if you're using Python, you should really know Pandas and NumPy, NumPython and Pandas data frames. For the given points, how will you calculate the Euclidean distance in Python? So back to our basic algebra from high school. Euclidean distance is the line on the triangle. And so if we're given the points plot 1 equals 1, 3, plot 2 equals 2, 5, we know that from this we can take the difference of each one of those points, square them, and then take the square root of everything. So the Euclidean distance equals the square root of plot 1, 0 minus plot 2 of 0 squared plus plot 1 of 1 minus plot 2 of 1 squared. Mouthful there. And you can remember if you have multiple dimensions that go past 2 dimensions, you could have plot 3 can simply be the distance from plot 1. You only need to do one side of that. Or plot 2, you can do either way and square that and take the square root of that. Another mind bender. How to calculate something, how to figure out the solution to something. What is the angle between the hour and minute hands of a clock when the time is half past 6? So you want to kind of imagine that clock where the large hand is pointed down to the 30 and the other half is going to be right between the 6 and the 7 because it's half past 6. There's actually a couple ways to solve this, but let's take a look and see how they did it. Note, a clock is a complete circle having 360 degrees. In 1 hour, the hour hand covers 360 over 12, so it equals 30 degrees for each hour. In 1 minute, the minute hand covers 360 degrees over 60 minutes, or 6 degrees per minute. The minute hand has traveled for 30 minutes, so it has covered 30 times 6, which equals 180 degrees. So we know that's 180 degrees from the 12. The hour hand has traveled for 6.5 hours, 6.5, 6.5, so it's covered 6.5 times 30, which equals 195 degrees. The difference between the two will give the angle between the two hands, thus the required angle equals 195 minus 180 equals 15 degrees. And this is nice the way they solved it, because you can now punch in any kind of time within reason. The hard part is on the hours, is you have to be able to convert the hours into decimals. Explain dimensionality reduction and list its benefits. Dimension reduction refers to the process of converting a set of data having vast dimensions into data with lesser dimensions, fills, to convey similar information concisely. It helps in data compressing and reducing the storage space. It reduces computation time as less dimensions lead to less computing. It removes redundant features. For example, there's no point in storing a value in two different units, meters and inches. And I certainly run into a lot with this with text analysis. I've been known to run a text analysis over a series of documents, ends up with over 1.4 million different features. That's a lot of different words being used. And if you do what they call connect them, you connect two words together, now you're up to 4.8 million different features, and you start having to figure ways to bring that down. What can we get rid of? That kind of thing. So you can see where that can get really high end on processing, and learning how to reduce the list dimensions is very important. How will you calculate eigenvalues and eigenvectors of a 3x3 matrix? And what they're really looking for here is when you write it out, for the eigen is that you know that you're going to use the lambda. That's the most common one. Obviously you can use any symbol you want, but lambda is usually what they use. And that you do it down the middle diagonal. And so when you take that matrix and you take the characteristic equation, you end up with the determinant, and that's the minus 2 minus lambda, minus 4, 2, minus 2, 1 minus lambda, 2, 4, 2, 5 minus lambda. And that's what they're looking for, and you know that's equal to 0. So when you're doing a matrix in the eigen setup with the eigenvectors, that's all going to come out equal to 0. And then you can go ahead and write the whole equation out. So we can expand the determinant, as you can see right here, the minus 2 minus lambda times, it's a mouthful. I'll leave it up here for a second so you can look at it. When you break it down into the algebraic functions, you end up with minus lambda cubed plus 4 lambda squared plus 27 lambda minus 90 equals 0. So now we have a nice algebraic equation built from the eigenvectors. And always remember, you can hit the pause button, and you can also send a note. Send a note to Simplilearn if you have more questions on vectors or on this. Definitely have that resource available to you, or post down in below on the YouTube video comments. And so when we calculate the eigenvalues and eigenvectors of a 3x3 matrix, as we continue on down the math of this, and to be honest, I really don't like working with matrices like this. It's important to understand the math behind it, and it's important to know the code just enough so that you're not lost when someone's explaining it or it comes up when I'm working on different data science models. Of course, if you're dealing with the high-end math side of it, then you better know this. First is by hit and trial, so you try in different variables to solve for 0, and you can come in here and you'll find that if we put in the 3 in there, we end up with a 0 at the end, and substitute the 3. Hence, we end up with lambda minus 3 as one of the factors. And you can do the math going out on that, where we have lambda cubed minus 4 lambda squared minus 27 lambda plus 90 equals lambda minus 3 times lambda squared minus lambda minus 30. So eigenvalues based on that one are 3, minus 5, and 6. And then from there we can calculate the eigenvector for lambda equals 3. And you can see here where the matrix as we write it out is the minus 5, minus 4, 2, minus 2, minus 2, minus 2, 4, 2, 2. That was from the beginning. Put in the x, y, and z equals 0, 0, 0. And so when we put in those numbers and we calculate them out, we have for x equals 1, we have the minus 5 minus 4y plus 2z equals 0, minus 2 minus 2y plus 2z equals 0. And subtracting the two equations we just had, we get 3 plus 2y equals 0, y equals minus 3 over 2, and z equals minus 1 over 2. That's going back to the first equation. And similarly, we can calculate the eigenvectors for minus 5 and 6. How should you maintain your deployed model? Ooh, distribution time, my favorite. I spent 10 years in software distribution. So first thing, and this is true not just of your data science model, but of any computer code going out there. This is basic setup can work, although usually there's a little added steps in there. First, we're going to monitor it.
So we have a constant monitoring of all of the model is needed to determine the performance accuracy of the models. So yeah, we want to just keep an eye on it. We want to make sure they're accurate. We want to make sure that whatever they're supposed to predict, or I threw in that bonus word, postscript, where you've changed something and you want to figure out how your changes are going to affect things, we need to monitor it and make sure it's doing what it's supposed to do. Evaluation metrics of the current model is calculated to determine if new algorithm is needed. And then we compare it. The new models are compared against each other to determine which model performs the best. And then we do a rebuild. The best performing model is rebuilt on the current state of data. And this is interesting. I found this out just recently. If you're in weather prediction, the really big weather areas have about 7 or 8 different models depending on what's going on. And so you actually have almost a little forest going on there where they're like, which model is going to fit best, and this is what we're going to use to predict the weather with. So not only do you don't necessarily get rid of the models, but you figure out which models fit data of what's going on, or the current state of data. What are recommender systems? Most commonly used nowadays in marketing, so very big industry, understanding recommender systems, predicts the rating or preference a user would give to a product. And they're split into 2 different areas. One is collaborative filtering, and a good example of that is the Last.fm recommends tracks that are often played by other users with similar interests. So people who, if you're on Amazon, people who bought this also bought that. This got me a few times. And then there's content-based filtering. And we're looking at content instead of looking at who else is listening to the music. They use the example Pandora, which uses the properties of a song to recommend music with similar properties. So you have collaborative filtering and content-based filtering. How to find RMSE and MSE in linear regression model. Hopefully you remember what the 2 acronyms mean, because that is like half the answer. We have the root mean square error and the mean square error in linear regression model. So we're looking for error. The RMSE and the MSE are the 2 of the most common measures of accuracy for a linear regression model. And you can see here we have the root mean square error, RMSE equals, and this is the square root of the sum of the predicted minus the actual squared over the total number. So we're just looking for the average, mean. So we're looking for the average over the n. And the reason you need to know about the difference between RMSE versus MSE is when you're doing a lot of these models and you're building your own model, why do you need to take the square root of it? It doesn't change the value as far as the way you're using it, because you're looking as to see whether the error is greater or less than. So why add that extra computation in? So a lot of models use the MSE, which indicates the mean square error, or the average error. And it's the same formula minus the square root at the end, or across the whole thing. Another riddle to solve. If it rains on Saturday with a probability of 0.6, and it rains on Sunday with a probability 0.2, what is the probability that it rains this weekend? And the trick in probabilities on this case is we need to know what is the probability of it not raining. What's the chance of it not raining on Saturday? And if it doesn't rain on Saturday, we want to take that and combine that with the chance of it not raining on Sunday. The total probability, which in this case we're just going to use 1, minus the probability that it will not rain on Saturday, so that's 1 minus 0.6. We're going to take that as a union, which we simply just multiply them together, of the probability that it will not rain on Sunday. And it's important to recognize the union here, or and you can see by the formula down here, we end up with 0.68 or 68% chance that it will rain on the weekend. And there are a couple other ways to solve this, but this is probably the most traditional way of doing that. How can you select K for K-means? So first you better understand that what K-means is, and that K is a number of different groupings. And most commonly we use is the elbow method to select K for K-means. The idea of the elbow method is to run K-means clustering on the data set where K is a number of clusters. Within the sum of squares, WSS, is defined as the sum of the squared distance between each member of the cluster and its centroid. And you should know all the terms for your K-means on there. And with the elbow point, and again, here's our iteration in our code. We talked about that earlier. You iterate starting with, usually you don't start right at 1, but you might start with 2, 3, or 4. And you just see where it comes out, and you can see the nice elbow there, which is easy to see graphically, where the number of K clusters and the WSS value drops, and then it just kind of flattens out, and there's no reason to take the K-means any further. What is the significance of p-value? Oh, good one. especially if you're dealing with R, because that's the first thing that pops up. P-value typically less than or equal to 0.05 indicates a strong evidence against the null hypothesis, and you should know what a difference, why we use null hypothesis instead of the hypothesis. So you reject the null hypothesis. Very important, that term null hypothesis in any scientific setup and also in data science. It doesn't mean that it's true, it means that there's a high correlation that it's true. So if your null hypothesis means it's not true, your hypothesis has a high correlation that it's probably true. And if the p-value is typically greater than 0.05, it indicates a weak evidence against the null hypothesis. So you fail to reject the whole null hypothesis, and if you reject that, then your actual hypothesis is probably not true. The correlation of your data with what you think it's saying is probably incorrect. And if you're right at the cutoff of 0.05, it's considered to be marginal. Could go either way. And again, you can use that p-value on different features to decide whether you're going to include your features as far as something worth exploring in your data science model. How can outlier values be treated? Ooh, good one. You can drop outliers only if it is a garbage value. So sometimes you end up with like one outlier that just is probably someone's measurements way off. Height of an adult equals ABC feet. This cannot be true as height cannot be a string value. In this case, outliers can be removed. If the outliers have extreme values, they can be removed. For example, if all the data points are clustered between 0 to 10, but one point lies at 100, then we can remove this point. And again, sometimes you just look for the outliers so you can see what's going on, if there's something unusual there. So maybe the equipment's not calibrated correctly. If you cannot drop outliers, you can try the following. Try a different model. Data detected as outliers by linear model can be fit by nonlinear model. So be sure you are choosing the right model. So if it has like more of a curved look to it instead of a straight line, you might need to use something other than just a straight line linear model. Try normalizing the data. This way the extreme data points are pulled to a similar range. If you can use algorithms which are less affected by outliers, example random forest. So there's another solution, is you can come up with the random forest, which a lot of times completely bypasses your outliers. How can you say that a time series data is stationary? Oh, that's an interesting term. Stationary, meaning it's not moving, but it's a time series. We can say that a time series is stationary when the variance and mean of the series is constant with time. And the graphic example is very easy to see. We have our the variance is constant with time, so we have our first variable y and x being the time factor and y being the variable. As you can see, goes through the same values all the time. It's not changing in the long period of time. So that's stationary. And then you can see in the second example, the waves get bigger and bigger, so that's non-stationary. Here the variance is changing with time. Again, we have y, which stays constant, so that if you look at the bigger picture, it's the same wave over and over again. And then of course we have where the wave is growing in size going up. It can also go down, so it'd also be non-stationary. How can you calculate accuracy using confusion matrix? Oh, great one. Confusion matrices are so useful when you're taking that first look at data, and also when you're showing the shareholders and you want to ask them for money. How can you calculate accuracy using confusion matrix? So you have your total data that we're looking at is 650, and you have your predicted values and your actual values, and you have your predicted P and your actual P. And so when you look at this, you'll note that if the predicted P and the actual P are 262, but our predicted P also had 15 that weren't correct. So you can see there's a false positive there of 15. And the same thing with the N. You can see where N predicts N, and it has a false negative of 26 out of the total number of N values in there. And so we can do an accuracy on there. The true positive plus the true negative is our total observations. So you have a total of 0.93 accuracy, or 93%. And just a quick note on this, this is so important, because it's one thing if someone is being diagnosed with, say, cancer. You know, this is life-death, or is my nuclear reactor going to blow up? Suddenly, if the P is the probability of it blowing up, and this, let's say you have 15, that's a lot less than, say, the 26 chances of it blowing up. You know, so the actual domain of your data is very important. So if you're non-positive, you don't really care about the predicted value having non-positive as positive, because they're going to go do a biopsy on the cancer or whatever anyway. But you're very interested if you have a positive, an actual positive value, which is looked at as negative, a false negative. That's really important in that domain, depending on what domain you're in.
Write the equation and calculate precision and recall rate. And so continuing with our confusion matrix, I was just talking about the different domains. We have the precision equals 262 over 277. So your precision is the true positive over the true positive plus false positive. And the recall rate is your true positive over the total positive plus false negative. And you can see here we have that 262 over 277 equals a 94%. And the recall over here is the 262 over 280, which equals 9.9 or 90%. And oh good, we're going to take a pause for another brain teaser. If a drawer contains 12 red socks, 16 blue socks, and 20 white socks, how many must pull out to be sure of having a matching pair? The last time I went through these kind of brain teaser things was like 20 years ago, and I had 6 people sitting across the table waiting for my answer. That's kind of mind-numbing when you're in an interview like that. Hopefully you're not stuck in an interview like that. But on this, you need to ask yourself, how many different colors of socks are there? So they've thrown a lot of extra data in here that you don't need to solve the answer. The answer is 4. An example, your first pick is white, your second pick is red, third pick is blue, so no pairs yet. And that means when you get to the fourth pick, there's a 100% chance you're going to have a match. So the most is going to be 4 that you ever have to pull out of your drawer. If it was 4 colors, the answer would be 5, and so on. It doesn't matter how many white socks you have or how many red socks or blue socks, different pairs you have. It's the different colors, the number of different colors. People who bought this also bought recommendations seen on Amazon as a result of which algorithm? Ooh, we covered this earlier. Recommendation engine is done with collaborative filtering. Collaborative filtering exploits the behavior of other users and their purchase history in terms of ratings, selection, etc. It makes predictions on what you might interest a person based on the preference of many other users. In this algorithm, features of the items are not known. And we have a nice example here where they took a snapshot of a sales page. It says, for example, suppose X number of people buy a new phone and then also buy tempered glass with it. Next time when a person buys a phone, he'll be recommended to buy tempered glass along with it. And if you remember the vocabulary words we covered earlier, this is the recommendation. This is collaborative. The other word was content-based. So looking at things with similar content versus collaborative, which is similar people. And remember, you're not going to know every vocabulary word, but it also doesn't hurt to get your 3x5 cards out and make yourself a vocabulary stack of cards. Buy an app on your phone for it. SQL query. I remember back in the 90s, it was so important to know SQL query and only a few people got it. Nowadays, it's just part of your kit. You have to know some basic SQL. So write a basic SQL query to list all orders with customer information. And you can kind of make up your own name for the database. And you can pause it here if you want to write that down on a paper. And let's go ahead and look at this. We have to list all orders with customer information. And so usually you have an order table and a customer table. And you have an order ID, a customer ID, order number, total amount. And then from your customer table you have ID, first name, last name, city, county. And so if we're going to write in SQL with this, we're going to select, keyword there for SQL, selecting, order number, total amount, first name, last name, city, country. So that's the columns we're going to look at. We're going to do that from our order, where we're going to join it with our customer, and we're going to join it on the order customer ID equals the customer ID. So very basic SQL query that's going to return a table of data for us. You are given a data set on cancer detection. You've built a classification model and achieved an accuracy of 96%. Woo, 96%! Why shouldn't you be happy with your model performance? What can you do about it? That's an interesting one because this comes up. That's one of the standard data sets on there is for cancer detection. Cancer detection results in imbalanced data. In an imbalanced data set, accuracy should not be based as a measure of performance because it is important to focus on the remaining 4%, which are the people who were wrongly diagnosed. We talked a little bit about this earlier. You have to know your domain. This is the medical cancer domain versus weather domain. Weather channel, they can get by with 50% wrong. In cancer, you don't want 4% of the people being wrongly diagnosed. Wrong diagnosis is of a major concern because there can be people who have cancer but were not predicted so. In an imbalanced data set, accuracy should not be used as a measurement of performance. Which of the following machine learning algorithm can be used for inputting missing values of both categorical and continuous variables? So we have a couple choices here. We have k-means clustering, we have linear regression, we have the k NN, nearest neighbor, and decision tree. And which of the following machine learning algorithms can be used for inputting missing values of both categorical and continuous variables? Now, certainly you can use some pre-processing to do some of that, but you should have gone with the K nearest neighbor, because it can compute the nearest neighbor, and if it doesn't have the value, it just computes the nearest neighbor based on all the other features. Where when you're dealing with k-means clustering or linear regression, you need to do that in your pre-processing, otherwise it'll crash. Decision trees also, although there's some variance on that too. Can you solve? Another riddle, always fun ones. Given a box of matches and 2 ropes, not necessarily identical, measure a period of 45 minutes. And in this particular setup, the ropes are not uniform in nature, and the rope takes exactly 60 minutes to completely burn out. So each rope takes up to 60 minutes to burn out. And there's actually a couple different solutions to this. But let me go ahead. And one of the things is they're not uniform in nature. So even though they take 60 minutes... Anyways, let's go ahead and see what they did to solve it. And then we can also look at different options. We have 2 ropes, A and B. Light A from both ends and B from one end. Okay. When A is finished burning, we know that 30 minutes have elapsed and B has 30 minutes remaining. Now light the other end of B also, so that the remaining part of B will burn, taking 15 minutes to burn. This we have gotten 30 plus 15 equals 45 minutes. Excellent solution. Mine, which I like, was to take one rope, fold it in 2, so we know it's a half hour. Take the other rope, fold it in 4 places, so we know that that one's 15 minutes, and then you can just connect the 2 and burn it straight across. I think they're trying to cover that by saying they're not regular. The ropes have some irregularities. Maybe that's what they meant by that, is you couldn't do something like that. But that's my solution. Below are the 8 actual values of target variable in the train file. So we have a training file, not to be confused with the train on the tracks. We have 0, 0, 0, 1, 1, 1, 1, 1. What is the entropy of the target variable? We mentioned earlier that you should know your entropy and how to calculate the entropy. What is the entropy of the target variable? So we have a couple options here. We have minus 5 over 8 logarithm of 5 over 8 plus 3 over 8 logarithm of 3 over 8. Okay, let's just see where they got those numbers from. We have 1, which is going to be 5 ones and 3 zeros, and then we have a total of 8. Okay, and then we have the option of 5, which is number of ones, 5 8 logarithm of 5 eighths plus 3 eighths logarithm of 3 eighths. And we also have 3 eighths logarithm of 5 eighths plus 5 eighths logarithm of 3 eighths. And then we kind of reverse those numbers around. And let's see what you're going to get here. Which one did you think it was? You should check the first one. So what is the entropy of the target variable? The key there is the target variable. So we're looking at the target in this case is going to be 1. Usually that's what you're looking for. And so the entropy of that one, we want to subtract out the entropy of the non-target variable. Whoops, I had that backwards. We're looking at 0, so we want to subtract out the 5 eighths from there. So 5 eighths logarithm 5 eighths, or negative 5 eighths logarithm 5 eighths plus 3 eighths logarithm 3 eighths. And they have the hint on the bottom, entropy equals I of P of N. So we have a negative P plus P and N times the logarithm base 2 of P over P plus N minus the N over P plus N times the logarithm 2 of N over P plus N. We want to predict the probability of death from heart disease based on 3 risk factors: age, gender, and blood cholesterol level. What is the most appropriate algorithm for this case? So we have 3 features, and we want to know the predictability of death. Okay, a little morbid there. Choose the right algorithm. Do we want to use logistic regression for this, linear regression, k-means clustering, or the Aporia algorithm? And if you selected logistic regression, then you probably got the right answer. Linear regression, remember, deals with you take your line and draw a line through the data. And of course, you don't necessarily have to use a straight line. There's other means for that. But you're dealing with a lot of numbers. And k-means means we're just going to cluster objects together. With the logistic regression, though, you can mix those things together in buckets. So really, the logistic regression is what you want to use in that model, would be the most apt fit. After studying the behavior of a population, you have identified 4 specific individual types who are valuable to your study. You would like to find all users who are most similar to each individual type. Which algorithm is most appropriate for this study? Certainly, identifying census in just about a lot of different markets is common, so maybe they have a census or whatever it means. But let's take a look at some of the different algorithms we might use on this. We have k-means clustering, linear regression, association rules, and decision trees. And I'll give you a hint. We're looking for grouping people together by similarities, and by 4 different similarities, so very specific. They gave you one of the values, specifically the K value. So K-means clustering would be great for this particular problem. You have run the association rules algorithm on your data set, and the 2 rules, banana apple is associated with grape, and apple orange is associated with grape, have been found to be relevant. What else must be true? So this would challenge you to understand association rules. You could picture in this particular one, you're going shopping, and you almost always see somebody who has bananas, they usually have grapes in their bag also. And somebody who has apples usually has grapes in their bags. And then apples and oranges is also associated with grapes. And let's go ahead and take a look at that. And we have a couple different options here. First one is banana, apple, and grape, orange must be a frequent item set. Not so much. Banana, apples, oranges must be relevant rule. Grape is common with banana, apple, must be a relevant rule. And how about grape, apple must be a frequent item set? Let's go back and take a look at that. And we notice that we have bananas, apples to grapes. We have apple, orange to grape. Boy, there's a lot of grapes and a lot of apples in there. And so if you said the last one, grape and apple must be a frequent item set, then you got it correct. Your organization has a website where visitors randomly receive one of 2 coupons. It is also possible that visitors to the website will not receive a coupon. You have been asked to determine if offering a coupon to visitors to your website has any impact on their purchase decision. Which analysis method should you use? And so let's go ahead and start by giving you another hint and give you some limiting your selection. We have a one-way ANOVA. K means clustering, association rules, and student t-test. So obviously you should know what each one of these means, but let's take a look at the question again. So you want to know which method should you use to see if the coupon's valid for their purchase. Well, we're not clustering and we're not associating things together. We want to know the end result. Student t-test also drawing that little t in boxes and switching them around. There's really only one answer that works in here, and that's a one-way ANOVA.
Thank you for joining us on this journey through our comprehensive data science full course. From the basics to advanced topics, you have gained valuable skills to thrive in dynamic world of data science. Keep learning and exploring. There's always more to discover. If you found this video helpful, please like, subscribe, and share. And stay tuned for more such videos from Simplilearn.
Staying ahead in your career requires continuous learning and upskilling. Whether you're a student aiming to learn today's top skills or a working professional looking to advance your career, we've got you covered. Explore our impressive catalog of certification programs in cutting-edge domains, including data science, cloud computing, cybersecurity, AI, machine learning, or digital marketing. Designed in collaboration with leading universities and top corporations, and delivered by industry experts. Choose any of our programs and set yourself on the path to career success. Click the link in the description to know more.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.